In the 1950s, computer scientist Arthur Samuel built a checkers program that learned to play better through experience. This simple experiment introduced a powerful idea that machines could learn from data instead of being explicitly programmed. Today, that same idea powers almost everything around us. From Netflix recommendations and fraud detection systems to self-driving cars and voice assistants like Alexa, machine learning is behind it all. At its core, machine learning is about teaching computers to find patterns in data and make decisions on their own. It enables systems to predict, recommend, recognize, and adapt, getting smarter with every piece of information they process. And that's exactly what we will explore in this machine learning full course by Intellipaat, a practical, hands-on journey designed to help you build real-world machine learning skills. You will start with the fundamentals of statistics and data pre-processing, move on to supervised and unsupervised learning, and then dive deep into algorithms like linear regression, decision trees, random forest, and SVMs. You will also get hands-on experience with Python, scikit-learn, TensorFlow, and real-world projects that bring every concept to life. So if you have ever wondered how machines actually learn, predict, and evolve, this is the perfect place to begin. Let's get started and explore how machine learning is teaching computers to think for themselves. If you're just getting started in data science, here's something important you need to know. You don't have to be a hardcore programmer. That might come as a surprise, but it's true. Data science is not about building complex apps or writing thousands of lines of code. It's about making sense of data, understanding patterns, finding insights, and solving real-world problems using numbers. And to do all that, the tool you'll use the most is Python. When you first start learning Python, you might feel the urge to dive into data structures and algorithms. And while it's useful to know the basics, you don't have to spend months solving binary trees or linked lists. Yes, you do need some programming, just enough to be able to work with data, read it, clean it, transform it, and get results out of it. Before we dive into the main concepts, let me quickly give you an overview of some basic Python that you'll need along the way. Now, if you've worked with languages like C or Java before, you'll find Python a lot easier to pick up. Let's start with creating a variable. In Python, you don't need to mention whether a variable is an integer, a string, or a float. You just need to assign a value and Python figures it out for you. For example, writing height equal to 175 is enough. Python knows it's a number, and if you write name equal to John, it understands that it's a string. Now let's say you have two variables representing the heights of two people. You can use a simple if condition to check who is taller. After that, one of the most important things in programming language is functions. And in Python, creating a function is as simple as using def keyword, giving it a name, and writing the block of code you want it to run. Then there's something you'll use a lot in data science, that is lists and dictionaries. In Python, a list is just a collection of items. It can hold numbers, names, or even a mix of different data types. You can add, remove, or change items easily, and Python gives you a lot of built-in tools to work with them. Next is the dictionary, a set of key value pairs. A dictionary lets you look up a word, the key, and get its meaning, the value. So if you want to know the person's age, you just use person and in the bracket you use the age and it'll give you the value. Now let's talk about NumPy, which stands for numerical Python. You might be wondering why use NumPy when we already have lists. Well, NumPy arrays are faster, take up less memory, and come with tons of built-in mathematical functions. Most importantly, NumPy allows you to create multi-dimensional arrays like tables or matrices, which are extremely common in data science, especially in machine learning. So instead of just a one-dimensional list, you can create something like this. This represents 2 rows and 3 columns in a matrix. You can also perform operations on entire rows and columns at once without any loops. NumPy is built for high-performance computing, which makes it perfect for scientific computing. So before we move ahead with pandas, I want you guys to understand the basic difference or the basic requirement why we need pandas. Alright, so basically we saw in NumPy how we were able to perform various numerical as well as arithmetic operations on our arrays. That was basically a data given to us in the form of arrays, right? So why exactly do we need pandas, or what is pandas? Alright, so in order to understand that, I am going to go ahead and show you guys an Excel sheet. So as you can see over here, I have some data. So once you guys get familiar with data analysis, you guys will be able to tell me that this is something known as house price prediction data set. But we need not get into the details of that right now. So for now, all you have to understand is that there are different features or different columns representing the features of a house, right? So we have the square feet, that is the area of the house. We have the city, we have the state, we have the condition, we have the waterfront, which basically is telling us whether there is a waterfront. So basically 0 and 1 is how our data is being represented. Okay. So the number of floors, the price, all right. So we have all these features in our data, all right. Now, if I were to represent the same thing in a NumPy array, I would have my array something like this. Okay, so say I'm just representing two houses, and these two houses have two bedrooms, two bathrooms, okay, and the other house has just one bedroom and one bathroom, okay. This is what my NumPy array would look like, okay. This is basically my house 1, my house 2, and this is my bedrooms, and this is my bathrooms. Okay, so do you guys agree with me or not? Would our NumPy array look something like this or not? Except we wouldn't have this information with us. We would just have an array that would look like this. So this is the major issue that comes in NumPy when we are dealing with data. Okay, so since we only have two columns over here, maybe we can try and remember that the first one is bedrooms, the second one is bathrooms. But in case we have 12 or say 50 columns, how are we going to remember what each and every column is representing? So this is where Pandas steps in. Pandas is nothing but a tabular format of data, just how we saw in Excel. It gives us a similar representation of data in our notebook. Alright, so before we go ahead and see the demonstration with Pandas, first we'll understand why Pandas. So here are some of the important features that Pandas provides us. So it gets very easy to import our data sets. It could be a CSV file, it could be an Excel sheet, okay? It could even be your SQL database. So you can import any sort of data set in your Pandas environment. I'll be using Google Colab in this video, but you can use Anaconda or even your VS Code, all right? Then comes your data cleaning. So this is a very important step. Now, what exactly does data cleaning mean? So when we say data cleaning, we are talking about missing values and majorly the invalid values. Okay. So when we talk about missing values, okay, let me go back to my Excel sheet. Okay, so this is the data that I have, right? So say in case of this particular value over here, 10500, what if I had a blank cell over here? That would represent my missing value. Okay, so that is basically what missing value means. So if we have a particular data set and some of the values in our data set are missing, so whenever we're dealing with that kind of scenario, we will be dealing with those missing values. Okay, we will be seeing how we can do that with Pandas. And the other case is invalid values. So say I have an age column. Okay, now we know our age can normally range from 0 to 100. Taking the worst case scenario over here, we have 100 or say 120. Okay, it cannot go above that and it cannot go below 0. Alright, so this is basically a standard age range. But what if I have a value say 200 in my age column? Now this is basically an invalid value, right? I cannot have an age that is 200 if it's for humans especially. Okay, so I would understand that there is some typing error or there is some mathematical error, and the common way of dealing with this invalid value would be dividing by 10, right? So 20 is a valid age, but 200 is not. Okay, so that is basically what invalid value means. Size mutability. So we can easily add and delete columns or rows. Okay, then we can reshape our data set, we can pivot our data set, we can efficiently manipulate and extract from our data set. And most important step is statistical analysis. Okay, so we can easily have all the statistical analysis of our data with just a few lines of code. Okay. Now moving on to the prerequisites to learn Pandas. So you need to know any programming language, preferably Python. But if you know any other programming language as well, it's not an issue. Okay. And the next one is maths. That is basically you need to know some stats or inferential statistics. You need to have a basic idea like what is standard deviation, what is variance, what is mean, median, mode. So basically you need to have a basic idea of all those terms. So moving on to Pandas, we have two primary data structures in Pandas. First is series, second is data frame. Okay, now what is data structure? Data structure is basically a collection of data types that provide the best way of organizing the items or the values in terms of memory usage. Okay, so series is going to be our one-dimensional data structure, whereas data frame is a two-dimensional data structure. Okay, now series basically represents only a single column from the entire data set, whereas a data frame is able to represent the entire data set. Okay, that's the basic difference. So let's go ahead. Okay. So series we already discussed is one-dimensional. Why it's one-dimensional? Because a series would look something like this. So say I have a price column and these values would be represented by an index value by default. Okay, and remember our index is always and always going to start from 0. So this is our series. Okay, so over here you cannot say this is a two-dimensional or it has two columns. This is the index and this is our one and only column. Okay, so this is why series is a one-dimensional data structure, because it can accommodate only one column and you can extend it to as many rows as you want. Okay, so it is a one-dimensional labeled homogeneous array. Homogeneous array means it can accommodate only either integers or string values. Now, it's not that if I were to add, say, a string ABC, I would get an error. Rather, if I were to add a value like this, all of my integers would be converted to string. Okay, so this is why series is called a homogeneous array, because if I add a single string value into my series, all of my integers are going to be converted into string, and my data type of this series would be object. Okay, if I were to have only integers, my data type would be integers. Okay, so this is basically what it means. And very important property is it is size immutable. Now what this means is I cannot delete a particular row from here. I can only remove it, and when I perform the remove operation, basically I am going to be returned a new string. That is, my string originally is not going to get manipulated, rather I'm going to be returned a new string where my values would look something like this. Okay, so this is basically what size immutability means. And even if we try to append a new element, we would be again returning a new series rather than manipulating or rather than changing the original series itself. Okay, now moving on to data frames. It is a two-dimensional data frame because we can have multiple columns. So we can have a price column, we can have number of bedrooms, number of bathrooms, and so on. Okay, we can have unlimited, or you can say n number of columns and n number of rows. So basically it can be extended in this direction as well as this direction, whereas series was able to extend itself only in this direction. Okay, and this is going to be a size mutable tabular structure, and it can be heterogeneous type. Heterogeneous means we can have, say, integers in this column and a string, all the string values in this column. Okay, so we can have multiple data types supported in data frames, and it is size mutable, means you're easily able to add and delete the rows and columns. Okay, so I hope the difference between series and data frame is clear. So let's go ahead and look at the implementation in our notebook. But before we do that, I hope you guys remember you are supposed to install pandas using pip install command. Let me just show you guys quickly. So you can go to your terminal or any command prompt, and all you have to do is type pip install pandas. When you run it, you're going to have a few lines of code run for you, and then finally you're going to get your requirement is satisfied, and then after that you can proceed with importing pandas as PD. Okay, so again, this is an alias. Just like we used an alias for NumPy, we are going to use one for pandas, which is PD. Okay, so I'm going to run it. And if you guys remember, I told you guys in the NumPy video that NumPy is going to be used throughout your data analysis process. So right now we are going to focus only on the pandas features, but when we come to real data sets, which I'll be showing you, I'll be importing a real data set also using a CSV or an Excel file, and then I'm going to show you how NumPy and pandas both are going to be used to perform various operations on that data set. Alright, but right now we are going to be only focusing on pandas, understand the features and the implementation. Okay, so as you can see, I have successfully imported my pandas, and the green tick over here basically represents that the operation was successful. Okay, so now what I'm going to do is I'm going to create a basic series using pd.series, and I'm going to do so using a list. Okay, now if I go ahead and print it, so you can see my data type is int64 because all of these are integers, and by default I got an index value of 0, 1, 2, 3 and 4. Okay, so as I told you, my index is always and always going to start from 0, And now if I were to add another element, say a string value ABC, you can see now my data type is object, and all of these that were integers earlier have been converted into a string form. Okay. So I am going to remove this for now because I want to show you guys some operations that we can perform in series. So I can go ahead and check the data type of my series. It's in 64. Then I can go ahead and check the values of my series. Okay. So you do not need any parenthesis. So these are the values of my series data structure. So you can use s.index to check the index of your series. So you can see over here my starting value is 0 and my stop value is 5 and my step value is 1. Alright. So basically I have my index from 0 to 4. So here you can get an idea about your index as well. Okay. And lastly you have s.name. So it's not printing anything because it's none. So if I print s.name, you can see it's none because we have not given any sort of name or any sort of value to our column. Okay, in order to assign a value to our column, we can just say s.name and we can assign a value to our column, say those are just numbers. So I'm going to write numbers, and if I print my series, you can see this is what my series is going to look like. Alright. So that was it about the random functions. Now we're going to look at an important topic called indexing. Okay. So you can do indexing using square brackets like we normally do for lists, and we have also done for NumPy arrays. So similarly, you can do it for your series in pandas. So if I want the first element, I'm going to say S0 and I get the first element, that is 10. Okay. So if I want multiple elements, all I'm going to do is S0 to 2, and you can see my ending index or my ending value is not included in my output. So let me just comment it over here. And then we have the step value. So we have done this indexing in list as well. And you guys are well aware that your starting value is always included, whereas your ending value is never included. Alright, so whichever value you want at the end, you give your stop value plus 1 to your desired value you want in the end. Alright, so say I want values at index 2 and 3. My syntax for that would be S2 to 4. Okay, so as you can see over here, I got my values at index 2 and 3. Alright. Now another way to perform indexing is by using a function called ilog, which basically does location based indexing. So what this means is it is going to use the indexes, that is the 0, 1, 2, 3, 4 that you have as indexes, and it is going to fetch the values at those particular indexes for you. So all you have to do is say s.ilog and value at 3, and I print it, and you can see I got 40. So at index 3, I have value 40 and it's giving me the correct value. Okay. Now if I want multiple values, all I have to do is s.ilog and use double brackets and pass all the indexes that I want my values at. Okay. So I want value at index 1, 3 and 4. So as you can see, I got my output just as I intended. So this was all about location-based indexing. Now another important feature in series is that you can change the index according to you. Okay. So instead of 0, 1, 2, 3, 4, these numbers actually represent the calories. Okay. These are the different calories. So you can see I have changed the column name to calories. And now I want these calories to represent the fruit. Okay. So I'm going to create a list of all the fruits that are present in my carries. So you can see I've created a random list of fruits and I've stored it in the variable index. Now what I'm going to do is I'm going to say s.index and I'm going to pass my index variable, and then I'm going to print my series. So you can see over here, I am basically trying to say my apple has 10 calories, banana has 20 calories, grapes has 30 calories and so on. Okay. So this is how you can change your indexes according to the information you are trying to represent. Now do not comment that I have put wrong calories for the wrong fruits. This is just a random data that I have created just to show you guys how indexing works. Okay. So now if I try to access any value using my indexes, so if I want to find the calorie of grapes, I can just say s grapes. Okay, in square brackets. Now can I use ilog function over here? Let's try it. Okay, so I get an error because this is not a location anymore, right? So when I had my numerical indexes, ilog was working absolutely fine. So I can still use ilog, but for my numerical indexes, right? The original indexes. That is, we have indexes in lists, we have indexes in NumPy, we similarly have indexes in series as well. Okay, so we can do that by ilog, but again, how will we remember what is index 3, right? So that is why we have another function called log. This is label based indexing. Okay, so using log, we can go ahead and say, and you can see I get my value. Okay. Now, another important thing you need to remember is in label based indexing, your start as well as stop value both are included in the output. Okay. Now, this is a very important thing that you need to remember, because unlike normal indexing or the indexing that we do in list, numpys and all, whenever we are using a normal list, our stop value is never included. Alright. Now, say I want my calories of banana, grapes and orange. Okay. So, what I'm going to do over here? So, you can see my banana, grapes and orange. So, all three of them, that is my starting value as well as my ending value, both have been included. I hope label based indexing and location based indexing, that is your normal indexing, the difference between both of them is clear. Difference between log and ilog is clear. Okay. So let me give you guys a quick recap. We learned how to create a series using a list. Okay. We saw the default indexes. We saw the default name, which is none of the column. Then we saw how to check the data type of the series. We saw how to check the values and the indexes of the series. Then we saw how to rename our column or the series. Okay. And then we went ahead and looked at indexing. We saw normal indexing. We saw indexing using ilog. Okay. Then we went ahead and changed the index of our series. We gave a different set of indexes to our series using s.index equal to the new index. And then we went ahead and performed indexing on our labels. That is, we used the new indexes to index the values. And then we also looked at the label based indexing, that is using log. Okay. Now, if I want to access multiple elements over here, multiple values, again, I have to give double brackets and I can say grapes and then I want apple and I can print it. So you can see I got my desired output. Okay. So that is all about indexing. Now, let's also see how we can create a series using a dictionary. Okay. So I have already created a dictionary for you guys, which is basically fruit protein. So our keys are the fruits and our values are the proteins or the grams of protein stored in that particular fruit. Okay, so this is our dictionary. Now, if I want to create a series out of this dictionary, all I have to do is say, I'm going to name it S2 because this is my second series, and I'm going to say pd.series fruit protein and I'm going to print it. Okay, so you can see, and by default, the name of our column over here that is representing the protein is 0. So I can go ahead and say name equal to protein. Let's run it. Now my series is giving us a complete information of what our data is representing. Okay. And you can see the data type over here is float. Okay. Again, you can go ahead and perform the similar kind of operations on this particular series. I will be sharing this notebook with you guys in the description below so you can download it and do the necessary operations that we saw in our earlier series, that is our series S. So all those operations can be performed on this particular series as well. So I want you guys to pause the video, download the notebook and perform these operations. And if you guys face any doubt, comment it in the chat box below. I will respond to you guys at the earliest possible. Okay. Alright, so I'm assuming now you guys are done with the earlier operations. Now we'll be looking at something important and something new, which is called conditional selection. Okay. Now what conditional selection basically means is, now I want to fetch all the fruits over here that have protein greater than 1. Okay. I want to find out all the proteins that are greater than 1. So what I'm going to do is, I'm going to say S2 greater than 1. Now you can see over here I've got boolean values that are representing true and false. So wherever I have protein greater than 1, I got a true. And wherever it is less than 1, I got a false. Okay. But what if I want only those rows in my output that have the value greater than 1? So what I'm going to do is I'm going to put this conditional selection statement inside my series. So I'm going to pass it inside my original series and you can see I got the result. Okay, so all these fruits have protein greater than 1. Okay, so this is basically how conditional selection works. It is first going to provide you with a mask series, which is basically a series of Boolean values true and false. And if you pass that masked series into your original series using square brackets as we just did, you get your desired output. So our next topic is logical operators. Okay, logical operators, we have and, or, and not. So I hope you guys are clear with what is and or not. Okay, if you guys are not, let me just give you guys a quick example. Okay, so say I have two values, one is true, the other is also true. Now if I do a and between these, if I perform an and operator between these, my result is also going to be true. Okay, now if I have a true and a false and I perform an and operation between these two values, my result is going to be false. Okay, similarly, if I have a false first and a true later on and I do an AND operation, my result is going to be false. And if both my values are false, my result is again going to be false. Okay, so we need both our values to be true in order to have a result true. Okay, but in case of OR, any one of our value has to be true. This is going to be true. But if I have true or false, it is again going to be true. Okay, if I have false or false, then it is going to be false. Okay, so this is basically and or. Okay, now let's see how it is used in a series. So say I want to give a range. Okay, I want to have all my fruits, or I want to see all those fruits which are greater than 0.5 but less than 2. Okay, so all I'm going to do is s greater than 0.5 and s is less than 2. So this is the syntax that you have to follow. Okay, so you can see I got the true and false values. Now if I want to find only those rows which satisfy this condition, so you can see all these values are going to be between 0.5 and 2. Okay, I can see I can say less than or equal to 2, and now I have my fruits which have the protein value equal to 2 as well. Okay, so this is how AND is performed. So basically what happened there is wherever we had 0.5 and greater but less than 2, this range was passed to us when we use the AND operator. Okay. Now if I were to use the OR operator in this particular scenario where I'm trying to find this range, would I get this desired output? No. For the OR operator, my first condition would be greater than 0.5. So I would get all my values that are greater than 0.5. And then my second condition would be less than 2. So I would get all the values which are less than 2. That means below 0.5 as well. Alright, so as you can see over here, I have 0.3 and I have 2.6 as well in my output. So this is basically telling me that I have used an OR operation over here. Okay. So similarly, you can use AND and OR and you can also use your NOT operation. So I can say I want all my values which are not greater than 1. Okay. So you can see all these values are smaller than 1. Okay. So this is how the logical operators like AND, OR and NOT are performed. And then finally we have a topic of modifying the series. Okay. So say instead of my calorie of mango to be 0.8, I want it to be 2.8. So what I'm going to do is, just like a normal list, I'm going to go ahead and say S mango and I'm going to say 2.8. Okay, so it's run successfully. Now if I print my series, you can see my mango protein has been changed to 2.8. Okay, so this is how you can modify your series. Okay, at any particular index. You can change the value. You can also change the index, but you will have to pass your entire index again. Okay. So this was all about series. Now we are going to move ahead with data frames. So I hope series was clear. If you guys have any doubt, comment your doubts in the chat box below. I will respond to you guys as quickly as possible. And do make sure that you guys have this particular notebook downloaded in your systems and you guys are working with me side by side. So that's going to make the entire process more fun. Okay. So far you guys have gotten a basic understanding of series and we have already covered NumPy. So I have a question for you guys. So basically I have a series and I want you to find the answer of this particular query. Okay, so if I say s dot not null and I say I want a sum of all the values that are not null, I want you guys to quickly comment the answer in the chat box and tell me what's going to be the answer in if we run this particular query. Okay. So moving on, let's look at our very next topic, that is data frame. So it is important and very interesting if you guys understand it carefully. So basically I have some data in the form of dictionary, as you can see over here. So I have some names, I have some ages, and I have some departments and salaries. Okay. And now I want to convert this particular, so if I print this data, it's going to look like this. Okay. It's not very neat and it's not very easy to understand. So what we're going to do is we're going to go ahead and convert it into a data frame, and let me just print the data frame for you. Okay. Alright, so I have this particular data set with me. So if I want to see just the starting values, I can just say df.head and say I want to see the first two rows. Okay, so I can do it using .head function. And if I want to see the last values, I can just say df.tail. Okay, so by default the parameter over here is 5, but if we want we can tailor it to our own needs. So I want to see the last three rows, so you can see 5, 4 and 3. Okay, so moving on, we can again use our log and ilog functions just like we did with our series. So say I want to fetch the first and second row of my data set. So what I'm going to do is I'm going to say df.ilog and I'm going to say 1 to 3. Okay, so you can see I have my first and second row and all the columns. Okay, so now in case of all these columns, what if I want only department and salary in my output? So what I'm going to do is I'm going to say df.log. So instead of ilog, I'm going to use log and I'm going to say rows 1, 2, 3 and I'm going to say I want columns age and department. So I'm going to have a comma over here to separate the columns. So you can see over here I have age and department and my 3 rows. Okay. So we discussed earlier, whenever we use the log function, our starting as well as ending indexes are going to be included. So I have 1, 2 and 3 rows instead of just 1 and 2. So if I want just the 2 rows, I have to say 1 and 2. Alright, so I hope this is clear. Okay, so we can use ilog and log in this manner. But if I wanted to include my first and second column in my ilog column itself, so you can see I have my first 2 columns in my output. Okay, so basically when we're using ilog for data frames, we have to pass our rows and our columns, and the range for these are going to be separated by a column. Okay, so we can do that using ilog and log. So we'll be using this a lot. Okay, direct indexing in a data frame gets a little complicated, so that's why we'll be only using ilog and log functions. Okay, so you can go ahead and play around a little with ilog and log and try to access different rows and different columns. So now we'll be moving to accessing only an individual column. Okay, now if I want to access just one particular column, all I can do is say df_age. So this is how I get only the age column. Okay, now if I want multiple columns, I have to add another bracket and I can simply separate my columns and say I want age and department. So you can see this is how I get my output. Okay, now what if I want to drop this age column? Okay, so you can see I have a null value also over here. Now I want to drop this age column because I feel it's not very relevant to my data set. So how I can drop it is I will just say df.drop and I will say age. Okay, and I will pass axis equal to 1 because I want this entire column to be gone. Okay, if I want a particular row to be gone, my axis would be 0. Okay, so it is a particular row wise operation. But if I want a column gone, I want my axis to be 1. Okay, so if I run it, now you can see my age has been disappeared from this particular output. But if I print my data frame, you can see the age is still there. Okay, so until and unless we use the parameter in place equal to true, by default in place is equal to false. Okay, so in place is basically telling us to perform the operation in the original data frame. Okay. So if we want the changes to be displayed in our original data frame, we are going to use in place equal to true. Otherwise, by default, it is going to be false, and it is only going to return a new data frame, and our original data frame is going to remain unchanged. Okay. So as you can see, it has been unchanged. Now this is a missing value over here, this and this. So we'll be dealing with these missing values later on. But first, let's understand a few more functions. So we can go ahead and check the shape of our data set using df.shape. So this is telling us that we have 6 rows and 4 columns. Okay. 1, 2, 3 and 4. Okay. So again, the indexes are not counted as a part of a column, just like we did in series. Okay. So these are by default values over here. And we have 6 rows. Okay. So we basically have 6 samples. Okay. These are known as samples. This is the sample sets. Okay. So we can also go ahead and check the data type of our data frame. So we can also go ahead and check other information about our data set. So using info. Okay. So this is telling us that we have these particular columns: name, age, department and salary. Okay. And these are the data types in our column. So we have 2 columns having float data type and 2 columns having object data type. Okay. So name has object data type, age has float data type, department has again object data type, and salary has float data type. Okay. Now over here we have a non-null count. Non-null count basically means that we have 6 non-null values. That is, we have total 6 samples and all of these 6 samples are non-null. Okay. So basically in the name column we have 0 null values. Okay. And we move to the age column, and over here we have 5 non-null values. That means we have 1 null value over here, and over here also we have 1 null value, whereas over here we have 0 null values. Okay. It is also displaying the memory usage to store this particular data set. Okay. And another operation that you can perform on your data set is describe your data set. So over here you get statistical information on your data. So over here we only have 2 data sets that are of type float or integer. Okay. So we can perform these particular operations, that is the count, mean, standard deviation, minimum value, and these 25%, 50%, 75% are basically the outliers in our data set. Okay. And the maximum value. Okay. So using the describe function, you get a basic information about your data, like you have 5 values in your age column and 5 values in your salary column that are present. Then the mean value of your age column is 28, whereas mean value of your salary column is 58400. Standard deviation is this. The minimum value of age is 25 and minimum salary is 50,000. Then you have other information about your data set. Okay. So in NumPy, we saw an important concept called broadcasting. Okay, we also looked at the rules for broadcasting. Now we'll see how broadcasting is performed in Pandas. Okay, so I have a salary feature over here. So our columns are also known as features. Okay, so these are our columns or our features. Okay, so if I want to say increase the salary of all the people over here, okay, of all these people, I want to increase the salary by say 5,000. All I have to do is say df salary, and I will say df salary plus 5,000. Okay. Now you guys must be wondering, this is a scalar digit or an integer, whereas this is a one-dimensional array, right? If I just print df.salary, let me go ahead and print df salary. If I print this, you can see this is a one-dimensional array, right? This is basically an array having 5 rows and 1 column, right? And this over here is just a scalar value. Now I want to increase all these values by 5,000. So do you think if I perform this particular operation, I will get an error or will it successfully perform? So if you guys said it will successfully perform, you guys have understood broadcasting really well. So if I go ahead and print my salary now, so you can see it has been increased by 5,000. Okay. So what's happening over here is, instead of treating this as a scalar value, it has been broadcasted to match the shape and size of this particular column. Okay. And then the operation has been performed over here. Cool. So moving on to the next concept, we have renaming columns. That is, we can rename the columns in our data. Okay. So if I want to rename a column, all I have to do is called df.rename and pass my columns. Okay, so I want my department column to be displayed as DEPT. Okay, and I'm going to say in place equal to true because I want this operation to be performed in my original data set itself. Okay, so if I go ahead and print my data, so you can see my department has been changed to DEPT. Okay, so this is how you can go ahead and rename your columns using dot rename function. So you can also go ahead and check the unique values in your data for a particular column. So I want to see all the unique salaries in my data set. So you can see over here, these are the unique salaries in my data set. Okay. I can check it for another column. So I can check the unique departments. So again, these are case sensitive. So if I check the unique departments in my data set, so I have 3 unique departments, that is HR, IT and finance. Okay. Now, if I want to see how many employees are in which department, I can go ahead and do the value count of these departments. So I will say DPT dot value counts. Now, as you can see over here, HR department has 3 counts, IT has 2 counts and finance has 1 count. Okay, so basically it's telling us that there are 3 people in HR team, 2 people in IT team and 1 in finance team. Okay. So this is how you can check the distribution of one particular column across your data set using value counts. Now, what if I want to create a new column called promoted salary? That is, I want to check the salary of all the employees after the promotion. Okay. So say some of my employees have been promoted and I want to create a promoted salary column in my data set itself. So if I want to do that, all I have to do is say df original salary, and after the promotion their salary is going to be say multiplied by 10. Okay, so if I run this particular query and then print my data frame, so you can see the salaries have been increased in my promoted salary column. Okay, so they have been multiplied by 10. Again, this is a broadcasting rule again. Okay, so this is how you can go ahead and create a new column in your data set or your data frame. Alright, so now that we have learned how to create a new column, I think it's time to dive into data cleaning. So as you can see, we have a few null values in our data set. So I want to get rid of them because till I have those, I will not be able to perform some operations, plus it doesn't look very good. Okay, so first I'm going to check how many null values exactly I have. So all I did was I checked for my null values inside the entire data set and then I did a sum of all those values. So as you can see over here, my name column has 0 null values, my age column has 1 null value and my salary column also has 1 null value. And so does my promoted salary column. Okay. So I have a few options over here. I can either just get rid of all the rows that have these null values. Okay, so I can do that by using df.drop na. Na stands for null values. So I'm basically dropping all the null values, and if I just run this prompt, if I just run this without any sort of argument or without any sort of parameter, as you can see, I'm just left with 4 rows. Okay, so basically any row that had null value has been removed. And again, I have not used in place equal to true, so my original data set is still untouched. Okay, so this is basically just a new sort of data set that has been altered and returned so that I can see how it's going to look. Alright, so by default over here, you can see my argument of how I want my null values to be deleted or dropped is any. So basically any row that has any sort of null value has been dropped. Okay, so if I run this using how equal to any, so again my result is the same. So we saw one sort of parameter in drop na, that is how equal to any. Now the other parameter in drop na is all. Okay, now the other argument that drop na takes is all. Now what this is representing over here is particular row. Okay, when we said how equal to any, we were just saying any row that had any null value. Okay, so whichever row had any null value was dropped. Now over here we are saying if all the values in a row are null, we are going to drop that row, otherwise we are not going to touch it. Okay, so we do not have any row that has all the null values, we just have this row that has 2 null values, but again, we have 3 non-null values as well in this particular row. So again, none of my rows were altered and the data remains as it is. Okay. So this is one option when we are dealing with missing values. We can just get rid of those null values. Okay. The other way is to fill those missing values. Now, how I can do that? So let me just find, okay, here is my null value, right? So I can either fill this null value with the most repeated value in this particular column. Okay, that is one option. Let me just write it down for you guys. Okay, so dealing with missing values is one of the most important aspects when it comes to a data set, because you will be dealing with a lot of unclean and messy data sets, and missing values is going to be one of them. Okay, so let me just write missing values. So one way of dealing with missing values is getting rid of them, which we just saw by using drop NA. Okay, and the next one is by filling them up. And for filling those missing values, we use the function fill NA. Okay, so this is the second method. Let us see how it works. Okay, so all I have to do is say df.fill_NA. Okay, and let me just run it. So I must specify a fill value or method. Now I want to fill all the null values with say 0. So you can see this is what my data set is going to look like finally. Okay, but this is again a very noob method to perform on a data set, because I do not want my age to be 0 or my salary to be 0 just because it's missing, right? So instead, what I can do is, for my age column, I am going to fill all my missing values with the mean. Okay, and I'm going to say, okay, let's not keep it in place equal to true, because I do not want to modify my original data. But if you guys want to, you guys are free to do it. Okay, so I'm just going to replace all my missing values in the age column with the mean of the age. Okay, so initially my third row had a missing value and now it has been replaced with the mean. All right. Similarly, for the salary column, what I'm going to do is, if I replace it with the mean, it's not going to be very technically or mathematically correct. So instead, what I can do is, I can replace it with the median, right? I can go ahead and replace my salary in my df column, and I'm going to say I want it to be filled with the median of my salary. So you can see over here, my fourth row was missing in my salary column, and now it has been filled with the median value. Okay, so this is another way that you can fill your missing value. Okay, now this is something that we can do mathematically, right? But what if I want to just randomly fill my value? So this was the missing value, right? So there is another method in fill NA. Instead of providing a default value, what we can do is something known as forward fill. So basically, when we use fill NA, we have two methods, forward fill and backward fill. So in forward fill, what happens is we move from top to bottom, okay, and say this was our missing value. So when we use forward fill, 35 is going to be replaced in our missing value. Okay, and similarly, when we do backward fill, 29 is going to be replaced for our missing value. Okay, so this is basically what forward fill and backward fill means. So let us quickly go and perform forward fill first. Dot fill NA, and in our method, we're just going to pass forward fill. Let's run it. So you can see 35 has been replaced in our missing value column. Okay, so it has been done using forward fill. Similarly, I can perform a backward fill. So you can see 29 has been replaced in my missing column. Okay. Now using these methods, backward fill and forward fill, can be a little tricky, and they can also give you errors in cases where your first or last value is null. Okay, so in case your first value is null and you try to do a forward fill, your first value will still remain null. Alright, and same goes for backward fill. If your last value is null and you do a backward fill, your last value will still remain null because there won't be any value before that to replace it with. All right. So in cases like that, we go for statistical operations like mean, median, mode. All right. According to what's more technically sound. Okay. So these are some of the methods to uh, deal with your missing values. Okay. So now we saw how we can deal with missing values. Now we'll look at another operation where we can say replace a particular value randomly. Okay, so say instead of Charlie over here, I want to replace this name with another name. So now, just because we did not use in place equal to true throughout our queries when we were dealing with our missing data, does not mean we have not already dealt with them. We have already dealt with our missing data, and currently we shouldn't have any sort of missing values in our data set. Okay, so moving on, I want to just randomly replace this particular name, say with Rose. Okay, so I want instead of Charlie, I want Rose in my name column. I just have to say df dot replace. Okay, df in the name column. Okay, I have to specify the name. Sorry, I have to specify the column, and I have to say replace Charlie with Rose. Okay. So as you can see, my operation has been performed successfully. Okay. And again, if I wanted this change to be reflected in my original data set, I would have to say df name, and I would basically be storing the change in my original data set. And now I can go ahead and run it. So as you can see, I have changed the name from Charlie to Rose in my original data set as well. Okay. So this is how you can make your changes permanent. Okay. All right, so let's look at the next concept when we're cleaning our data, that is dealing with duplicate data. Okay, so we already saw how we deal with missing values. Now we will see how we deal with duplicate values. Okay, so as you can see in this particular data set that we have over here, we have the entry Alice twice. Okay, and as you can see, the age, department salary, and the promoted salary, they match for both these records. Correct? So how do we deal with duplicate values? So we already have an inbuilt duplicated function. So in order to check for all the duplicate values, all you have to do is say df.duplicated and pass it in the data frame variable. And when you run it, and your output will be your second repeated record in your data set. Right? So we are not going to consider this as duplicate. Rather, we're going to consider this as duplicate. So let's see how duplicated works. Okay, so say I have a record over here of different countries. Okay, so I have Italy, France, Greece, and then Italy again. Okay, so if I go for duplicated method, what happens is we work our way from the top itself to the bottom. Okay, so first I'm going to check for Italy. So Italy is not present. No problem. I'm going to simply add it to my list, or uh, a list where basically I'm keeping a track whether an element is duplicate or not. Right. Then comes France. So it's not there. No problem. I add it to my list. Then we come across Greece. No problem. I add it to my list. Then I come across Italy, which is already present in my list. So therefore, this element is going to be marked as duplicate. Alright. So this is basically how the duplicated method works by default. Alright. So basically we can pass a parameter called keep, and we are going to say keep first. Okay. So let's see what happens now. So you can see our first element is not going to be marked as duplicate. So this is basically by default the parameter that duplicated takes. Okay. If I say last instead of first, you can see my first element is marked as duplicate. Okay. So when we say keep last, basically we are going to work our way from bottom to up. Okay. So that's why this element is going to be marked as duplicate. Alright. So I hope this is clear. So if we want to drop this duplicate value, all I have to do is, okay, so I'm not going to pass anything because I would prefer my second record to be deleted. So I'm just going to run it. So if I print my data set, you can see my duplicated record, that was the second record, has been removed or deleted from my data set. Alright. Okay. So I hope the data cleaning process is clear. We have learned how to deal with missing values as well as duplicate values. Okay. Alright. So let's see how we can deal with invalid values. Okay. So since I want to make the changes in my promoted salary column, I have simply written df and promoted salary in the brackets. And now in order to do these changes in the column of a particular data set, I will be introducing you guys to a very important topic or an important function called lambda. So you guys must have studied this in Python as well, right? So all we have to do is promoted salary, and I will say apply lambda x, and I'm going to say divide that x. X is nothing but the records of my column promoted salary. So this is my input variable x and this is my output variable x divided by 10. But I have a condition: if x is greater than 6,50,000, right? Else, if it is not greater than 6,50,000, I'm simply going to return x. Alright. So let me run it. Okay, so it has run successfully. I'm getting some sort of documentation, but I'm going to ignore it for now. Okay. So as you can see, the two records that I had that were greater than 6,50,000 have been divided by 10. Alright. So this is how you can deal with your invalid values using the lambda and apply function. Alright. So this is the syntax for that. So moving on, we'll also look at some string functions. So in this particular sample data set that I have taken, we do not have any sort of explicit need to do these string functions. Okay, so maximum times whenever you have a string input, okay, so say the names. Over here, I just have the first name, but in case I had a name like Alice underscore, say, Fernandez, okay. So in order to deal with inputs like this, all I would have to do was df, and I would create two separate columns saying first name and last name, okay. And then all I would do was VIF, and I would split my name column. So basically right now I'm using name as this name instead of my column name because I do not have any sort of input like this which I want to demonstrate to you guys. Okay. So even though this is not a column per se, this is just a variable that I've created, and I'm pretty sure I'm going to get an error. Okay. So I am going to split it using string dot split method. Okay. And I want to split it based on underscore. Okay, so wherever I have an underscore, I want to split my string. Okay, so in case instead of underscore all I had was a space, I could use an empty string over here. Okay, but since I have an underscore between my first string and my second string, I'm going to split it based on my underscore. Okay, and let me see if I run it, what's going to happen. Okay, so I do not have any column name, but again, this is how you would split your data set. So obviously this code is not going to run for me because I do not have any column called name, and wherever I have name, I do not have any sort of connectors between two strings. These are just single names. Alright, so I will not be able to split these particular strings over here that I have. So this is just a demo for you guys, that in case you have a column like this is how you're supposed to deal with it using string.split method. Alright. So now that we are clear with data cleaning, I want to show you guys a few more examples of apply and lambda. Okay, so because there will be instances where these methods are going to be very useful because they let you change the single entries of a column or a row, right, based on particular conditions. All right, so let me create another scenario where I want to multiply the age. Okay, I want to multiply all the ages by 2. Okay, so all I'm going to do is age, and then I'm going to call my age function, age column over here, and then I'm going to say I want to apply. Now instead of passing lambda, what I can do is I can go ahead and create a function where I am multiplying my age. Okay, I'm going to have my input as x, and then I'm going to simply return x into 2. Okay, so instead of calling lambda over here, what I can do is I can say multiplying age and pass x. Okay, so it will not take any input. I'm sorry about that. So let me run it. Okay, so now if I print my data frame, you can see my values of age have been multiplied by 2. Okay, so let me bring back my ages to the original value. Now this time I will use lambda instead of creating a function by default. Okay, and I'm going to say apply, and I'm going to pass lambda, and I will say x, and I will say x divide by 2. Okay, now there are no conditions, there are no if else conditions. I want all of these entries in the age column to be divided by 2, so I'm not going to pass any if else like we did previously, right? So I'm going to run it, and if I print my data frame, my ages are back to the original values. Okay, so this is how lambda and apply functions are used, and you will be using them quite a lot. Okay, so moving on, I want to tell you guys about another very important concept, that is joins and merges. Okay, now in order to understand joins, let us go through a quick overview of what are joins. Okay, so consider this scenario where I have two data sets, A and B. Okay, now when you're dealing with large data sets, it's not necessarily that you're going to have all the columns in one particular data set. Okay, so if you guys remember, I showed you guys an Excel sheet of various columns or various features of a house, right? Number of balconies, number of bedrooms, the location, the state, and so on, right? Now I had all those columns in one particular sheet. But what if I had two sheets, A and B, where in one sheet I only had, say, the features of the house, that is, the number of bedrooms, the number of bathrooms, the balconies, and in another sheet I had the different features, say when the house was built, where it's located, what's there nearby, and stuff like that. Okay, so I had two separate sheets. Now I want to combine these sheets. All right, so there are different methods. So if we talk about joins, there is left join, right join, outer join, and inner join. Okay, these are the joins that exist. And another method is to merge. Okay, merge is similar to inner join. All right, so let's quickly see what left join would look like. So if we were to combine these two data sets on, say, a particular property, and we perform a left join, our left side of the data set, okay, whatever there is common between the two data sets is going to be ignored. Whatever exists in only data set B is going to be ignored. Rather, we are going to have something that is solely available with data set A, and this happens in left join. Okay, similarly in right join it happens the opposite way. We're going to have only the properties of B in our data set. Okay, and when we perform a full outer join, we're going to have everything of A and B. Okay, so each and everything that we have in A and B is going to be included in our outer data set, sorry, outer join. And when we perform an inner join, it basically happens over here. Okay, only the common properties between A and B. And when we merge two data sets, we merge them based on this particular common column, and whatever properties A and B have, both are visible in our merged data set. Okay, so let me say this is another data set. So let me just convert it into a data frame. So I'm going to call it df2, and I will say pd dot data frame, and I will pass my department. Okay, so let me just print my other data frame. So as you can see, this is my second data set. So now if I want to combine the information from this data set and the data set that I had earlier, I have something known as concat. Okay, so concat is going to let me merge the information from both these data sets. So if I use pd.concat and pass the two data sets that I have, this is the output that I'm going to get. Okay, so since in our second data set we have a location and manager, but we do not know which employees have this location and this manager, we have a null over here. Okay, so by default both my data sets are being combined in a horizontal manner, that is, they are being stacked horizontally, right? So wherever I don't have the names, I am getting null, and wherever I don't have the location and manager information, I'm getting a null. Okay, but if I were to do the same operation column wise, that is, if I were to combine these two data sets in this particular direction, I would have to say pd.concat, pass my two data sets df and df2, and I would say I want it to be joined on axis 1. So as you can see over here, wherever I have department HR, my location and manager is for the department HR, right? So this is how you can combine or merge two data sets using pd.concat. Okay. There is another function called pd.merge. Okay. So you can pass your data sets df, df2, and I want it to be merged on my column department because that is the common column. So as you can see over here, my department is being repeated twice. But if I do not want that to happen, I can use merge, and as you can see over here, my department column appears only once and my data is managed accordingly. So wherever I have HR department, I'm going to have my location as New York and manager is going to be Laura. Okay, it is, you can see it over here as well, New York and Laura. Alright, so this is also how you can merge or combine your two data sets into one. Okay. So these were basically all the operations that were there to know on data sets. The basic operations, obviously, as you go down the line, you deal with bigger data sets, your operations get more complex, but this is the standard basic base that you require to get started with Pandas. Alright, so now we're going to look at how we can import a complete data set file, that is an Excel or a CSV file, in our notebook. So since I'm using a Google Colab notebook, I cannot directly pass the entire path of my file or my CSV or Excel sheet. If you're using Anaconda or VS Code, you can do that. So if you're using those platforms, all you have to do is right click on your data set and click on copy as path and create a variable and just say pd.read underscore CSV because this is a CSV file, and all you have to do is pass the path inside the parenthesis as an argument. Alright, but since this is a virtual environment and it is not going to be able to access my local environment, what I have to do is I have to upload my data on Google Colab. Okay, so I'm simply going to select it. So as you can see, it's uploaded over here. Okay, so now all I have to do is, in quotes, I have to say data.csv. So you can see it's run successfully, and now I can do data.head. That is, I'm trying to get the first 5 rows of my data set. So you can see this is the date, price, bedrooms, bathrooms. So I can easily access all the columns and I can go ahead and perform the basic operations, like I can check the shape of my data set using data.shape. So I have 4600 rows and 18 columns. Alright. So accessing such information in an Excel sheet would have been a much more difficult task. So this is why we use Pandas, which helps us gather information like this in a much more efficient and easy manner. Alright. So I can also go ahead and check the information of my data using data.info. So you can see I have 4600 non-null values. That means I have 0 null values in my entire data set. I have 0 null values. Okay. So you can also check the data type of each and every column. Now you can see over here, this is an object data type, but date is supposed to be in a time format, right? You're supposed to be able to access the day, time, and year of a particular date in an efficient manner, but this is stored in an object manner. All right. So I'm just going to quickly show you guys how you can convert this date time from an object to a time. Okay, so this is the syntax that you have to follow. So I'm going to pass my date, and then I'm going to use pt.datetime to convert my date from object to, okay, so it is data. Okay, so as you can see, it has been executed successfully. Now if I go ahead and check my information of the data, you can see it is converted to date time format. Alright, so this is how you can convert your date time features into the valid format using Pandas. Alright, so this is again only a one-line code, but you should be aware that it can be done, and this is how you bring your data to the correct format. Alright, so this was it for this video. I think we have covered almost everything there is to know about Pandas, and I'm sure you guys got a basic understanding of how you guys can implement Pandas on even a large data set. And I am going to give you guys this notebook link in the description, so you can go ahead and download it and practice on this dataset, or you can download datasets from Kaggle. Let me show you guys the website. So you can go ahead and type Kaggle and click on the first link that you get. Register on this website and you get hundreds and thousands of data sets for absolutely free. You can download them and you can also go ahead and check out the discussions if you face any issues or doubt, right? In this video, I'm going to walk you through the basics of visualizing data using one of the most popular Python libraries out there, Matplotlib. And something important that I'll be discussing, which is often neglected while learning Matplotlib, is how to choose the right type of graph based on the kind of data you have. Not just that, we will also see how to read these plots and make sense out of them. But before we jump into it, let's take a moment to understand what data visualization actually means and why it matters. Data visualization is all about turning raw data into visuals using things like charts, graphs, or maps. These visuals help us quickly see patterns, spot anything unusual, and just get a better sense of what the data is telling us. Here's a quick example. Let's say you have a list of sales numbers for each month of the year. Sure, you could look at those numbers one by one, but if you plot them on a line chart, you'll instantly see how sales went up or down over time. That's the beauty of data visualization. It helps make data clear, simple, and easy to understand. Now coming back to Matplotlib, this is a Python library built specifically for creating visualizations. It's been around for a long time and is widely used in areas like data science, research engineering, statistics, and business management. What makes Matplotlib so powerful is its flexibility. You can create all kinds of plots like line charts, bar graphs, scatter plots, histograms, pie charts, and even 3D plots. And the best part is you can fully customize how your plots look, from colors and styles to labels, titles, and legends. When it comes to using Matplotlib, there are two main ways to make your plots. The first one is through something called the PyPlot API. This is the simpler and more commonly used method. You just import it using import matplotlib.pyplot as PLT and then use functions like plt.plot or plt.bar to make your charts. The second way is through the object-oriented API. This one gives you more control and is better suited for complex or customized visualizations, especially when you're building something that needs to be more advanced or integrated into an application. In this tutorial, we are going to explore both methods using easy examples. So go ahead and open your Jupyter Notebook or Google Colab and let's get started with Matplotlib and the world of data visualization. So before we get started with the implementation of Matplotlib, I want to quickly show you guys the anatomy of a Matplotlib figure. So a figure in Matplotlib is basically the entire window or page. It's basically the entire canvas that represents the various components like legends, your axes, the grids, your labels, everything, right? So all the components are contained inside a figure. So let us quickly go ahead and see what are these different components. So first we have the axis. So we have x-axis and the y-axis, and what these axes are representing is basically shown by the labels. So we have x-axis label and y-axis label. So say for example, I have the data of number of hours studied versus the marks scored. So I can represent my x-axis as the number of hours studied and I can label it as number of hours studied, and similarly I can do it for y-axis label as the marks scored. So I know what I am showing on my plot. Then there's something known as ticks. So we have major ticks and minor tick labels. So major tick labels are basically these marks that you can see on your axis. So 0, 1, 2, 3, 4 are basically your major tick labels, and your minor tick labels are the in-between marks like 0.25, 0.5 and so on. And then we have something known as a legend. So this basically represents what each color or mark is representing. Right, so over here we have a blue line and a red line. So whatever these blue lines and red lines are representing, that can be shown in a legend. Then you have your grids. So these are the dotted lines that help you figure out or read your plots in a more efficient manner. Then you can also label your entire figure. So you can give a title to your figure using the title component. So that is pretty much it about a figure. So these are basically the major components inside your figure. As we go ahead, we will see how to tweak these different components according to how we want our figure to look like. Alright, so in order to get started, I want you guys to quickly open any terminal and just run the command pip install matplotlib. And once you run it, you will see a few lines of code run over here for you. And finally, when you get the message requirement satisfied, that means your library is installed successfully. Now, once your library is installed, you can go ahead and import it in any environment that you like. I'm using Google Colab. You can use VS Code or Jupyter Notebook, right? According to your preference. So I'm going to go ahead and import my Matplotlib. If I run it, so it's imported successfully. So along with my Matplotlib, I'm also going to import pandas. And if I run it, so both my libraries are imported successfully. So just to give you guys a basic gist of what Matplotlib does, I'm just going to create two variables for you guys. So I have my variable x as 1, 2, 3 and my variable y as 4, 5 and 6. Okay, so these are my x and y variables. Now, in order to plot these variables using Matplotlib, all I have to do is say plt.plot, pass my variables x, y, and just say plt.show. And as you can see over here, this is what Matplotlib gives me. So over here, what Matplotlib is trying to do is, it is trying to plot my data like this. So 1, 4, then I have 2, 5, and then I have 3, 6. Okay, so these are the variables that I passed, and this is the data that Matplotlib is trying to plot over here. Okay, so if you go ahead and see 1, 4, 2, 5, and 3, 6. So if I want those dotted grid lines that we initially discussed in our figure, all I have to do is say plt dot grid and run it. See, now you can see I have my grid lines. Now it gets much easier to read my data in a more efficient manner. Now I can easily spot that this particular dot represents 2, 5 and this particular spot represents 1.75, 4.75. So now you're easily able to figure out what each of these points on this particular line represent. Right? So this is basically the major idea or the major implementation of Matplotlib. Now, using this functionality of Matplotlib, we are going to try and plot different kind of plots for different data sets. So, as we discussed earlier, Matplotlib has two types of plotting. So, one is using the PyPlot API and one is using object-oriented API. So, first we're going to cover the PyPlot API. So, let me just write it down that we are only going to discuss PyPlot API right now. In the end of the video, I'm going to discuss how you can use object-oriented API as well. Okay. So in order to understand which particular plot is to be used for what kind of data, let me quickly introduce you guys to univariate analysis. So a univariate variable basically focuses on one variable at a time. It could be a height, weight, or a category like yes or no. Alright, so first we're going to cover the numerical column. So in order to understand, let me just create a data where I have a column, salary, and it looks something like this. Okay. So this is my salary column and this is just a dictionary and I have to convert it into a data frame. So I'm going to call my data set df and I'm going to say pd.data frame and I'm simply going to pass my data. Now if I try and print the first 5 records of my data set, this is what it's going to look like. Okay, so this is my salary column and these are my records. Let me also go ahead and check the total number of records in my data. So all I have to do is say df.shape and if I run it, so I have 20 records and I have only one column. So over here I have 20, 1. Alright. So now in order to visualize this particular column in my data frame, the first plot that I have is a line plot that we have already seen, but now we're going to see it in much more detail. So in order to plot a line plot, all I have to do is plt.plot. And in my parentheses, I just have to pass my column inside my df variable, that is my data frame, like this. So if I run it, so this is basically how my salary column is varying. Okay. So at some point it is really high, that is the highest salary is going to 55,000, whereas the lowest salary is somewhere around 25,000. Okay. Now what I can do is I can also go ahead and make some changes in my plot. Like I can say I want my color to be red and I want my grids to be shown, and I can also have my markers. So I can have my marker as letter O. Now what this marker is going to do is wherever I have a data point, it is going to be marked. So for example, over here, basically wherever I have a data point, it's going to be marked with the letter O. I can also go ahead and change the line width. Let me just run it. So as you can see, my color has been changed to red. I have grids in my plot and my marker is being represented with a dot over here, as you can see. Now instead of a straight line, I can change my line style to a dashed line like this. So now you can see my line is a dashed line, or I can also change it to a dot using the colon. So now you can see my line has been dotted. I can also go ahead and change the width of my line using the line width parameter, and I can say I want it to be 2. Okay, so as you can see, the width has been increased. So if in case I want my marker to be represented with a star, all I have to do is pass this particular symbol and you can see the marker style has been changed. Okay, so you can go ahead and play around a little with the parameters that are available in Matplotlib. Again, Seaborn offers a bit more functionality compared to Matplotlib, but this is great when you want to deal with your plots at a lower level. Okay. Then the next way we can visualize our column is through a histogram. So in order to plot a histogram, all you have to do is say plt.hist and pass your column in the parenthesis. And for now, I'm going to exclude the bins parameter and just show you guys how the salary column is going to look like in a histogram. Alright, so histogram basically tells us the frequency of our data distribution. So what this graph is basically telling us is that there are around 3 people that have the salary in the range 25,000 to 30,000. Then 2 people have the salary in the range 30,000 to 35,000. And there are 3 people again in 35 to 40 range. Okay, so this is basically how our data is being distributed. Now, in order to make it more clear, I can go ahead and pass bins, and I'm going to, no, I don't want grids for this particular graph, and I'm going to say my color is going to be green. So now I have divided my plot in 5 bins. So now it's more clear and more readable. Okay, so I have 6 people earning 25,000, then 5 people earning 30,000, then 3 people earning 35,000 and so on. Okay, so this is how you can read your data through a histogram. Then the next plot that we have is a box plot. So in order to plot a box plot, all you have to do is say plt.boxplot and pass your column over here and simply say plt.show, and this is what your box plot is going to look like. Okay, so whoever is not clear with what a box plot is exactly, let us quickly understand it with the help of this image. So a box plot has 2 endpoints. One represents the minimum value and one represents the maximum value. Then there's a line that is connecting the minimum value to the lower quartile, and it's called the whisker. Now your lower quartile is known as Q1, which basically represents 25 percentile. So basically 25% of the data is below this particular point. Okay, then you have your mean value and your median. Median is also known as Q2 and it's the 50th percentile. This represents 50% of the data is below this particular point. Then you have Q3, which is 75 percentile. So 75% of the data is below this particular point, and then you have your maximum value. Okay, so Q1 to Q3 is known as your interquartile range. And then you have something known as outliers. Now outliers are basically the extreme values that are either lower than the minimum value or greater than the maximum value. Okay, so these are basically the extreme values and they are plotted outside the box plot. So box plot makes it very easier to identify whether there are any outliers in your data or not. Okay, so as we can see in this particular plot over here, there are no outliers currently. But if I were to add a salary, so at index 20, I'm basically adding a salary 0. Okay. Now, if I run it, now I go ahead and plot a box plot. You can see over here, I got an outlier value, which is at 0. So this is the value I just inserted, as you can see over here, through df.loc. So we have already covered LOC and ilog in my previous video of Pandas full course. If you guys have not watched it or you guys do not understand how I have added a new record in my dataset, I suggest you guys to quickly go ahead and watch that video before you continue with this video, because we will be using Pandas somewhere or the other throughout this video. Alright. So as you can see, I've got my outlier value over here, which is really far away from my entire box plot. So it's suggesting that whatever range my other salaries are in, this particular salary does not match that range. Okay. So I can simply go ahead and remove this value from my dataset in order to avoid any bias in my entire calculation when I'm going ahead with prediction models and all. Okay. So I'm just going to go ahead and remove this value. Okay. So I'm back to my original dataset. Now this was all about when you have a single numerical column. Alright. So salary was something that contained all numerical values. But what if I had a column that had all categorical values? So now we're going to deal with a univariate categorical column. Okay. So in order to deal with a categorical column, let me just quickly go ahead and add another column to my dataset called department. So now let me go ahead and check my data frame, what it looks like. So as you can see over here, I have a salary column and a department column. And my department column is a categorical column. I can also go ahead and check that using the info parameter. So you can see this is of type integer and this is of type object. So basically, all of the data that I have in my department column is of type string. Alright. Now if I want to visualize this particular column, I cannot use a line chart or a histogram or even a box plot because those are used for a numerical column. So in order to visualize this column, I'm going to use something known as a pie chart. Now in order to plot a pie chart, what I have to do is I have to create a count variable where I am simply going to count the number of unique values in my department. So this is what it's going to look like. So I have 8 HR departments, 6 IT and 6 finance departments. Okay. Now I can go ahead and plot this data in my pie chart using plt.py. Simply pass my count variable, and if I print plt.show, this is what it looks like. Now over here, I do not know what these different colors are representing. So in order to have that on my pie chart, all I have to do is say labels equal to count dot index, and if I print it now, you can see the green color represents my finance, blue represents HR and orange represents IT. But again, another issue is I do not know the values of these sectors. So in order to get my values printed in my pie chart, all I have to do is say auto PCT and pass 1.1%, 1.1 F. So you can see I have 40% HR, 30% IT and 30% finance. Okay. So the format I've given over here basically represents that I want one decimal. If I were to pass 1.0, I would get only my integer parts over here. If I were to say 1.2, you can see I got 2 decimal values in each of my sectors. Okay. And another important parameter in pie chart is explode. So the explode feature basically helps us decide if we want to separate any particular section in our pie chart. So let me just show you guys. So I can simply say 0, 0.1 and 0. If I do that, so you can see IT, which is my second sector over here, has been separated from my entire pie chart by 0.1 distance. Okay, I can do that for 2 sectors at a time also. I can say I want this to be separated by 0.2, the last sector finance. So this is what my pie chart looks like now. Okay, now if you feel that your pie chart is not a complete circle, it's not a proper circle, you can quickly go ahead and say axis and pass equal in the parenthesis, and that will make your pie chart in a complete circle. Okay, so this was one way of visualizing a categorical column. The other one is known as count plot. So in order to do a count plot, all you have to do is say plt.bar and pass your count.index and count variable and simply say plt.show, and now you can see your different sectors represented as a bar chart. Okay, you can easily understand that HR has 8 values, basically 8 people working in HR, 6 people working in IT, and again 6 people working in finance. You can also go ahead and change the color of your bars. You can make it, so if I want different colors for different bars, so I can go ahead and say green, black, red. So you can see I have different colors for my different bars. Okay. So this was all about univariate analysis. That is when we had to deal with only one column. Either it was just a numerical column or just a categorical column. But what if we had two columns at a time? That brings us to our next type of analysis, that is bivariate analysis. And over here, we basically try to analyze the relationship between two features or two columns. So first we're going to look at two numerical columns. Okay. So right now, if I check my data set, I have one numerical column and one categorical column, right? So in order to perform numerical analysis, I should have another numerical column. So let me just go ahead and create a new column. I'm going to call it age. And okay, so this is my new column called age. And if I go ahead and check my data frame now, so you can see I have three columns. Two are numerical columns and one is a categorical column. Alright. So now if I want to visualize salary and age column together, the first plot that I have is known as a scatter plot. So a scatter plot is basically going to help us analyze the direct relationship whether salary increases with age or not. Okay, so if you want to check that, all we have to do is say plt.scatter and pass my age column, my salary column, and I'm going to give the color orange, and I'm simply going to say plt.show. So as you can see over here, my age and salary are increasing together. Okay, so this is also known as a positive correlation. Alright, so when my age is around 20 to 25, my salary is somewhere around 25,000 to 30,000. But as my age increases, so when I reach the age of 40, my salary is somewhere around 55,000. Okay, so this is how you can analyze the relationship between two numerical columns. And the next way of visualizing two columns is again by using a line plot. So as we saw in our initial example, we had two features x and y. So right now we have two features called age and salary. So I'm going to go ahead and plot my line graph over here. So as you can see, my line graph is not very easy to visualize over here. You can see the lines are very random. So instead of line style as dotted, I'm going to have my simple and plain line style. So as you can see, it's going back and forth a lot. So why is this happening? Because my age column is not sorted over here. So I have random age values and random salary values. So in order to have a better visualization, what I'm going to do is I'm going to sort my age feature. I'm going to create a variable called sort age, and I'm going to simply sort my values of age. Okay, and over here, instead of passing my age directly, I'm going to pass my sorted age. So as you can see over here, now my line chart is giving me a better visualization of the relationship between the age column and the salary column. Okay, so this is how you can plot a line chart between two numerical columns. Then the next visualization graph that we have is a bar chart. So in order to plot a bar chart, all you have to do is say plt.bar, pass your age. I'm going to pass my sorted age features and my salary column, and I'm going to say I want my color to be green for all the bars. And as you can see over here, it is giving you the visual representation in forms of bars. Okay, so at the age of 22, I have my salary in this range. At the age of 25, I have the salary at this range. So I can also go ahead and create bins. So I want only 10 bars to classify my age. So I can also go ahead and align my bars, and I can say I want my bars to be in center. So if I run it, so they were initially like this. Now if I say I want them to be left, so align supports center or edge parameters. Okay, so this is how you visualize two numerical columns, but what if you had a numerical and a categorical column to visualize? So let me go ahead and show you guys bivariate analysis, but with a numerical and a categorical. So I'm going to consider my salary feature and my department feature, and now I want to see the visualization of how my salary is distributed according to my department. Okay, so what I'm going to do is I'm going to create my feature called HR salaries, and here I'm going to fetch all my salaries that have the department of HR. So basically my HR salary variable is going to contain the salaries of only the HR department. So basically these are the people working in the HR department and these are their salaries. Okay. Similarly, I'm going to do that for the other two departments as well. So I'm going to create IT salary, and similarly I'm going to create finance salary. Okay. So once I have my salaries for all the three departments separately, I can go ahead and plot them in a box plot. So I'm going to go ahead and create a box plot. So in order to do that, all I have to do is say plt.boxplot and pass all the three salaries that I have together. And you can see the distribution like this. Okay, so I have one salary that is an outlier, that is 55,000, which is okay. So I need to also go ahead and label them. So I'm going to say label, and I'm also going to show the legend for my plots. So if I plot this, you can see I have three box plots, and over here you can see I have an outlier value for my first box plot, but in this particular figure, I'm unable to understand which box plot is referring to which department. So in order to clarify that, I can go ahead and say I want my labels to be HR, IT, and Finance. So if I run it now, you can see my first box plot represents the HR department, and I have an outlier value in the HR department. Okay, so this is how you can analyze a numerical column with a categorical column using box plots. Okay, you can also check their median values. So the median HR salary is in the range of 25,000 to 30,000, whereas IT median salary is 35,000, and finance has the highest median salary, that is 40,000. So this is how it gets much easier to visualize data using plots in Matplotlib, right? If you were to find out such insights just looking at the data, it would take you much longer, right? But using graphs like this, I can easily figure out which department has uh, a higher median salary, or the maximum salary, or the outlier lies in which department, right? So box plot was one way. Another way where you can visualize your numerical and categorical column together is pie chart. So in order to plot my pie chart, what I'm going to do is I'm going to sort, or I'm going to group my salary by department, and I'm going to say df dot group by department, and I want my salary to be grouped, and I'm going to use the sum instead of mean. So this is what it looks like. So I have a total of this number for my finance department. So basically all the people in finance together are earning this much salary, whereas all the people in HR are earning this amount, and in IT they're earning this amount. Okay, so now I can go ahead and plot it in a pie chart. I can say plt.pie, and I can give my salary by department variable, and I can call my labels as the index, and I'm going to label them using auto PCT. And once I print my pie chart, so in my pie chart I can easily see the distribution of salary in percentage for the three different departments. Okay, so this is another way of visualizing. So in my box plot, I could easily figure out the minimum salary, the maximum salary, and the median salaries for all the departments. And over here, I can see the distribution or the percentage for each department, that is the total amount being earned by each department. Okay, so another way when you can visualize your numerical and categorical column is by using a bar plot. So I want to show the mean salaries of all the departments in my bars. So what I'm going to do is I'm going to say HR mean, and I'm simply going to say sum of HR salary and I'm going to divide it by the length of HR. And similarly, I'm going to do it for IT and finance as well. So once I run it, I can simply go ahead and plot my bar chart over here. I'm going to say plt.bar, and I'm going to pass my HR, IT, and finance as labels. And I'm going to pass these as variables as well, and I'm going to say I want my bars to be of color green, black, and red. And once I print my chart, this is what it's going to look like. Okay, so in my bar chart over here, I can easily see the mean or the average salary for the three departments in a very clean and neat manner, right? So my HR mean salary is somewhere around 35,000, whereas IT is a little more, and finance is almost crossing 40,000. Let me just use my grids over here. So you can see, now you get a better visualization of the mean or the average salary for the three departments. Okay, So this is going to further help you in analysis where you are building large predictive models. Right now, I just have 3 columns and the values are really small, so I could even look at the data. But when you have a larger number of columns and larger values, visualizing your data becomes a much more easier, or you can say efficient way to understand what the data is trying to tell you, right? So with this, we finish our bivariate analysis. Next comes our multivariate analysis. So basically, this is where we're trying to understand how the 3 columns affect each other and how they change with each other, right? So first, we're going to look at three numerical columns. That is numerical, numerical, numerical. So I'm just going to write 3 numerical columns. So in order to have 3 numerical columns, right now I just have 2 in my data set. Let me just check. Yeah, so I have 2 numerical columns, that is salary and age. I need to add another numerical column in my data frame. So let me just say DF and let me add experience. Okay, so you can see I have added another numerical column, that is experience. So basically, this column is telling us how many years of experience the person has. So over here, there's 1 year of experience. Here, over here, the person has 2 years of experience, and so on. Okay. Also, another thing that I missed over here is a few parameters in pie chart. So over here, there's something known as shadow. So if you want to give these effects to your pie chart, you can simply say shadow equal to true, and over here you can see a shadow like structure has been created below your pie chart. Okay, so it kind of gives your image a 3D effect, right? And you can also go ahead and say explode and pass a list of the distance that you want your each sectors to be away from the radius. So I'm going to say 0.1, 0 and 0.1. So basically this makes your pie chart look a little more interactive and different from the normal images that are out there. So you can go ahead and customize it. Okay. Alright, so moving on with our multivariate analysis. So I have 3 numerical columns, as you can see over here. So now in order to analyze these 3 columns together, I'm going to use something known as a bubble plot. Okay. So a bubble plot is nothing but a scatter plot where your third numerical column, so in this case we're going to use experience as our third numerical column, and this experience column is just going to define the bubble size. Okay, so with that you get an idea of how much experience the person has. So basically, the larger your bubble, the more the experience the person has. Okay, so let me go ahead and quickly create this plot for you guys. So I'm going to say plt.scatter. So basically I've passed my age column, my salary column and my experience column as the size of my bubble. And I'm saying I want orange bubbles. And if I print this, okay, so as you can see, the size of my bubble by default is very small. So basically the smallest bubble is representing 1 year of experience and the largest bubble is probably representing 5 years of experience. But in order to have a better visualization, what I'm going to do is I'm going to multiply this by 20. Okay, so now you can see the bubble size has increased and now it's much more easier to visualize this particular graph than earlier. I can also go ahead and increase the number of multiplication. Okay, and I'm going to give the color blue because that would give a better bubble effect. So this is what my bubble plot is going to look like when I have 3 numerical columns. Okay, so you can go ahead and easily visualize that person of age 27 is earning around 35,000, and again the experience is also good, right? So I'm simply going to give the color as sky blue, and I can also go ahead and customize it as edge color. So I'm going to give my edge color as black so that I have a better understanding of my bubbles. Alright. So see, this is what my bubble plot is going to look like. Again, I can give a title to my plot. I can say plt.title, age versus salary versus experience. And my X label is going to be age, my Y label is going to be salary, and I do not need a grid. So now you can see my plot looks much neater and easier to read, right? So this was when we had 3 numerical columns. But what if we had 2 numerical and one categorical column. So in this case, we are going to again use a scatter plot. So the two numerical columns are going to be our age and salary, and our categorical column is going to be the department column. Now, in order to plot this on a scatter plot, instead of using a bubble plot, we're going to use a scatter plot again. But for the different departments in our department column, we are going to use different colors. Okay, so what I'm going to do is I'm going to say plt dot scatter, and I'm going to pass my age column, my salary column, and I'm going to say I want my colors to be of the different departments, that is DF department, and I'm going to say I want the colors of a rainbow. So I want different colors in a rainbow, okay? Or if I didn't want rainbow, I'm going to show you guys how I can customize the colors in my own way. So I'm going to say X label, and my X is going to be age, then Y label, plt.x label, and plt.y label. My Y label is going to be salary, and I'm going to give a title to my plot, and I'm also going to print my legend. Okay, so I cannot use a rainbow color. Rather, what I'm going to do is I'm going to say df.map, and I'm going to map the different departments. So if I have an HR department, I'm going to map it with, say, color yellow, and similarly I'm going to map my other two departments as well. So I'm going to say IT, I want to be mapped to color blue, and finally I have finance, say orange. Print it now. So as you can see over here, I've tried to print my legend, but I am not really getting an output. So I can resolve this by simply saying labels equal to df department. So as you can see over here, I have tried to print my legend using plt.legend, but I am not really getting any output for that particular line. So the reason being, I have explicitly defined what colors each of my departments are going to get, and Matplotlib is unable to read that. So I have to explicitly define the labels using label, and I'm going to say HR, IT, and finance. So if I print it now, so as you can see over here, even though we've passed the plt.legend parameter, our legend is not getting printed. So the reason is because we have explicitly defined the colors over here, and even if we try to get the label parameter as df department, so you can see it is not going to work for us. So we cannot use this particular strategy. Rather, we have to follow a different kind of format over here where we explicitly define our color using a variable. So I'm going to say my HR is going to be linked with yellow, IT is going to be with blue, finance is going to be with orange. Okay, now I'm going to iterate through each of my color and my department. So I'm going to say for DPT and color in color.items, and basically I'm going to classify each of the departments separately, and then I'm going to print my scatter plot of age and salary. I'm going to say my color is going to be the specific color for each department, and I'm going to label my department. And if I run this and I go ahead and print my legend, so now you can see I've got my legend successfully, because now Matplotlib knows which department is representing which color. Alright, so that is why it is able to generate a legend successfully. Earlier in this case, Matplotlib had no idea about it. So this is how you can create a legend when you're plotting two numerical and one categorical column in a scatter plot. Alright, so that was all about our PyPlot API plotting for a single numerical column, a single categorical column, then two numerical columns versus a numerical and a categorical column. Then we went ahead and saw multivariate plotting, and we did all that using the PyPlot API. That is, we directly went ahead and used terms like plt.bar, plt.boxplot, and so on. Now we're going to dive into object-oriented API. That is, we're going to create objects before we start plotting. Okay, so let me just comment it over here. So object-oriented API basically allows subplots or multiple axes or multiple plots in a particular figure. Okay, so till now we saw one particular plot in one figure, but now what we can do is we can have multiple plots and subplots in a single figure. Okay, so let's quickly see how. So first I'm going to create two objects called figure and axis, and I'm going to say plt.subplots, and I'm going to pass 1 comma 3, and I'm going to say my figure size is going to be 10 comma 5. Okay, so this is basically the x and y ratio. So in terms of x, I'm going to have the figure horizontally expanded and vertically just 5. Okay, so basically what I'm telling my subplot parameter is that I want one figure, and in that one figure I want 3 subplots. Okay, so now let's go ahead and create our first plot. So I want my first plot to be a line plot. Okay, so as you can see over here, this is one complete figure and I have 3 subplots. Right now all these 3 plots are empty. Okay, so I'm going to go ahead and create my line plot first. So in order to do that, I'm going to use my sort age variable. Let me see if I still have it. Yes. Okay, so I'm going to use my sort age variable. So I'm going to say at my axis 0, that is my 0th x-axis, I want to plot a line plot, and it is going to be sort age, pass my age and salary, and I want my color to be red, my marker to be a star, and my line width to be 2. Okay, I can also go ahead and define my marker size. So I'm going to say marker size equal to 2. So I can go ahead and set the grid. I can also set my title for this particular plot. I'm going to say it's a line plot, and I can also go ahead and set my x label and my y label for this. So I'm going to say dot set x label, and I'm going to call it age, and y label is going to be my salary, and then I'm just going to run it. Okay, so since I've not called my plot till now, it's not being generated. Now I'm going to go ahead and plot my histogram. Ideally, all this should be run in a single cell. So I'm just going to paste it in my cell over here. And then I'm going to plot my histogram. And over here, my axis is going to be 1, so that Matplotlib understands that this was my first plot. And I'm going to use axis 1 over here throughout histogram, so that Matplotlib understands that this is the second figure, while the earlier where I use 0 for axis is going to be my first figure. Alright, so basically I'm referencing to my first figure and my second figure over here. So I've created a histogram for my salary, and I'm going to give the color sky blue. And I'm going to set my title for histogram, and I'm going to set my label salary, and y label is going to be frequency. Then my third plot is going to be a box plot, where I'm going to say axis 2, that means my third figure, and I'm going to plot my salary over here. I'm going to set my title as box plot, and I'm setting my x label as salary again. And if I run plt.show, that is I print all my plots, this is what it's going to look like. So as you can see over here, my plot is sort of coinciding with my second plot. So I can go ahead and increase my x-axis direction. So I can say 15,5. Now you can see it's fitting perfectly. Okay, so you can go ahead and adjust the dimensions for your plots, that is your figure size. Okay, so this is how you plot multiple plots together, okay, in using object-oriented API. Cool. Now, if I want to save this particular figure in my local environment, maybe I want to use it for some sort of presentation or any sort of document that I'm preparing, and I want to use this figure in that, how do I do that? Okay, so you can either just right click and go to copy image, but that's not the right way. So Matplotlib offers an inbuilt feature where you can save your image. So all you have to do is say plt.save fig and give a name to your image. So I'm just going to say multiple plots, and now you can use any particular extension. So I'm going to use PNG. You can use the JPG format, or you can use the PDF format. Okay, any format that you want to download your image in, you can just use that particular extension in the end using the dot. So whichever image I need to save, I just need to run this particular line before the plt.show. And if I run this, so let me see if my image has been saved. So as you can see over here, multiple plots.png has been saved in my drives. So since I'm using Google Colab, it is unable to access my local environment, and hence my image is saved only in my drive, that is my disk space over here. If you're using VS Code or any other notebook like Jupyter Notebook, you can specify the path that you want your image to be saved in. Okay, so you can directly go and say, I want it to be stored in my C drive. Okay, so you can use a path like this so that your image is stored in that particular folder. And I can also go ahead and download it from here. So this is how you save an image. I can also save it in, okay, let me just go ahead and, so if I click on this is what my image is going to look like. Okay. Now, before we wrap up with our 3D plots, I want to show you guys another interesting scenario where we have a data somewhat like this. Okay, so basically I have multiple numerical columns. Now, if I want to visualize all these particular metrics over here, like the sales and profit and expenses all together in one chart with reference to the year column, this is how I can do it. So first I'm going to convert it into a data frame. I'm going to call it df2. This also ideally should be data2 because I already have data variable initially. Okay. So in order to do multiple plots, all I have to do is say plt.plot and pass my year as my x variable. So this is going to be fixed throughout. All my x variables are going to have the column year because I want all these particular metrics to be represented with reference to year, but in a single plot. Okay, so this is how I'm going to do it. So I do year and let me plot sales, and I'm going to label it as sales. So similarly, I'm going to do it for profit and expenses column as well. Okay, and I'm going to label it as profit and expenses. So if I give my plot a title, financial analysis, and I'm going to label my X label as year and Y label as the amount. So now my Y label, that is the amount, is going to vary according to sales, profit and expenses. Okay. So if I run this, okay, so as you can see over here, I have my profit, my expenses and my sales. Now how do I know which line is representing what? I can see it through the legend over here. And my x-axis is representing the year and my y-axis is representing the amount. Okay, so basically we had lesser profit and our expenses were greater than our profit throughout the years. So basically the company is in financial loss. So that is something that we can easily predict through this particular graph. Although our sales were pretty high, we are not generating the required profit, right? So this is how you can analyze financial data in just a few lines of code. All right. So now coming to the last topic for this particular video, that is a 3D plot. So let's plot a 3D plot for this particular data frame that we have. Okay, so in order to do a 3D plot, all you have to do is create a variable. So I'm going to call it AX and I'm going to say plt.figure and I'm going to say projection equal to 3D. Okay, and now I'm going to create my scatter plot and I'm going to pass my variables. So I'm going to pass my age, salary and experience column and I'm simply going to say df plt.show. Okay, sorry, it's not going to be plt.figure, it's going to be plt.axis and my d is going to be small. Okay, so as you can see over here, I've got a 3D plot. So in order to clarify what each of these axes is representing, I'm going to label these axes. And in a 3D plot, I'm going to use set X label, set Y label and set Z label. Alright, so once I run it, so as you can see over here, this particular axis represents age, this represents salary, and this one over here is supposed to represent experience, but I'm not really getting the label over here. So this code is going to perform better if it was run on a visual code or Jupyter notebook. Okay, Google Colab does not really support a lot of 3D animations. So if you were to run this particular code in VS Code, you would be able to rotate your graph on different axes and be able to visualize the data better. So if you want to achieve the same functionality in Google Colab, all you have to do is import plotly.express as px, and if you run it, so it's run successfully. And then you can simply go ahead and create your figure, which is going to be your scatter plot 3D. So it directly comes with a 3D scatter plot, and you can pass your data frame, and your variables are going to be age, salary, and experience. So what I've done over here is I've created a figure variable and I've used px.scatter3d. So it's directly going to plot a 3D scatter plot, and I've passed my data frame, my age, salary, and experience variables, and I've titled it as 3D scatter plot. Okay. Now all I have to do is say fig.show, and if I run it, so as you can see over here, now I am able to rotate my graph. I can visualize the data on a 3D level. Okay, so this is how you can do it using Plotly library. Okay. Matplotlib also offers this particular option, this particular functionality, but just not in Google Colab. Okay, you can do it on Visual Code or Jupyter Notebook. So this was it for this video. I hope you guys were able to understand Matplotlib, the functionalities, and most importantly, which plot is supposed to be used for what kind of data set. So we've discussed univariate, bivariate, and multivariate analysis along with PyPlot API and object-oriented API. Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampark IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
All right, so let's get started now. Now, I'm assuming that all of you have a basic understanding of Python, NumPy, Pandas, visualization. Now, till now, you can assume that you have had. So let's say if you wanted to do something on a computer, right? If you, let's say, wanted to use Microsoft Office, MS Word, and things like that, the first thing that we need to do was what? That we had to familiarize ourselves with a computer, right? So till now, what you guys have done is that you guys have actually uh, familiarized yourself with Python, right? What is Python? Python is a tool which will help us in creating these machine learning models that we are going to study about, right? So we have familiarized ourselves with the tool. Now that we are familiar with the tool, we will move on to the machine learning part of the course, wherein we will be picking different kinds of machine learning models that we have, and we will be implementing them through Python, right? What is going to come now is what exactly machine learning is, right? So let's get started. Machine learning using Python. This is just a basic visualization which we'll be covering. Let's get started with machine learning around us, right? Now, there is a lot of machine learning, there is a lot of data science that we are able to perceive around us as well, right? If you go back 10 years from today, maybe not as many companies, maybe not as many websites and applications were using data science, were using machine learning per se, right? But now you can see that every platform, right? Because there are so many users, there is so many data that they are collecting, right? There is so much amount of data that they are collecting that they cannot do without the implementation of, let's say, data science in their application, website, whatever system they have, right? Now, we are going to go through some of the common examples that we have of machine learning around us, right? Some examples from personal life: Alexa, recommendations on Netflix, reel suggestions, Instagram, Facebook, YouTube, Spotify, yes, Google Ads, Siri. The way we use our phone changes the way battery charges. That's a very specific example. YouTube, songs, autoplay. Autoplay, it will, let's say you go ahead and you select one song, And then on the basis of that, let's say that song was a Kishore Kumar song, right? It will go ahead and it will start selecting old songs, right? Amazon, Swiggy food suggestion, facial detection, self-driving cars, prediction of weather, mobile unlocking through face, Google Maps, face recognition, Spotify, Hi Siri, Gmail, spam emails. You see that automatically your spam folder gets on getting like keeps on getting updated, right? Even though you are not marking emails as spam or not spam, but automatically your inbox will know that okay, these mails might be spam, the probability of them being spam might be high, and hence your email right your service provider will automatically take them to the spam folder, right? Chatbots, exactly. Autonomous vehicle, that is your self-driving cars, right? Your ADAS, right? ADAS level 1, ADAS level 2, 3, 4. This is nothing but the complexity of the machine learning deep learning models going up, right? Ad suggestions, smartphone cameras, YouTube ads, chatbot, traffic signals. So there are certain traffic signals that actually work on the incoming traffic, right? Now your timing of the traffic signals will be adaptive, right? Depending upon, let's say, the timing of the day, or depending upon a feed from camera, which actually gives you the real time number of vehicles, right? That might be present in the different lanes that you have, your traffic signals can be adjusted. So not all traffic signals, but I'm pretty sure that the major cities that we have, there will be certain traffic signals. I know that in Delhi we have certain traffic signals. I'm from Lucknow. I know that in Lucknow there are certain traffic signals where you can see that the timing actually adapts itself automatically, right? Same goes for Bangalore, Mumbai and all. So that's a good example. Speech recognition, fingerprint sensor, stock market prediction, chat GPT and Bard, right? So let's go through these, right? Very quickly, right? So recommendations of products, right? The recommendations of products that we see on Amazon, right? That is generally a recommendation model, which is nothing but data science, right? Alexa, your Siri, your voice-based assistants coming from any other, let's say, a product, right, is nothing but your pure play data science, right? It is pure play voice to text translation, and then on the basis of that, you go ahead and you do whatever the person is saying to do, right? Is asking you to do. All right. Movie recommendations on Netflix, right? On Netflix, Instagram, Facebook, YouTube, everything. Now, how does this work? The recommendation works on your historical data, on your historical behavior. Now, you would have seen that nowadays the recommendations have become so dynamic that even if you go ahead and if you, let's say 5 minutes back, you were watching, let's say, a couple of reels on cricketers, on Virat Kohli, on, let's say, World Cup, right? You will start getting recommendations on that. And the moment that you start not watching those, right? So see, when you are watching the reels, you are being exposed to every content that is out there. But there will be some reels wherein you are just going to swipe up, right, within maybe a second, because the content might not be interesting to you. There might be some which you watch more than one times, there might be some which you like, there might be some which you share, right? So all of this behavior is being tracked, all of your historical behavior is being tracked, and on the basis of that, your recommendations are getting more dynamic in nature, right? Even within a short span of, let's say, 20-25 minutes of you using social media, right, your recommendations can keep on getting changing if you keep on changing your behavior, right? So that is the level of recommendation systems that we have today. Traffic prediction in Google, right? So if you want to go from point A to point B, so Google comes up with an estimated time, right? So that estimated time is not a random time. It is not, because see, the estimated time from point A to point B will change depending upon what time of the day is, what day of the week it is, right? Is it a holiday? Is it not a holiday? And lots of factors, right? It will also depend on certain factors, such as that whether there is a political rally that is going on, whether there is, let's say, an international match that is going on, whether there is a concert that is going on, right? Now, all of these things actually, so what they do is that they take historical data, they take real-time data, and they merge both of these data sources and come up with an ETA, right? Generally, you will see that the ETA that they give is generally precise, right? It depends upon the way you drive. You can drive as fast you can as you can. You can drive as slow as you can. At the end of the day, there will be a difference of maybe plus minus 5-10 minutes only, right? Because it takes into account all the conditions. It takes into account the traffic conditions. It takes into account the weather conditions. Everything is taken into account, and then an ETA is given from, let's say, point A to point B, right? So these were just some general slides on what are some of the examples of machine learning data science around us. All right. All right. Now moving on to introduction to machine learning. Now, what is machine learning, right? Let's try to understand what machine learning is. We know that there is enormous amount of machine learning products and, let's say, solutions that are around us. But what exactly machine learning is? Let's try to understand that, right? All right. So what is machine learning? Now, machine learning is a subset of artificial intelligence, gives machine the ability to learn without being explicitly programmed, right? I'm going to explain all of these textbook definitions to you. But before that, let's try to understand what machine learning exactly is, right? All of you just think of a skill that you would have developed, right? Maybe in your childhood, maybe playing the piano, maybe playing a particular sport, maybe driving a car, anything, right? Was it something that you were able to perfect right in one attempt, or you had to, let's say, practice, and then you were able to, let's say, perfect that? Obviously, let's say I take playing the piano, for example, right? If you play the piano, or let's say let's take something more common, let's say driving a car, right? Now, driving a car, most of you would have maybe driven a car, maybe driven a bike, active or whatever, right? Now, see, you might know the basics from day one. You might know that, okay, accelerator, brake, clutch, steering, gear, and things like that, right? But once when you actually go on the road, and once when you start accumulating data, right? Once when you know, so maybe the first time when you go on the road, you hit the brakes too hard, right? What is it that you learn? You learn that, okay, my brakes might be sensitive. So if I want to, let's say, stop the car in the next 5 meters, this is the amount of pressure that I need to apply. If I want to stop the car, let's say, immediately, right? This is the kind of pressure that I need to apply, right? Maybe the second time when you take the car out, you realize that, okay, for the steering wheel, when you have to take a U-turn, right? Maybe you make some space towards your right hand side, only then will you be able to make a U-turn in only one attempt. Otherwise, you might have to reverse the car, and then you have to adjust, and then you would have to do that, right? So there is a lot of learning that you do, right? And on the basis of that, finally, maybe let's say an year down the line, maybe a couple of years down the line, you can say that, okay, I am a skilled driver, because there are so many aspects. And historically, taking whatever experiences you have had, right, taking whatever data you have collected, you have actually gone ahead and you have perfected the process of driving, right? So just like this, machine learning is what? Machine learning is that creating let's say, I'll talk about models, right? What models are and all. Right now, just let's just think that a model is a machine learning framework, right? Creating a model which takes in historical data, right? And tries to do a specific task. So let's say I want to create a model which can effectively predict which customers of mine are going to leave my store, and or let's say, take a simple example, a model which will predict which customers of mine will buy a protein shake, which customers of buy will not buy a protein shake, right? A simple question. I want a model that will predict that will give me the probability of customers buying, let's say, a protein shake, right? Now, what I will do is that I will give some data to this model, right? Now, this model is not, it is not magic, right? It is not Harry Potter in real life, right? That it will go ahead and it will know everything. I need to give some historical data to this. So if I go ahead and I give, let's say, for the last 1 year, I give the historical buying behavior of all my customers. Maybe I have, let's say, 1 million customers walking into my store in the last 1 year. And out of these million, let's say I had 50,000 customers who were buying, who actually went ahead and bought a protein shake, right? Now, I have this data. This is my target variable. That is for all the customers who have gone ahead and bought in the protein shake. my target variable will become 1. For the customers who have not bought this particular product, the target variable will become 0. What do I mean by the target variable? The variable that I want to predict, or the thing that I'm wanting to predict. I want the model to predict, right? Now, along with this, can you guys think of any other factors which will help me in finding out whether my customer will buy a protein shake or not, right? I want you to think of factors such as age, factors such as what other products they are buying. What features can you think of which will help me in telling whether my customer is interested in buying a protein drink or not? Gender, income, exercise, are they exercising or not? Are they going to a gym or not? Now I want you to I want you to think from a retail store perspective. If you're a big bazaar, will you know things such as whether my customer goes to the gym or not? Will you know the profession? No, right? Then how can I identify whether these are people who might be interested in a protein shake? See, physique, appearance, all of these things are what? This is manual data. You cannot input. See, when I'm talking about a million customers, will you wait for a million customers to step into your store and take a look at them and tell them that, okay, this one looks fit, this one might buy a protein shake or not, right? This is not effective. I want you to think of data that we can collect easily. Other food item choices, right? Maybe those buying milk bought related products, right? History, previous purchases, number of times, location, similar products, right? Other products, buying preferences. So the gist of this is what? The buying preferences. See, how can I differentiate between someone who is interested in a protein drink and someone who is not, right? Let's say I as a customer go to the store and buy Maggie. I as a customer go to the store and I buy cake. I buy, let's say, chocolates. Do I look like the kind of a customer who will go for a protein shake? No, right? Maybe if I'm a customer who's buying, let's say, granola bars, who's buying oats, who's buying, let's say, healthy stuff, right? Maybe the probability might be higher there, right? Now, if let's say I'm able to collect this data, let's say for every customer, I'm able to collect data about the kind of products that they have bought in the last 1 year, right? Do you think that for people who have gone ahead and bought in, let's say, a protein drink, the products that they have bought along with this, will they be different for those from those who have not bought a protein drink? The patterns will be different, right? People who are buying the protein drink, they might also buy oats, they might also buy, let's say, fruits and vegetables and paneer and chicken and whatnot, right? People who have not bought in a protein shake, maybe they are buying chips and wafers and Maggie and whatnot, right? Right? So if I pass the correct data to the model, right? If I pass the target variable along with that, if I pass the correct data, if I have a model, a mathematical model, which is able to extract these patterns out from the features and relate them to the target variable, just like when we were learning how to drive, our human brain, right? Our brain was the model over here, which was able to extract these patterns, right? Your brain was able to figure out that when you apply the brake with this pressure, the car will come to a dead stop, and maybe passengers who are traveling might bang their head on the dashboard, right? Then you went ahead and you adjusted the force. Just like that, if I have a model in place which is able to extract these patterns from this data, the data about the products that these customers are buying, and correlate that with the target variable, which is whether they will buy a protein shake or not, right? Now, this process is known as machine learning, right? This overall process of collecting the data, tying it to the target variable through a model, a mathematical model, is something which is known as machine learning. All right. So, Jyotsna, the target variable is the question of interest, right? When we talk about data science, when we talk about machine learning, we talk about making predictions, right? My predictions can be on any aspects, right? So prediction can be, I want to predict whether it is going to rain tomorrow or not. So my target variable will become whether it rained or not, right? Now, in this case, can you guys think of features that will be helpful for us? My target variable has now changed to whether it will rain or not tomorrow. Now, using the historical data, can you think of features which will help me in predicting whether it is going to rain or not? Weather conditions, whether it was humid or not, whether it was cloudy or not, right? So if you see, as soon as my target variable changed, My target variable became rain or not, right? So let's say you go back 365 days. For each and every day, let's say you collect the target variable, that is whether it rained on that day or not. And along with that, you also collect other factors such as the humidity, the precipitation amount, whether it was cloudy or not, whether it was summer, winter, autumn, spring, whatever, right? You collect all of these factors. Will you or will you not be able to make predictions? You will be able to, right? If you collect the correct set of features, obviously you should be able to make predictions, right? All right. Now, see, if I tell you that in order to predict whether it is going to rain tomorrow or not, right? I take a feature which is the number of red color cars that are present in a city, right? Do you think that this feature will be important in making predictions? No, right? So when I asked you that my target variable is rain or not, relevant features, right? You thought of features which will help you in predicting whether it is going to rain or not, right? So just like that, see, if you see your machine learning, your data science, it is not magic, right? It is common sense. You have a certain variable that you want to predict, the target variable, right? Now, the target variable obviously will be affected by some factors, right? When I want to say whether a customer will buy a protein shake or not, that also depends upon his or her other choices, right? So you want to find that. Now, if in this example, let's say whether a customer is buying a protein shake or not, right? Let's say if I would have taken into account some random feature, right? Let's say the height of a person. Do you think that the height of a person will have anything to do with their probability of buying protein shake or not? No, right? So first skill that you need to have as a data scientist is understand this concept, right? That see, there will be random data that will be given to you, right? But first thing that you need to do is that you need to ask the question, what is it that you want to predict? Then you need to sit and decide what features will be important, because if I would have taken random features and if I want to go ahead and predict whether it is going to rain or tomorrow, no model in the world will be able to do that, because the features that you have collected are totally random. They are not related with the target variable that you have, correct? So this is one thing that we need to understand. This entire process of your collecting the data, having a target variable, creating a mathematical model on top of that, this entire process is known as machine learning, right? Now, if you look at this over here in this definition, one key term that we have is it gives the machine the ability to learn without being explicitly programmed, right? Now, this is important because if you see, if I pass the correct data, if I pass the target variable, I don't have to manually sit and I don't have to tell the model that this is this and this is that, right? It will automatically extract the patterns. It will automatically extract the relationships. So machine learning is I just need to provide the correct data to the model and it will automatically uncover the patterns that are out there, right? All right. So machine learning is not this. Do not imagine a set of robots studying in a class. This is just Intellipaat being humorous, right? So how does a machine learn? If you look at this over here, right? This is an example. If you look at this, right? How can you just focus on these images, right? Just focus on these ones of a chihuahua and a cookie, right? Muffin, right? How are you able to identify which images are of a dog and which images are of muffins? What are the things that you are focusing on? Placement, maybe the texture, right? Muffins can be rough. Dogs are mostly smooth, right? The shape of the head for a dog, it is kind of triangular. For a muffin, it is kind of round, right? The dog will only have three black spots, two eyes, and one nose, whereas the muffin, in some cases, can have more than three, or in some cases, can have less than three as well, right? Now, if I'm able to understand these differences, right? I should be able to make out the difference between, let's say, a dog and a muffin, right? Correct. So this is exactly how your machine also learns. If I pass all of this data to my models, right? Those models which are able to deal with image data, right? They will try to extract these features. They will see that, okay, all the dogs, they have three black spots, right? They might not know that these are the eyes and the nose, but they see that, okay, these are three black spots. All the images wherein I'm saying that it is a dog, it is kind of a triangular structure, right? But if I move to the image of muffins, in most cases, it is kind of round, right? In the case of muffins, I can see that the black dots can be more than three or can be less than three as well, right? So it will try to extract all of these rules and then it will tie them up together, right? So this is exactly how your machine learning model learns, right? So just like that, if you see the right side example as well, we have a dog, and then we have the Kentucky, we have a fried chicken, right? But so this is how it learns. Once when we move on to complicated models which deal with images and all, right, then we'll be talking about this more. But I hope for now you are aware of how machine learning models work through the examples that I have talked about at least. Okay, all right then. So let's move forward. Now, see, the example that I took, right, when we were collecting historical data, do you think that that example will work if I don't have any target variable? Let's say I go ahead and I collect all the data about the products that my customers have bought in, everything. And I want to predict which customers have, let's say, bought, like which customers will buy a protein shake or not, right? I want to predict that. But let's say that is the data that I don't have. Historically, I don't have the target variable. Do you think that my model will be able to go ahead and make predictions, or will my model be able to learn which customers will buy, which customers will not buy? No, right? So without the target variable, there is nothing that we can do. No, right? All right. So now let me give you an example. Now you remember CAPTCHA? We used to do this a lot. Nowadays as well, we are doing this a lot. Now, see, there are millions and billions of images that are being uploaded on Google, correct? And if you go ahead and if you want to search with, let's say, image of a dog, image of, let's say, something, anything, Google will automatically come up with thousands and thousands of options for you, right? The search result will give you thousands and options. Do you think that someone is manually going ahead and labeling those images? Do you think that that is possible for them to do? What Google did was, and what almost all of these platforms do is that, if you remember, from the last 10 years, we have been manually creating target variables for all these tech giants, right? How? Because if you go ahead and if you see, there are cases for these captcha like things, right? Google will ask you, what are the images of a fire hydrant, right? What are the images where you can see, let's say, a traffic light, right? So you are manually creating the target label for them. Now, if there are millions and millions of users on Google, every user is, let's say, tagging 9 images. If you take this, these are 9 images, right? So when you say that this image contains a fire hydrant, this image does not contain a fire hydrant, right? You are manually creating target labels, correct? So it's a two-way street. For them, they are authenticating whether you are a robot or not, right? Initially, when we used to do this, right, maybe for the first year, we were only creating labels for them, right? They were not bothered. They just, because let's say if you go back to 2010, 2011, our technology was not so advanced that a chatbot can go ahead and can tick which ones are, let's say, fire hydrant, which ones are not, right? So we are going ahead and we were actually manually creating these target variables for Google, right? Now, when Google had, let's say, millions of images, and in front of that, they had the target variable, which you were actually creating for them. They went ahead and they trained the models. And you fast forward to 2017, 2018, your Google Photos app, it automatically goes ahead. You search with photos with car, you search with photos with dog, it will automatically give all the photos in your Google Drive, in your Google Photos, which have a car or a dog. So you can see how they have used your input to create a model to give you an application which is helping you to do things easily. So creation of the target variable becomes very, very important. Data, obviously, your features, historical data is important, but along with that, the target variable creation is also very important. One more example, go back 8 years from today, Facebook, right? You remember we used to manually tag photos. okay, this is me, this is my mother, this is my friend, right? Manually, we used to tag profiles. Remember? These days, we do not do that. Why? Facebook was asking you to create the target variables for them because it doesn't know that the image contains you, your mother, your father, your sister, brother, friends, and all, right? So we were actually creating target labels for them. Now, let's say after a year, Facebook had, let's say, 50 samples of your photo, maybe 50 samples of your friend's photo, because maybe 10 samples are coming from your profile, 30 samples are coming from his profile, another 10 samples are coming from some other profile, right? So when you had enough number of samples, you go ahead and you train a model, and now automatically for any user that who has been on Facebook, Instagram for a long amount of time, it will automatically be able to label them, tag them, right? Okay, it will also ask you, is this you, right? For images which are blurred, for images wherein maybe your face is not visible completely, maybe a side face is there. So if you see, it is constantly improving the model, it is constantly trying to better the model that is there, right? All right, so let's move forward then. Now we are going to bust some machine learning myths, right? So we are going to talk about some notations. What do you mean by AI? What do you mean by machine learning, deep learning, and all, right? So let's go through that. Now, first thing that we need to understand is that this is the overall hierarchy of things, right? Artificial intelligence is the bigger block, then we have machine learning, and then we have deep learning, right? Now, let's try to understand one by one, what do all of these things mean? Artificial intelligence, I want every one of you to pay attention, right? Any product, anything that humans create, right, which tries to replicate the job of a human is artificial intelligence, right? And a robotic vacuum cleaner, right, which automatically goes ahead and cleans your house depending upon the placement of items and furniture in your house, which will automatically create a trajectory, is artificial intelligence. A self-driving car, right, which goes ahead and which takes input from the roads, and it tells the car what it needs to do or what it not needs to do, right, is artificial intelligence. But all artificial intelligence is not machine learning, right? If I give you the example of the robo vacuum cleaner is not working on historical data. It is only working on a bunch of sensors and radars through which it is laying out the map of your house, right? It is laying out the structure of your house, and it is coming up with a movement plan, right? That, okay, this is how I'm going to move, maybe in a zigzag way. Let's say that there is a table in front, it is going to change the route. So it is totally an optimization model, right? It is not machine learning. It does not need any historical data, right? On the basis of whatever the present situation is at your house, the sensors will leave out signals through which the radars and the sensors are going to create a trajectory for your house, and on that your robo vacuum cleaner will work, right? This example is not machine learning, but this is artificial intelligence. Why? Because the robo vacuum cleaner is actually helping you do something which otherwise a human would have done, right? So artificial intelligence is something that is artificially created which assists a human. All right. On the other hand, a self-driving car is also artificial intelligence, but a self-driving car cannot work without historical data, right? Now, a self-driving car will come under deep learning or machine learning, because so artificial intelligence, there can be two kinds of outcomes. One, you can have products which are artificial intelligence products, but they are not using any historical data, just like a robo vacuum cleaner. But you can also have those products which are using historical data, just like a self-driving car, just like a recommendation system, just like Alexa, just like Siri, correct? So your functional robot as well, right? Let's say you go ahead and you create a robot which will help you in cleaning your dishes, right? So that is artificial intelligence. It might not take any historical data, right? So anything that you are creating, right? So you have seen robot restaurants, right? You would have seen in most of the cities nowadays we have a robot restaurant wherein a robot will serve food to you, right? Now, that is not machine learning, because the robot cannot improvise on what it needs to do. There is a predefined set of steps that it will have to do. But so that is artificial intelligence, but that will not be considered as machine learning or deep learning, right? Now, within artificial intelligence, we have, if you see the smaller bubble is what machine learning. Machine learning is that all of the products within artificial intelligence which can work only with the presence of data, right? The ones that, so if you see over here, so if I talk about the robo vacuum cleaner, right? The robo vacuum cleaner will be here, okay? But if I talk about, let's say, a recommendation system, right? A recommendation system which is working on historical data will be here, correct? Because a recommendation system cannot work without your historical data. So it will be within machine learning. All right. AI is the superset, ML is the subset, DL is not the intersection of both, DL is a subset of ML, right? So now I will come to deep learning. Within machine learning, right, there are certain advanced models, right? There are certain machine learning models which try to imitate the functionality of a human brain, right? If you see, the human brain is the most complicated model, right, which can learn things on its own, correct? We know that we have been learning so many skills right from the day when we were born. We learned how to walk, we learned how to sit, we learned how to speak, and gradually we keep on learning more complicated things, right? Now when you are 20, 25, 30 years old, right, with the combination of movements of your hand and foot and whatnot, you can do so many complicated things, right? You can multitask. The potential of the human brain doing stupendous things is unlimited, right? Correct? So there are some models which are highly advanced, right, which try to imitate the functionality of the human brain. How does it try to do that? All of that we will be covering when we get started with the deep learning part of this course, right? But those models within machine learning which are way too advanced, right? So it is just like in the world of cars, if let's say all cars were machine learning, right? So your electric cars can be deep learning, right? Because they are actually slightly more advanced, right? They are actually working without the need of, let's say, fuel, right? They are working on a battery. But both of the cars are doing the same thing. They are transporting you from point A to point B. So all the machine learning that you have, their end goal is to go ahead and make predictions using data. But within that, there will be a subset of models which are highly advanced, which try to imitate the functionality of the human brain. And that is what those models are known as deep learning models. So deep learning, right? Within machine learning, there is a separate bunch of models, right? Inside machine learning, which are known as deep learning models, right? Now, the deep learning models are specific models which are highly advanced, which try to imitate the functionality of the human brain. How it does that and all that is something that we'll save for later. Right now, all you need to understand is that you would have heard of models such as neural networks, right? Artificial neural networks, deep neural networks, recurrent neural networks. And have you heard the word neurons in a human brain? Presence of perceptrons, neurons in a human brain, right? So just like the neurons work in the case of a human brain, right? When you do something, there is a certain part of your brain, there is a subset of neurons within your brains that actually fire, that gives signals to the different body parts that you have to do this, you have to do that, right? Just like that, there are certain deep learning models which try to imitate the functionality of the human brains. They try to create artificial neurons. These neurons only fire when the need is, right? Right now, it's not the time to go ahead into the technicalities. All you need to understand is that these are complicated models which try to imitate the behavior of a human brain, all right? And that is deep learning. So now if you see, if I talk about chat GPT, now chat GPT is something that will come over here, right? So chat GPT is if you see chat GPT exactly behaves like how a human will, right? You ask something and it comes up with an immediate response, right? A dynamic response. And that is what you have over here in chat GPT. All right. So all of this we have explained. Artificial intelligence area of computer science emphasizes the creation of intelligent machines that work and react like humans, that is AI. ML, a subset of AI which gives the machine the ability to learn without being explicitly programmed. We have talked about this as well, that when we give data to a machine, it will automatically learn what it needs to do, what it not needs to do, that is ML. DL, it is a subfield of ML which is concerned with algorithms which are inspired by the structure and function of the brain called artificial neural networks, right? So I hope all of this is clear to everyone, AI, ML, and DL. Now we will move on to myth number two, robots will take up our job, right? What do you guys think? Is this a myth or is this a reality? So partially true, right? It's not totally true. See, it is not going to take up your job. It is going to make your job simple, right? See, 50 years before, when the computers were invented, people were scared that computers will take up their jobs. Did it take up jobs? It might have, right? Maybe 10% of the jobs. But did it create extra jobs? So many, right? India, Bangalore, Gurgaon, cities like these, right? They are existing. They are into, they are dominating the Indian ecospace. Why? Because of computers, correct? So with the advent of computers, yes, there were jobs that were taken, right? But then there were, maybe if 10 jobs were taken, 100,000 jobs were created as well, right? So yes, there will be certain recurring jobs that might be taken away. But then that is why you guys are here, right? That is why I have a batch of 190 people who want to learn about ML and DL and what data science is, right? Because you guys want to upskill yourself. With upskilling, obviously, you might be able to do much more complicated things in a more easier way, right? So it will not take up your jobs, right? And that is something, because see, I've been using ChatGPT for 8, 9 months now, right? I know that ChatGPT, right? The output that it gives depends upon the sophistication of the question that you ask to it, right? You will ask a dumb question, it will not have that much in intelligence that it will tell you that no, you have framed the question incorrectly. It will give you a response, right? So it takes a human to extract relevant information out of tools like these. So it will not take your job, it will make your job easy. How it has made my job easy? So last year I did something for my client which took 5 days for my team to do. This year the same thing we had to do for the same client, and we did it in a day, right? Because of ChatGPT, we were able to come up with a code which was able to, so we did not spend too much time writing the code. All we had to do was we had to give instructions. But these instructions, if I ask someone who is from, let's say, a non-data science background, they will not be able to give that because they don't have the experience. So if you don't have the experience, now you can be a very good driver of cars, but if I give you a truck to drive, if I give you a bus to drive, will you be able to drive that? No, right? It will require experience, right? So obviously these tools are there to help. Your artificial intelligence, all of these things are there to help, right? It will enable you to do more things. It will enable you to do things fast, right? It will enable you to do more complicated things in an easier way. But see, for people who don't like to stay updated, right? You would remember the case study of Nikon, right? Nikon was the, I think, camera, Kodak or Nikon, right? I'm not sure if I remember the name, but they actually, when digital pictures came in, right? Kodak was a company. They actually were resilient. They said that okay, this is not going to stay. They did not upgrade themselves, and eventually they went out of business, because right now we are living in a world wherein physical cameras are not even, no one is using that, right? Nokia also, right? So you need to be, obviously you need to be updated with time. Things are getting more tech savvy, so you need to be updated. That is why I have you guys here, and there are thousands and millions of people who are not doing this, who are still living in a bubble that okay, AI is not going to take the world, right? It is doing that, but if you work along with it, you will also grow, right? All right. So this is obviously a myth. Yeah. Now we will move on to the types of machine learning models, right? Now we have talked about machine learning. But there are different kinds of machine learning models that we have, right? So let's try to understand what these are, because all of the models that we will be studying in the duration of this course will either belong to one of the three categories that you see over here, right? So there are three categories that we have within machine learning, the kind of models, right? The first is supervised learning. Now, what is supervised learning? The examples that I have taken, right? If you see in those examples, we had some data and we had a target variable, right? So there are a bunch of models within machine learning which are known as supervised learning models. These are the models that work with the presence of a target variable. So these are the models which are very similar to the example, that is, let's say I tell you that this is what your target is, right? Let's say your father, he comes and sits next to you and he keeps on telling you that, okay, this is the target, you have to do this. Let's say the next thing that you have to do is this. Next thing you have to, let's say, drive on a highway, you have to change the gear from third to fourth and all, right? You know the target, you know what you are given with, right? And you go ahead and you try to come up with a solution for that, right? So supervised learning is that branch of machine learning wherein you pass a set of features to the model, your data to the model. Along with that, you also pass the target variable. The target variable will tell you that historically, this is how your customers have behaved, right? Go ahead, take the target variable, take the data, and try to come up with patterns that are there, right? So that is known as supervised learning. In supervised learning, we will have the input as well as output variable, right? So your target variable will also be there and your features will also be there. Now we also have another sets of models which are known as unsupervised learning, right? Now what is unsupervised learning? As the name suggests, there is no target variable over there, right? There is only features, right? Now there can be cases when you don't have a target variable, but you have lots and lots of data, right? So these are models which do not require a target variable to work with. Now, let's say if I go ahead and I give my customer data, all my historical customer data, that how many customers I have, what are the products that each and every customer has bought in the last 1, 2 years, whatever, right? And if I apply such models without any target variable, what these models do is that they try to come up with general trends and patterns. So a very common unsupervised learning model is clustering, right? What clustering does is that it tries to identify customers who are buying similar products. Now, see, for clustering, I don't need any target variable. If I see that, let's say these are 1,000 customers, all of whom are only buying, let's say, liquor and snacks from my store, I will go ahead and I will say that, okay, these are similar customers. Let's say I have another bunch of customers who are buying bread, butter, eggs, chicken, and let's say such fresh items, right? Maybe all the fresh items, they are not buying pulses, they are not buying rice, they are not buying, let's say, bathroom essentials and all, right? So on the basis of the products that these customers have bought, these unsupervised learning models will group them together, right? So unsupervised learning, that branch of machine learning which does not require a target variable. It still requires historical data, right? That is why it is machine learning, but it does not require a target variable, right? Supervised needs a target variable, unsupervised, no target variable, right? So let's move on to reinforcement learning. Now, reinforcement learning is the third kind of machine learning. Now, these are those models which automatically, right, adjust their predictions, they adjust the quality of predictions on the basis of your data distributions, right? Now, what do I mean by this? Your reinforcement learnings are those models. So this, you can say that these are the deep learning models which have the ability to adapt, right? When I say the ability to adapt, so let's say I created a model. Let's say I created a supervised learning model back in 2020, which was predicting what are the, let's say, items that my customers are going to buy from a medical store, right? Now, back in 2020, this supervised learning model would not have known that COVID is about to come. So maybe this model does not know that mask or sanitizers will become an important part of the future, right? So this model, even today, if you go ahead and use this model even in 2023, because it was created using 2019, 2020 data, it does not know that masks and sanitizers have become a crucial part of every human's life today, right? But the reinforcement learning model, if I talk about reinforcement learning models, right, these are models which keep on updating their predictions as per the customer behavior keeps on changing. So what the reinforcement learning models do is that they have a feedback loop. That is, from the prediction, the feedback loop will go to the data. Now, let's say back in 2020, my customers were buying something. Now in 2021, as soon as my customers started buying masks and sanitizers, your reinforcement learning model will retrain itself, right? It will retrain itself and it will adjust the predictions accordingly, right? So as and when your time progresses, if your customer behavior keeps on changing, your reinforcement learning models, which are slightly more complicated models, try to adjust the quality of predictions that they have, right? So that is your reinforcement learning. We are going to talk about all of these in detail as and when we proceed to the course, right? Right now, all you need to understand is that what are the differences between these three, correct? So if you see, supervised learning is nothing but you have a teacher which is actually helping you in understanding what is an apple, what is not an apple and all, right? Okay, so if you see, that is supervised learning. What are the use cases of supervised learning? Use cases are spam classifiers. We have spam classifiers automated in the emails, which will automatically detect whether an email is spam or not spam. How does it do that? It sees that historically all the emails that are spam, let's say they contain, you have won $10,000, $1 lakh, or let's say apply for a credit card and things like that, right? So any future email that comes, whichever emails have these critical keywords, right, it will automatically assign them as spam, right? Fingerprint analysis, right? All of this is what this is supervised learning. Your historical data is there. As soon as you go ahead and let's say you enter your fingerprints on the sensor, whatever, right? It knows automatically that this is you. It will have all your details, right? Maybe Aadhaar card or things like that. Unsupervised, if you see, there is no target variable. If I give this data to my model, it will automatically find out on the basis of similarity. Now it sees that these three bananas look very similar, so maybe I should group them together. It sees that orange is right, these three look very similar, the color is same, the texture is same, so maybe I should group them together. It sees these apples and it says that, okay, these look similar, so it will automatically group them together, right? So if you see, for unsupervised learning, I do not give any target variable. I do not give any, I explicitly do not tell the model that these are apples, bananas, and all. It will automatically cluster them into your different segments, right? Right now, use case of unsupervised is voice-based personal assistant. If you see voice-based personal assistant, right, they don't have any target variable. Their objective is to just take an audio data and convert that into text, right? So that is unsupervised learning. How all of this works, we are going to understand later. Netflix recommendations, if you see, if I'm able to group the movies which are similar together, right? Let's say I group all the fictional movies, I group all the action movies, animated movies, right? And let's say you as an end user, you went ahead and you watched animated movies. Now I can start recommending any animated movies from that cluster to you, right? So your recommendation systems are nothing but unsupervised learning, right? All right. So supervised learning, unsupervised learning, clear to everyone. Now we'll move on to reinforcement learning, right? Now reinforcement learning, as I've discussed in this case, right? We observed select action using policy. This is nothing but we collect data and we select a model, right? And the model will go ahead and give us the predictions. The predictions are nothing but action, right? So when it goes ahead and gives the predictions, then we collect. So let's say if I have 100 customers, right? Now for 100 customers, let's say for 60, the model gave the correct prediction. And for 40, the predictions were incorrect. So accordingly, we will either reward or penalize the model. Now, in an ideal situation, the model should be able to score 100 points. Let's say one customer, correct prediction for one customer attributes to a single point. Ideally, the model should collect 100 points, right? But let's say if it gives 60 correct predictions and 40 incorrect, let's say there is a +1 point for a correct prediction and -1 for an incorrect, the model will end up gathering only 20 points, right? Because 60 plus 60 minus 40 will be 20. Now the model tries to optimize, or the model tries to maximize the points that it can achieve, right? So if you see after that, in step 5, it will update the policy. It will try to update the rules, that is because something that it is doing is incorrect, right? Because of which these 40 predictions are coming out to be wrong. So it will try to improvise on that, right? And then this process will go on and on and on until it is able to come up with the maximum number of points, right? So that is what reinforcement learning is, right? And if you see, this is something that we can showcase through this example, right? Now, let's say before conditioning, there is a dog, and this dog, let's say, goes ahead, and whenever this dog sees food, it starts to drool, right? Now, reinforcement learning is forcing something to do something which you would want this person or this object to do, right? Now, let's say the next time, whenever you give food to this dog, you ring a bell, right? Every time you keep on doing this, whenever you give food to the dog, you ring a bell. And finally, let's say that you have done this process for many number of iterations. Now, one day, if you just go ahead and ring a bell, you don't even give any food, the dog will automatically start drooling, right? Now, this is kind of reinforcement training that usually people do, right? In order to train dogs, in order to train, let's say, animals and all. This is not very close to the example that we have taken, but this is just an example of how Pavlov was maybe a scientist or something, how he actually trained his dog using reinforcement learning, right? So this is just a general example of how exactly reinforcement learning works, right? Now, the typical use case for reinforcement learning is self-driving cars. How? So now all of these cars that you are seeing, right? XUV 700, the self-driving cars, right? With ADAS level 1, ADAS level 2 and all your Teslas and all, right? Do you think that these cars are straight away made and then just rolled out for public? No, right? There is years and years worth of testing and training that has already happened. When let's say if I take an example of an XUV 700, when it is, let's say when it was rolled to the public, right? The model that it is using, that would have that would have been trained on using years and years of data. Maybe XUV 700, the inception of the car would have also not been thought of at that point of time, but the model training would have actually commenced, right? Because you can train the model on any car, right? Now, what is this training? This is, see, when, let's say when I want the car to apply a brakes, right? Let's say in the first iteration, it does not go ahead and it does not apply the brake, and maybe it rams into an object, right? Now, what will happen? I will go ahead and I will give a penalty to this particular action, right? Now, the next time the model that is running the car will try to update the policy, and on this basis, it continuously, we expose the car to different scenarios, we expose the car to different let's say locations and different situations, right? And we expect the car to train automatically. Why do we want to do this? Because when I don't want to create a model which is limited by its learning capability, right? As and when, because see, when, let's say I buy an XUV 700 and I am, let's say, an aggressive driver, right? Some other customer buys an XUV 700 and this person is a safe driver, right? Now, the ADAS that you have, right? It needs to adapt as per the driver, right? Now, if the driver is aggressive, then maybe the reaction time needs to be slightly fast, right? Now, right now, we are not at a stage wherein we are actually able to see such level of autonomous driving, but eventually, once when these models keep on training, right? Just like in the case of Facebook, now that it is automatically able to tag photos, just like that, eventually when we would have collected enough amounts of data, right? We will reach a situation wherein this automated driving can actually be made seamless in, if not all, then probably most of the driving situations, at least in India, right? But this is the, at the back end, the model that is working is nothing but a reinforcement learning model. right? So this was supervised, unsupervised, and reinforcement learning, right? So now moving on to what we can do with machine learning. So if you see what kind of questions we can solve, right? Now we can answer any kind of questions using machine learning, right? Questions such as, is the email spam or not spam, right? Questions such as, what is the price of a house, right? Questions such as, will my customer buy a product? Questions such as, how much spend my customer is going to do in total, right? So there are any kind of questions that you have, we are able to answer those through machine learning. But depending upon the type of questions, we again go ahead and we divide these models into the different categories. Let's try to see what these mean actually, right? All right. Now, if you remember the supervised learning models, right? So if you remember when we talked about supervised learning models, right? Now, supervised learning models were what? They'll have a target variable, right? The difference between supervised and unsupervised was that there should be a target variable. Now, see, what if my target variable is a yes or no thing, right? Let's say whether the customer will buy a product or not. Should I give should I give a loan to this customer or not, right? Will this customer default on his or her payment or not, right? So if you look at this target, in all of the examples, my target variable is a category, right? Is a yes or no thing. So I can represent this as a binary variable, right? Maybe one means pass, zero means fails. Maybe one means rain, zero means not rain. Maybe one means pass the loan, maybe zero means do not pass the loan, correct? So the supervised learning models wherein the target variable is categorical in nature. Categorical meaning that the target variable is a category, right? Those models are known as classification models. What can be some real life examples that we can have? Just like predicting spam or not spam, predicting loan default or not. Exactly, right? So all such problems wherein your target variable is a category will be known as your classification models. So within supervised learning, we have something known as classification models. Classification models are those models which have a categorical target variable, right? Okay, now moving on, what are the examples of classification? If you see, one example is whether the transaction is fraud or not, someone trying to hack our network or not, right? So this will be one example. Clustering algorithm, which type of house lies in this segment, what type of customers buys this product, right? Here as well, if you see, this is not exactly clustering, but you can use classification to, let's say, group customers, customers who are buying protein shake, customers who are not buying protein shake, customers who are buying healthy, customers who are buying not healthy, customers who will buy the product on an offer, customers who will not buy the product on an offer, right? If you see, in all such cases, my target variable can be categorical in nature, right? Now, moving on, the second kind of supervised learning model is a regression model. Now, if classification is categorical, what do you think regression will be? Second option that we have is what? Either my target variable can be category or it can be a continuous numeric value, right? So when your target variable is a continuous variable, right? Then those kinds of supervised learning models are known as regression models, right? Can you think of any real life, real world problems which might be regression problems? So height prediction, price prediction for houses, weight, BMI, COVID numbers, stock prices, predicting the exact stock value is regression, weather forecasting. So your temperature forecasting, predicting the age can be regression. If you group the age, then you are actually creating categories, right? How many runs will Virat Kohli score? Yes, that is a regression problem. Air quality prediction, if you are looking at AQI index, right? Exact AQI index, that is regression. Share market, number of employees leaving my company, that can be regression. Road accidents, blood pressure, taxi demand and supply, right? So if you see regression, wherever my target variable is continuous in nature, my supervised learning models will be known as regression models, correct? All right. All right. So now supervised learning, if you remember, we can divide it into two types, right? One when my target variable is categorical in nature, one when my target variable is continuous in nature, right? How do we name those? What are those models? Within supervised learning, what will we call a model which has a continuous target variable? And what will we call a model which has a categorical target variable? So classification and regression, right? So classification will be what? Classification will be those supervised learning models where the target variable is categorical in nature. Regression will be those supervised learning models where the target variable will be continuous in nature, correct? Now, the kind of model that we are studying is a linear regression model. So when I say linear regression, can you tell me something about the kind of target variable that we will have over here? Continuous, right? So now, since the model name is linear regression, so by the name itself, you should be able to understand that this is a regression model. And if this is a regression model, this is a supervised learning model which takes into account continuous target variables, correct? Okay, so let's get started with this model. Now, linear regression, what is linear regression? Now, if you look at the name, right, linear regression. Now, what do you understand by the word linear? So linear may be a line, or maybe, so if you talk about, let's say, processes, let's say if I increase the speed of my car from 30 kilometers per hour to 60 kilometers per hour, how much distance will I be traveling in an hour? The first case, I would have traveling 30 kilometers. In the second case, I would have been traveling 60 kilometers, right? So if you see, there is a direct relationship between, let's say, the speed of the car and the distance that it travels, right? So there are many processes in and around the world which have a linear relationship. So by linear, so see, let's assume that you study for 10 hours and you score 50 marks, right? Let's assume that if you would have studied for 20 hours, you would have scored 100 marks, right? But if you study for 40 hours, will you score more than 100 marks? No, right? The maximum cap will be 100. So maybe the number of hours you study and the marks that you get, it might or it might not be a linear relationship. But if you look at the speed that a car travels with and the distance that it will travel, right, in a fixed amount of time, this will be a linear relationship, right? If my speed is low, the distance traveled will be low. If I increase the speed, let's say 5 times, my distance traveled will also increase by a margin of 5 times. Is that correct? Okay, so if now let's try to understand what we mean by linear regression, right? Now, linear regression, it is a technique of finding the relationship between two or more variables, right? Now, change in dependent variable is associated with change in one or more independent variables. Now, before jumping into this definition, let's first try to understand what we mean by dependent variables and independent variables, right? So dependent variable is the target variable, right? The variable that is dependent upon other factors, right? So see, whenever I'm saying target variable, whenever I'm saying dependent variable, whenever I'm saying, let's say your label, right? All of these words refer to the same thing, that is your target, right? The variable that you want to predict, correct? Whenever I'm saying independent variable, I say features, I say, let's say, dimensions of the data, right? Whenever I'm talking about these things, it means that I'm talking about the features, right? So let's say if I wanted to predict the time that it takes for me to travel from point A to point B, right? And let's say I take the speed of my car as a factor, as a feature. So my feature will become the speed of the car, and my target variable or my dependent variable will become the speed of the car, right? Right. So now if we go through the definition, so linear regression is nothing but it's a technique of finding the relationship between two or more variables. So my one variable will be the target variable that I want to predict. The other variable will be the independent variable, or it can be a host of independent variables. Either you can have a single independent variable, or you can have 2, 3, 4, whatever, depending upon however independent variables you have or you need, right? So linear regression is a model which basically establishes a relationship between the target variable and the independent variables or the features that you have. Okay. Now, change in the dependent variable, whatever change we have in the dependent on the target variable is actually dependent on all the features that you have. So that is why we are including these features in the model, right? If you remember, when we were trying to predict whether it is going to rain or not, we were taking independent features such as what will be the humidity, is it cloudy or not, right? What is the temperature and things like that, right? So we know that target variable is actually related to the features that we have, and the linear regression model is a model which helps us in finding out this relationship, right? This connection between the two, right? That is what the linear regression model does. Now, if you look at the definition, it only tries to capture the linear dependencies, right? So if you have two features which are varying with each other in a linear fashion, that is, as one increases, the other also increases by the same amount. As one decreases, the other also decreases by the same amount. If you have such relationships in your data, then linear regression model will be able to go ahead and will be able to map the relationship and create a model for you, which you can go ahead and use for future predictions. All right, so let's move forward. Now, if you see, regression is a technique that displays the relationship between variable y based on the values of variable x, right? Now, if you see, there is one more notation. Now, let me just write this down. Now, whenever I say target, whenever I say dependent variable, whenever I say predictor, right? Whenever I say y, right? All of this means your target variable, right? Whenever I say features, independent variable, right? Or your, let's say, dimensions or your x, right? All of these are your features. So don't get confused by these. Target, dependent, predictor, y, all of this will generally be y. I am saying y because once when we'll be working on Python, generally the target variable we denote by the variable y, right? Generally the features we denote by the variable x, right? This is a notation. This is a general kind of a thumb rule, you can say, that we use. So that's why just don't get confused by all of these, right? Now, if you see, regression is a technique that displays the relationship between variable y based on the values of variable x, right? So if you see over here, let's say this, which is your temperature, right? Your temperature is the independent variable. The number of, when your temperature is your independent variable, that is your feature, and the number of clothes that a person needs to wear is your target variable or the dependent variable. So you can see over here that as the temperature will go down, the number of clothes that a person is, let's say, supposed to wear or wants to wear will obviously keep on going up, right? So as and when it becomes colder, maybe you start wearing more layers of clothing, right? As and when it becomes hotter, you decrease the layers of clothing, right? So if you see, both of these variables will have a linear relationship. Does this have a inverse relationship or does it have a direct relationship, these two variables? Inverse, right? If you see, when one is decreasing, that is when temperature is decreasing, your number of clothes that you are wearing is actually going up, right? So it will be inverse relationship. Okay, so let's move on. Now, some examples, let's say temperatures versus number of cones sold at ice cream store. Now, what do you guys think? Will this have a direct relationship or an indirect relationship? These two variables, temperature and the number of ice cream cones sold. Direct, right? Why direct? Because let's say just try to take some examples, right? Assume that the temperature is 40 degrees. Obviously, you will sell more ice creams. When the temperature is, let's say, 10 degrees, obviously ice creams will not sell as much, right? Okay. What about the second one? Do you think that there is any kind of a relationship? No relationship, right? There is no direct relationship that we can see. Maybe, let's say, there might be a certain percentage of people who might be planning to buy cars, let's say. So it's not, buying a car is not dependent upon whether it is going to rain or not, right? Maybe you are buying a car, maybe you are planning to buy a car and you decide to buy a car during the rainy season. But if you are someone who knows about cars, you will definitely not want to purchase a car during the rainy season, because then it might catch rust and things like that, right? So ideally, there is no direct relationship. There can be some hidden relationship over here, but there is no evident relationship with the inches of rain and the number of cars that are sold, right? All right. Now the last one, daily snowfall versus number of skier visits. It will be direct. As snowfall increases, the number of skiers who are visiting will obviously increase, because more the snowfall, more people would be interested in skiing, right? Now there are different kinds of regression model. We are studying about linear regression, right? Now, if you see, in case of linear regression model, the output that we have from the model is the equation of a straight line, right? In case of linear regression, the output will be the equation of a straight line. We also have a different kind of a model which is known as logistic regression, right? Let's just look at the differences between these two. Now, linear regression and logistic regression, right? These are two models which might have a similar name, because if you see, both are end with regression, right? But there is a very basic difference between the two. The linear regression model is a regression model, whereas the logistic regression model, right, the name is a misnomer. It is not a regression model, it is actually a classification model, right? Why this is called a regression model, this is something that I'll talk about once when we start with logistic regression. But this is ideally, right, this is a regression model, right? Linear regression. But this, on the other hand, is a classification model, right? This is the essential difference. Now, if you see over here, this works on a target variable which is continuous in nature. Logistic regression works on a target variable which is categorical in nature. Solves the problem of regression, solves the problem of classification. Output is a straight line. The output is a S-shaped curve over here, right? Don't get worried about what logistic regression is right now. The only thing that you need to understand is that logistic regression actually comes from the linear regression model only, right? It is a slight variation of the linear regression model. That is why the name remains the same. But at the end of the day, logistic regression is a classification model. The name is a misnomer, right? Do not confuse it by, if someone asks you whether logistic regression is regression or classification, this is the only model whose name is confusing, whereas it says that it's a regression model, but ideally it's a classification model. All right, so let's move on. Okay, now moving forward, simple linear regression is useful for finding relationship between two continuous variables, right? Now, obviously the model is trying to find out relationships between the target variable and and the features that you have. So this model will help you in establishing the relationship between, let's say, two variables or howsoever many variables you have in your data, right? One is predictor or independent variable, and the other is response or dependent variable. If you see, there are so many terms: predictor or independent variable, or you have response or dependent variable or target variable, right? Now, simple linear regression is the most simplest form of linear regression model, where we have only one independent variable and we have only, obviously the target variable will remain one, right? In case of simple linear regression, I am limited by only a single feature. Only a single feature is used to predict the target variable, right? So let's try to first understand how simple linear regression works. Once when we are able to understand that, then we will move on to the complicated model, which is multiple linear regression, wherein we will be using more than one independent variables, right? All right, so let's look at an example, right? So let me give an example from, let's say, a separate example, right? Okay, so let's assume that I have an x-axis, something like this only. Let's say I have the x-axis here, right? Let's say I have the x-axis and I have the y-axis. On the x-axis, I have my independent variable, which is the, let's say, the quantity of products bought, right? Let's say the quantity of milk purchased, right? How many units of milk someone is purchasing, right? On the y-axis, which is my dependent variable, I have the target variable, which is the overall spend, right? So this will be your, right? This is your overall spend. This is my target variable, spend. I have on my x-axis, I have the independent variable, which is quantity. Now let's assume if I start marking this, right? If I mark this, so this is 0. Let's say 1, 2, 3, 4, 5, 6. 6, right? And let's say on the y-axis, you have your spend. So I will take, let's say I start with, this is 100. Let's say I have 90, 50, 70, 40, 30, 20, 10, and 0, right? Now, let's say I have one customer who comes in and buys one packet of milk, right? One packet of milk, and let's say a packet of milk costs 20 rupees, right? Half-liter milk costs, let's say it costs 20 rupees. So if I want to mark this customer on this graph over here, where will I mark him or her? Quantity bought is 1. The price or the overall spend that this customer has done is what? Is 20. So this cross, do you think that this cross represents the customer correctly, right? Let's say I have another customer. This customer bought 3 units of milk, right? For 3 units of milk, this customer spent, let's say, 60 rupees, correct? I have another customer who bought 2 units. This customer spent 40 rupees. Another customer who bought 4 spent 80 rupees. Another customer who bought who bought 5 and spent 100 rupees, correct? Now let's assume I also have customers who actually had some existing points and they went ahead and they took some discount, right? Now let's say I have one customer who bought one packet of milk, but this customer did not spend 20. This customer spent slightly less than 20, maybe 18 rupees, right? Now let's say I have one more customer who bought 3 units of milk, but this customer paid, let's say, slightly less. And I had one more customer who bought 5 units of milk, but this customer, let's say this customer also bought membership, some kind of a membership along with the milk, and this customer paid slightly extra, right? Maybe this customer paid slightly extra, right? Now, if you look at this, can I draw a straight line that can pass through all of these points? No, right? So what is the best alternative that I have in that case? If I'm not able to draw a line that can pass through all the points, what is the best alternative for me? I have 7 points over here, right? You cannot remove the points. That is your data. So the best option is what? The best option is that I will take a line which is passing through the maximum number of points, right? So if I look at these 5 points, so the 5 customers who did not avail any kind of a discount, if I look at that, that is actually something that is giving me the general trend in my data, correct? If you look at this is actually giving me the general trend in my data. And what if I go ahead and I plot this regression line, right? Now, see, what the model will try to do is that the model will try to fit the maximum points that it can in a line. Obviously, there will be some customers who are paying extra. There will be some customers who are paying less. But if you see, for majority of the customers, this is a linear relationship. And this is what the model tries to do. All of this we'll be trying to understand later as well, right? All right. But this is exactly what linear regression model actually tries to do, that it tries to come up with a linear relationship, right, between the target variable and the independent variable. The target variable over here is the spend. The independent variable over here is the quantity of milk, correct? All right. Now, if you see, let's go through some examples of the relationships that we can have, right? Now, if you see over here, I hope this is clear to everyone. What is the independent variable? What is the dependent variable? All of you would have studied y equals to mx plus c in school, right? School, college, wherever. So a line which has a positive slope, that is such an angle, it means that there is a direct relationship, right? As and when my independent variable is increasing, the dependent variable is also increasing, correct? Examples from real life of such a relationship, just like the one that I had given to you, distance traveled and the speed of a car, that will have a positive relationship, right? Can you think of other examples as well, which might have a positive relationship? Ice cream and temperature, student score and our study, experience and salary, petrol price and tax. Yes, that will have a linear relationship. Engagement versus productivity, oil price and flight ticket, that can have a positive relation, because as the oil price increase, right, the ticket price will also increase. I hope you are able to understand this, right? So there will be some variables which will have a positive relationship, right? So this is the one that we are seeing. For the variables which have a positive relationship, the line that you have will have a positive slope, right? Or if you don't understand slope right now, don't worry. The line will be just like this, right? It will be an increasing line. As one variable is increasing, if you see, as my independent variable is increasing, the dependent variable is also increasing, correct? So now what can you say about this? This is a negative relationship, right? If you see, as my independent variable is increasing, my dependent variable's value is going down, right? How will you identify that? If you see over here, let's say I take any random point over here, right? Let's say I take a random point over here. For this value of x, the value of y will be this. If I increase the value of x, the value of y will actually go down, right? So this shows a inverse relationship between the independent variable and the target variable. What are some examples? Less trees, more temperature, speed versus time, winter and ice cream consumption, amount of fruits in market versus price. Okay, pressure versus area, price and demand, demand supply, distance covered versus fuel, marks versus spent time for studies, altitude and oxygen level, cost and demand. Demand will increase, so the cost will decrease. Demand will decrease, cost will increase. Okay, I hope all of you are able to understand this. There can be certain variables which might have a negative relationship with each other, right? All right, so let's move on. This is the same, nothing different in the slide, almost the same. Now this line, right, whatever this line you're seeing, this line is known as the line of linear regression, right? So we have talked about this earlier as well. Now let's take a look at some examples how we actually plot this line, right? So let's go through that. Now these are observations. I've explained this already, that depending upon your independent variable value and your dependent variable value, you will get some observations which we need to plot, right? Now, let's assume that this is the data that we have, right? Let's assume that I have some target variable, right? Let's say if I pick some examples, right? So let's take the example of child's age and child's height, right? So let's say on my x-axis, you have the age, right? And on the y-axis, you have the height, correct? All right. Now let's assume that these are the actual distributions. These are the actual data points that have been distributed, right? Now, there will be different children. So let's say I have a child whose age is whatever this represents. And according to that, this is the height, right? So you will have all the whatever data points. Now, can you tell me how many data points we have in this graph? How can I identify the total number of data points? Is there a way to identify that? 11, right? If you just count these dots, if you just count these circles, these are the observations. Each and every circle, right, is an actual observation, is a student. Let's assume that it is a student, right? Now, if you look at age and height, generally with age, height will increase, right? But there can be some children for whom the height increase is exponentially higher, right? And there can be some for whom the height increases, let's say, slightly lower as compared to the normal, right? Not exponentially high, but let's say if a couple of years, if let's say the age, if let's say the height increases by 6 inches, maybe there can be some children for whom it increased by 7 inches or 8 inches. Maybe there can be some for whom it increased by 4 to 5 inches only, right? Okay. But if you see the general trend, as and when my age is increasing, my general trend is saying that your height will also increase. There are outliers that are present in this data, and outliers will be present in every data, right? If you see this is an outlier, right? If you see this one is an outlier, if you see this one is an outlier, to a certain extent, the points that are far apart from this particular line are outliers, right? But then we have gone ahead and we have created this particular regression line, right? Why have we done that? What do you guys think? Now, see, obviously, in your in your real world data, right, your relationships will not be purely linear. There, you can estimate them as a linear relationship, but it will not be purely linear, because obviously there will be certain outliers. There will be slight variations that might be happening in the data, but that is fine, right? When I'm creating a model, I'm predicting the general range, right? I might not be able to predict for outliers, but at least for, let's say, 90% of my population, I will be able to go ahead and come up with a decent prediction value, right? See, now we will try to understand how do we arrive at this line of best fit, right? I hope you guys are able to understand what this graph is talking about. What are these data points? What is this regression line? Now, the next topic that we'll be talking about is how do we identify this regression line? Because, see, if I talk about this data, I can have n number of regression lines that can pass through this data, right? I can have, let's say this is one line. I could have had also one line which might have gone through this, right? I could have had one line which would have gone like this. Why did I go ahead and why did I create this as my final regression line? Why did I not create the other brown lines that you are able to see on the screen, right? Because the model will have the option to go ahead with n number of lines, but from those n number of lines, it will choose the best fitting line. How does it identify the best fitting line, right? How does it arrive at the equation of the best fitting line? That is something that we will try to find out now. Okay. Okay. So let's move on. Now, if you see, when we are trying to find out the line of best fit, right? Let's try to understand certain things about this, right? Let's go back to this particular graph and let's try to understand some things or how we actually work with this data, right? Now all of these blue points, right? All of these blue points are your actual data points. If you remember, I have talked about training and then I have talked about once when you will train the model, after that you will go ahead, you will use the model to make predictions. So having that thought in mind, just remember that these points that you are seeing, right? These blue points that you are seeing, these are the training data samples. Imagine that these are 11 children in your class for whom you have gone ahead and you have just taken their age and you have taken their respective heights, right? That is it. Okay. I'll just write this down once again. This is age over here and this is height over here, right? So imagine that these are your current students in your class, these 11. For them, you have gone ahead and you have plotted the age and height, right? From these data points, let's assume that you arrive at this particular best fitting line. How did we arrive at that? Don't worry about that right now. Just imagine that you arrive at this particular point, right? Now, this regression line will become your final model, right? Let's try to understand how we use this model to make predictions, right? Now, let's assume that a new student, your teacher informs that a new student is coming to your class and the age of the student is 13 years, right? Is 12 years, let's say, right? Now, 12 years on the x-axis, let's imagine that 12 years sits somewhere over here, right? 12 years is something, or let's say 12 years sits somewhere over here, right? On the x-axis. Now, as per the model, my model will go ahead and my model will make a prediction that the height of this particular student should be this, right? Let's assume that this is a point that intersects at 5 foot 4 inches, right? Let's say this on y-axis intersects at 5 foot 4 inches. All right. So what you can say is that for this student, when the age was, let's say 12 years, my model's prediction actually came out to be 5 foot 4, right? Okay. Now let's say that once when this student walks in my class, right? Once when I see this student, I realize that the height of the student, the actual height of the student is actually, let's say, over here only, right? Let's say the actual height is somewhere over here, right? So your model actually went ahead and predicted 5 foot 4, but your real height for the student, when the student walked into your class, when you saw the student, was actually, let's assume, 5 foot 6, right? So now can you calculate the error that you have? You have the actual height of the student, you have the predicted height of the student. By how many inches are we off in predicting the height of the student? 2 inches, right? If you see, if instead of doing all of this, if I would have just gone ahead and if I would have just taken this difference of the point from the line, would I have not gotten the same 2 inches value? If you see the distance of this point from this line, the vertical distance of this point from this line will give you exactly 2 inches, right? So can we say that the vertical distance of this point from this line is actually the error of the model? not the model, but for this particular point. Now, if I ask you to go ahead and calculate the error of the entire model, or if I ask you to calculate the error of all the data points, how can you calculate that? If you go ahead and if you calculate all of these vertical distances, would that not give you the error? I will go ahead and I will calculate all of these vertical distances, right? Summation of all the distances. If I do that, will I not get the error of the model? I will, right? So let's say that the vertical distances or this error for this line, right? Let's say the error for black line comes out to be, let's say, some value, right? Let's say the error comes out to be 25. Just a random value I'm taking, right? Let's say this error is 25. Now, I'm drawing one more regression line, right? Let's say I draw one more regression line, and this line is, let's say I'll change the color. The new regression line is, let's assume this. Not the new, but let's say one more option that we had for the regression line. Let's say it was this, right? And let's say the next option was this, right? Now, if I ask you to go ahead and calculate the error of this line, right? This particular orange line from all of these points, right? This error of orange line will always be greater than this 25, right? Why? Because the black line, let's assume that this comes out to be 40. Now the black line is my best fitting line. When I say the line is a best fit line, it means that the vertical distances of all of these points from this line is the least. So any other line, you can try drawing any other lines through all of these points, and you will always realize that the error of all the rest of the lines will actually be greater than the line of best fit. And that is the reason why it is known as the line of best fit, because this is the line that is giving you the minimum error. This is giving you the minimum vertical distance of all the data points from this line, right? And that is why this is called as the line of best fit. All right. So if you see, this is what they are explaining over here. The error is what? The error is this vertical distance, right? Your estimated value was the red point, whereas let's say your actual value was this blue point. So this will be the error, right? This will be the error over here. If you go ahead and if you calculate the error of all the data points, your objective is to minimize this error. When your objective is to minimize this error, you will need to find a line of best fit, which is actually giving you the least value of this error, right? So that is what we are trying to do over here. These are some examples. Speed and distance, they have a positive relationship. Distance and speed, right? If you see, y becomes your target variable, which is distance. X becomes your independent variable, which is your speed of the vehicle. M, which is the slope, right? M is the slope, that is the angle that this line will have, right? That is your M. And C is the constant value, that is when X equals the value 0, then what will be the value of the target variable, right? So y equals to mx plus c. You can see that y is the target variable, x is the independent variable, m is the slope of the line, and c is the constant. All right. So now if let's say there is a negative relationship, let's say I take time and speed, for example. So when I will take time and speed, in that case, your y remains the same. Let's say y becomes time. My x becomes the independent variable. Over here, if you see in this example, your slope will become negative, right? As soon as the relationship of the target variable with the independent variable becomes inverse, the slope of basically the coefficient that is involved with the independent variable will actually become negative, right? If you look at this over here, right? When my speed is, let's say 10 kilometers per hour, the time taken will be more. When my speed is, let's say 60 kilometers per hour, then the time taken will be less, right? So let's start with one example, right? One mathematical example as well. So now let's assume that I have two variables, x and y. The value of x is such 1, 2, 3, 4, 5, and the value of y corresponding to the value of x is 4, 3, 4, 2, 5, right? Let's go ahead and let's plot these data points on this line, right? One by one. First point is what? X is 1, Y is 4, correct? So when X is 1 and Y is 4, it will be plotted somewhere over here, right? Similarly, I plot all of these points. You can go ahead and you can check. First one is 1, 4. The second one is 2 and 3. The third one is 3 and 4. Fourth one is 4 and 2. And the fifth one is 5 and 5. Now let's move on. Let's see what happens. If I calculate the average of X and if I calculate the average of Y, right? The average of X will come out to be 3 and the average of Y will come out to be somewhere around 3.6 something, right? 3.6, 3.8, whatever. So if I just plot these vertical and horizontal lines, so we are just plotting the averages of Y and X for now, right? Because that is something that will give me the slope in a way, right? That will give me the slope of the line. So we need to find out the average. See, first of all, guys, you don't need to do all of these things manually. These are just examples. We are just trying to explain how internally linear regression works. Once when we'll move to the hands-on, you will see that all of these things, right? This is something that Python will automatically do for you. All you need to do is that you need to pass a set of independent variables and the target variable, call the model, take the model, run it on the data, take the output and use it as your predictions, right? This is just to understand what internally happens, right? Now, if the average of X was 3 and the average of Y was 3.6, then your line of best fit, right? This will pass through this 3, 3.6. Now, this is mathematics. This is something that because your slope is nothing but Y minus Y average and X minus X average, right? No need to get into the definitions and all. No need to get into the mathematics. But generally what happens is that your line of best fit will pass through the average of X and Y both, right? That is what you can see over here, right? Now, if this point is 3, 3.6, my best fitting line is the line which is passing through this particular point, right? Okay, let's try to map. Let's try to see how we arrive at these values. Now, the definition of slope is this, right? You don't need to, you can go ahead and if you want, you can calculate the slope using this formula. But once again, as I've said, no need to do that because Python will automatically do this for you. Slope is nothing but summation of X minus X bar, right? So all the values of X, you are going to subtract it from the average of X multiplied by Y minus Y bar. All the values of Y, you are going to subtract them from Y bar and you are going to divide it by the summation of X minus X bar whole squared, right? We are going to do this manually. Let's try to find out how, right? So in order to calculate the slope, right, which is M, I need to find out X minus X bar, Y minus Y bar, and X minus X bar whole square. I have the values of X and Y. I have the value of X bar and Y bar. Can I calculate X minus X bar and Y minus Y bar? We can, right? So we'll do that. So for the first point, my data point was 1. The average of X was 3. I do a 1 minus 3, right? Similarly, so I get the value minus 2. Similarly, then I move ahead to the second point. For the second point, the data point was 2, the average was 3. So I do a 2 minus 3, this becomes minus 1, right? Like this, I will do this for all the X data points, right? If you see 3 minus 3 becomes 0, 4 minus 3 becomes 1, and 5 minus 3 becomes 2. Now, can I go ahead and can I calculate Y minus Y bar as well in a similar way? So you can go ahead and you can do that. We will be calculating Y minus Y bar, right? And it comes out to be 0.4 for the first, then it comes out to be minus 0.6 and I get all of these values, correct? Now I have both of these. I also need to calculate X minus X bar whole squared. I will just take a square of this particular column and I will get the X minus X bar square as well. I get those. I substitute these values, right? So I calculate the sigma. First of all, if you see it's sigma, so I need to multiply X minus X bar with Y minus Y bar. I do that. Minus 2 into 0.4 minus 1 into all of this, right? So I do this and I get these values. And then we calculate the summation of all of these values, right? Sigma of X minus X bar whole square and sigma, that is summation of X minus X bar into Y minus Y bar, right? And I do that, I get this value. This gives me a slope of 1 by 10, right? So I was able to find out the slope of my line, right? Now, this is exactly how internally the linear regression model comes up with the slope of the best fitting line. There is no need to plot n different lines and all. Mathematically, this is what we need to do, right? So now that we know the slope, right? I know that the slope is 0.1. I have my data points as well, right? I can go ahead and I can substitute these values to find out the value of C as well. So my X becomes 3, which is the X average. My Y bar becomes 3.6, right? So my Y average was 3.6, my X was 3. So if I go ahead and if I multiply this, right, 3.6 equals to 1 by 10 into 3 plus C, I will be able to find out the value of C, which comes out to be 3.3, right? So now C becomes 3.6 minus 0.3. So eventually your C becomes 3.3. So you are able to find out both your M and C for the linear regression equation. And the final equation that you have actually becomes y equals to 0.1x plus 3.3. The 0.1 was the slope that we have found out. After finding out the slope, we have imputed the slope and the values of y average and x average in the equation to find out the value of C, right? Once when I find out the value of C, I get the final equation, which is the equation of my linear regression line, right? And this becomes my final line. Now, if you see, this line is not passing through all of the data points, but this is the line which is giving you the minimum distance, or this is the line which is giving you the least error from all of these points, right? If you take a vertical distance from all of these points and calculate the error, try creating any other line that passes through these points or that passes far away from these points, you will realize that the minimum error you are getting is from this particular line only. And that is why this is what the linear regression model tries to do. So now you can also calculate the mean square error, right? Now you have the regression line and you have the actual data points. When you have the regression line and you have the actual data points, all we need to do is that we need to get the predictions. So now for x equals to 1, from the line, I am getting the value 3.2, right? From this particular red line, I am getting the value 3.1 and so on and so forth. So I will get the predicted values. I have the actual values, right? Using the actual and the predicted, I can go ahead and I can calculate the mean square error or whatever error you want to calculate. Now, finding the best fit line, we have gone through that. This is just kind of an output that we get from the Python model. So I will be showcasing this to you once when we start with the hands-on. So let's hold on for now. Now, the next thing that we need to understand is the evaluation metric. Now, for our linear regression model, there is an evaluation metric that goes by the name of R square, right? Now, what is R square? R square is basically a metric that tells us how good your line of best fit is or how good your linear regression model is, right? So let's try to understand what do we mean by R square, how do we calculate it, right? And what does different values of R square tell us about, right? So first of all, R square is a metric that is also called as goodness of fit, right? Goodness of fit or R square. And this is a value, nor this is a metric that you get after running your linear regression model, right? In Python, you will be getting outputs, and in the output, you will be getting the R square value as well. Now, R square value ranges from between 0 to 1, right? So first thing that you need to understand about R square is that it ranges between 0 to 1. The second thing that you need to understand about this is that, let's say I have a model A, right? So let's say model A has R square of 0.5, right? Let's say I have model B. This model has an R square of, let's say 0.8, right? So a model, or let's say that linear regression model which has a higher R square is a better model, right? So we aim, when we are creating the linear regression model, our aim or our objective is to get an R square value close to 1, right? So generally any model which has an R square of, let's say, greater than 70%, right, is considered to be a good model, right? Anything less than that, it means that you might probably need to add more features to the model. right? You might need to, let's say, do some feature engineering. Maybe you need to look at whether the variables that you have included are actually correlated to the target variable or not, right? So an R square value of anything less than 0.7, 0.6, that is not a very good R square value. Anything which is greater than 0.7, 70% means that you have created a decent, or you have created a good model, right? Right. Now let's try to understand what R square is, right? Now, let's say, let me take an example, right? So let's say I have the target variable of customer spend, right? And I take my feature, I take one feature, which is, uh, let's say, the age of customer, right? I take only one feature, the age of customer, and using this, I get an R square value of, let's say, 0.5, right? Now let's talk about a second model. In this model, my target variable remains the same, but now I am using the age of the customer. I am using, let's say, whether the customer is a member of my store or not, right? I am using what is the income of the customer, right? Let's say now I'm using three features. In order to predict the same variable, that is customer spend, now I am using three features: age of customer, whether the customer is a member or not, and the income of this customer. Now let's assume that my R square increases to 0.8%, right? 0.8. Now what does this mean? Now, how do we interpret this value, right? How we can interpret this value is R square of 0.5% means, or 0.5 means that given whatever features you have used in the model, you are able to capture 50% variation of the target variable, right? The 50% variation that is happening in the target variable, you are only able to capture that, right? As soon as you added more variables which are important, right? If you see, if I add the whether the customer is a member or not, what is the income of the customer, my R square increased to 0.8, meaning that now I am able to explain 80% variance of the target variable, right? Using these three features, right? So you can understand that you need to include relevant features in your model, right? Your independent variables should be relevant. If you are including garbage variables, let's say where you go ahead, you include 20 different variables, but all of these 20 variables are random variables, they are in no way related to your target variable, your R square will not increase, right? Only when you add significant variables to your model, your R square value will increase, right? That is the only way to increase the R square value. All right. So R square signifies how good the prediction of the model will be, right? So the more relevant or the more significant features we will have in our model, the better the model's R square value will be, right? Now the formula for R square is the one that you can see over here at the bottom, right? That is the predicted value, right? Whatever your predicted value is, subtracted by the mean and divided by the actual, whatever your actual data point is subtracted by the mean, right? So this is just a formula. Don't worry about this. You don't, if you remember the formula, that's okay. No one is going to ask you the formula and all, but you should just understand what we mean by R square and how the R square varies when we are adding significant or insignificant variables to our model. How we find YP, Yatharth, I assume YP, you mean the predicted value. YP is the predicted value, right? That you will get from the model. Just what we have done over here, this, substitute the values of X in your equation and you will get a predicted value, right? So this is just an example of how we can calculate R square. But once again, there is no need for you to do this. We'll go through this, but at the end of the day, Python will do all this calculation. Now, if you see, if my Y predicted was 3.2, right? And my average of Y, if you remember, that was 3.6, right? So you will calculate all of these values, right? Then you have your actual Y, it is 4, and you will subtract it by your mean of Y. You will get all of these values. You will square these values up. And after doing this, if you look at the R square of the model, if you substitute all these values, right, you will find out that the R square of the model, if you see, they're just calculating all the values, yp minus y mean whole square, y minus y mean whole square, all of this is calculated, and we get an R square. I get sigma 1.9 and 5.2. I substitute these values and I get an R square of 36%, right? So 36%, you can see that this model is actually not a good model because the data points are actually way far off, right? Hence the R square is coming out to be a smaller value as well, right? Now, see, the linear regression model cannot do anything. If you are giving in data points which are having a non-linear relationship, over here, if these data points do not have a linear relationship at all, right? These are distributed in a random way. Obviously, linear regression model will not be the best fitting model, and hence that is why you are getting an R square value of 36% only. So what is good R square value? I told you that just now, Arundhati, right? Anything above 70% is generally good. Anything below 70%, it means that you can add more significant variables, right? So see, R square gives you an intuition of how many relevant features you have included. Let's say for the first model run, you go ahead and you use, let's say, 10 features. And using 10 features, you end up getting an R square of, let's say, 60%, right? Now you know that there are some additional factors that you have not considered. Maybe if you go ahead and if you consider those factors, you should be able to increase the R square value, right? So then you will have to go back, you will have to do some digging, you will have to find some other variables, some other factors, right, which might influence the spend of your customers, right? Now here, if you see, if I want to predict the spend of the customers, do you think that age, income, whether the customer is a member, do you think that that is enough? Apart from that as well, there can be other factors, right? So let's say the lifestyle choices, right? Whether they are married or not, whether they have kids or not, right? There can be n number of factors that can actually drive how much a customer is going to spend in your store, right? So if you get a lower R square value, means that you should do more, you should invest more time in identifying important and significant features. If you're able to identify those, then you should be able to create a model which will be able to give you a better R square value. Now, if you see, as and when my data points start coming closer, now if you see here, my data points were far apart, so my R square came out to be 0.36. Now, if you go ahead and if you calculate the R square for this, here you can see that the data points are much more closer. My R square becomes 0.6. If my data points are almost on the line, my R square increases to 0.9. If my data points are exactly on the line, right, my R square becomes 1. And hence your R square cannot go beyond 1, right? 1 is the maximum value that your R square can attain, right?
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampark IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
Okay, so let's try to understand what do we mean by VIF. Now, see, VIF is, let me open. Now, VIF, do you guys know the full form of variance inflation factor? So VIF stands for variance inflation factor, right? What has been told to you, why do we use VIF? What is the need of using VIF? For multicollinearity, right? What do we mean by this particular term used for multicollinearity, right? Now, what do you understand by this particular term? That is multicollinearity. So multicollinearity, right? Multicollinearity means correlation amongst the features, right? Now see, when we are talking about linear regression model, correlation between features, right? Now, see, linear regression model, it says that your independent variables, right? Independent variables should be correlated to the target, correct? What it says is that let's say you have features which is spend, quantity, visits, discount that a customer has gotten, right? And then you have the target variable, that is whether the customer buys the product or not, buy or not buy, right? So these over here, if you see, these are my features, right? Spend, quantity, visits, and discount. And this is my target variable. Is everyone able to understand this? Now, what is the objective when I'm building the linear regression model? The first objective is that uh, so the first objective is that each of these variables, right? Now, spend should be correlated to my target variable, correct? So my first requirement is that this spend should have a correlation with the target variable. Quantity should be correlated with the target variable. Visits should be correlated and discount should be correlated, right? That is the first assumption, or that is the first rule of the linear regression model that we have. Now, the second rule says that your independent variables should not be correlated, right? This is what the second rule says over here. Independent variables should not be correlated. What does this mean? This says that I want the independent variables, or I want my features to be correlated with the target variable, but I do not want these variables to be correlated amongst themselves. Spend should not be correlated with quantity. Spend should not be correlated with visits. It should not be correlated with discounts. Similarly, quantity should not be correlated with visits or discounts, or visits should not be correlated with discounts, and vice versa, right? Now, first of all, let's try to understand why do we have this particular assumption, right? Now, let's assume that I give you two variables, right? I give you a variable which is spent in dollars, right? And I give you a variable which is spent in rupees, right? And I have the target variable, which is whether the customer will buy a product or not buy, right? Now, these two variables, do you guys think that these two variables will be correlated to each other? The spend in dollars and spend in rupees. Now, see, spend, let's say you spent 100 rupees. You can have two variables, that is the spend in rupees was and the spend in dollars was, let's say, $1.1, whatever. You can have that, right? So these variables will be what? These variables will be correlated between themselves, right? Now, what will happen if I go ahead and if I use these two variables in my model, the same effect, right? Let's say that this spend in dollars has a correlation with buy not buy of a 20%. This spend in rupees has a correlation with this buy not buy of, let's say, 20%. Now, if I'm using both the variables together, I am using the same effect twice, or I am calculating the same effect that spend in dollars and spend in rupees is giving. I am calculating that effect twice. So if, let's say, I was to predict whether the customer was buying or not buying, right? This, using these two features, I might be able to capture the same effect. Whatever information these two variables contain is exactly same. So I'm feeding similar data to my model, but it's just I'm saying that the name of the columns is different, right? So what will happen is that if I'm passing variables which are correlated, then my prediction of the target variable will get wrong, right? Because you might be calculating the same effect more than once. If you're calculating the same effect more than once, obviously your predicted value will become way more off, right? So that is why the second assumption that we have is that your independent variables, your features should not be correlated between themselves, right? And in order to find that, the method that we use is known as VIF, that is variance inflation factor. So now let's try to understand what do we mean, like how do we apply VIF, right? First of all, do you guys know the formula for VIF? So the formula for VIF is 1 minus 1 divided by R square, right? I hope everyone remembers R square. What was R square? R square was the explained variance divided by the total variance, goodness of fit, right? Not the evaluation matrix. R square is just a, yeah, not evaluation matrix. You can say evaluation metric, right? Metric is still fine, not matrix. So the formula for VIF is 1 minus 1 upon R square, right? So let me take one example. Let's say I go ahead and I have these features. I have the spend. I have the spend in dollars. I have the spend percentage. I have quantity, and I have quantity ratio, right? Now, or let's take only two of spend in percentage and spend rupees, right? Now here you should be able to see that your spend percentage and spend dollars will be related to each other, and your quantity and quantity ratio will be correlated to each other, correct? Now see, one simple way of dealing with highly correlated variables is what? That you go ahead and you either select one of each, right? Let's say you go ahead and not use spend dollars, or you go ahead and not use quantity ratio. You just go ahead, use spend percentage and quantity, and that's it, right? That is one way to do so. But generally, see, it might happen that spend percentage and spend, maybe 80% of the information that these two variables contain is same, but maybe there is some amount of information that spend percentage has which is extra as compared to the spend variable, right? Similarly, quantity and quantity ratio, it might be that these two variables are correlated with each other only by 80%. So meaning that only 80% information that they contain is very similar. The remaining 20% might be dissimilar. So if you're going ahead and if you are directly dropping spend dollars and quantity ratio, you might be missing out on some critical information that you might have wanted to feed to your model, right? So generally, we don't do that. We do not try to get rid of correlated variables manually. If you see that there are 2-3 variables which are such highly correlated that you're getting correlation values of 90, 95, right? 80, even greater than 80, then you can go ahead and you can exclude those. But in the real world, this will not happen. In the real world, you can have variables which are correlated by, let's say, 30, 40%. So if you get rid of one variable, the 30-40% correlation aspect that was about to get doubled, you have dropped, but the remaining 50-60% information that was new in this variable, that also you have dropped. So you might have dropped some important information from the model, right? So that is where the application of VIF actually comes into play, right? Now, if you see VIF, when we apply VIF, right, you remember, if you would be remembering what you would have realized, that they would have applied the VIF function only on your feature space. They would have not applied your VIF function on your target variable. So now, let's say what I do is that now I am assuming that one of the variables, or there are some variables in these which are highly correlated, right? So what if I do one thing, right? I take one of these variables as a target variable, right? Let's say I take spend percentage as the target, right? I take this as a target and I build a model, right? I'm just explaining to you how VIF works, right? I build a model using spend dollars, quantity, and quantity ratio. Now, just answer me one thing. If assuming that this spend percentage has variables which are correlated with itself, right? A spend dollar, quantity, quantity ratio, do you think that the R square of this model will be high or low? R square is the same metric, right? That we have talked about. If we have variables which are correlated with spend percentage, the R square of this model will be high, right? Okay. So if my R square will be high, can you tell me what my VIF value will be? VIF value will be small or large in that case? VIF will also be large, right? Because if you see 1 upon R square will be small, but if you do 1 minus 1 upon R square, it will also be large, right? Deepak, it is R square, not R. Goodness of fit, we have, right? So just try to understand this thing, that if I go ahead and if I try out different combinations over here, right? Let's say the next combination that I try is spend dollars. I regress it with the remaining features, which is spend percentage, quantity, quantity ratio, right? Similarly, I take quantity, I regress it with spend percentage, spend dollar, and quantity ratio, right? And I take quantity ratio and I regress it with, let's say, spend dollars, spend percentage, and quantity, right? Now, let's assume that what happens is that the R square for this model, right? R square for this model is high. Let's assume the R square for this is medium, for this is low, and for this is also low, right? If my R square is high, correspondingly, what will happen? My VIF value will also be high, because you can see that the formula for VIF is 1 upon 1 minus R square, meaning that your VIF value will also be high, right? Here VIF will be medium, here VIF will be low, and here VIF will also be low, right? Now, out of all of these variables, which variable would you want to remove from the model? Is it the variable which has a high R square, or is it the variable which has a low R square? The variable which has a high R square, it means that it has variables which are correlated with itself, right? Because if the variables are correlated, only then your R square will be high. So what I'll do is that I will go ahead and I will exclude this first variable from my model, right? Okay. Now I will repeat this process again and again and again. I will only get rid of one variable per iteration, right? Now in the second iteration, I will be left with only these three features, right? Now with these three features, I will run the VIF code once again. If let's say I get a VIF value of high for any variable, I will exclude that. Let's say I get VIF value as low for all three, right? I will go ahead and I will use my model, or I will build my model using only these features. Now for VIF, right, the general principle is that, see, your VIF value will never be negative, right? If you look at this over here, 1 minus 1 upon R square, the formula, right? Your VIF value will always be in the range of 0 to infinity. It can go from 0 to infinity. Let's assume that your R square value is very small, right? Right, so this is the formula for VIF. Right, now if you see, if your R square will be high, that is close to 1, then 1 minus a value which is close to 1 will be a small value. If you divide that by 1, so this overall VIF will be a very large value, right? If your R square is close to 0, then your 1 minus 0 will be 1, and 1 divided by 1 will be equal to 1, right? So for those variables which are not correlated to the rest of the features, your R square will be low, and hence your VIF will be close to 0, right? Not 0, close to 1. So your VIF can range between 0 to infinity. The general rule of thumb that we have is that anything in the range of 0 to 5 VIF is considered, you can go ahead and you can accept those features. Any variables which have a VIF of in the range of 0 to 5, you can accept that. Anything which is greater than 5, right, or greater than equal to 6, right? Any variable that has a VIF value of greater than equals to 6, you have to remove that from the model, right? That is the general rule of thumb that we have. Calculate the correlation after converting categorical variables to numerical. But as I said, right, let's assume you have a couple of variables which are correlated, and the correlation between them is only 50%. Now, how will you decide which feature you want to take away? Because both of the features contain 50% information which is mutual, but both of the features contain an extra 50% information that is new as well. So which feature do you decide to take away from the model? So manually, if you're trying to identify correlated features, then generally it becomes a very cumbersome process. You might get rid of an important variable in the process. When you run this, when you try to exclude variables using VIF, you are actually using a statistical approach wherein you are eliminating those features, the information for which is actually contained in the rest of features, right? So let's say if you eliminate a feature which has an high R square value with the rest of the features, meaning that when you eliminate this, no information that this feature contained is actually absent in your data. Everything is still there. Even when you go ahead and you drop this variable, whatever information that variable contained is being accounted for in some variable or the other that you have in your data, right? So that is why VIF is a more robust solution. It is a more statistically accurate solution and method, right? We'll get started with the hands-on of the linear regression model. So the case study that I have for you is a Boston house price prediction case study. We have Boston house price data. Boston is a city in the US, and for this city, we have the data of some houses that are there in this city, and we have certain factors about these houses, right? Factors such as where the house is located, how far is it from, let's say, a highway, how far is it, let's say, from a corporate center and things like that, right? And using all of this data, we will try to go ahead and we will try to predict the price of the different houses that we have, right? So that's the objective. We are working on collab. I am working on collab. You can work on anything, Mohammed Ansari. This is collab, right? So see, the only thing that is different, this is Google Colab, right? Now most of you might be using Anaconda, Jupyter notebooks and all, which is nothing but your locally hosted uh, Python versions, right? Now, this is a platform that is by Google. You can also use this if you have a Google Drive. If you are able to save your data on your Google Drive, you should be able to use Google Colab as well. The only thing that is different in Google Colab, now the interface is Python ID, everything is Python. Now, the one thing that is different here is that while reading the data, if you remember in your usual Jupyter Anaconda notebooks, right? All you have to do is that you have to do a pd.read_csv, and you just have to give the path of the file, right? Wherever that file would be in your local system, you have to give that, right? Over here, because we are working through Google Drive, our data needs to be in our Google Drive. So here, if you see, this is my Google Drive. And if I go to my drive, if I go inside Collab Notebooks, Intellipaat, Weekend Batch, Linear Regression, this is where you will find my data, right? Now, if I want to read this data, I will have to set up my Google Drive. This is a predefined syntax, nothing, you don't need to change anything. You need to give permission to Collab to access the drive, right? So from google.collab, I'm importing drive and I'm mounting the drive. When I mount the drive, you will get a request to authenticate this. And once when you authenticate that, just like I would have done a minute back, you should be able to go ahead and you should be able to establish the connection. Now, if you see when I do this, this is the path of my file on my Google Drive, right? As soon as I do this, I am able to read this data, right? And that is the only difference. Other than that, every syntax that you are able to run on Python, on your Anaconda Jupyter notebooks, the same things you will be able to run here, right? It is essentially Python and nothing is different, right? It uses your Google Drive, so your data should reside on your Google Drive. Most, I would say 70 to 80% of the corporates that you have, right? They are using either Google Colab or a similar platform. So if you will be comfortable with Colab in your resumes, in your CVs, right? You can add this as a skill as well. Generally, people are familiar with your Anaconda Python notebooks and all your locally hosted machines. But when you're working for large corporates, you're not working on locally hosted systems, right? You might be connected to GCP, you might be connected to cloud distributed computing and all. And in those cases, Collab or similar platforms are much more easy to use. Audrey content drive will remain the same. And then from here, so till content drive and my drive, everything will remain the same. Even collab notebooks will remain the same. After that, you will have to create your folders. Wherever your data is present, you will have to add that. So we have been able to read the data, and this is how my data looks like, right? So let's first try to understand what does this data contain? What is our problem? What is the objective? Let's try to understand all of these things, right? Now, if you see over here, I have the description of all the variables, right? This is the description that we have for all the variables. Let's try to understand this. Now, see, each and every row over here in this data is the data about a particular house, right? So if you look at this, this is the data for a particular house. This is the data for maybe, let's say, some other house located in Boston. This is the data for some other house, right? Let's focus on one row. Let's focus on the first row. If I focus on the first row, the first variable that I have is what? Is the variable which is crim. Crim is nothing but crime. So this variable gives you the per capita crime rate by town. So wherever your house is located, right? For that particular location, for that particular pin code, what is the crime rate? That is what the crim variable talks about. Okay. Second variable is Zn. Zn is what? Proportion of residential land zoned for lots over 25,000 square feet, right? Now, imagine that you are living in a sector where there are lands over 25,000 square feet, which are, let's say, uh, given to industries, or let's say given to societies, right? So Zn is a variable that actually talks about that. That is the proportion of the land in that particular area, right? That is given to, or that is zoned for lots over 25,000 square feet. Now, for over 25,000 square feet, it can mean that there is a factory that is coming up, there is a mall that is coming up, there is a society that is coming up, anything. But this is talking about the proportion of land, right? Now, an area which is, let's say, located in an industrial area, it will have a higher proportion of land which has greater than 25,000 square feet of an entire land given to one single unit, right? So if you see over here, it says 18% of the land for wherever this particular house is located is given to lots which are greater than 25,000 square feet. Moving on to the third variable, Indus. Indus is proportion of non-retail business acres per town, right? So Indus will basically tell you what is the non-retail business acres in that particular area. So when I say non-retail business, once again, you can have retail specific businesses which can be there around your house, right? You can have malls, you can have a big bazaar, a Spencer, and things like that. But let's say when you start having industries, right? Let's say when you start having the shop for a footwear, right? Or let's say you start having the shop for, let's say, some other thing, maybe for a car showroom or things like that, right? So it is talking about that. It is talking about the percentage of non-retail business acres. Now you can imagine that an area which is a proper housing society, all of these percentages will be low, right? Zn and Indus and all. For a house which is located in an industrial area, or let's say for a house which is located in a corporate area, right? For those houses, all of these proportions will be high, right? Moving on to the fourth variable, it is CHAS. It is the short form for Charles River dummy variable. It is a binary variable. It just says that whether or not your house is situated along the Charles River. Now, Boston as a city, it has a river that flows through it, which is the Charles River. So this is a binary variable which tells you that whether your house is situated on the banks of the river or not. Now, do you guys think that this is an important variable in predicting the price of a house, or all the variables till now, do you think that these are important? These are important, right? Because a house which is situated on the on a river bank, obviously it should have a high cost. A house which has a low crime rate, it should have it should have a high cost, and so on and so forth, right? NOx is your pollution related variable. So it talks about nitric oxides concentration. So if NOx percentage will be high, then it means that this house is situated in an area where pollution is high. Maybe this house is situated next to industries, next to malls, right? And hence the pollution content might be high. So this once again talks about the uh, quality of living that you might be having if you choose this house, right? RM is the average number of rooms per dwelling. So RM is, let's say if I talk about a particular area, let's say if I talk about South Delhi, in South Delhi, let's say if I take, if on an average, each and every house, if I take the average of all the houses, the average of the rooms, let's say it comes out to be 2.5. So I'm saying that on an average, a house that is located in Saket will have 2.5 rooms. So just like that over here, your RM says, when it says 6.5, it means that the houses over here are pretty big. And on an average, they contain 6.5 rooms in this particular area. The age is proportion of owner occupied units built prior to 1940, right? Now, age is a variable which tells you about those percentage of houses in this area which were built before 1940. So in this case, it is saying that 65% of the houses in this area are historical and they were built before 1940, right? So this talks about whether the houses that are there in this area are new or old. If the houses might be old, maybe the price might be more high, or maybe it might be lesser, right? So age variable talks about that. Moving on to the DIS variable, this is the weighted distances to 5 Boston employment centers, right? DIS variable. So this gives you the, so let's say if you want to purchase a house, right? Now, if you're aware with Gurgaon, a house which might be situated closer to Cyber Hub, which is a corporate hub which has all the companies, will probably be the best option for someone who works in a company, right? So the distance, if I go ahead and if I calculate the distance of a given house from the 5 important corporate centers of the city, right? So this distance will give you that uh, information, that is whether this house is situated centrally, whether this house is situated close to the corporate centers, or this house is something which is maybe situated on the outskirts of the city, right? Now, RAD, the next variable, is your index of accessibility to radial highways. So just like distance was talking about the distance to corporate centers, RAD is talking about the index of accessibility. How far are the highways from this particular house, right? Is it situated inside the city, which might be far away from the highways, or is it something that is situated close to the highways that you have, right? Then tax is the full value. What would weighted mean in distance? So weighted is, if you have 5 corporate centers, right? Let's say the distance from one is 5 miles, the second one is 10 miles, third is 20 miles, and so on and so forth. So you'll just take the average of that, right? Now, tax is the tax that you are paying for that particular house, right? So that is the tax amount per $10,000, right? So per $10,000, you are saying you are paying $296 for this house. PT ratio is pupil to teacher ratio, right? What do we mean by this? So PT ratio tells me that in this area, if there are 15 students, then there is one teacher, right? Now, this tells you about the number of schools that you have in and around this particular area. Do you think that a PT ratio of a high PT ratio will be a good thing, or a low PT ratio will be a good thing? Low is good, right? Low means that there are more number of schools in and around your locality. So low PT ratio will actually give you tell you that this area contains more number of schools. If there are more number of schools, then obviously you have more options to put your children in, right? Then black is the percentage of black population. If you see, black will be the proportion of blacks in this town, right? So this, once again, not the proportion of blacks, but count of black people per 10,000 people in total, right? So if you see 396 and all, so this is now generally in the US, if let's say a locality contains more number of black people, maybe there is a high chance of uh, let's say robberies and all, right? So maybe the price of the house might not be very high there, right? So this is talking about that. L stat is the percentage of the lower status population that is living in that particular area, right? So L stat is, if you see 4.98, so 5% population belongs to the lower status, 10% belongs to lower status, and so on and so forth, right? And then medv is the target variable that you have, that is the median value of all the houses that are there in this particular area, right? So if you look at this, medv becomes your target variable. So our objective is to go ahead and predict the medv variable. Ideally, your crime rate should be correlated to, let's say, the proportion of, or the black variable, or maybe the lower status variable as well. So this is something that we can check once when we are checking the correlation matrix. So Saurabh, if PT ratio is high, it means that there are low number of schools. If there are low number of schools, then see, when you go to buy a house, right? The important factors are what? That your house should be close to highways, your house should be close to malls, your house should be close to schools, hospitals, and all, right? So if it is high, it means that schools, there are not many schools which are around there. So probably the price of the house can be low, right? All right. So this is the data that we have, and the target variable that we have over here is medv. So let's move forward then. So this is, I have done a data dot head over here. So these are the top 5 rows. I also have a function which is known as data dot tail, right? Tail, what it will do is that it will show you the last 5-10 rows. If you don't give any value, it will automatically show you the last 5 rows. If you want to, let's say, see the last 10 rows, you go ahead and you give a 10, and it will show you the last 10 rows. Correct? So now from here, we can see that there are 505 rows over here in this data in total. Okay. Let's look at the shape of the data. We'll do some basic data exploration now. So my shape of the data is I have 516, I have 506 rows and I have 14 columns, right? I will describe my data. Let's go ahead and describe this data. What does this dot T do? Any idea? Transpose, right? So I've just done this for ease of readability. If you do it like this, when you have more number of variables, right, this can you'll have to scroll towards the right, right? So if I just transpose this, it becomes easy to view. So that's why I've transposed this, right? Why do we use this describe function? What do you think is the use of this? Let me go through the common answers now. So first of all, I had insights on crime rate and ZN, right? If you see crime rate, there are areas wherein the crime rate is close to 89%, right? Meaning that these are very unsafe areas. So within Boston City, you have areas wherein the crime rate is as low as 0%, and you also have areas where the crime rate is as high as 89%, right? Similarly, if you look at ZN, there are certain areas in this city where the entire 100% of the land is actually zoned out to lots greater than 25,000 square feet, right? Then in age, average age is 68, 75, 94, 75 people. Understanding of this variable is incorrect, but yeah, the insights that you have extracted are good. Them blacks are nearly equally distributed, right? If you look at this variable, even the 25th percentile for black is 375, 50th percentile is 391, 75th is 396, max is 396, right? So if you look at the black variable, right, it generally, the proportion of blacks per 10,000 people in the city is in the range of 370 to 390, right? So that was a good insight. Chas has low accuracy. Chas will not have accuracy. Is a binary variable, but I think what you're talking about makes sense. If you see, there are only 7%, close to 6.9% of the houses which are situated along the Charles River, right? Zn, if you see, the max value of Zn is what? 100%, right? 100% means that this variable was giving you the percentage of houses, or sorry, the percentages of the total land which was zoned out to greater than 25,000 lots, right? So there are areas wherein there are locations in the city wherein there are all the land that is zoned out is greater than 25,000 square feet. No land is less than 25,000 square feet. So maybe this is an area which contains of industries. Maybe this is an area which contains of farmhouses only, right? So that's what your ZN is talking about. All right. So all good points. I just wanted to ensure that now see, apart from these insights, the describe function also comes in to be very useful as a sanity check of your data, right? Now let's assume over here I had an age variable. Now our age variable means something else, but let's assume I had the age of customers, right? Now let's say you go ahead and look at the minimum and maximum value, and you're seeing that the minimum value is coming out to be 0 and the maximum is coming out to be 200. Then obviously you have to go back and you have to question your data team that how can age be 200? How can age be greater than 80, 90? How can age be less than, let's say, 10, 11, 18 years, right? Whatever your minimum age might be. So your describe function, it helps you in understanding your data, but it also helps you in identifying anomalies, identifying outliers that might be present in the data, right? All right. So let's go ahead and do some basic visualization. First thing that we need to do is that we need to start with the visualization of the target variable. What is a target variable over here? A target variable is medv, which is a numerical variable, which is a continuous variable. So I go ahead and I import cbond as SNS and I call the dist plot function, right? This will be the distribution plot. Uh, this is the histogram and this is what I can see, right? What do you guys think? Is this a normally distributed data, or it has some amount of skewness? Or looking at this data, anything that you can make out? Any insights that you can think of? not left skewed, right skewed. It has a tail towards the right, right? Right skewed, but if you see towards the end, there is a very high percentage over here, right? So there are houses which are very expensive, and there are lots of people who are buying these houses. So if you look at this, right, this is actually true because let's say if you focus on cities like Delhi, Mumbai, and all, maybe mediocre people like us, we might be able to afford a house in the range of 50 lakhs, 1 crore, maybe 1.5 at the max. But then there will be, let's say, people who are rich, people who are businessmen, people who have been living in the city. Their generations would have been in this in the city for years, and these are people who have huge amounts of money, and this will also contribute a significant percentage, right? And these are people who are living in, let's say, villas and farmhouses and all, and hence you can see that for your extremely expensive houses as well, there is a good percentage of distribution that I can see over here in this data, right? So this looks like that this actually looks like real world data because most of your data is populated towards the left hand side, meaning this focuses on your let's say people who are below average, or let's say mediocre families, maybe average families, right? Most of the people in a city will be like this. Then if you move from here, right, if you move to 30 till 48 onwards, this percentage will be less because as and when the price keeps on increasing, the amount of people who are buying those houses obviously goes on decreasing, right? But then there will come a point wherein you are going to reach to the audience which is super rich. The super rich audience, they don't care, right? Even if a house is priced at 50 crore, they have the potential to go ahead and buy it. And that's what we are able to see over here, right? So looks good. I think this is something that tells us about how real world interaction also happens, right? How you identified medvi as the target column? I know that medvi is the target, how I have created this case study. Now, if you want, you can use any other target variable as well, right? But because I know that all of these variables will be correlated to the price of a house, I have taken medvi as the target. You see, you do not identify medvi as a target variable. Uh, you take a business problem and you convert that to a mathematical problem. If your business comes to you and they say that I want you to predict the spend of the customer, and they give you 20 features, will you identify the target variable, or do you already know the target variable? Your target variable, you know that it is the spend of customers, right? Now you will try to collect data which is correlated with spend. This case study is a case study which aims on predicting the price of a house, right? So that's why your medv is the target variable. Aishwarya, go back to the basics of your distributions, visualization and all. This is right skewed because this has a tail towards the right hand side. All of this is basic stuff. This is a normal distribution, right, with no skew. This will be a normal distribution which is skewed towards the right hand side, or positive skew. This will be a normal distribution with a negative or a left hand skewness, right? Left side skew. All right. Now, like this, you can go ahead and you can plot all the rest of the columns as well one by one. I will not be doing that. But you can see that this is the distance variable. Now for the distance variable, this was the distance from highways. So you can see that most of the houses that you have are actually situated very close to the highways in the city. But then there is certain percentage of houses that you have which are actually situated very far apart from the highways, right? So just like this, you can go ahead and you can visualize it for all the variables one by one. But this is an EDA that you can do. Now let's try to clean this data slightly. Let's see, uh, either you can check if the data has dropped, if the data has duplicates or not, or you can just directly go ahead and drop the duplicates, right? So what I'm doing is that directly, I'm not checking if there would have been any duplicates in the data, they will be automatically dropped, right? So you do not need to worry about whether there are duplicates or not. Just go ahead and add this condition, drop duplicates, and it will automatically drop your duplicates from the data, right? Now I'll go ahead and I'll check the information on this data. What this will talk about is if there are any missing values in the data or not, and the data type, right? So there are no missing values. All the variables have exactly 506 values populated, and the data type is either float or int, right? So there are no categorical values over here. All the variables are either integer or float. Now let's go ahead and let's check for correlation of all these variables with respect to our target variable, which is medv, right? So what I do is that I go ahead and I call the correlation function, and I limit the output to only the medv variable. So if you see, this output tells you about the correlation of each and every variable with your target variable, right? I want you to go through each and every variable and check if there are any null values. We have checked that over here, right? It says that there are 506 values populated in each and every column, and there were 506 values in my data in total. So means that there are no null values. What is the difference between dist plot, hist plot? Both seems to be histogram. So there is not a very big difference. See, dist plot and hist plot. Hist plot is the histogram directly. Dist plot, in case of dist plot, right, you can also have a distribution along with this. There are certain parameters that we have. I don't remember. Just let me check. So, bin range. There was one parameter which is different in his plot. I'm just trying to find that out. Otherwise, there is no difference between his plot and dist plot as well. Okay, so this is his plot, right? This was this plot. So let's look at this. Yeah, so here I think you can also play around with the kind, right? So kind, if I give as, let's say, there are options which I can give. I'm not sure what options are there. But in the kind, actually, you can change this histogram to a kernel density estimation as well, I think. Let's try KDE. Yeah, so if you see KDE, yes, kind equals to KDE. Disk plot, we have options. If you go ahead and if you can convert this to a distribution plot as well, right? If you want to plot a histogram, you go ahead with the standard option, or you can mention this over here. Let's come to this correlation. Now, I want you to go through these correlation values and see if they are making sense, right? I'll give you one example. So if you look at this over here, my crime rate has a negative correlation with medv, telling me that if crime is higher, then the price of the house will be low and vice versa. And this is something that makes sense, right? This is something that is expected. Now, just go through each and every variable one by one and see if all of the variables are, or the sign of the correlation matrix for all of the variable is making sense or not. Okay, just do this once. It does not mean that. It means that houses which are situated next to the river have a higher price. More number of rooms, obviously more the price of the house will be high. So for the black one, the correlation looks out to be counterintuitive, right? That is where there are more number of blacks, the price of the house is high, right? Now, see, this is something that you can see. Ideally, you will have assumptions about the data. Now, Boston as a city might not be that much affected by, let's say, blacks in a negative way, right? So this is what our data is telling me. So although the correlation value looks out to be counterintuitive, ideally from a normal point of view, maybe if there are more number of blacks, then the crime rate should be high and all. But as you see in our data, for 10,000 people living in an area, there are only blacks in the range of 350 to 400, which is what? Which is only 40 4% or 0.4% of the population, right? Just 0.4%. So that's a very low value. So hence, over medv has a negative correlation with tax. So that means that if tax will be higher, the price of the house will be lower. So maybe the tax structure in Boston would be such that the more that you're paying, right? So see, generally in certain US cities, the flat structure, the tax structure is flat. Even if you buy, let's say, a house of, let's say, $1 lakh, you are paying, let's say, 10,000 as a tax. even if you buy a house of $5 lakh, you're paying the same 10,000 as a tax, right? So maybe they have a flat structure for tax. That is why we are seeing a negative correlation. So LSTAT is negative, right? So LSTAT says that lower status population. So the lesser lower status population, the higher the price, and vice versa. RAD is negative, meaning that houses which are situated close to the radial highways, their prices are less. Houses which are situated far apart from the radial houses, their prices are more. Maybe this indicates on the fact that people do not want to live near busy highways where it can be noisy, where maybe the pollution can be high. So people in Boston, they prefer living in areas which are slightly far apart from the highways, so that they have more peaceful and quiet living, right? So, as I said, we are done with the EDA, right? So, this was a concise EDA, but ideally you should go ahead and you should look at all the different variables, visualize the variables univariate, bivariate. That is something that you can do on your own time. Need to do is that we need to divide our data into our features, that is independent variables, and the dependent variable, that is the target variable, right? So what we will do over here is that at first, what I'm doing is that I will only take the highly correlated variable, right? So first, what I'll do is that I'm using, let's take the most highly correlated variable, which is LSTAT, right? So I'll take LSTAT over here as my independent variable. I'm not starting with a multi-linear regression model as of now. As a first step, I'm just starting with your single model, simple linear regression, wherein we will have one single variable and one target variable, right? And for that, I am picking the most highly correlated variable. If you look at this over here, your LSTAT is a variable which has the highest correlation, right? Followed by RM, and then there are other variables as well. So I'm just taking LSTAT as a variable and then MEDV as the target variable. Now, if you think about, let's say, if you have to eliminate 50 variables, you will be running 50, you will be running this loop 50 times. So that is, if you have 100 variables in the first iteration, 99 in the second, 98 in the third. So you can do the maths that. So as a first step, first, what we are doing is that we are building a model using only one single independent variable, which is LSTAT, followed by the target variable, which is MEDV. If you look at this becomes my data. X is my feature and Y is my target variable. Okay. All right. So what is it that we need to do next? We will look at the size of both X and Y. My X contains 506 elements, Y contains 506 elements. Next thing that we need to do is that we need to divide our data into training and testing. Why do we need to divide our data into training and testing? Then what is test for and to test, right? So train data will be used for training the model. Test data will be used for testing the model's performance, and this will tell us whether the model is overfitting, underfitting, whatever, right? So I can create a model which is giving me a 90% accuracy on training data, but that will not be useful unless if I have a similar accuracy on the testing data, right? So for that, we are using train test split. Train test split is a function, right, which needs input. You pass any data as an input to this model. Over here, I'm passing my X and Y. I pass a test size parameter mark at 0.2. 0.2 meaning that 20% of your rows are going to go in your testing data, right? So for 506, 20% close to 100 rows will be going into your testing data, right? Now, random state equals to 23. What this hyperparameter does is that, so let me explain this to you through an example. Now, let's say I run this. Let's take away the random state variable. I will run this and I will show you what xtrain contains, right? Just look at the index of xtrain values. I will run this once again, right? And I will plot xtrain once again. Now compare this xtrain with this xtrain. Do you see the indexes to be same or different? Different, right? So if you do not specify any random state, then what will happen is that each and every time random values will be going into training and testing, right? Now, random state you can specify as any value, right? Now, let's say if I go ahead and specify this as 20, I go ahead and I run xtrain, right? 7 268 80. I will run this once again and I will show you what xtrain looks like once again, and you can see that the exactly same indexes are going into your train data each and every time. Why do we need to do this? We need to do this because let's say you run your model once without using random state and you get an accuracy of, let's say, 70%. Now let's say you run the same model in front of your senior and this time you get an accuracy of 68%. Now they will come to you and they will say that why you were saying that it was 70, why is it 68, right? So if you want to replicate the same outputs each and every time, then you should be using a random state value. It can be anything, Kaushik, it can be any random number. As long as you are taking the same random number each and every time, it does not matter. It will select the same number of rows. Test size is for the test data. 20% is the testing data size. If you look at this test size, if you look at the shape as well of our data, our X train contains 400 rows, X test contains 100 rows. So 80% is for training and 20% is for testing. And then we go ahead and we build our model. In order to build our model, I have my training data, I have my testing data. I will import the model from sklearn library, sklearn dot linear model. I import linear regression. I instantiate the model object linear regression in a variable named as regressor. I do a regressor.fit. When I do a dot fit, it will train the model because here I'm passing the training data, that is X train and Y train, right? If I run this, now your model training is complete, right? If you look at this, the model training is done. It can be 70-30, it can be 80-20. As in when we proceed during this course, I will be talking about instances when it can be, let's say, 70-30, when it should be 50-50, right? But as of now, for 90 to 95% of the use cases, 70-30, 80-20, anything between this will work fine. Fit means that, yes, as soon as you fit it, it will go ahead and give you the coefficients for the best fitting line, right? So now, once when the model has been trained, you can see that I can go ahead and I can find out things such as the intercept value. Intercept was what? It was the constant. And I can find out the coefficient of the model. Now, because I have one single feature, this will become my coefficient. So if you look at this, my equation has actually become medv is equal to 34.927 minus 0.966 multiplied by lstat. Lstat was the variable, right? Yeah. So now from here, you can see that the equation of my linear regression model, the equation from the best fitting line is coming out to be this, right? Because my intercept was the constant, that is 34.927, and my coefficient corresponding to the single variable, which is lstat, is coming out to be 0.966, right? So this becomes my equation. Although you don't need to use it manually, you will still be able to arrive at this equation, right? Usually you will take more data points on training and a decent size on testing. Now that the model training has been done, what do we need to do? We need to make predictions on our testing data, right? So I will go ahead and I will use the same model object, that is regressor. And this time I use the predict function. For training my model, I had used my fit function. For predicting using the same model, that is the same line of best fit which we have gotten, I use a predict function. I do a regressor.predict and I pass my testing data. And whatever values I get, I save it in a variable known as ypred, right? Now ypred, I just convert this to a data frame. If you look at this over here, if I show you ypred, this will be an array, right? Now these are your 104 values of your testing data, 104 predicted values of your testing data, right? So we go ahead and we convert this to a data frame. This is the predicted output. You have created a model to get predictions, right? So this is the predicted output that you are getting. Now, what do we need to do in order to check the performance of the model? We need to compare these predicted values with the real values, right? Actual values. So what I'll do is that I'm converting this to a data frame first of all, right? This array has been converted to a data frame using pd.dataframe function. I pass the array and I pass the column name as predicted, right? To this array, I will append my actual values as well. If you look at this, y test was my actual values, right? These were my actual 102 values. So what I'll do now is that I will add both the actual and the predicted to a data frame known as df underscore pred, right? And I'm just doing some resetting, right? My actual becomes my test data and my predicted becomes my ypred. Because both of these were data frames, I'm just resetting the index, because if you see over here, these have different values. I want the index to have these values 0, 1, 2, 3 till 101, right? And this becomes my actual versus predicted. Now, can you go ahead and can you calculate the error, different kinds of errors? First of all, before going ahead and calculating the different errors, just having a look at this, do you think that the predictions are somewhat close to the actual values, or they are far apart, or they are, let's say, decently apart? Right? So for some cases it is close, for some it is off. If you look at this over here, actual was 21, model is predicting 14. Here 13 and 12 very close. Here 18.9, 18, 13, 16, right? So how can we check the overall performance of the model? We can calculate our error metrics. Now, either you can calculate the error over here in the data frame. So what will be the error? If I go ahead and if I calculate the just the error, right, it will be actual minus predicted. So you can calculate it either like this, right? Or you can go ahead and you can see, this is a messy way of doing things. Functions in Python, right? From sklearn I import metrics, and this metrics will contain all the different kinds of errors that there are. So if you look at this, it has mean absolute error, it has mean squared error, it has your root mean square error. Anything that you need, it will go ahead and it will give you that. So if you see, what I'm doing is that I'm calling all of these functions one by one, and I'm passing my actual and the predicted values here. If I run this, this will give me the overall error of the model, right? If you see, your mean absolute error is 4.5. What does this tell you? That on an average, your predictions are off by 4, by a value of 4. So 4 over here is nothing but $4,000, right? So your predictions are off by close to $4,000, right? So we are using the actual function. sklearn is a library which contains all of these models. Okay. Now mean squared error is 35. Because this is a squared error, the unit will not be same. If you take the root of mean squared error, that will be RMSE, that is 5.8, 5.9, right? I can also calculate something known as mean absolute percentage error. So let's see. So if you see mean absolute percentage error, if I pass the same y test and y pred, I will get on an average, my predictions are off by what percentage, right? So if you look at this, so it says that on an average, my predictions are off by 21%, right? So the model is doing a decent job. It is not doing a very good job. But why is that happening? Because I'm using only one single feature, right? If you see over here, I'm using only one feature, which is LSTAT, and using only one feature, I am still able to create a model which is giving me a percentage error of around 21% only. So obviously, if I increase the number of features, my model accuracy or my model error should decrease, right? Okay, let's try to get the R square score, R square. For R square as well, sklearn.metrics, it has a function which is R square score. All we need to do is that we need to pass y test, y pred and all, and it will give me the R square score. What is the R square score coming out to be? 44%, right? Meaning that these three variables, sorry, this one variable is only able to capture 44% of the variation of your target variable. Features will be significant. You will get more accuracy. Not aware of these errors. I think this should have been completed in your. Okay, so let's assume that these are your actual and predicted values. So what will be your absolute error? Absolute error is what? It will be the doesn't matter what the sign of the error is, you're just taking a difference of actual minus predicted, right? This will be the actual error that we have. If I take the average of this, that will be what? That will be mean absolute error, right? So this will be MAE. Okay. If I take the average of my actual values, all the actuals, and then I just calculate a percentage, right? That is error divided by the actual average of actual. This will give me mean absolute percentage error. Because here, if you see, I'm converting this error to a percentage with respect to my actual average. Okay. Now there is also something known as MSE. MSE is what? MAPE is percentage error. This 4.86, what percentage is that of your total average of actual value? If you calculate the percentage, this is 4.86 divided by 36 is what? Is around 14%. Now we have something known as mean squared error. Over here, what we do is that we take the square of the error first, right? So if this was my error, I'll do this into the same value, right? Okay. And then if I take an average of this will become your mean square error. Right? This will become your MSE. This is the squared error. And if you take a root of this, if you take a under root of this, that will become your RMSE, root mean square error. Why root mean square error? The logic of root mean square error is that the values which are more away, the predicted values which are more far apart than the actual, you want to penalize them more. If you look at this over here, this absolute error squared becomes 1. Square of 0 becomes 0, but the square of 9 becomes 81. So it means that you are giving more weightage, or you are penalizing those data points more, which are far apart from the actual value. All right. So these are your standard errors and how they are calculated. You have the Excel. Actual value is the actual value, right? You will have the actual value for the data, whatever your target variable will be. Right now, my R square is coming out to be 44.4%. So now what can we do next? Next, let's do one thing, right? I will add the second highest correlated variable, and ideally through the assumption, my R square should increase, my errors should decrease, correct? Does that make sense? So what I'll do is that over here only, right? I will repeat the same process, and I will add one more variable, which is RM to this. I hope that makes sense. So here what I'll do is that I will add the RM feature as well, because RM you can see is the next variable which has close to 70% correlation, right? So let's add RM and LSTAT. Now my features become two, LSTAT and RM. Target variable remains the same. I divide my data once again into training and testing. You can see that now the shape of your training data becomes 404,2. Why? Because now you have two variables. I fit the same model. This time in the model, I will get one intercept value as usual, but I will get two coefficients, right? If you look at this, I am getting two coefficients. My equation will be what? My final equation will be equation that we'll get from this model. What will be the equation? Med V equals to, give me the values, right? You're able to see the values of coefficients. My intercept is 0.24, coefficient is 66 and 4.98. So it will be minus 0.24. That's my coefficient. Minus 0.66 into LSTAT, because that was my first variable, plus 4.98 into your RM variable, right? Now here, if you see, the signs are actually telling you whether the variable has a positive influence or a negative influence on your target variable. You see, my lower status variable, because it was negatively correlated with the target variable, it has a negative coefficient over here, meaning that when the value of lower status will decrease by 0.66, your mid V, that is the price of your house, is going to increase by $1,000. If you look at this, when you are going to add one room to a house, the price of your house is going to increase by $5,000, right? All right. So now let's go ahead and let's check the performance of this new model, right? So let's get the predictions. So these are the new predictions. I will once again do the same things. I will convert this to a data frame. I will take my Y test. I will calculate the overall data frame, right? Now here you can see that this prediction, which was way more off earlier we were getting a value of somewhere around 20, right? Now I'm getting a much more closer value, right? Let's look at these errors, although this is just the overall error. I'll calculate now in a new line, I will calculate the new errors, right? Now I want you to compare the errors from above to below, right? This one was the errors when I used only one single variable. These are the errors when I use two variables. Do you see for each and every error metric, do you see the error value going down? And if I go ahead and if I print the R-square score now, can you see that the R-square score has also increased from 44 to 58, right? So we can see that as in when we are adding more variables, my overall model performance is actually increasing, right? So now what I'll do is that I'll straight away go ahead and I will use all the variables, right? Directly, right? I'll be using all the variables and we will go ahead and we'll see how our model is performing, right? I'll read the data once again because we have transformed some of the data. We have dropped some variables. So I'm reading the data once again. This is the same data. So what I'm doing is that I'm selecting all the features, but the last one as my X, that is the independent variables. I'm selecting only the last feature as my target variable. So if you see Y is my target variable, which is med V, and I proceed with the same steps. I split my data into 20% testing and 80% training. So the exact same values that we had. And there is nothing from a coding point of view, you can see that nothing changes, right? All you have to do is that you have to change the data and your model will automatically adapt. Now, if I'm passing all the features, I'm still passing the same model, calling the same model, nothing has changed, right? So if you see over here, I fit my model linear regression, but this time I will be getting many coefficients. Why do I get so many coefficients this time? My intercept will remain the same. Intercept will be the single value only, but I am getting these, right? Exactly, because we have so many features. So for each and every feature, I am getting a coefficient value. So let's go ahead and let's see what are the coefficients for the different features that we have. So what I do is that I create a data frame of my coefficient values. I create a data frame of my column names, right? And what I'll do is that I'll combine both of these data frames together to get these into one column, right? So I do a pd.concat. I concatenate these two and I get this data frame, which basically tells me that the attribute is crim and the coefficient is this. The attribute is Zn and the coefficient is this. Now you can do a very quick sense check that whether the signs of these variables is actually in line with the correlation. You see NOx, this was negatively correlated with my target variable. That is higher the pollution, lower the price. That is why the sign of this variable is coming out to be minus, right? You look at, let's say, anything else, maybe let's say Chas. So if a house is situated next to the Charles River, then the price will be high. Hence, it is positively correlated. Hence, the sign is positive. We go ahead and now we take the same model and make predictions. I do a regressor.predict using my testing data and I get my predicted values. And then I'll follow the same process. I have my actual values and I have my predicted values. I calculate the error of my model. And now, if you remember previously, let me show you the error from the last values, from the last model. it was 4.09, 26, and 5.17, right? And now it is coming as 3.2, 20, and 4.5, right? So you can see that the errors have actually reduced even more. If I look at the R square score now, you can see that the R square score has also increased to 73%, right? Talking about a new model, right? Logistic regression. If you remember when we started, when we were going through the introduction, uh, if I talk about, let's say, machine learning, right? Machine learning as a whole, I can go ahead and I can divide machine learning into what, two buckets? Does anyone remember? We have two broad buckets, right? What are those? So supervised and unsupervised, right? So those who are saying regression and classification, that is, before that you will have supervised learning and you will have unsupervised learning, right? I hope everyone remembers this. Then if we double click on supervised learning, this is something that we can break down into regression and classification, correct? Within supervised, you will have regression kind of models and you will have classification kinds of models. But can we go ahead and can we use a linear regression model for problems such as, will the property have a good neighborhood? Will it rain tomorrow or not? Is the email spam or not? No, right? We cannot use the linear regression model for these cases, right? I cannot use the regression model over here. I cannot use it over here. I cannot use it over here, right? And in that case, what do we need to do? We need to move on to some other model, right? So if we have a classification problem, that is my target variable is categorical in nature, we need to go ahead and we need to apply logistic regression model, right? So the objective of all of these 12 slides was only to lay the foundation of logistic regression and what kind of questions logistic regression will be able to. All right. Now this is again the same thing. Machine learning can be divided into supervised, unsupervised, right? Just go through this. I hope everyone is able to understand this. So let's move on. Now, before getting started with logistic regression, let's try to understand some basics, right? All right. So guys, I want volunteers our from you all only, right? I want to collect some data, right? Name, age, and target, that is working or student, right? I want 10 samples over here, right? I want you guys to start giving me details, right? Whether you're a student or you're working, okay? Just one by one. Charan is 23 and Charan is a student, right? Then we have Satyam. Satyam is also 23 and Satyam is also a student. Then we have Rishabh. Rishabh is 28 and working. Then we have Harshit, 31, working. Then we have Mohan, 25. I'll see how many I'm able to accommodate. I'll take all those. We have Jaya is 23 and Jaya is working, right? Itin 28 working. Itin 28 working and Vidya 23 working. Okay. 1 second, let's see how many we have. Gaurav 25 working. Then we have Audrey 33 student. Then we have Praneeth 21 student. I'll take some student examples now. Nandini 81 student, right? All right, so I'll stop here only, or let's take one more. This is the data that we have, right? We have around 12 data points, right? Now let's try to plot this data. What will we have on my, what will I have on my x-axis? What will I have on my y-axis? If I start plotting this data. So let's say on the x-axis I have age, right? And on the y-axis I have the target that is, let's say, status, right? I'll just write it as status. I'll start my age from 18. I think we have the minimum age as 18, right? So 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 30, right? I think 33 is the maximum that I have in my data as well, right? Yes. Okay. And then how will I plot my target variable over here? So my x-axis is fine. I am able to plot that. How do you guys, my target is what? My target is categorical in nature, right? So how can I plot that? So see, in Python, obviously, we will convert that into labels. Maybe 0 means that a person is a student, 1 means that a person is working, right? Over here, I'm just writing down the label over here, right? Just for our convenience. I'm just saying that if it is this particular, I'll just give the line. This is a student and this is, let's say, working, right? So I'll draw two horizontal lines which will just tell me whether the person is working or whether the person is a student. Does this make sense? There are just two lines wherever a person will be working. So I'll just give you one example. Let's start from the smallest, that is Nandini, right? The youngest in our batch or in this example. So we have Nandini. Where will we plot her name? She is 18 and she is a student. So I need to mark Nandini over here, right? Does this make sense? X-axis is on 18 and the y-axis is on student, right? Now let's move to the next person. After 18, we have Praneeth, who is 21, right? Do we have anyone else in the range? No, right? So Praneeth is 21 and Praneeth is also a student. Then we have 23, we have 3 people, right? Or 4 people. So 23 is interesting, correct? So if you look at 23, at 23, we have, we'll start from the top. We have Charan, who is a student, right? Then we have Satyam, who is also a student. So I will just give 2 crosses over here, right? Slightly above. Okay. Then we have Jaya and we have Vidya, both of whom are working, correct? So for Jaya and Vidya, we will have 2 marks over here, right? So this I will just mark slightly above so that you are able to see. Then who's next? After 23, we have 25, right? We have Mohan, who is 25 and who is working. So this is Mohan. Then we have after 25, what do we have? We have Gaurav as well, who is working. Yes. So we have Gaurav at 25 who is working. Then who's next? 28, right? We have 2 people who are 28, Rishabh and Nitin. And Rishabh and Nitin both are working. So we'll have 2 crosses here, correct? Just let me know if I'm missing out someone. 28 is done. Then we have 31, Harshit, right? Who is working. And then we have Audrey, who's 33 and who's a student, correct? So Audrey will be over here. I think we are done, right? We have 5 over here, 4 and 5 over here. All right, yes, 6 and 7 over here, right? 12 are done. Okay. So this is how our data looks like, right? Correct? Now, all of you know how linear regression model works, right? If let's say, can you try, first of all, can you try fitting a line of best fit which will cross through all of these data points or which will be closer to all of these data points? Or let's try to apply the linear regression model using the mathematics that we have understood. What will the model try to do over here? See, you can still apply the linear regression model over here, but the how how will you try to get the best fitting line is the question, right? Now, see, if I try to, let's say, fit a line which passes through all of these data points, or which is, let's say, closest, what I will get as an output will be something like this, right? Because if you have a line which is something like this, then what will happen is that if you calculate the vertical distances, right, the vertical distances will be somewhat the minimum in for this particular line. Correct, right? Let's assume that we went ahead. Let's say that we actually went ahead with a linear regression model. Now, can you tell me what will my line predict between student and working? So this student, let's say this student is signified by 0, right? By the label 0, and this working is signified by the label 1, right? Let's say this is what we get, right? Now, my linear regression model will say that for someone, so let's say I take this example 31, right? For someone whose age is 31, my linear regression model will say that the output is this, right? This might be the value, let's say 0.8. But what is 0.8? Is 0.8 a label that we have given? No, right? It is nothing. So it is near to working, but see, 0 and 1 over here are labels. I am saying that 0 is a student and 1 is working. But my linear regression model is giving me a value which is somewhere in the center. So how do I know what 0.8 is? It is close to working, that is fine. But then that is not the correct value, right? So do you guys think that linear regression model, first of all, this is the linear regression model is not appropriate over here because one single line cannot fit through all of these data points, right? Second point is that even if I go ahead and even if I apply the linear regression model over here, I'm not, if you go ahead and if you run the model in Python, it will work. But the predictions that you will get from the model, do you think that the predictions will be correct? In this case, you cannot say that as a probability, right? Probability is something else, right? This is just a linear value. You can still, so the best interpretation will be that this value is close to 1, so it means that the probability of, let's say, this person working will be slightly higher. You can say that, but this 0.8 is not a probability that you're getting. Correct? Ordinary linear and logistic both can work with more than one variables, right? I'm just giving an example with one single variable because that is easy to understand and explain. But both of these models can work with multiple independent variables, right? Independent features is not a problem. Now, let's say that what if I went ahead, what if I went ahead and I changed this output to, let me change the color. Let's say I went ahead and I changed this output to a curve which looked like this, not like this, sorry, to an S-shaped curve, right? Something, just imagine that this is a smooth curve, but something like this. What if I went ahead and I told you that this is a, I'm not fitting the line of best fit, but I'm fitting a curve of best fit, right? An S-shaped curve. If you look at this looks like an S-shaped curve, not exactly an S over here. But what if I get this? Will this fit our data points? Most of our data points, there is one data point which we are not able to fit, obviously, but the general data points that we have, the data points which are basically which are depicting the general trend in your data. If I go ahead and if I use this curve, do you think that it will fit the data points much clear? I will add one more data point. This is a random person, right? XYZ. And this person's age is also 23, right? And they are also working, let's assume, right? So I have added one more data point with 23, and this person is also working, right? Just to support this example slightly more. So let's assume I have one more data point over here, right? Now you have 3 points which are saying that at 23 you are working, and you have 2 points which are saying that at 23 you are a student, right? Now if I go ahead and if I try fitting a curve of best fit, right? Maybe I get an output which looks like this, right? Right? And this, if you see, this is an S-shaped curve. Now, at 23, we had we had 5 instances. We have 5 now. 3 people at 23 are working, two people at 23 are students, right? So what my model has done, so what this S-shaped curve has done is that using all the other rest of the data points, now at 23, it has realized that the probability at 23 to be working is slightly higher as compared to be a student, and hence it has gone ahead and it has adjusted this line, right? But given whatever data we have, do you guys think that this is the best fitting output that we can get? What are these values, right? Now see, this equation or this curve that you're seeing, this is a curve which will always give you values in the range of 0 to 1, first of all, right? And now let's assume I pick up a point. Let's say I pick up, let's say I go ahead and I get some new data, right? I get a new student whose age, let's say new student is uh, ABC, and the age of the student is let's say 27, right? What will happen? As soon as I get a student whose age is 27, my model will go ahead and draw a vertical line from here to here. As soon as it draws a vertical line from here to here, it will go ahead and it will map this over here, right? Now, this S-shaped curve that you are seeing, right? This is a sigmoid function. We will be talking about this. And the output of this function is always a probability. So if you look at this over here, when I drew a vertical line from here to here at 27 and a horizontal line from here to here, I might get the probability as 0.99, right? Or maybe equal to 1 as well, right? So what this curve does is that it gives me output. It will tell me that what is the probability of someone working or what is the probability of someone being a student, right? And this overall, this example that I've talked about, this is what we will be understanding in the next 30-40 slides. And this is what logistic regression is. What logistic regression does is that it basically, it evolves the output of the linear regression model. In case of a linear regression model, we are getting a continuous output. In case of the logistic regression model, we are just changing the equation of a straight line to the equation of a S-shaped curve. This S-shaped curve is a curve which gives us probability of a class either being, let's say, true or false, either being, let's say, a student or a working professional, right? So from this S-shaped curve, I will get probabilities. So my logistic regression model will give me probabilities. If it says that the probability of you being a student is 99%, it means that you are lying somewhere over here on the top. If it says that the probability, if the probability of you being working is 99 or 1, then you are on the top. If the probability of you being, let's say, you working is coming out to be 0, right, then it means that you are a student. 22, if you see this curve, if you draw a vertical line, this is cutting somewhere over here, this will cut somewhere over here, and this might give you a probability of around 0.4% maybe, right? So on the basis of the data, right, what what we are saying is that maybe 21 to 23 is a critical age wherein you will find a combination of people. At 22, you can have people who are pursuing their masters, and at 21, 22, you can have people who have pursued their bachelor's and who have started working as well, right? So using only age as a variable, probably you cannot go ahead and you cannot just for the age of 21 to 23, the probabilities might be confusing. But what if I added another variable over here? What if I added the number of degrees that you have, or what is the current degree that you are pursuing? Now, let's say if someone is 22 and they are pursuing their masters, then the probability is more that they are student. Now, let's say someone is 22 and the maximum degree that they have is, let's say, a bachelor's degree. Then maybe the probability of them being working will be higher, right? Now, see, over here as well, let's say if we had additional features, let's say if we had features that the background, right? Maybe Audrey is from a different background, or maybe let's say uh, if I captured marital status, maybe, right? Now, marital status, maybe there are people who got married at a very young age, and then let's say they went ahead and they spent 5 to 6 years in their marriage, and then they decided to come back at their career, right? And when they decided that maybe I'll go ahead and I'll pursue a higher degree, right? Anything. So if you are able to capture other factors which are helping you in quantifying, then the model will be able to predict. But over here, the model will still predict that at 33, you should be working, right? Now, there can be cases, or see, the model will just try to find out the general pattern. The general pattern is that generally 18 to till 22, right? You will be a student. Generally, after 22, you will be a working professional, right? Now, the model, obviously, the predictions that you are getting will be the generalized trend in the population that you're seeing, right? We have given the model that 33 is a student, right? But all the rest of the data points are saying that anyone who is greater than 23 is a working professional. So the model will not make an exception, right? The objective of the model is to generalize the patterns, right? Not to see if my model would have gone ahead and would have, let's say over here, I would have gone ahead and I would have changed this curve from here to here. Do you think that that would have been correct? Let's say I would have gone from here to here. Do you think that this would have been correct? What will this lead to? I'm sure there will be many people who will be greater than 30, let's say in our batch. So for those people, your model will start giving incorrect predictions, right? Now, what do you think? If let's say I have 10 people who are greater than 30 in this batch. Maybe for 8 out of 10 they are working. Maybe 7 out of 10 people they are working, right? So there is a 70% probability that anyone who is 33 years old should be working, right? So this will actually lead to overfitting, right? And you don't want to overfit. Overfitting is what? Uh, Overfitting is capturing specific rules with respect to the training data. That is not what you want to do. You want to capture general patterns. You want to capture the general trend. See, after 33, let's say if you have a age range of 33 to 35 wherein you are seeing many students, then the sigmoid curve will shift, right? But generally that will not happen, right? Okay, so now let's move on to the logistic regression part, right? Let's try to understand what happens in case of logistic regression, right? Now, logistic regression is a classification model, a statistical classification model, deals with categorical dependent variables. Your target variable can be binary or dichotomous, right? What do we mean by dichotomous? Dichotomous is again a similar word for binary. It means that your categorical variable can have uh, categories. It can be true, false, it can be yes, no, it can be rain, not rain, whatever, right? So that is what you mean by dichotomous or binary, right? Could be multinomial as well, right? So your target variable can be multinomial as well. That is, it's not that only logistic regression will work only for binary variables, right? It can also work for variables which have, you create a model which will predict the designation of an employee, right? Maybe the designation is a data scientist, maybe senior data scientist, maybe junior, maybe lead, maybe principal, right? So in this case, your target variable can assume, let's say, 4 or 5 different values. So your target variable can also be multinomial, right? Your input data can be both continuous or categorical, correct? What do you mean by it can be both too? At 33, you are saying that people can be both, right? Student or working professionals. So that's what, right? Now, see, if I would have gone and I would have collected more data, if I would have asked each and every 150 people of you, your age and whether you are a student or a working professional, do you think that there would have been many instances of people who are greater than 30 and who are student? You thought just like linear regression did, just like that, logistic will also be able to take any categorical data will be converted into labels, and then those labels will be converted into numeric values 0, 1, 2, 3, and that can be plotted, right? Now, what is logistic regression? It's a tool for applied statistics and discrete data analysis. All of these are just definitions. It gives outcomes in terms of probability. You have seen this. In turn, helps in classifying the given data, right? When you start getting probabilities, right, you can go ahead and you can arrive at a cutoff, right? You can say that anything above 0.5, let's say any probability above 0.5 that I'm getting in the model, I will consider that person to be a working professional. Any probability which is, let's say, less than 0.5, I will consider that person as a student, right? You also know that Okay, so let me give you an example. I have two cases. One, for one, the probability of being a working professional is 99%. For the other, the probability of being a working professional is 55%. Right? Do you think that the model is the model is confident in both the cases? The model is confident is only in only one of the case, that is where the probability is 99. Where the probability is 55, as soon as you see 55, you should also know that this is a critical age range, right? Because this might be somewhere in the 21 to 23 age group, right? So there, if you are getting a probability as 55, you can go ahead and you can say that this is still this prediction might not be correct, right? But anything, let's say above 90-95%, you can be very sure on those predictions, right? Okay, so let's understand this with an example. So this is an example. Take a look at this example. So I have email. My email can be spam or it can be not spam, right? Let's try to understand how logistic. Now this will be a very similar example that I've explained. So you should be able to understand this with ease. We will understand the variable, plot the data, draw the curve, and then we will find out the best fitting line, right? Let's get started. The independent variable that we are taking over here is the count of spam words, right? Now, in order to predict whether an email is spam or not spam, what do you guys think is the most important thing? The most important thing is that your email can be containing, let's say, thousands of words. But if in those thousands of words, let's say there are words such as lottery, right? Or let's say $1 million, right? Or let's say free gift, things like that. Do you guys think that these words are trigger words for something being spam or not spam? Correct? So let's assume that I have 100 emails, and for all the 100 emails, through some tool, I'm able to count the total number of spam words that are there, right? Now, obviously, mails which are coming from your known contacts, they might not contain these words a lot, right? And the mails which might be coming from unknown contacts, they might be getting some words such as, let's say, gift, or let's say business trip, or let's say thousands of dollars, $1 million, you have one thing like that, right? Now, if we go ahead and if we just take a count of these words and make that as my independent variable, right? So if you see most common spam words, buy, get paid, guarantee, winner, unlimited, things like that, right? So what I can do is that I can plot the data. Now, this, if you see, is the data that we have, right? Now, the emails that you're seeing over here, which do not contain this disclaimer mark, right? These are the emails which are not spam. The emails which are marked over here, right? These are the emails which are spam. On this axis, you have the count of words, right? The count of spam words. So you can see that when the count of spam words is less than 4, then the email is not spam. When the count of spam words is greater than 4, I can see that the email is coming out to be spam, right? And if I go ahead, now see, this is our data, right? This is our data, just like the data that I had created, right? This is a similar data. This is data that we have collected, right? Now, see, it might have happened that, let's say, a friend of yours has gone ahead and has sent you let's say, some kind of an email which is a joke, right? Or some kind of like something, maybe anything, right? So although the email contains 8 spam words, but it is not a spam. See, this is actual data, guys, right? See, your model. So just like in our case, we had people who were 25, 28 and who were working. And we had one case wherein the age was 33 and they were not working. So you will not go ahead and you are not going to change that, right? That is your actual data. So in your actual data as well, okay, so see, this is just a bunch of rules. If you are going ahead and you are identifying whether an email is a spam or not spam, it might happen that you have gone ahead and you have classified an email as spam because it contained, let's say, some words which were related to a spam email. But let's assume this was an email which came from your friend. Let's say this was an email which actually came from a bank, or let's say which came from a company wherein actually you would have won something. So in that case, obviously, in reality, it is not a spam, right? Let's assume that you applied for a contest and you actually won. Let's say you went ahead and you paid your bills through cred and let's say you won a ticket for a match, you will get an email, right? That you have won this thing, and you are asked to, let's say, collect your things from here, or let's say you are asked to call on this number. In most of the cases, let's say 90% of the cases, these emails will be spam. 10% of the cases. Now, this is something that you guys would have also seen, right? Some of the emails that you are actually expecting to be in your inbox, sometimes they go to your spam folder. Why does that happen? Because the model is predicting it to be a spam. That might be a genuine email, right? But the model is predicting it on the basis of whatever content that email has. It is predicting that it is a it is a spam email. The probability of the words, because of the words, the probability of this email being spam is high. Okay, right? So this is actual data. Now, through this actual data, we will try to come up with a generalized curve, right? That's what the objective of machine learning is. There will obviously be outliers. There will always be outliers when you are working with actual data, right? Let's say when you are predicting whether a customer will buy a product or not, do you think that there will be a very linear uh, distribution of data, that let's say anyone who is greater than age of 30, they will buy a diaper, anyone who is less than 30 will buy it? No, right? Even you can be 18 years old, maybe you go to the store and you go ahead and buy a diaper for your sister, for your brother, right? Not for your sister, brother, but maybe the child of your sister or brother. But you can also do that, right? So there will be outliers, but the majority data will suggest that if you are greater than 30, you are greater than 25, 28, then you are buying a diaper, right? But it does not restrict you from going ahead and buying a diaper. Okay. So can we go ahead and can we plot this data just like we did in the last case? We can do that, right? I have a 0, I have a 1, which is my target variable. On my x-axis, I will have the count of words. If I go ahead and if I plot this, if you see this, there are two cases which are outliers, right? This case is an outlier and this case is an outlier, but that doesn't matter. The general trend, what does that say? My general trend suggests that this is how your data is distributed. There can be some outliers, but that's totally fine, right? Now, see, that's what your real world behavior, right? Your actual real world behavior, when you're collecting real world data, things are not too much rule driven, right? Exactly. Because see, in the real world, you can have a 20-year-old person driving a BMW, and you can have a 40-year-old person driving a Maruti 800, right? But the general trend will say that, let's say, someone who is greater than 40 might be driving a BMW, someone who is in the age of 18 to 20 might be driving a bike or let's say a two-wheeler, or let's say a small car, right? But obviously there will be outliers. Now, once when we have gone ahead and once when we have plotted our data points, next was what? We actually went ahead and we identified an S-shaped curve, right? Now, just like in the case of linear regression, we were finding the line of best fit. In this case, in this case, we can have multiple lines, right? I could have had a line which was, let's say, which looked like this, right? I could have had an S-shaped curve which would have looked like this, right? I could have had an S-shaped curve which would have looked like this. I could have had an S-shaped curve which would have looked like this, right? Why did we go ahead with this particular curve? What is the objective of that? Less error, minimal error. But in this case, right, the error, can we see if a class is, let's say, if the actual value is whether it is where the person is working or a student, and the predicted value is a probability, right? Then error per se, calculation of error. So in this case, right, we do not, we find something which is known as the maximum likelihood estimate, right? So I'll talk about that once when we arrive at that point. But over here, the method will be different, but the objective is the same. The objective is to identify the best fitting S-shaped curve, right? Earlier, in case of linear regression, the objective was to find the best fitting line, right? Best fitting linear line. And over here, our objective is to find the best fitting curve, right? So we need to find a regression curve which would be best fit. That would be our logistic regression curve, right? But how do we find the best fit curve? Now, This is the mathematically how we try to find this out, right? That is what we are trying to do over here. So let me explain to you how we actually arrive at this best fitting curve, right? That is what next we'll be trying to understand. That is how do we arrive at this particular equation. Now, first thing that we need to understand over here is that something known as odds, right? We have something known as probability and we have something known as odds, right? Okay, so let's say let's say India versus New Zealand, right? Let's take the hot topic. Let's say India has won 6 games and New Zealand has won 4 games. These are made up numbers, right? But let's say India has won 6 against New Zealand and New Zealand has won 4. Can you guys calculate the probability of India winning a match? What will be the probability of India winning the match? 10, right? 6 divided by 6 plus 4, right? So odds are something that says that what are the odds of something happening, right? When I say odds, so my odds of winning will be 6 in favor, 4 will be against, right? So when I say odds, the odds of India winning will be 150%, right? So in case of odds, right, we are not dividing this by the total number of combinations, right? So if you see in probability, we are dividing the favorable events by the total number of events. But in case of odds, we are saying that, right, whenever India plays New Zealand, 6 times India has won, or 6 times India will win, and 4 times New Zealand will win. So the odds of India winning against New Zealand is 3:2 or is 6:4. Does that make sense? Right? This is just the basic definition of how odds are calculated, right? Now, this is the mathematical process of how we actually go ahead and how we find out the best fitting curve, right? So I'll just take you through the process. Uh, Obviously, once when we are building the model, all of these things you don't have to calculate, right? Just like in the case of the linear regression model, we had gone through the mathematics, we have gone ahead and we had understood all the concepts of how we get the best fitting line and all. So see, in case of logistic regression, the first thing that we do is that we calculate the odds and we calculate the log of odds, right? Now, don't ask me why we are doing this. See, at the end of the day, what we are doing is that in order to calculate the probability, all of these things we are doing because we want to go ahead and we want to calculate the probability using the sigmoid function, right? So that is why the first step that we do is that using this particular input, this data that we had collected, if you remember, this was the data, right? So we go ahead and we calculate the log of odds, right? For each and every event, right? So what are the log of, first of all, what are the odds of an email being spam or not spam when the count of words is 5? What are the odds of an email being spam or not spam when the count of words is 10, right? If I go ahead and if I calculate this log of odds is a value which can fluctuate between minus infinity to plus infinity, right? Any log, if you take, right, your log of any particular number, right, it can fluctuate between minus infinity to plus infinity, right? So that is why this log of odds is also something that will fluctuate between minus infinity to plus infinity. And this generally is a straight line, right? That is what we get as an output of this particular thing. But do you think that this is the output that we need? This is first of all a straight line, and this is giving me values in the range of minus infinity to plus infinity. So this obviously is not what we need, right? What we need is an S-shaped curve which gives us values in the range of 0 to 1, correct? So somehow I will go ahead and we will try to convert this line, this straight line, into an S-shaped curve, right? That is what the model tries to do. Now, the objective over here, if you see, is this input. This is something which is varying between minus infinity to plus infinity, right? I want to convert this from which looks something like this to an output which looks like this, right? If you see over here, I am getting my outputs in the range of 0 to 1, correct? And this is something that we do through the use of a sigmoid function, right? Now, a sigmoid is the function that we are basically using in our case in order to go ahead and in order to convert this equation of a straight line, the one that you're able to see over here, into an S-shaped curve. The sigmoid function takes any possible input, right? You can give any possible input to the sigmoid function in the range of minus infinity to plus infinity, right? The output of the sigmoid function will always be a number in the range of 0 to 1. Okay. Now, if I talk about the sigmoid function, for sigmoid function, the definition or the function is 1 plus e to the power minus x, right? This is the formula, or this is the definition of the sigmoid function. Now, if I give you an example, right? You can calculate this as well, right? You can give any value. So let's say I give a value which is a very large value, right? If you go ahead and calculate the output of this, right? If you look at this, the output of this, let's say if I give 100, right? Output is 1. The greater value I give, it comes out to be 1. Let's say I give minus 10. If you see this, the output is still in the range of 0 to 1. If I give, let's say, something like this, it becomes 0. Let's say I give 100, it will become 3.72 into 10 to the power minus something, right? So if you see the value, the output will always fluctuate between 0 to 1 for the sigmoid function. You can try it, right, for any given range of values, and it will always be in the range of 0 to 1. So what we do over here is that after calculating the log of odds, we apply the sigmoid function. Okay. So that's what we will be doing over here. Let's move forward. See, this is your likelihood is nothing but odds, right? We will calculate the individual likelihood is basically the odds of an email being spam or not spam when the count of words is, let's say, 2, 3, 4, 5. Through that, we will calculate the log likelihood. So wherever you are seeing likelihood actually refers to odds, right? Through my data, I will calculate the individual likelihood, that is the individual odd of anything happening. So let's say, if I give you an example, let's say when my count of words were 5, right? When my count of words were 5, I had spam emails as 4, and I had not spam emails as 1, right? So what will be my log of odds? What will be my odds for spam is to non-spam? It will be 4 is to 1, right? 4 is to 1, correct? So we need to calculate this for all the possible values. That will be the individual likelihood. Through this, we will be calculating the log likelihood. So my output will be 4 over here. This will not give 4 is to 1. The output will be equal to 4, right? So we are going to go ahead and we are going to take the log of 4. Now, obviously, as and when if you see the log of odds of, or the odds of something happening will increase, the log value will also increase. As and when the odds of something happening will decrease, right? The log of that value will also decrease, right? So that is what we do over here, right? Once when we have calculated the likelihood or the odds, we will go ahead and we will calculate the log likelihood, and then we will go ahead and this value, whatever this value is coming out to be, we are going to take it through the sigmoid function, and this will give me the S-shaped curve. That's what the objective is. More than 2 labels, what happens is that in case of multi-classification models, right, there will be multiple equations that will come out as an input, right, as an output. So let's say if your target variable is, your target is, let's say, high, medium, low, right? Let's say first value is high, second is high, third is medium, then fourth is low, then this is medium, then this is low, right? So you are actually creating 3 separate models. First will be, let's say, target 1, right? Or let's say target high. Over here, all the values which are high will be 1, rest all will become 0, right? Second will be, let's say, target medium. Over here, all the values which are medium will become 1, rest all will become 0. Third will be target low, and everything which is not low will become 0, right? Now this, you will go ahead and you will fit 3 different logistic regression models, right? You are not going to do that. The model is going to do that internally. But through this, the model will give you three probabilities. So let's say it gives you the probability of high as 70%, the probability of medium as 20%, and the probability of low as 10%, right? So that's how you will do. So if you are able to understand binary, the same binary model will be applied many times whenever you are working with multi-class models. So whatever value 6 by 4 you will get, you go ahead and you calculate the log of that. So see, likelihood is nothing but odds. So if the odds of India winning is 6 by 4, which is 1.5, if I take a log of that, log of odds or log likelihood, right? Both of these things are same. So log likelihood will be nothing but log of 6 by 4. Okay. Each and every word. So let's say I have 6 spam words, right? For my data, which contains 6 spam words, can it happen that let's say 10 emails are spam and let's say 2 emails are not spam? So can you calculate the probability of an email being spam or not spam in this case? What will that be? What is the probability of an email being spam when 10 are not 10 are spam and 2 are not spam when your word count is 4? What is the probability that you will get? 10 by 12. What will be the odds that you will get? Odds in favor 10 by 2. So that's what we are calculating, right? Now this we will calculate for each and every word count, right? So spam words 1, what is the odds? Spam words 2, what are the odds? Spam words 3, what are the odds? And so on and so forth, right? And then you will calculate the log of the same values. This will give you an output which will look like a straight line. The output can be anywhere between minus infinity to plus infinity. This output, if I want to go ahead and if I want to convert this into a value which is in the range of 0 to 1, we will be applying the sigmoid function, right? Now over here, they are explaining, we will be explaining, we are explaining odds, right? So the same examples that I have taken. So this guy went fishing 5 times, caught a fish 2 times, failed to catch 3 times. What is the probability? So the probability of catching a fish is 2 by 5, right? But the odds are 2 by 3, right? This is the same example that I have explained. For your historical emails, you should be knowing what emails were spam, what emails were not spam, right? And then you should also have additional variables such as how many spam words were there, how many spam words were not there, right? Your data collection will obviously happen. And for your historical data, for your historical emails that are already there in your inbox, you can manually label them, right? That whether they are spam or not spam. So using that data only we are actually going ahead and calculating all of these words, right? Now, if I go ahead and if I take the log of odds, right? So if I calculate the odds and if I take the log of that, right? So if you see log odds of catching on sunny day is this, log odds of catching on rainy day is this. And there is something known as log of odds ratio. That is, what we do is that we calculate the log of both the ratios, right? That is odds in favor of catching a fish, odds in favor of catching a fish on a rainy day, right? So if I do this, this is something which is known as log of odds, right? Log of odds ratio. And this is what we are calculating in our data, right? In our data, if I go back to my example, if let's say my odds were 4 by 1, or let's say let's take 6 by 4, odds for India winning, right, was 6 by 4, and odds for New Zealand was 4%, right? So my log of odds ratio, I have something known as log of odds ratio, will be log of 6 by 4, right? This whole thing divided by log of 4 by 3, right? That is the log of odds ratio. Odds and odds ratio, if you see the difference, odds is nothing but you calculate the log of odds. Odds ratio is that you calculate the ratio first of all of your odds, right? That is, odds can be two value, right? It can be in favor of, let's say, India winning, in favor of, let's say, New Zealand winning. And then you calculate the ratio of that and you calculate the log of that particular value. The sigmoid function is calculated on the odds ratio, log of odds ratio. All right. And now if you see, if I go ahead and if I calculate the log of odds, you know that this is odds ratio, right? So what we do is that we calculate the log of odds ratio for each and every. Now, See, if for my input data which look like this, if I calculate the log of odds, my output will look like this, which is minus infinity. My output will go in the range of minus infinity to plus infinity, right? Now, once when I get this, the second option is that I go ahead and I apply the sigmoid function. We are getting the log 0.44. So how will we see the impact of the database? Database, there is no database. Your original data, which was class 0 or 1, these were categorical, these were hard classes which were converted into labels, right? Now these labels we are converting into a numerical value by taking the log of odds. Now this value can be anywhere in the range of minus infinity to plus infinity. So your 0.44, if let's say you are getting 0.44, that will be somewhere over here in this curve. Do you understand this now? So basically we are converting our classes, our hard classes to log of odds, because till now our 0 and 1 were actually just representing whether an email is spam or not spam, right? And these were categorical, this was a categorical variable converted into labels. Now through that I am getting a numerical value which is giving me the log of odds. Now, this is just an explanation of why your log of odds can be minus infinity to plus infinity. Now, see, log of anything divided by 0, right, will always be infinity, plus infinity, because this will be a non-defined number, right? So, whenever in the cases when the probability of an email being spam is high, right, this will be 1 by 0, right? And your 1 by 0 will be tending to infinity, right? Similarly, if you look at this over here as well, this will be 1 by 0 and all of this will be tending to plus infinity, right? Once again, don't other case when let's say it is the probability of not spam is 0. So this will become log of 0 by 1, which will be log of 0 minus log of 1, which will become minus infinity, right? So this just tells us, this is just a mathematical proof that the log of odds ratio will be a value which will be in the range of minus infinity to plus infinity. Now, this is the output that we are getting, right? When we go ahead and we take the log of odds ratio, this is the output that we will be getting, that is in the range of minus infinity to plus infinity. Now, this is what we get, right? When I take the log of odds, I get values in the range of minus infinity to plus infinity, right? And now for each and every email, these are the log of odds which we can get, right? With these values only, we have plotted this equation of straight line, right? Now, if I apply the sigmoid function on this straight line, which was the log of odds value, right? If I apply the sigmoid function, I will start getting something which looks like this, right? My output will become an S-shaped. This is a standard, this is the property of the sigmoid function, that any input, it can be any value, minus infinity to plus infinity, it will convert that in the range of 0 to 1, right? And this is how we actually get the probability using the logistic regression model. That's what I'm saying, right? This is just to explain why the log of odds will be in the range of minus infinity to plus infinity. So these slides are slightly confusing. Can take values in the range of minus infinity to plus infinity. This is not what we are taking in case of logistic regression, right? Then a probability close to 1 will tell you that the mail is non-spam. A probability close to 0 will tell you that a mail is spam. Now, what does the sigmoid function mean? All of this is same, right? Sigmoid function is the standard function that we use in the case of this model, logistic regression, right? The sigmoid function is this, e to the power x plus upon 1 plus e to the power minus x. If you will simplify this, it will become 1 upon 1 plus e to the power minus x, right? Something like that. Once again, no need to go into the mathematical details, right? If you look at this, it can either be, you can represent it as e to the power x plus upon 1 plus e to the power minus x, or if you divide this whole thing by e to the power x, it will become 1 upon 1 plus e to the power minus x, right? Now, a sigmoid function, the property is that it approaches 0 as and when your x approaches minus infinity, right? And it approaches 1 as in when your x approaches plus infinity. This is the property of a sigmoid function, because of which we are using it as a transformation in the logistic regression model. When we calculate the log of odds, after calculating the log of odds, we use the sigmoid function. right? So if you see in our example as well, if we go ahead and if we apply the sigmoid function after calculating the log of odds, we will get an S-shaped curve which looks like this, right? It takes any real valued number and maps into a value between 0 to 1, helpful while solving classification problems. Now what will happen by on this particular output, we will apply the sigmoid function and it will give me this particular output, right? It will give me the equation of the S-shaped curve, correct? Now, the important part that we need to understand is now, just like in the case of line of best fit, we were calculating the sum of squared errors, right? Now, let's try to understand what will happen in this case. In our case, how will we try to find out the best fitting S-shaped curve, right? So let's try to understand this concept. This will be important. Now, if you remember, we had data points. Let's say we had, right? I'll plot some data points over here. And let's say I plot some data points over here, right? And I have, let's say, some outliers over here and here, right? Now, obviously, from these data points, I can pass many S-shaped curves. Is that correct? There can be many different S-shaped curves that can pass through these particular data points, right? So let's say this is one. Let's say this is one, right? Let's say this is one. And let's assume this is one, correct? Let's take 3 examples, multiple different outputs, right? Right now, let's try to see. Now, see visually, can you tell me which is the best fitting S-shaped curve out of these 3? Is it the red one, the blue one, or the green one? Visually, it is green, right? But over here, can we apply any concepts such as calculating the vertical distances from the line? And because this is not a regression problem, right? This is a categorical problem. It is green, right? Because green, if you see, is passing through the majority of the data points correctly. The red one is not passing through these 4 and these 2, 6. The blue one is not passing through these so many data points, right? So the green one is the best fitting one. Now see, in this case, what if I do a simple thing, right? I want that S-shaped curve which maximizes the probability of each and every data point, right? So let's say when I say the probability of point 1 till the nth point, right? That sigmoid curve. Now see, look at this look at this green curve that we are talking about. All the data points that you're seeing over here on top, what will the probability be for these data points? In what range will the probability be for these data points? The red ones, close to 1, maybe 0.99, right? So let's say there are how many? 1, 2, 3, 4, 5, 6, 7 data points. So for these 7 data points, let's say the probability is 0.99, right? I'll not take 1, let's say it is 0.99. And for the bottom data points, that is these are 7 top data points, these are 7 bottom data points. What is the probability for them being spam? So this is spam, right? And this is not spam. That will be close to 0, right? 0.001 maybe. So if the probability of spam is 0.001, what will be the probability of not spam? 0.99, correct? Now, if I multiply all of these data points, right? Now see, for these 2 data points, the probability will be incorrect, right? So let's write those as well. 2 data points, the ones that you are seeing over here, the probability will be close to 0. Is that correct? For these 2, the probability will be close to 0, right? Because my model is saying that these 2 data points actually should not be spam. And for these 2 data points, the probability will be close to 0.99 for these 2, the bottom 2. The probability of spam will be 0.99. So the probability of not spam will once again be 0.01. Now, if I go ahead and if I multiply all of these probabilities together, right? Let's assume I go ahead and I multiply all of these probabilities and I get some value, right? Multiplication of probability. Let's say I get this value as, I will obviously be getting a value in the range of 0. 99 something. Let's say I cannot have a value which is greater than 1. Let's say I get a probability of 0.9, or let's say I say probability red, right? I get this as 0.99. Now, if I calculate the same for the probability, if I multiply all of these probabilities with each other, let's say I get a value of in the range of 0.99. Now, if I calculate the same probability for red, will this probability be greater than 0.99, less than or equal to? Calculate the mispredictions, calculate the total number of correct and incorrect. Now, if you see for the red line, there are 5 data points at the bottom which will have probability of 0.99, and it will have 7 on top which will have 0.99. So 12 will be 0.99, but there will be 6 data points for whom the probability will be 0.01. So 0.99 to the power of 12 in this case. In the first case, it was 0.99 to the power of 14, correct? If I calculate the same probability for the blue one, what will that be? So let's say for this probability of red, I get 0.98, right? If I calculate the same thing for probability of blue, the probabilities for blue will be in the range of 0.99. Can you give me a count? One is on the top, but at the bottom as well, you will have 0.99 as well, right? So 6, 7, 8, 9, right? So I will have 0.99 to the power of 9, and then 0.01 to the power of 7, 8, whatever, right? So let's say I get probability of blue as 0.96. Which line is the best fitting line? The green one, right? Because it is actually, see, the green line is the line which is accurately predicting most of the probabilities. So obviously, if I multiply all of these probability values, whatever value I'm getting will be the largest possible value, right? And this is what is known as maximum likelihood estimate, right? Maximum likelihood estimate. So just like in the case of linear regression, we used to calculate what? In the case of linear regression, we used to calculate sum of squared of residuals, right? In order to find the line of best fit. In this case, in the case of logistic regression, we are finding the maximum likelihood estimate. The maximum likelihood estimate is that S-shaped curve, which is giving you the maximum probability. Okay. So now if you look at this, right, the probability that we calculate, right? If we go ahead and if we calculate these probabilities for each and every data point, right? So this, if you see, we are just calculating the sigmoid function to find the line which is maximizing these probability values that we are multiplying. Yes, we need to maximize. We need the line which is maximizing these probabilities, the multiplication of probabilities. Hence, we are using MLE, maximum likelihood estimate. All right. So let's look at this. Let's say that, let's assume this is my X and Y axis, right? Now, within my X and Y axis, you will have some, let's say your X axis is the age, the same example that I had, and your Y axis is the status, that is whether you are working or you are a student, right? Now this variable, this could have two values. If I label in code my classes, I can have, let's say, working encoded as value 1, right? Or I can have, let's say, student encoded as value 0. I'm keeping it slightly above so that it is easy to see, right? Now let's say for people who are less than a given age range, I was getting that in most of the cases, these students or people who are less than a given age, right, are students. And for other cases, let's say we were seeing that beyond a given age, right, generally you will be working, right, something like this. Then there could be outliers as well. Maybe let's assume that there is a 19-year-old person who is working. Maybe they have their own startup, right? I can have, let's say, a 30-year-old person who is a student. Maybe these are people who have pursued their jobs for 10, 12 years and now they have opted to go for their master's or PhD or whatever, right? But if you look at the general trend of this data, what does the general trend look like? If you look at the general trend, I can see that beyond a given age, right, the probability of you working will be higher, and below a given age, the probability of you being a student will be higher, right? Charan, yes, combination of two or more models is possible. Ensemble learning, right? This is what we call it. Ensemble learning is that you can have three models exposed to the same data. It goes ahead and gives you a prediction, and then you can combine those predictions, right? We'll be learning about such models in due time. But yes, that is possible, right? Now, if you remember, we knew that the sigmoid function is a function which gives us an S-shaped curve, right? So the sigmoid function is a function which gives us an S-shaped curve as an output, right? Now, let's say I go ahead and I get an S-shaped curve which looks like this, right? Or let's say I get a different S-shaped curve which looks like this. Or the one that I'm marking in green is apparently the correct curve. Let's say I get an S-shaped curve which looks like this, right? Now my logistic regression model, right? Which curve out of these three it should select? How will we find that? Just like in the case of linear regression, we were talking about how do we select the line of best fit. Over here, my question has changed now that how will you identify which line is the best fit? The green one will be the best one. That is obvious from here. Now, why do we think that the green is the best one? So green one covers the maximum points. That is correct. How can we identify that the green one is covering the maximum number of points? If I multiply the probabilities of all of these points, right, the probabilities that I have gotten from the model, if my line is covering maximum number of points, then the probability of the predicted probability that I'm getting from all of these points should be high, right? Now, let's do a very simple exercise. I want you to go ahead and although counting is not possible, but still if you can use thinner lines. So let's say this is the green model, right? Let's say this is the red model, right? And let's say I have a blue, which is this one, right? Let's say these are three lines. Now, can you go ahead and can you tell me how many classes will be predicted accurately by the green line? You will have to count. For the green one, how many are predicted accurately? At the bottom, we have 9, and on the top, we have once again 9, right? So we have 18 correct predictions for green. And how many predictions for green? Incorrect for green will be 1. Is it 1? No, right? It will be for green, you have 1, 2, 3, 4, 5, 6. 6 will be incorrect, right? What about red? The red one looks to be doing better, right? If you see the red one, it is giving us 19 correct predictions and only 5 predictions which are incorrect, right? And what about the blue one? Blue one, 14 correct and 10 incorrect, right? Now, which line do you think will be the best performing line? Is it the green or the red? Red, right? Why is red? Why will red be the best performing line? If I go ahead and if I multiply all the correct probabilities, right? Now the correct probabilities, the 18 ones that you are seeing, the ones that are there on the top will be close to will be close to 1. So let's say I take 0.99. So I will have 0.99 to the power of 18, correct? This will be multiplied by let's say I say the incorrect probabilities are coming out to be 0.01, right? So this will be multiplied by what? Multiplied by 6, right? This is for the green one. Similarly, for the red line, what I will have is that I will have this to the power 19 and this to the power 5. And for the blue line, we will have this to the power 14 and this to the power 10. Which value which value do you think will be the maximum out of these three? The red one, right? Right. So this is what we mean by a maximum likelihood estimate. We are trying to identify a line which is giving me the maximum probability. When I multiply all possible probabilities that are coming out, it gives me the maximum probability, right? all of these points are very close to the line. So I am taking the probability as 0.99. But obviously the points which will be closer to the line, the probability will be might be greater than 90%, 95%. This is just to explain to you how maximum likelihood estimate works. That for an incorrect probability, if you look at these points, right? If you look at these points, my model is predicting a probability of somewhere around, or let's take this point. For this point, my predicted probability should have been 0.99, but my predicted probability will be somewhere down below, right? So down below, I'm assuming that it will be close to 0. Okay. Now the same concept has been explained in the examples on this slide, right? Uh, so we had done till here. If we go ahead and if we start getting the predicted probabilities now, right? Now, if you remember, this was the log of odds. This log of odds, if I take this through the sigmoid function, I will get a predicted probability, right? If I get this for all the possible values, right? If I go ahead and I get this value for all the possible emails that I have in my training data, right? I will get the probabilities for each and every point. If you see, for this point, second point, I am getting the probability as 0.99. For the third point, I am getting the probability as 0.01. After passing through the value, whatever value we got through the log of odds, if we pass that through the sigmoid function, these are the probabilities that we are having. If I go ahead and I generate the probability for all the data points using this transformation, using this particular log of odds, right? I will be getting these as the probability values, right? Probability of a mail being spam. The first point, it is around 0.01. Second point, once again, same. Third point, 0.03. Fourth, 0.05. For the fifth point onwards, it is coming out to be 979999, right? Okay. Now, how will I find the maximum likelihood value over here? I will have to multiply these probability values, right? Now, if you compare this with actual data, these are the emails which were spam. In the real data as well, these were the emails which were spam and these were the emails which were non-spam. So the probability of these mails being spam is coming out to be high, which is good. How will I be able to calculate the probabilities of these emails not being spam? How can I get that? If the probability of being spam is 0.01, then what will be the probability of these mails not being spam? Probability of not spam. If my probability of spam is 0.01, then what is the probability of not spam? So 1 minus 0.01, so that will be 0.99. So now, since these points, since these points in reality are not spam, right? I am marking them by green. Since these points in reality are spam. So what I need to do is that I need to multiply these 4 by 0.99, which was the probability of being spam. I need to multiply these 4 with the probability of them not being spam. Not being spam, I will do a 1 minus of 0.01. So that's what we'll do, right? We'll go ahead and we will multiply all of these. Now, if you see, for the first 4 probabilities, we are taking 1 minus 0.01. For the last 4, they will be as it is. Because the first 4 emails, in reality, they were not spam. When they were not spam, then the probability of them not being spam will be 1 minus 0.01. For the last 4, these emails were spam. Since these emails were spam, the probability remains as it is. Now this, if I multiply, I will get a value, right? If I multiply this, now generally what we do over here is that we take the log of this as well, right? In order to calculate the log likelihood. So I am taking the log of this. When I take the log of this entire thing, I get a value which is minus 0.084, right? This is the log likelihood that I'm getting for this particular equation, that for this particular sigmoid curve, right? Instead of just multiplying the probabilities, we have multiplied the probabilities and calculated the log of the sigma, right? Not a very big difference. Calculated appropriately. This is all values are less than 1, right? Log of 1 base 10 will be equal to 0, right? So log of anything less than 1 will be equal to less than 0, right? Log of 10 base 10 is 1. log of 1 base 10 is 0, and log of anything which is less than 1 base 10 will be negative. So now, see, I drew this line as 1. What if I go ahead and I rotate this line slightly, right? If I will rotate this line slightly, my sigmoid curve will also change. If I rotate this line like this as well, my sigmoid curve will change, right? So if I rotate this curve multiple times and I calculate this same value, this log likelihood that you are seeing over here, right? This log likelihood, what do you think this value will be the maximum for which curve? The curve which is covering the maximum number of points, right? This value will be maximum for only that curve which is going through the maximum number of points in my data. If the point is going through the maximum number of points, then it means that we are able to cover the majority proportion. Hence, that is the best fitting S-shaped curve that we have, right? So what we do is that we go ahead and we rotate this line further. Now see, all of these things you don't have to do. I'm just explaining the concept of internally how the logistic regression model tries to come up with the best fitting S-shaped curve, right? If I rotate this line further, let's say like this, my probabilities will change because my sigmoid curve will change. Now, maybe you get these values, right? If you go ahead and calculate the log of this, you are seeing that the value has gone down even further, minus 0.207. Line A, my log likelihood was minus 0.084. Line B, my log likelihood was minus 0.207. Which line has the maximum value of the log likelihood out of these two, out of A and B? B, right? Or A? Which line has the maximum value? Is it A or B? A is minus 0.084, B is minus 0.07. So obviously it will be A, right? These are negative values. So line A has a better likelihood value than line B. Hence, you will go ahead and you will choose the line A as the best possible. Now, the model, what it tries to do is that it rotates and tries to come up with multiple sigmoid curves and sees the one which is giving you the maximum likelihood value, right? But that is the overall process. You will keep on rotating the line until we get the maximum log likelihood value, right? Whichever line is giving you the maximum log likelihood, that particular line will become the logistic regression model's output. All right. And this is what we do while when we are finding out, when we are trying to find out the best fitting S-shaped curve using MLE. MLE is nothing but maximum likelihood estimate, wherein we are calculating the log likelihood. All right, so this is logistic regression. Summary, we have taken a look back at the linear regression model, looked at the kind of problems that linear regression would not be able to solve. That's where we laid the foundation of logistic regression. And after doing that, we go ahead and we have understand what logistic regression model is. Why do we need to use the logistic regression model? How does the model work? And through that we have been able to understand how this particular model works, right? So we start by plotting the data, we draw a regression line, pass it through the sigmoid function which will give us an S-shaped curve. We keep on rotating the line. While rotating the line, we are trying to identify that S-shaped curve which is giving me the maximum likelihood, right? And we use MLE to find out the best fitted regression, not line, it will be the curve. And this is what the process is, right? We start with the log of odds, then we use the sigmoid function, and then we use MLE in order to estimate the equation of the line of best fit, right? Or S-shaped curve of best fit over here. To that now. Now, you guys remember for our uh, linear regression model, what were the uh, 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 evaluation metrics that we had? Evaluation metric for the regression models. What were those? We had many, right? Mean squared error, yes. R square, yes. MSE, yes, that is the same. Root mean square error, that is RMSE. These metrics, are these sounding new to you? Mean absolute percentage error, absolute error. Same evaluation metrics will be applicable when we are working on a classification problem. So ideally, no, right? That will not work. Now, why it will not work? Let me explain that to you. Say I had a target variable of rain, right? or let's say I take some other target variable. Let's say whether the customer will churn or not, right? I believe everyone is familiar with churn, right? Attrition churn, I have discussed this. So let's say I have my customers, right? My customers are over here. Let's say I have customer IDs. Right? I'll have 10, right? So 10 are fine. Okay, so let's say these are the customer IDs that we have, and the actual data that we had is this customer churned, this customer did not churn, this customer did not churn, this churned, this one did not, this one did not, this one did not, this did, and this one did not, right? This is my actual data. Okay, now let's assume that I build a logistic regression model, and from this I get a predicted churn. After building the model, I will be able to get a predicted churn, correct? Now, how many types of predictions can I get from the model? I can get a I can get correct predictions, right? Correct predictions will be what? Correct will be, let's say, actually my customer churned and my model also predicted the same. Or let's say, actually my customer did not churn and my model also predicted the same thing, right? So these will be the correct predictions. Okay. I can also have incorrect predictions, such as my customer churned, but my model said that no, they are not going to churn. Or my customer did not churn. In this case, my customer did not churn, but my model said otherwise. Or I can have the vice versa case as well. That is, the customer churned, but my model said that no, your customer did not churn. Do you think that these are the 4 kinds of predictions that we can get from a classification model? Does this make sense? The first 2 are correct predictions. If you look at this, whatever my model is predicting is actually correct. And the second 2 are incorrect predictions. Does this make sense? All right. So let's do one thing, right? I will go ahead and I will generate this entire data randomly. So let's say this value, this is correct, this is correct, this is incorrect, this is correct, this is correct, and this is also correct, right? Let's say these were the actual and the predicted values, right? Now, can you calculate the accuracy of this model? How can we calculate the accuracy of this? We cannot do actual minus predicted over here, right? That is not correct because these are classes. What I can do is that I can, let's say I create a flag variable, that is whether the predictions are correct or not, right? Okay. So let's say this one, actual and predicted, both are correct. This is correct prediction. This is correct prediction. This is not correct, right? This is also not correct, right? This is correct. This is correct. This is not correct. This is correct. This is correct. And this is correct. Does this make sense? I have just listed down the predictions which were correct and the predictions which were not correct. If I go ahead and if I take a sum of this should be this is not a binary variable. So let me do 1, 0. This 1 is for correct predictions, 0 is for incorrect, right? This is 1, this is 1, this is 0, 1, 1, 1, right? Now, if I take a sum of this will give me how many predictions were correct for me, right? And what were my total number of predictions? My total predictions were 10, right? Now, can you give me the performance of this model? How can I calculate the performance? Accuracy will be what? It will be this divided by this, right? Which will be 70%. Okay. Now, this is the accuracy, right? But if you look at the incorrect predictions, right? If you look at the incorrect predictions, there are 2 kinds of predictions that we have in incorrect as well. Even in the correct predictions, there are 2 kinds of predictions we have. This over here is known as a true positive, right? TP. What is TP? TP is that your actual value was also positive and the predicted value was also positive. This is a true positive prediction from my model, right? If I look at this one, that is 0 and 0, these are true negatives. That is, my actual value was also a 0 and my predicted value was also a 0. Both of them were 0. Both of these are true predictions, but between the correct predictions as well, I also have two types. One are the positive predictions, that is, people who are churning out, right? The model is able to predict them correctly. People who are not churning, the model is also able to predict them correctly. So the true positives and the true negatives, these are the two kind of correct predictions that your model will be able to give. Now let's come to the incorrect predictions, right? If I come to the incorrect predictions, this one over here is what? In reality, my customer did not churn, but my model is saying that the customer is actually churning, right? So this is something which is known as a false positive. My model is incorrectly predicting that this customer is going to churn. So this will be a false positive prediction. And similarly, this one over here will be a false negative. Why? My model is incorrectly predicting that this customer is not going to churn, right? I think I'm looking at the flags. I had to look at these two, right? So let's focus on these two. This is true positive, right? Because my actual is also 1 and my predicted is also 1. These ones, 0 and 0, are your true negatives. Why? Because your actual is also 0 and the predicted is also 0. This one over here is what? This one is a false positive. Why? Because this model over here for this row, the model is incorrectly predicting that this customer is going to churn, whereas in reality, the customer did not churn. Similarly, this last one is a false negative, right? My model is predicting that this customer is not going to churn, whereas this customer has gone ahead and this customer has churned. Does this make sense to each and everyone? Any questions? Now, can you go ahead and can you tell me the labels for the rest of the classes? What will this be? This will be TP. Next one, TN. This one, FP. This one, this will be TN. This will be TP. And this will also be TN. Correct? All right. Now, what if I go ahead and I now do something which is, so if you look at this, right? If I take the model predictions over here, and if I take the actual values over here, right? I can have my true positives over here. That is, my model was predicting correct, and actuality as well, my outputs were correct. I can have my true negatives over here, right? I can have my false positives over here, and I can have my false negatives over here, right? I'll explain what this is. This is something which is known as a confusion matrix, right? Now, what is a confusion matrix? I'm just trying to explain that to you. So if I go ahead and if I populate all of these things like this, right? I have my model results on the row. I have my actual results on the columns, and I just populate. If I go ahead and if I populate these numbers, right? Let me do that over here and see what happens. Now, can you give me a count of true positives that are there in this data? How many true positive predictions are there uh, in these 10 values? 3. So true positives are 3. What are the true negative values? How many false positives? 2. How many false negatives? 1. Right? Now, this is something which is known as the confusion matrix. You have the model predictions here. You have the actual values over here. And let's try. This is how we, first of all, calculate, or this is how we create the confusion matrix. Right? Now I will tell you what the use of this confusion matrix is, right? Now, from this confusion matrix, we can calculate many different metrics which will be used for any classification model, right? First, we'll start with accuracy. Can you give me the accuracy from this confusion matrix? What are the total number of correct predictions that we have? 7. What is 7? If you look at 7, 7 is nothing but TP plus FP, right? TP plus TN, right? Your correct number of predictions are what? Nothing but TP plus TN. If I divide this by the total predictions, right? Total predictions are what? TP plus FP plus TN plus FN. Correct? So your accuracy of the model will be this. Make sense? Now there is something known as precision, right? Now precision, the formula is TP divided by TP plus FP. Let's try to understand what this means. First of all, can you give me what the precision of this model will be using the count of values that we have? What will be the precision? What is TP? TP is 3. And what is FP? FP is 2. TP plus FP will be 5. So your precision will come out to be what? Your precision will be 60%, right? Now, what does this mean? If I only limit my model's predictions to the positive predictions, right? If I only go ahead and I limit the predictions to the positive ones. All right, so let me just color code this. So if I just limit my model's predictions to the positive predictions, that is the ones which have where my model is predicting a 1, right? This, let's say this, right? This, and this, right? My model in total is giving me 5 positive predictions. Out of these 5, how many predictions are correct? 3, right? Only 3. So what my precision is saying, if you look at precision, my precision is saying that out of the total number of positive predictions that my model is giving, how many are actually correct? Right now, I am only focusing on the positive predictions. I am calculating the precision for only the positive predictions. If my model is saying that 5 customers are going to churn, out of those 5, how many are really churning out? That is what my precision is telling me about. Correct? Now, I have also one more metric, which is known as recall, right? Now, recall is TP divided by TP plus FN. Can you calculate the recall for this model, first of all, before we move forward? Recall for this model will be what? 3 by 4, 75%. Now, what does recall mean? Now, recall over here is telling me that out of the total positive predictions that were there in the actual data, let's try to mark this, right? What are my TP plus FN in my data? My TP plus FN are nothing but, if you look at this data, right? All of the predictions that were positive or that were 1 in the real data. In the actual data, how many predictions were positive? If you look at this, in the actual data, there are only 4 predictions which were positive, right? Out of these 4, how many my model is correctly able to identify? If you look at the first one, the model is able to correctly identify. If you look at the third one, the model is correctly able to identify. If you look at the last one, the model is correctly able to identify. So my recall becomes 75%, right? Now see, a very simple, let me explain this through an example, right? Let's say you have 100 patients, or let's say you have patients 1,000. Out of these 1,000, you have uh, 10 patients who have cancer, right? And you have no cancer. You have 990 patients who don't have cancer, right? Okay. Let's assume my model, I create a model which goes ahead and says that all the 1,000 patients do not have cancer. What will be the accuracy of this model? My model is saying that all 1,000 patients, they do not have cancer. What does this mean? Can you give me the accuracy of this model? So if my model is saying that all 1,000 people have cancer, these 990, for these 990 patients, the prediction will be correct, right? Because they don't have cancer. But for these 10 patients, the prediction will be incorrect. But if you calculate the accuracy will be what? It will be 990 divided by 1,000, right? Because 990 predictions are still correct. So the accuracy will come out to be what? 99%, right? But do you think that this is a good model? So you might have killed these 10 people for whom you were not able to predict that they have cancer. Maybe they went ahead, they did some tests, and through the tests, you were able to say that, okay, you don't have cancer, but in reality, these patients actually had cancer. So do you think that this model with an accuracy of 99% is going to help you? No. So the first point that I was making, that I have made over here, is that accuracy will not always be the key performing indicator for you, correct? Because depending upon the uh, seriousness of the predictions, right? It might happen that only 1% people have cancer. It might happen that only 1% people have COVID. Your model can go ahead and say that all 100% don't have COVID. Still, your accuracy will remain 99%. But that does not solve your problem, correct? So this explains the fact why accuracy is not the best performing evaluation metric for classification. Now let's come to the second aspect, right? Now, if not accuracy, then what, right? So let's try to understand this through another use case. Let's say in this data only, right? Let's assume I give an example from a similar domain. Let's say I have 1,000 customers. Out of these 1,000, let's assume that the customers who have churned are 50. Yeah, right? The model that you create, right? It predicts, model churn says that 100 customers are going to churn, right? Your model says that 100 customers are going to churn, but in the 100 customers that your model is saying that are going to churn, only 30 customers who have actually churned are there, right? Only 30 from the actual base are there, right? Does this make sense? See, your model can go ahead and can say that 100 customers have churned. Or 100 customers will churn, right? Or let me take another example, right? Let's say my model is saying that 20 customers are churning, and through this, it is able to capture 15 customers who had actually churned. Or let me make this simple. Let's say all the 20 customers who are churning, your model is able to identify those 20 correctly, right? I'll make this simple. In reality, there were 50 customers who were churning, but your model is only able to identify 20, right? Now, can you go ahead and can you calculate the precision of this model? What will the precision be of this model? My model is saying that only 20 customers will churn, and those 20 are actual customers who have churned in the data, right? These 20 in reality have churned. So my precision will be what? The true positives, that is 20, divided by true positives, which is 20, plus false positives. Are there any false positives? My model is not making any incorrect prediction. For all the 20 customers to whom it is, for whom it is saying that they will churn, they are actually churning. So this will be 0, right? So your precision will come out to be 100%, right? But do you think that this is a good model? Your model has not been able to identify 30 customers yet. If you calculate the recall of this model, the recall of this model will become 20 divided by 20 plus 30, because there will be 30 false negatives that will be there in the model, right? And your recall will come out to be 40%. So even though you can have a precision of 100%, your recall is coming out to be a lesser value, right? Now, if you go back to the definition of precision and recall, your precision looks at, out of the total positive predictions that you are getting from the model, how many are correct. It doesn't matter how many are there in the actual data. In actuality, there might be 100 patients who have cancer. But if your model is predicting 20 have cancer and all the 20 in reality do, the precision will become 100%. But the recall will become 20 by 100, which is only 20%. The recall will focus on what? On out of the total people who have cancer, how many your model was able to predict correctly. Precision, if you look at this precision over here, precision only focuses on the positive predictions that your model is giving, right? Let's assume that 100 patients had cancer, but your model says that only 50 have cancer, right? and your model is able to correctly identify 50 customers or 50 patients from the set of 100 patients who had cancer. Now, your precision for this model will become 100%. Why? Because the model was saying that 50 people will have cancer, and these 50 people in reality have cancer, right? They actually went ahead and they had cancer. But do you think a precision of 100% will do justice to your model in this case when you have 50 other people who are not being identified correctly? No, right? So in order to capture the entire data, we have something known as recall. What recall says is that out of the total number of people who have cancer, how many your model is able to identify correctly, right? So your recall will be 50, which is the number of people your model is able to identify correctly having cancer, divided by the total number of people who have cancer, which is 100. So the recall will become 50%. Even though you have a precision of 100%, as soon as your recall becomes 50%, you will realize that your model is not doing a very good job. Okay, so we have covered the logistic regression model theory. We have covered the evaluation metrics, right? That these are the important aspects. And now we will move on to the hands-on. The data that we have is data about patients who have suffered from a heart attack and of certain other people who have not suffered from a heart attack, right? So the target variable that we have over here, this target variable is a categorical target variable, which indicates whether a person has suffered from a heart attack or not, right? Has had a heart disease in the past, right? So that's the target variable. Now we want to predict this target variable by using a bunch of factors, right? By using a bunch of medical factors that we have collected about these patients, right? So we have the age of a patient, right? So my data will be unique at a patient level, right? For each and every patient, my target will say whether the patient has had a heart attack in the past or not. And then I will, let's say there is a patient who had a heart attack. I will talk about the aspects such as what is the age of this particular patient, right? That will be one. So the age, what is the sex of the patient, right? Male, female. What is this CP? So CP is the short form for chest pain type, right? So there can be different kinds of chest pain that a person can have, right? So if you see, these are 0, 1, 2, 3. These are medical terms. Someone who is familiar with these will be able to explain or understand these. But even if you're not familiar, that's okay. Then we have the rest BPS. This is the resting blood pressure of the patient, right? What is the resting blood pressure of the patient? So you will have that metric, right? Then we have cholesterol. That is the cholesterol level of the patient. We have FBS, which is fasting blood sugar. We have rest ECG. So this stands for resting electrocardiographic results. So your tests that we have, right, with respect to heart, ECG. We have THALAC. This refers to the maximum heart rate achieved by the patient during an exercise test. So there is an exercise test that usually is carried out for people who have heart diseases in order to identify the in order to find out the maximum capacity of the heart, right? So that is THALAC. So, right. Exang is once again, this is once more a kind of a test, whereas exercise, when a patient does exercise, right? When you are, let's say, running, there will come a point wherein you start feeling some kind of a pain in your chest, right? So that is your exang variable. Old peak, this represents the depression induced by exercise relative to rest. Slope refers to the slope of the peak of exercise. So now, if you see, all of these are highly specific, highly technical terms. CA stands for the number of major vessels colored by fluoroscopy. So basically, this tells you how many vessels are blocked, right? That will be that we will get to know by CA. Finally, we have the target variable, that is whether or not the patient has had a heart attack in the past, right? So this is the data that we have. Now, what do you guys think? Do you think that the features that we have are important, are significant features which will help us in predicting whether a patient might suffer from a heart disease or not? right? So looks good. So let's go ahead, let's read this data. So the data that I have explained just now, the same data is contained in this CSV. This CSV, if you see over here, this heart1.csv is the one that we are reading. And you can see over here that this is all the variables that we have talked about. They are present over here, right? And we have the target variable, which is whether the person has had an heart attack or not, right? So looking at the target variable, looking at the features, do you guys think that logistic regression is the best suited model for this? Yes, right? All right. So let's get started with the EDA, right? We'll commence with the EDA of this model. So EDA, first we'll try to find out the distribution of the target variable, right? Now the distribution of the target variable, that is how many patients suffered a heart attack, how many patients did not in this data. Let's try to find that out. I have 303 rows in total over here. So there are 303 patient records that we have. Now, if I go ahead and if I call the value counts function, right? So either you can do datasets.target or you can do dataset colon, in double quotes, you can give target, right? So if you look at this here, I can see that 54% of the patients in this data have had an heart attack in the past, right? 45% patients have not have not suffered from a heart attack. What does this do? Normalize equals to true. If I do not give this parameter, this will give me the count, right? This will just give me a count. If you want to see the proportion or the ratio, you will give normalize equals to true, right? So this gives me 0.54, 0.45. If you want to look at the percentage, you will multiply this by 100, right? As simple as that. Shape of the data, 303, 13. This we have already seen. So 303 patients in total. So that's good. We have seen the value counts, so no need for this. I will eliminate this. We can go ahead and we can plot the target variable distribution as well. So I'm using a count plot, passing my target column. Data becomes data set. I give a palette. If you want to change the color, you can give a specific color. If you exclude this, it will take the default color of, I think, blue and orange, whatever that has, right? If you see blue and orange, right? So if you want to change the color, you can give the palette as well. Any color that you want to give, you can give that. Let's look at the correlation matrix over here, right? A similar level of EDA you are supposed to be doing over here as well, right? So let's look at the correlation heat map. So dataset.core, this will give me the correlation output. I go ahead and I just plot this in a heat map, right? And this is what my output looks like, right? Now you can either look at this heat map or you can also look at the tabular output as well, right? You have to give the figure size. Try figuring that out. Yeah, figure size is there, right? Now, if you want to look at this, you can see this. Now let's focus on the target variable at the bottom, right? Let's look at the target variable at the bottom over here. You can see that the target variable that we have, just go through this and see if you feel that this target variable is correlated with the variables that we have or not. Do the correlations look good? So if you see, each and every variable has a decent correlation with the target, right? Now, I will not see very high values over here. Why? Can someone tell me why I will not see very high values over here for correlation? Not multicollinearity. So see, our target variable is categorical in nature, right? Our target variable is not linear in nature. Now, correlation is a metric that works well with two variables which are linearly distributed, right? Over here, one variable is categorical. The other might be linear. But if you are trying to find out the correlation of a categorical variable with some other linear variable, you will be able to get values, but the correlation can never become 1, right? It can not become -1, because what will happen is that your one variable can only assume two values, that is 0 and 1. The other might extend from, let's say, 0 to 100, 0 to 500, 0 to 1000, whatever, right? So, but For categorical variables, a correlation of 20-30% is also very good, right? So in such cases, what you're seeing, right, a correlation of, let's say, 43%, right, 13-42%, all of these things are very good, right? This correlation tells us that there is a decent, healthy correlation of my target variable with these variables, right? So it means that the variables are correlated to a good effect. Now, if you just wanted to see the correlation of the target variable, we could have also seen it like this, right? Just limit the output to the target variable. All right. In this case, although we have not checked this, but let's also look at the data set.info. This will tell us if there are any null values or not. You can see that there are no null values in this data set, right? We'll go ahead and we'll describe the features that we have, right? Have a look at this. What do you see over here? Can you come up with some generic insights? Anything which is out of the ordinary that you're able to see over here? Just go through just do a basic sanity check of each and every variable and see if it makes sense or not. If I eliminate t, this is the output. If I keep t, this is the output. And this is just for transpose. Okay, transposing it, if you have more number of features, it is easy to look at the output then, right? Otherwise, you'll have to scroll towards the right hand side. So everything looks good, right? Age minimum is 29, maximum is 77, right? Similarly, this is your heart rate, right? You can see that heart rate is minimum 94, maximum 200, right? You have all your thallic and all of these things, right? So everything looks good. So I think the data that we have is good. There are no funny values. There are no incorrect values that are there in the data. So I think we can get started with model building, right? Shall we get started with model building? So first thing that we need to do is we need to divide our data into features and target, right? So I will divide my data into X and Y. So for that, I'm selecting all but the last features in data frame X. I'm selecting only the last feature in my data frame Y. So if you see, this is my X variable, which contains all the features, and this is my Y variable, which contains only the target, right? Next, we will go ahead and we will split this data into training and testing, right? Now for training and testing, what do we do? I call the train test split function. I am passing both my features and my target variable. I give the test size as 20%. So 20% will be for testing, 80% will be for training. The same objective, whatever we were doing in linear regression, random state has the same objective here as well. The function remains the same, right? And this function will return 4 different values: x train, x test, y train, and y test. And x train, x test will have 80-20% values of your x data frame. Y train, y test will have 80-20% values of your y data frame, right? Odd rate, generally it will be either 20%, 30%, right? Your test size will generally fluctuate in these ranges only, right? Is getting divided into x train and x test, right? If x data frame had 100 rows, x train will have 80, x test will have 20. All right. So now this is how our data looks like. If you see, x train has 242 rows and x train will have x test will have the remaining, that is 61 something rows, right? 61 rows in x test. Right? And this is all that we need to do with our data. And now we are ready with building the model, right? For building the model, just like in our linear regression, we had imported the linear regression model. This time we are importing the logistic regression model. From sklearn.linear model, we import logistic regression, right? I call the model object in the log model variable, right? I instantiate logistic regression. To train the model, I use the fit function and I pass the x train and the y train data, right? So this is my training data. X train will contain the features, y train will contain the target variable, right? Now my training is done, right? My training of the model is done. I can use this model to generate predictions, right? So what we'll do is that we will start with the predictions. Now, once when the model is fit, I can use this model to make predictions, right? I have my actual data. I have my predicted data, right? First, I will get my predictions. So I use my test data, right? I use the log model object and I predict. Now this time I'm not using the fit function. I'm using the predict function. So log model.predict, I pass the testing data. As soon as I use log model.predict and pass my testing data, I will get predictions over here in Vipred, right? So I do this. You can see that this is the length of Vipred. I have 67 predictions, and you can see that this is what I'm getting as predictions, right? If you see, I am directly getting the predictions as 0 or 1. How do I get 0 or 1? Any probability which will be greater than 0.5 will become 1. Any probability which will be less than 0.5 will become 0, right? Automatically, the cutoff will be created by the model. If I want to print the accuracy of the model, I have a function which is log model.score. If I pass the training data over here, this will give me the accuracy of the training data. So the accuracy of this model on training data is around 85%. For the same, if I give the testing data, log model.score x test y test, you can see that the accuracy of the same model on testing data is 80%, which is decent, right? I do not see that the accuracy has gone down by a very high margin, right? The accuracy has remained almost stable. 85% on training and 80% on testing. This is a good enough number, right? All right. But now we know that accuracy obviously is not everything that we have to focus on, right? In this case as well, if you remember, we have heart patients. Now, it might happen that my model is incorrectly predicting someone to be not having an heart attack when they have a higher risk of getting an heart attack, right? So do you think that accuracy will be the metric that will help me, or do we need to go with any other metric? If yes, then which metric do you think we should use? Recall, right? So we will be using recall, precision recall together, but recall will have the higher weightage, right? So for that, let's try to generate the confusion matrix. So for the confusion matrix, what I do is that I call from sklearn.matrix, I import the confusion matrix function, right? This is a pre-built function that we have. You can see over here that this is your confusion matrix function, right? It's there in the sklearn.matrix library only. I call the confusion matrix function. To this function, I need to pass the actual values of y train and the predicted values. So actual is y train, the predicted is log model.predict x train, right? Either you can save it in a variable and pass that, or you can directly get the predictions, right? I run this, and you can see that this is the confusion matrix that we are getting, right? Now for the confusion matrix, you can see that this is for your 0 class, this is for your 1 class, right? Similarly, this is for your 0 class and this is for your 1 class, right? So let's see what my performance is. Now, 120 people out of around 142, my model is correctly able to identify that these people will have heart attack, right? 14 people, it is incorrectly classifying that they will have heart attacks. 22 people, the model is not able to classify that they will have heart attacks, right? Now, if you want to identify the precision recall, I have a metric. Now, confusion matrix will just give me the TP, FP, TN, FN values, right? It will not give me precision recall and all. So if you want to generate the precision recall accuracy, I have another function known as classification report. Now the classification report, I call this function on the same training data, the actual Y and the predicted Y. I run this and you can see that these are the precisions and recalls that your model is giving for the class 1. Now, if you see for the class 1, that is people having heart attack, the precision is 85% and recall is 90%. This is decent, right? My model is covering 90% of heart attack patients. In reality, 90%, if there are 100 people who had a heart attack, my model is able to cover at least 90 of them, which is good, right? My model is doing a decent job over here. I can also generate the same confusion matrix for my testing data. This was for my training data, and this is the same for my testing data. And I can also generate the classification report for my training data. Sorry, for my testing data. So you can see that for my testing data as well, my recall is 84 and my precision is around 79%, which is decent, right? This log model.predict x train will give you the predicted value only. If you run this will give you the predicted value, right? You can directly take the variable or you can directly pass the values. You could have taken this particular variable as well by pred, right? Whatever you are comfortable with doing, you can do that. 79%, see, accuracy is not the evaluation metric that we are focusing on over here, right? I think precision, Karan, you're talking about precision, 7984. So this is not very good. Considering this is a medical use case, this is not a very good metric. But logistic regression is a very simple model, right? As compared to other classification models. This is what logistic regression is able to do. But as in when we move ahead in our course and we start studying about more complicated models, we will try to increase this value, right? Right now, the model is doing a decent job. It is not doing a very exceptional job. So yeah, I think that's it. There is not much to the case study over here. You guys would have seen this logistic regression. Uh, Implementing the model is quite easy. Understanding the model is actually what is slightly more tough, right? Now, this is a simple case study that I've taken. Once when we will proceed through the course, right? Once when we have seen almost all the popular models, then I will be taking you through a bigger case study wherein I will be talking about how in the real world we approach such problems, right? In the real world, if you have a categorical target variable, right, you will not generally go ahead and fit only one single model, right? You will, when you go to when you have to buy a car, do you go ahead and do you just take the test drive of one? No, right? You will take, let's say, many test drives, and then whatever car suits you the most, you will buy that. So just like that, while building the model, we do not build just one model, right? So right now the knowledge that we have is limited, so that is why I have taken a simpler case study. But once when we know about all other classification models as well, after that I will be taking one more complicated case study wherein we will see how we can test out different models, how we can identify the best performing model, and how then we can take that model and improve the results even further, right? Audrey, this is incorrect. This is for some other notebook. Don't. If you look at this confusion matrix, the result is telling you that there are 23 plus 26 correct predictions. These are the TP and the TNs. And there are 5 plus 7, that is 12 incorrect predictions.
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampal IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
Okay, so let's assume that these are two columns, right, in our data. Okay. Now, these are obviously non-numeric columns, but the models that we are studying about, they are numeric models, right? So how do we convert these values or these columns into numerical type, right? That is what label encoding or one-hot encoding is all about, right? Now, let's first look at label encoding. Now, what is label encoding? If I was to go ahead and if I was to convert this data into labels, right? I have to convert this into a numeric form, right? How can I do that? Let's say I go ahead and the same two variables, the most easiest thing for me to do is what? The most easiest thing for me to do is to assign numeric labels to these columns, right? Let's say same data, I have gender, right? I have designation, right? Same data. Now what I say is that male, right? All the values which is male will become 1, right? All the value which is female will become 2, right? So let's say I go ahead and I take this as an example. So male becomes 1, female becomes 2, 2, 1, 1, 2, 1, right? This will become your data, right? Now this is what label encoding is, right? Similarly, if I take designation, let's say data scientist becomes 1, senior data scientist becomes 2, data scientist 1, lead data scientist becomes 3, data scientist 1, then 2, right? So this is how I can convert my data to a numerical form. Okay. But if you look at these two variables, right, these two variables are categorical, but in categorical as well, right, these variables are slightly different. See, for designation, there is an order, right? A data scientist is the junior most position. Then you have a senior data scientist. Then you have a lead data scientist, right? Over here, the values are related to each other, or there is a sequence, there is an order in the values. But do you think that within male and females, do we have any order? It's not that a male is greater than female or a female is greater than male, right? Such kinds of variables, categorical variables, where the values are not related to each other or do not have a specific order, are known as nominal categorical variables, right? I'll say nominal only, nominal variables, right? The second variable, if you look at this designation has an order, right? What is the order? I know that data scientist is junior, senior data scientist is 1 level up, lead is 1 level up, right? These kinds of categorical variables are known as ordinal variables, right? Now, now that we understand the difference between nominal and ordinal, now see, when I convert this gender to a numerical value of 1, 2, my model will automatically assume that 2 is greater than 1. That signifies that female is greater than male. Is that true? Do we have any implication wherein we know that female is greater than male or male is greater than female? Male is greater than female. Obviously, people have those thoughts, but let's talk about facts, right? These are things that you cannot have an order, right? We cannot say, let's say if I have data about countries, right? I cannot say that, let's say country A is greater than country B. Obviously, on the basis of certain economical aspects and all, you can say that, but with respect to whatever problem you're solving, it doesn't matter, right? So do you think that converting this gender to these labels makes sense? This is incorrect, right? Because if I'm making male as 1 and female as 2, I am automatically inducing bias. I am introducing bias in my model. I'm saying that female is greater than male. If I do vice versa, I will say male is greater than female. So that's incorrect, right? And if you look for the second variable, designation, do you think that this label encoding makes sense for the second variable for designation? Second makes sense, right? Because 3 being assigned to lead data scientist, 2 being assigned to senior, 1 being assigned to data scientist, that's correct, right? So if you see, label encoding over here in this case was incorrect for the gender variable, but it was correct for the designation variable, right? So then how do we treat variables such as gender, right? How do we treat variables which are nominal in nature, right? Now let's move to another thing, which is known as one-hot encoding. Now what one-hot encoding does is that it takes the same data and it transforms it in a slightly different way, right? I'll take all 3, all 2. So this is for, let's say, the gender. This is for designation. I'm giving you examples of both, then we'll decide which one is correct, which one is incorrect, right? So now when I will do one-hot encoding, right, there are functions in Python that will automatically do all of this. But let's say this variable becomes gender underscore male, right? I'm just writing G. because there's no space. This will become gender underscore female. This will become designation underscore DS. This will become designation underscore SDS, which is senior. This will become designation underscore LDS, which is lead, right? I'll explain what this means. Now let's focus on the first variable, which is gender, right? Now what one hot encoding does is, one hot encoding is this one, right? It creates binary variables for every nominal variable that you have or any categorical variable that you pass, right? Now for the first row, it's a male, right? When it's a male, this will become 1 and this will become 0, correct? For the second person is a female, so male column will become 0, female column will become 1, right? Same for this one, right? Then we'll have this, then we'll have second last one will be female, and then we'll have this once again. Now, what I have done is that I have taken the gender column and I have created binary variables for all the unique values that this particular column can take, right? Now, if I do the same thing for the designation variable, what will happen? This is 1, 0, 0, right? This is 0, 1, 0, right? This is once again 1, 0, 0. This is 0. This is lead, right? So 0, 0, 1. Then once again this, and then 0, 1, 0, right? Now, first of all, if we focus on the male, or if we focus on the gender column, this is completely bias free now. That's correct, Charan, right? So do you guys think that this is a correct conversion of this particular variable gender? This is correct, right? I am not saying that male is greater than female or not. I am just replicating the same information in a numeric way with a bias free approach, right? I am not giving any bias to any of the values that are there. Why did I not give any bias? Because obviously gender is a nominal variable, right? Now, if I move to the second column, which is designation, now see this, we all should agree, right, that this is the correct approach. This one is correct, right? This is correct. Now, what do you guys think about these last three columns? Is it correct or is it incorrect? How can I make that 0 now? So let's say this is 0, right? All right. Now for the designation column, do you think that this transformation, one hot encoding, do you think that this is correct? See, in the nominal variables case, this was incorrect. But over here, do you think that this approach is incorrect? This also looks correct, right? What is different in this one? So if I compare, let's say this from this, what is the difference? So see, for our ordinal variables, right, both approaches can be correct. But if you look at the second approach, in the second approach, you are losing information about this variable. The information that you are losing is the order, right? So although it is correct. It is saying that this first person is a data scientist, second is a senior, third is a lead, and so on and so forth, right? Whatever. It is that information is intact. But the model now does not know that a senior data scientist is greater than a data scientist. A lead data scientist is greater than senior data scientist. So you are only portraying 50% of the information. So there is lack of information that is happening in the second case, right? So this is how we treat our categorical variables, right? Now, these concepts, I have interviewed people having 8 to 10 years of experience, and these concepts were not even clear to them, right? But now if I go ahead and if I give you a case study, right? I go ahead and I give you a case study, I'll tell you that you have two columns. One is the department of the products that they belong to, right? And one is the product name, right? Now, I want you to tell me how will you convert these two categorical variables into a numeric form? What will be your response? One is department, the other one is the name of the product. How will you convert these into a numerical form? This is a question. So assume that the department column, right? I believe the example would be confusing, but assume that the department column has, let's say, milk is mapped to dairy, dairy is mapped to consumables, consumables is mapped to, let's say, something else, right? So if that is the case, if let's say department is something that has an order, right, then in that case, that will be uh, transformed using one-hot encoding. Sorry, label encoding, and the product names will be classified or will be converted using one-hot encoding, right? So let's get started with decision trees now, right? Linear regression, logistic regression. Linear regression was what? Classification. No, regression. Logistic regression was classification, right? Does data science end here? No, right? When you go to buy a car, is it only Tata, Maruti? That is there only just one brand? No, right? You have options. Just like that, in case of machine learning data science, we have options. It's not that there is only one model for classification, one model for regression. There are different models. We need to go ahead and we need to explore all the models. We need to see which model is working the best, right? Whatever model is working the best for us, for our case, right? We go ahead and we choose that. Just like maybe for you, you might prefer, let's say, a Skoda car or a Volkswagen car. Your father might prefer a Maruti, right? Right. And your, let's say, someone else might prefer a Tata or a Mahindra, right? So just like that, depending upon what your requirements are, your requirement might be stability, your requirement might be features, your requirement might be anything. Just like that, from a model as well, your requirement might be a simple model, your requirement might be a non-linear model, your requirement might be explanation of the factors that are driving the model, right? On the basis of that, we actually select the model. Even on top of that, not every data will fit to all the possible models that are out there. Every data distribution is different, and every model that we are studying, the inherent architecture is also different, right? So when the architecture is different, then when we are exposing different distributions of data to the same model might respond well to one kind of a data and might not respond well to another kind, to which, let's say, some other model might actually do a better job, right? So hence, it is not only linear logistic that we use. There are other models as well, right? When I say other models, this week we will be focusing on decision trees and random forests, right? These are very common models in the world of data science, these tree-based models. So we'll first try to understand what a decision tree is. Then a decision tree, once when we understand decision trees, then we will move on to random forest, because random forest is nothing but it is a variation of the decision tree model. Decision tree, your random forest, they can be used for both classification and regression tasks, right? So the linear regression model that we have studied till now, it was only limited to regression, right? Logistic regression was only limited to classification, right? Whereas our decision tree models that we are studying are models which can do both the things, right? It can also help you with a target variable which is categorical. It can also help you with a target variable which is continuous in nature, right? So let's get started with the theory. Now, tree-based models are said to be the most used supervised learning models. They can be used for both classification and regression problems. We can create highly accurate and stable predictive models using these tree-based models, right? Now, tree-based models are very, very popular. Why? They are easy to use, right? They are explainable, and this is something that we have been doing a lot, right? So they are easy to understand as well. When I'll be talking about the concepts, right, you will find that you are able to relate with these tree based models, because generally that is what we also do in our life, right? That's what our objective also, whenever we have to do something, right, we go ahead and we apply a bunch of rules, right? We apply a bunch of conditions, right? So let's say I take a very simple example. Let's say that you need to hang out with your friends, right? And you need to decide on a place where you have to go and meet and eat, right? Is it a straightforward process? First of all, let's say you have five friends, and let's say one friend comes up to you and they say that, okay, we'll go and we'll meet, we'll have dinner in, let's say, a particular restaurant, right? Let's say Burger King, right? Not even a restaurant, a fast food joint. But does that happen this way? No, right? There will be so many factors. So let's say 5 friends, you get together, you go ahead and you decide that you have to finalize a restaurant, right? Now, can you guys think of what factors can be there which might affect which restaurant you might go or you might not go to? What factors drive food? What kind of food you want to eat? Distance, proximity, ambience. Is it dinner? Is it lunch? Season, cuisine, price? So many factors, right? So let's do one thing. Let's try to build a decision tree and see how the decision tree will actually help us in making certain decisions about the population, right? Now, let's say this is my entire data. This is my entire data. I will take restaurants in NCR, right? Delhi NCR. Taking this as an example, you can extend this to your city. Let's say that the total number of restaurants in Delhi NCR are 1,000, right? Just for example, let's say I go ahead and I take this, right? Okay. Now let's try to identify. Okay, so what according to you guys will be the most important aspect over here? When 5 friends are meeting, let's assume one is from Noida, one is from Gurgaon, one is from Faridabad, one is from Ghaziabad. Then what is the first thing that you will have in your mind? Distance, right? Let's assume that the first aspect or the first condition for everyone is distance, right? So a very simple rule, let me go ahead and let me apply a very simple rule over here in this data. I will go ahead and I will say that, let's say every friend is saying that I don't want to travel more than 20-30 kilometers. The friend who is situated in Noida, if he has to go to Gurgaon, he or she might have to travel 50-60 kilometers, right? Similarly, Faridabad has to go to Ghaziabad 40-50 kilometers, right? So let's say the first condition that we apply is distance less than 25 kilometers, right? What are all the restaurants, right? That what are all the possible restaurants which have the distance of less than 25 kilometers or greater than 25, right? Now let's assume that distance less than 25 kilometers, out of the 1,000, there are only 200 restaurants, right? Which will have distance of less than 25 kilometers, right? These are 200, and let's say these are 800 restaurants, correct? Now, what do you guys think? What will be the next criterion? What might be the next criterion over here? Cuisine, maybe. I think let's go to cuisine. So, right. So let's say in cuisine, or let's say first, let's try to decide whether it is veg or non-veg, right? So you can have a condition such as, let's say, is it Navratri? Or let's say simple, right? I'll just write veg, all the veg restaurants and all the non-veg restaurants. Let's say on whatever factors you are able to arrive at a decision, do you want to eat veg or do you want to eat non-veg, right? Now let's say you decide that you have to go ahead and you have to eat non-veg, right? Let's say 80 are veg, 80 restaurants, 120 are non-veg, right? Okay. So let's say this is then 80 and 120. Now you will go ahead and you will split this further, right? Now this process will keep on happening, correct? Now the next uh, filter can be, let's say, what kind of cuisine within non-veg do you want to go for? Mughlai? Do you want to go for Punjabi? Do you want to go for American, Italian, Mexican, whatever, right? So this, you can imagine, this tree will keep on growing. Does that make sense? Right? We can keep on growing this tree to any extent possible, but as long as we are keeping features which are important, right? As long as we are keeping features which are relevant, our decision tree will stay relevant and significant, right? Now let's assume that I take a case of 5 friends who are in college who want to select the best possible or a place wherein they can eat, right? So for them, what will happen? This decision tree will come from here to here, right? This will then come from here to here because they decided that they have to eat non-veg. And then let's say on the basis of all the rest of the conditions, they finalize that they are going to go to these, they have these 5 restaurants as the option. Now they will go ahead and they will decide these 5 amongst themselves, right? Now see, this decision tree can also serve a purpose for other cases as well, right? Now let's say the same in the same area, we have a group of friends who want to eat at a restaurant which is less than 25 kilometers, but they are looking for a veg option. Now, within the veg option as well, if you keep on growing this tree further, right, you should be able to identify the best options for you, right? Even over here, towards the right-hand side, if you would have grown this tree forward, you would have seen that, okay, greater than 25 kilometers, maybe you travel to Gurgaon, maybe you go to Murthal, whatever, right? But if you see, if you capture all possible outcomes, right, out of all the 1,000 restaurants that are there in Delhi NCR, you can go ahead and you can divide each and every restaurant to each and every condition or a combination of conditions, right? And this is how we generally create a decision tree, right? Similarly, when you have to go and you have to buy a car, how do you decide? You will decide a budget, you will decide features, you will decide whether it is petrol, diesel, electric, you will decide what brands you need to go for, right? There are so many factors, and on the basis of this, yes, 5-seater, 7-seater, SUV, hatchback, sedan, saloon, whatever, right? So isn't this how we actually arrive at decisions? Isn't this that in most of the cases you make, whenever you're making a life decision in a, let's say, in a uh, disciplined way, isn't this how you will actually approach a question or approach a situation? Okay, so this is clear to everyone. So this is generally what we mean by decision trees. Let's go through some theory around decision trees, and gradually we will try to understand how decision trees actually work, right? Now, tree-based models are the most used supervised learning models, algorithms. They can be used for both classification regression. We have gone through this. There are two kinds of tree-based models that we will be going through: decision trees and random forest. However, it is not limited to these two. There are other models as well. But if you understand these two, you should be able to extend the knowledge from here to the other models as well. Let's get started with the decision tree. How is it different from putting criteria and assigning weights to them for decision? We are not assigning weights over here, right? We are dividing our population as per our need, right? As per our requirement. There are no weights that are being applied over here. If you're comparing this with logistic regression, linear regression, in case of linear logistic regression, we were getting the output by combining all the factors, assigning different weights, and then coming up with a common factor. Here, we are taking each and every factor and we are seeing what we are applying conditions on that, and we are trying to come up with homogeneous groups, right? So let's say if your entire population was this, right? So let's say you have, so let's say these are the different options or the different, this is how your data is distributed, just an example. So what decision tree is doing is that it is creating boundaries, it is creating rules. It is saying anything which is from here to here will be a cross. Anything from here to here will be a tick. Anything from here to here will be a heart, right? During this process, there can be misclassifications, but over here, we are not assigning weights. We are creating these decision boundaries. The rules that we are applying, they are actually dividing your data into homogeneous groups, right? Kind of like if else, right? Now, decision tree, a graphical representation of all possible solutions to a decision. A decision tree is mostly used on classification problems. Decisions are mainly based on some conditions. Decisions made can be easily explained, right? So just go through this definition and see if you're able to understand this. Let's say distance has highest precedence, wedge is priority. You might still arrive at the same conclusion. Here you have only assigned, you have not even assigned weights, right? You are just saying that, see, when I say that distance has the highest precedence, it is not only distance which is going to give you the prediction, right? We are taking distance as the first cutoff or as the first criterion. After applying distance, you are applying some other criterion as well. I am not saying that the distance has the highest weightage over here. I am saying that I am splitting my data on the basis of distance first because that makes sense first, right? Then if I take some other, if I'm taking any other variable after distance, it does not mean that the importance of that variable has gone down. Overall, all of these rules that you are creating, they work together to go ahead and to come up with the final predictions. So in case of logistic regression, linear regression, we were assigning weights. Here, we are not assigning weights anywhere. We are just trying to come up with a combined set of rules, which helps us in getting homogeneous groups, right? If I'm looking for people who have churned, if I'm looking for people who have not churned, we are trying to identify those groups. Random forest builds multiple decision trees and merges them together to get a more correct and stable prediction. These types of models, right? Random forest is something that is called, these models are actually called ensembles, right? Ensembling is a technique wherein you combine multiple learners together, right? So if you see where a group of weak models combine to form a powerful model, right? Now, this is trained with the bagging method. What is bagging? Bagging is nothing but you create a bag of models. All right. Now, let's try to understand. Let me give you one more example about decision trees, right? Now, let's come back to a data science problem, right? The most common data science problem that we have been seeing is the problem of churn, right? Let's say we have a look at this, or let's take something relatable, right? Everyone would be following cricket, I'm assuming. Let's say India versus England, right? I'm going to make up these numbers, but I think this should be, you should be able to relate to this. Let's say India versus England. Let's assume that India has played, the total matches that have happened are 100. I'm just taking a random example, right? These are not actual values. And let's assume the matches that are won by India are only 10, right? So the win percentage comes out to be what? The win percentage comes out to be 10%, right? Correct? Okay. Now let's see how can we, let's try to break this data down, right? Let's try to build a decision tree on top of this data, right? Now see, when we are building the decision trees, the objective for us is to increase the purity of the of the nodes of the decision tree. What do I mean by purity, right? Let's try to understand what we mean by purity first, and then we will move forward. Now see, this particular, or let me change this to, let's change this to 50%. India versus England. Matches are 100. One are 50, right? So the win percentage becomes 50%, right? Now, if you look at this root node, this has 50% observations of India winning and 50% observations of India losing, right? Now, can you guide what can be some factors which can help us in identifying when does India win against England, right? Any idea? What are some of the factors that you can think of? What might be the most important factor over here? So most important factor is where are they playing? Are they playing in India or are they playing in England? Correct. So let's say if I divide my data, let's say if I apply the condition playing in India, right, and playing in England. Let's say when I do playing in India, out of these 100 matches, let's assume that out of these 100, India has played 40 matches in India and India has played 60 matches in England, right? Out of these 40, let's assume that India has won 30 matches, right? And over here, out of these 60, now the remaining are what? Remaining are 20, right? India has won 20. Okay. Can you calculate the percentage of winning now? What is the percentage of India winning when they are playing in India? It is 75%, right? 30 by 40 will be 75%. The percentage of win when they are playing in England is what? Is 20 by 60, which is 33%. Does this make sense? Now, essentially, what I have been able to do is that I have been able to increase this 50 from 50 to 75 over here. And I have been able to decrease this 50 from 50 to 33 over here, right? What if I also see there will be n number of factors? How do I know that this is the most important factor? Let's say I take one more example, or I take one more factor. Let's say the second factor that I take is, let's say, pitch spin friendly, right? And pitch is, let's say, fast bowler friendly, right? Okay. Now, let's say using these conditions, if I divide the same data, let's say that India has played England in 60 matches when the pitch is spin friendly, right? And out of these 60, let's assume that India has won 40 matches, right? 140. And let's say when the pitch was fast bowler, it was a fast wicket. Over here, India has won how many? 10. Correct? Now, if you see, the win percentage will be how much? Over here, the win percentage will be what? 40 by 60 will be 66%, right? And over here, it will be how much? It will be 25%. Correct? Now, you have been able to increase this 50 from 50 to 66 and decrease this 50 from 50 to 25. Out of these two, which one will you select? Both will matter, but which one will have which one will be used as the first variable for split? What do you think? Now see, in the first case, the what I have, see, when I do 75 and see the 50% I was able to increase to 75. So basically 25% increase, and the 50% I was able to reduce to 33. So that is a 17% decrease. So if I add these two up, the amount of information increase or decrease that I'm getting over here is what? Is 42%. Right? Does this calculation make sense to everyone? See, I get 75 in one as compared to 50 in other. So that gives me a 25% increase. And for the second one, I get 50 minus 33, which gives me a 17% decrease, right? Overall, if I sum this up, I get 25 plus 17, which is how much? Which is 42% increase or decrease in the purity, right? This is the first case. If I look at the second case, I'm getting how much? I'm getting 66 minus 50, which is equal to 16%. And in the second case, I'm getting 50 minus 25, which is equal to 25%. If I sum this up, I will get how many? 41%. Which approach is giving me a higher increase or decrease in purity? Is it the first one or the second one? First one, right? Even though it is close, but it is the first split that is actually helping me in or it is, see, at the end of the day, I will be satisfied if all of the matches that India have won was over here on the left hand side. All of the matches that India lost were over here on the right hand side, right? So what I'll do is that I'll go ahead and I'll take this first variable as the split, right? So I'll say playing in India, right? Or I will say playing in England, right? When I divide this data, I will delete this now, right? Now, when India is playing in India, then my stats were what? I had played how many? 60 matches, 60 or 40? 40 matches, 131, and percentage was 75%, right? And when India was playing in England, I had played 60 matches, I had 120, and my percentage was 33%, right? Make sense, everyone? Now let's take this further, right? I'll split this particular node even further. Let's say now the second condition that we apply is spin friendly pitches, right? Now this is, let's say, spin friendly pitch, and this is, let's say, fast bowler pitch, right? Let's assume if I had gone ahead and if I had divided this, right? Let's say from here to here. So let's say that out of 40, there were 30 matches which were spin friendly, right? And out of this, India won all 30, right? Just an example, so don't go on actual numbers. Let's say 10 were fast bowler friendly, and out of this, India lost all, 0-1. Now, you can see that the win percentage becomes 0%, right? Does this make sense? Now, let's say over here as well, similarly, if I apply the same rule, right? That is whether the pitch was spin friendly or not. Let's say this was spin friendly and this was fast bowler friendly. And let's say spin friendly, there were, let's assume 25 matches in spin-friendly pitches. India won 20. Your win percentage was how much? 80%, right? And let's say over here, we had the remaining matches, right? 35 matches were smaller. India won 5. Win percentage was how much? 100 by 7. That will be how much? 14.3. Let's take 14.3%, right? So win percentage will be 14.3%. Does this make sense to everyone? Will it be 35? I'm not sure. 5 by 35, 1 by 7, 100 by 7, right? 7 will be 1, 4, yeah, 14 point something. Correct? Okay, yeah, this will be 0, 1 here. Sorry. Thank you, Charan. So there are no matches that are 1 here. So these are 35 matches. Sorry. Good catch. 0, 1. So 0%. Now see, what was my overall objective? My overall objective over here was to be to see over here in this case, if I had, let's say, if I had just this is just to give you an idea, if I had 15 ticks and I had 15 crosses, right? So basically, I have 50% representation of both the classes. Ticks can be wins and crosses can be lost, right? So let's say these are 15 and 15, 30, right? So this is not what I want. What I want is I want more number of, so let's say if I have 3 of these, and if I have, let's say 7 of the ticks. So although this is 75%, but let's keep it 70. This is what I wanted, right? In the second case, what I had was I had more number of crosses, right? Let's say 1, 2, 3. I had 6 crosses and I had only 3 ticks. So if you see overall, I am trying to increase or decrease the purity, right? In the final case, if you look at this particular output, I have all ticks, right? Whatever number are there, all are ticks. In this one, all are crosses, right? So the objective of the decision tree is to increase the purity of the resultant node. Either it should have all the matches which India had won, or it should have all the matches which India has lost, right? Now, if you see after doing all of this, now if someone comes to you, right, they say that India is playing a match against England in England and it is a fast bowler friendly pitch. What will you say? What will your prediction be? Will India win or lose? India will lose, right? If you say India is playing England in India and the pitch is, let's say, spin friendly, right? You will say 100% India will win. Now, these are just two variables. Obviously, you understand that India winning or losing will be a function of so many factors, right? But this is just to explain to you how exactly decision trees will work, right? All right, then. So let's proceed with the theory of decision tree. So now I want you to go through this example on your own. I've given you a couple of examples and see if you're able to understand this or not. Your target variable over here is label. Using the target variable label, they are trying to create a decision tree, right? Now just go through this and see. I think this should be, the example should be clear to everyone, but go through this example in detail. You should be able to understand each and every step. Don't focus on these terms as of now. The Gini impurity, information gain, leave them as of now. Only focus on the calculations, right? Just focus on the purity. All right. So if you see, this is easy. My target label has 3 unique values. It can either be mango, lemon, or cherry. We are trying to identify a fruit on the basis of the color and the diameter, right? So the first plate that it is taking is checking whether the diameter is greater than 3 or not. If it is less than 3, then all the cases, right? If you see, for when the diameter is less than 3, I'm getting a node which is 100% pure. I'm getting all cherries over here, right? So this is a totally pure node, and this is what my decision tree aspires to get, right? So this is good. Now, if I come to the right hand side, I see that there are 2 mangoes and there are 1 lemon over here at this split. Then if I apply one more split, that is color equals to yellow. Now, if you see, when the color is equal to green, when the color is not equal to yellow, and the diameter is greater than 3, 100% chances of that fruit being a mango, right? So this once again gives me the maximum possible purity. But over here, if the diameter is greater than 3 and the color is yellow, then you cannot be sure. Then there can be a 50% probability that it is a mango. Then there can also be a 50% probability that it might be a lemon. Using these two features, you cannot go ahead and you cannot identify what the fruit might be if the diameter is greater than 3 and if the color is yellow, right? So we'll proceed. Now let's go through the terminology of some of the decision tree things that we have, right? Now see, I'll start with here, let's say the root node. The root node is what? The root node is your overall population, the entire population. That is when you have not started splitting the tree into subsets, right? That is the root node. Your entire population will be the root node, right? The parent or child node will be any node that is broken down into subnodes, right? So the root node will become the parent node and all the other nodes that are branched. So if let's say if this was a tree, let's say this was a tree that we had created, let's assume. So first of all, my root node over here is what? The root node is the top one. This also becomes my parent node to these two childs, right? So my parent node will become this and the child nodes will become this. If I go ahead and if I split this even further, then this particular node will become the parent node, right? Now, for this split, right? If I do this split, now this becomes the parent node and this becomes the child node. If you talk about this split, this becomes the parent and these two become the child nodes, right? If I don't, the part wherein I stop my tree from growing, right? So let's say this was the entire tree. The nodes which are not divided further into child nodes are known as leaf nodes. So these 4 nodes that you are seeing at the bottom, these will become the leaf nodes because they are the leaves of the decision tree. There is nothing else that is going to come out from these leaves, right? This will become the leaf node. The process of splitting the root node or the parent node into child nodes is known as splitting, right? If you focus on specific area of the decision tree, let's say if you just focus on this area, this will be called as a branch or a subtree. So you can see that all the terminology is very, very synonymous to an actual tree, right? And the process of splitting, or let's say the process of cutting away a branch, right? And why do we do that? I will talk about that later. But let's say if I go ahead and if I take this branch away, this process is known as pruning, right? We'll talk about pruning in detail. Why do we need to pruning? What is the use and all? But these are the overall common terminology that we have for decision trees, right? Now let's have a look at one more example. Now this is a proper example with some data. Go through this and try to understand what we are trying to do over here. This is the target variable, that is play or don't play. And these are my features, right? So what are we doing here? We are using these 4 features, that is the outlook, the temperature, humidity, and windy conditions, that is the weather conditions. We are using these weather conditions to go ahead and predict whether you should play or not, right? So I'll take this data and I'll see how a decision tree will build itself. All right. So how to decide whether you need to go outside to play or not on the basis of the weather conditions. If you need to build a decision tree, let's see how the decision tree will be built, right? Now, the first thing is what we need to identify. Now, can you tell by looking at this data manually, can you tell which feature will be used for the first split? Is there a way to do that? Can we look or can we tell this by having a look at the data? No, right? We will have to, just like in the previous case, I was taking examples of, let's say, India playing in England, playing in India. What was the purity like? I took the second variable, whether the pitch is spin friendly or fast bowler friendly. And then I went ahead and I actually found out that whichever split is giving me a more purity increase, I will go ahead and I will take that, right? So I cannot manually decide this. I need to decide which variable will be selected as the first variable by looking at the purity of the split, right? So all of you who are saying outlook, temperature, now see, manually by having a look at the data, we can never tell. Now see, here we have only 10, 12 rows. In the real world, you might have thousands and thousands and millions rows, right? Will you have a look at the data and say that this is the column that you need to use? No, right? We need a statistical way of identifying this. Make sense? Let's try to find out how does this exactly happen. Now, a decision tree, right? There are 4 criterions that we can use, right? Not all 4 together. One of these 4 can be used to go ahead and to identify the best split, right? Which feature needs to be accounted for the best split. So we have entropy, we have information gain, we have reduction in variance, we have Gini index. All of these 4, the objective is simple. The objective is to identify how pure the resultant nodes are. If you remember from our previous example, when I had started with India and England, the overall distribution was 50% matches India had one, 50% matches England had one, right? Then when we went ahead with the splits, I was trying to manually identify which split is giving me a higher increase in purity, right? So instead of manually doing that, these 4 metrics, one of these 4 will help you in identifying which feature is giving you the best split, right? So entropy, information gain, reduction in variance, Gini index, these are the 4 options that you have. While building the models, you can play around with any of these options, right? Overall objective remains the same. It's just that the approach will be slightly different, right? So let's have a look at entropy, right? I'll give you an example of entropy, how entropy works. I'll give you this example with the actual data, and you will have a look at, you will be able to understand what or how entropy is actually used to calculate the best feature for the split, right? Now the formula for entropy is simple, right? Now if you would have studied entropy in school, entropy was what? I think you would have studied this in physics, thermodynamics and all, right? Entropy was what? And entropy was how much random your state can be, right? If you have a physical state which contains, let's say, 50% of one kind of values, 50%, or let's say we used to talk about entropy with respect to electrons and all, right? I don't remember everything now, but a system wherein the electrons are actually, let's say, moving in different directions will have a higher entropy. I am looking for a system which wherein the variance or wherein the electrons are moving in the same direction, right? I'm not sure if it was electrons, protons, neutrons, whatever, right? But it was something to do about mobility, right? Let's try to understand here. Entropy is nothing but the randomness of a state, right? The randomness of a given state. So here, if you look at this in our example, let's go back to our data. Let's calculate the entropy. The formula for entropy is simple. The probability of yes into the log of probability of yes minus probability of no into log of probability of no. Both of these values are coming out to be minus, right? Now, first of all, can you tell me from this data what is the probability of getting a yes and what is the probability of getting a no? How can we find that? Probability of yes is 9 by 14. I have 14 observations in total and I have 9 yeses and I have 5 no's, right? So probability of yes will be 9 by 14. Probability of no will be 5 by 14. If I apply this formula, right, over here, then I will get the entropy of the state, right? Now, see, let's try to understand this. Let's assume that the probability of yes in a system is 0.5. A probability of yes in a system of 0.5 means what? That there are 50% yeses and 50% no's, right? For such a system, the entropy will be equal to 1. That is, this system is totally random, right? If you look at this curve, the entropy will be equal to 1 when the probability is equal to 0.5. If the probability is 0 or equal to 1, then the entropy will be equal to 0, right? So in our case, let's have a look at what is the probability of the overall of the initial state of the decision tree, right? Now the probability of yes, or the number of yeses were 9, number of no's were 5. We can go ahead and we can impute all of these values. So minus 9 by 14 into log 9 by 14 base 2, minus 5 by 14 into log 5 by 14 base 2. Calculate this and you get an entropy of 0.94. What does 0.94 tell you? Does it tell you that your system is totally random, or does it tell you that your system is totally pure? This value is close to 1, right? All right. So this is the entropy of the root node. Now, what do I need to do next? Now, the information gain, I'll come to this later. Let's first calculate the entropy of the overall system, right? Now, how do I identify which variable I need to take? Is it outlook? Is it temperature, humidity, or windy? So what I'll do is that one by one, I will use each of the variables to divide this data, and I will calculate the entropy of the resultant state, right? So let's start with the first variable, which is outlook. If I divide this data by outlook, my outlook has 3 values, right? Sunny, overcast, and rainy, correct? So if I divide the data by outlook, my tree will look like this, right? It will have one branch for sunny, one for overcast, and one for rainy, correct? Can you give me the probability of yes or no for sunny? What is the probability of yes for sunny, the probability of yes for overcast, and the probability of yes for rainy? 2 by 5 for sunny, for overcast, 1, for rainy, 3 by 5, right? Correct? But this is the individual or these are the individual probabilities. So first let's calculate we will calculate the entropy, right? So what I do is that I calculate the entropy for outlook equals to sunny, for overcast and rainy. You can see this, these are the same things that you have talked about, right? 2 by 5 into log 2 by 5 minus 3 by 5 log 3 by 5. This is for sunny. This is for overcast. Now you can see that for overcast, it was a pure node. Your entropy is coming out to be 0, right? Then similarly, rainy, the entropy is 0.971. Now, if you want to calculate the overall entropy, right, for this split, you will have to take the weighted average of all the entropies that we are getting. So I take 5 by 14 into 0.97 because there were 5 values for sunny. I take 4 by 14 for overcast because there were 4 values, and I take 5 by 14 for rainy because there were 5 values, and the overall entropy comes out to be 0.693, right? Does this calculation make sense to everyone? Now, information gain is nothing but entropy of the parent node minus the entropy of the child node, because that tells you how much entropy, how much increase or how much decrease in purity you have been able to achieve. So my root node had an entropy of 0.94. My resultant node has an entropy of 0.693. So the information gain is 0.247, right? So if outlook is giving me an information gain of 0.247, I will calculate the same value for all the others. The variable which is able to give me the highest value of this difference, right, will be the variable that I will choose. Does that make sense? If I split using outlook, my entropy is decreasing from 0.94 to 693. That is a close to 0.25 decrease in entropy. So this is the information gain, right? So let's go ahead and let's calculate this for all the rest as well, right? Correct. So let's take windy, the next one. If I take windy, have a look at windy. When it is false, I get how many? I get the probability of yes equals to 6 by 8. When it is true, I get the probability of yes equals to 3 by 6. Correct? We can calculate the same values, right? I go ahead and I calculate I will calculate the entropy. 1 for windy, true. 1 for windy, false. What is my gain? 0.94 minus 0.892, 0.048. Now, out of Outlook and Windy, which variable will we select? Given that we had only these two, which variable would you have gone ahead and selected? Outlook, right? Because it is giving you more information gain. Windy is decreasing your entropy from 0.94 to only 0.892. Whereas Outlook was decreasing your entropy from 0.94 to 0.693. Our objective is to make this entropy value close to zero, right? So out of these two, we would have selected Outlook, right? Now this is the visual description. Now, if you go ahead and if you do this for all the possible variables one by one, right? I have done for Outlook, Windy, you do this for temperature, humidity and all, you will realize that Outlook is the one which is giving you the highest entropy value, right? Can you do this for temperature and give me what the entropy value will be? Let's do this for temperature as well. I will write the entropy values, the information gain for all. For Outlook, gain was close to 0.25. Windy, gain was equal to how much? For windy, it is 0.048. Can you calculate the same for temperature? Information gain should be high, Akshay. Entropy should be close to zero. So my information gain is parent node minus the entropy of the child node. So this is the gain, right? Now let's calculate this for temperature. What are you guys getting for temperature? Let's have a look at hot. This is no, this is no, this is yes, and this is yes. So the probability of yes will be what? Will be equals to 1 by 2, right? For hot. Correct? Similarly, if you look at mild, this is yes, this is no, this is yes, and this is yes, and this is no. Right? So over here, the probability of yes will be 3 by 5, no will be 2 by 5. If you look at cool, this is yes, this is no, this is this. Okay, one more mild was there, and this is yes, right? So I hope you can calculate this, right? This will be straightforward. We'll not do this. You can leave it if you want to, because we'll have to calculate logs and all. But this is straightforward, right? Now see, like this, we need to calculate the entropy of all the columns. Select the one which is giving you the maximum information gain, right? And you can imagine that this is doing this for such a small data, if this is time consuming, then obviously doing this for a large amount of data, it is something that will obviously be very more complicated, right? So hence, this is something that obviously we don't have to do in Python. Whenever we are calling the decision tree function, right, it will actually do this for us. Okay. So now we will move on to random forest. So let's move to the theory of random forest now. All right. Now, random forest, we have understood the basics. Now, decision trees have been around for a long time and also known to suffer from bias and variance. We will have a large bias with simple trees and a large variance with complex trees, right? Now, we need to understand what bias and variance is, first of all, right? Now, see, a decision tree, right? If I let the decision tree grow, right, to the maximum possible extent, a decision tree does not have any limit, right? It can keep on growing until and unless all your data points have been classified into the correct classes, right? So you can have a decision tree which might keep on growing, right? Let's say this results in 2, this results in 2, right? Let's say this results in another 2, then this results in another 2, right? Let me take this to this level only. Now you can see that this is how these two got split, then these two got split further, these two got split even further, then this got split from here to here, this is here to here, right? This one is split from here to here, and this is from here to here, right? Now see, if I keep on letting the tree grow, what will happen is that if I do not limit the growth of my tree, right? Each and every data point might become a node, right? If you have 10,000 samples, right? If you have 10,000 samples, your leaf nodes might become equal to 10,000. So what the decision tree will do is that it will actually create customized rules for each and every row of your data. Now, is this something that you need? Or do you need a generalized model at the end of the day? I need what? I need a generalized model, right? One split will result in only two. Yes, Vishal. If you have only two unique values in the target variable, even if it is a regression problem. So these are binary decision trees, right? They will always result in two, right? So if I keep on letting, if I let the tree grow to the maximum possible extent, the tree will overfit, right? When a tree overfits, it can give you, so the, how do we find out whether a tree is overfitting? Overfitting will give you around, let's say, 100% on training, or let's say something lesser on testing. Now, this is overfitting, right? We have also something known as underfitting. Underfitting is what, let's say, you knew that you can get an accuracy of around 80%, but the model is giving 60% on training, right? And let's say because it general model gives, let's say, 65% on testing, right? So this is overfitting and this is underfitting. Now if you look at this, bias is this, right? Bias is basically the how much your model is giving the accuracy on the training data, right? So the training data accuracy is known as bias. And the testing data accuracy is known as variance. Now, if you analyze this, what happens is that in case of a decision tree, we get a high bias and a low variance. High bias means that your accuracy, so, right? Or so see, bias is basically the error, right? So if I get 100% accuracy, that means we get a low bias and we get a high variance. High variance means that the error is high, right? So when my model is overfitting, in case of decision trees, if I let the model grow to the maximum possible extent, it will overfit. When it will overfit, it will give me a low bias, that is my error on training data will be low, but the variance, that is the error on testing data, will be high. I don't want such a model, right? I want a model which gives me a low bias and a low variance. That is, both the error on training and testing data should be low. In order to tackle this problem, we have something which is known as a random forest. What a random forest does is that it tries to tackle the problem of bias and variance, right? Ensemble methods combine several decision trees to produce better predictive performance than utilizing a single decision tree. So we have talked about this, right? Okay. Now, this is what ensembling is. Now, if you see, I have my data, my original data set. I will divide this data into different training sets, which are randomly sampled from my original data set, right? Now, training set 1 will be a sample of data set. Training set 2 will be a sample of data set, and so on and so forth. On all of these different data sets, we will be making our different decision tree models, right? So if you see model 1, model 2 till model K, I will go ahead and I will combine the results. And this is something that is known as ensembling of a model, right? Ensembling methods, ensembling models are models which create multiple base learners, take their predictions and then combine their predictions in order to give you the final prediction. All right. So ensembles, we have talked about this, right? What we are doing over here, the example that I took before, right? The example was that you guys were predicting my age, and a single model, a single decision tree, it might have a high variance, because if you remember from our example as well, right? We were able to see that there can be models which are actually predicting my age to be very high or to be very low, because of which my accuracy or the overall performance of the model will be impacted, right? But if we went ahead and if we create an ensemble of the model, if we go ahead and if we group by the data together, right? Then if we group the predictions together, then generally my predictions will not be very off, because we are averaging out the predictions, when we are averaging out the predictions, right? In that case, what is happening is that in that case, basically, so there can be one model which is overestimating my age, right? There can be one model which is estimating my age lower as compared to what my age will be. So when I take the average, right, I am actually mutually canceling out some of the predictions, right? So that basically what it does is that it helps us in finding out a better and more stable model, right? And that is what ensemble methods are. We create multiple models and then we combine the predictions, right? Now, a random forest is a bagging model, right? Bagging means that you create a bag of models, right? You go ahead and create a bag of decision tree models and then you combine them, right? Random forest, a technique to perform to create multiple decision trees, right? Used when our goal is to reduce the variance of a decision tree, right? What was variance? Variance was the error in the testing data, right? I want to decrease the error in the testing data, right? So whenever, or not whenever, it is always, whenever you are building a machine learning model, your aim is to always reduce the error on the testing data. Your training error will by default, you take any model, you take any tree based model, and the more it trains, the training error will eventually become zero, right? But the objective is to simultaneously, as and when the training error is becoming close to zero, the objective is to simultaneously decrease the testing error as well, right? Now, if I give you another example, so let's say that you had to appear for a test in school, college, whatever, and let's say this test was on, let's say, trigonometry, right? There were 50 questions in your mathematics book. You went ahead and you memorized all the 50 questions, right? And you expected that there will be questions that will be coming from this particular these 50 questions only in the test that you are about to give, right? So during training, although you have spent time in memorizing the functions, right? You have not spent time in understanding the general concepts, right? Now, what happens is that, let's say during the test, your teacher, they go ahead and they restructure the way the questions were asked. These are the new questions in the test are not the questions from the 50 questions in the book, right? Now, if you would have remembered, or if you would have understood the general concepts, right? The general uh, rules, whatever the concepts might be, you will be able to tackle these questions. But if you have only memorized the questions from the 50 set of question bank, right, you will not be able to replicate a similar performance on the test, right? So this is what overfitting actually means. You are overestimating yourself. While training, you are getting an accuracy of 100%, right? But while testing, your accuracy becomes 80%. So this is what you are, while training, you were doing great, right? But when the actual moment came to perform, right, when the model was exposed to new data, when you were given the actual questions from the test, you were not able to perform, right? And whenever you are in such a situation, these bagging models will actually help you in reducing the overfitting. All right. Okay. So if you see, a random forest is a bagging model. Now see, ensembling can be anything. Ensemble can be, I can also do one thing, right? I can, let's say I go ahead and I do, let's say this model is a, I build a logistic regression model, right? Let's say the second model is a decision tree model, right? Okay. Let's say the third model is a, let's say, knife based model, right? So I can also do an ensembling of models by using different models. That will be an ensemble model. But in case of a random forest, I am not creating different models. What is random forest? Random forest is a model wherein I am creating n different models, but all the n different models are actually decision trees. How are they different? They are different because each and every decision tree is getting a different sample or a different snapshot of the data, right? So this is what the concept of bagging is. Now, the basic differences between decision trees and random forest. If we input a training data set with features and labels, it will formulate some sets of rules which will be used to make predictions. Random forest will randomly pick observations and features to build several decision trees. If you have 100 rows, or let's say if you have 1,000 rows and 10 columns, decision tree will take all the data at once. A random forest will take a subset of the rows and a subset of the features, right? If you ask the random forest to build 50 decision trees, 50 decision trees will be built on, let's say, then you ask that, okay, 50% of the rows and 80% of the features. So every decision tree will get 500 rows and 5 columns of data, which will be randomly sampled from the original data set, right? And then you go ahead and you combine. Mostly a random forest prevents overfitting by creating random subsets of features and building smaller trees using these subsets. Deep decision trees might suffer from overfitting, right? Now, when we are, see, another example, I'll give you two team options, right? One is a team option wherein India as a team, right? I have, let's say I talk about batsmen, I have Rohit Sharma, I have Virat Kohli, I have Shubman Gill, I have Shreyas Iyer, I have Ravindra Jadeja, I have KL Rahul. I'm not sure if I mentioned that. I have all of these, right? This is one team wherein I have all performers who are equally likely to perform. Or I give you another team which has Sachin Tendulkar and it has four other players who are not very stable, right? They might perform or they might not perform. Which team will you go ahead with? Now, this is, I think, an incorrect example. Let me give you a general example. Two teams of 11 players each. One team contains 2 star players and 9 uh, average players. The other team contains 11 better than average players, right? Which team will you go ahead with? Is it the first one or is it the second one? Second one, right? Why second? Because in case of the second team, you are not heavily dependent on only a couple of players. The first team might overfit. That is, while practicing, it might happen that you are performing well because your 2 star players are performing well. But the day of the match, let's assume, right? Maybe 8 out of 10 cases your star players are performing well. But let's assume about those 2 cases when it is the semi-final or final, when they fail. As soon as they fail, the entire team will fail, right? So isn't it better to go for a model which is giving you a similar performance on both training and testing, right? So that's what, when I'm building a decision tree, I am banking on only one set of model. I am only banking on Sachin Tendulkar. If he will play, India will win. If he will not play, India will lose. But if I'm going with a random forest, I am banking on a team of different experts, right? It might happen that out of the 11, maybe 2 might fail, but still the rest of the 9 are doing their job. And if they are doing their job, then there is a high chance that you are going to get stable output, stable results, right? Now, how does a random forest work? So algorithm creates random subsets with random values. So this, I believe everyone knows by now, that if you want to create 50 decision trees, you will create 50 random subsets of the original data. For each subset, you will create a decision tree. Each tree is built from a sample. It creates multiple decision trees and then merges the results, right? Sampling is done on the training data. Every time a new sample is chosen to build the tree, introduction of random. So this is the same topic, that same part, that every decision tree will be built on a different sample of data. This prevents overfitting of the model, which is a serious concern. This also yields much better performing generalized models, right? Now, let's say I built 50 decision trees. And the problem that I was solving was a classification problem. Let's say out of the 50 decision trees, 40 are saying that India will win and 10 are saying that India will lose. What will the final output be? Why are you saying win? Because if you take a vote, you will say that 40 models or 40 decision trees are saying India will win. So the majority vote goes to India winning, right? So that's why. So in case of a classification problem, you are going to take a vote of all the individual models, and the category that gets the highest vote will get the will become the output, right? Now, what if this was a regression problem that I was solving, right? Let's say I'm predicting the runs that Virat Kohli will score, right? Let's say the 50 models, they are giving me a range of runs in the range of, let's say, 40 to 80, right? Now, what will, in this case, what are you going to take as the output? Let's say one model is saying 40, other is saying 45, other is saying 89, then one is saying 110, one is saying 70. Logically speaking, you will take the average, right? That's what you did in my case. When we were predicting the age, we took the average age, right? So in case of a regression problem, the random forest will take the average, right? In case of a classification problem, the random forest will take the mode or the popularity or the most uh, commonly voted class. Important hyperparameters in a random forest model, right? So number of trees will be one, right? Now, what is a random forest? A collection of different decision trees. How many trees do you need to build? That will obviously be a hyperparameter, right? Do you need to build 5, 10, 50, 100, 500? That will be a hyperparameter. So that's correct, Sandhya. What kind of splitting criterion you were planning to use? So the same hyperparameter that was there in case of the decision tree, that will also be applicable over here as well, right? That is the entropy, Gini index, information gain, chi square, whatever, right? Depth of the decision tree. This will also be an important hyperparameter. That is how deep your different decision trees can go, right? So that will be depth. Any others that you can think of? There are two that will be very important. So max features will be one. What is max features? How many features do you need to consider, right? In each and every decision tree. If you have 20 features in the entire data, do you need to use 80% of those, 70% of those? Because that is something that will uh, tell you what sample or what percentage of the data you are passing to each and every decision tree, right? So we have max features, max depth, right? So almost, yeah, I think these are the important ones. So let's have a look at this. The first one is n estimators. That is the total number of trees that you want to create, that you want to build, right? That will be one. Moving on, we have max features. That is the total number of features that you will pass to each and every decision tree, right? So is the maximum number of features the random forest considers to split a node or to create a decision tree. So max features, this is something that ranges between 0 to 1. If you give a value of 0.5, it will take 50% features of your base data, right? If your base data has 10 features, and if you take 0.5, it will take 5 features, right? A minimum sample leaf is similar to what we had in case of decision trees. That is, how many minimum samples should be present in a node to be considered as a leaf, right? So determine the minimum number of leaves that are required to split an internal node, right? What this particular hyperparameter, right? Minimum sample leaf, how will it affect a tree? First of all, do you guys understand this hyperparameter? Are all of you able to understand what we mean by this hyperparameter? Minimum sample leaf. Let's say my tree is coming from above, right? From top, and this is one branch of the tree. Let's assume this is one branch of the tree. This over here contains, let's say, 10 rows, right? Okay, this is just one node I'm talking about. Let's say I take this further. I take this one step further and I divide this into two other nodes. Now, let's say when I divide this, this has 7 rows, right, out of 10, and this has 3 rows. Now, let's say if I divide this further, I'm just giving you specific, I'm not dividing each and every node, but just for this example's sake, I am splitting, keeping on splitting this, right? So let's say now we have one row over here, right? And let's say I have 2 rows over here. And then this will go further, and then this will split itself once again into one row each, right? So one row will be over here, right? And one row will be over here. Do you see a problem with this particular tree, decision tree? Do you see any problem here? So what it has done is that, right, it has actually built the decision tree to the maximum possible depth. So this decision tree will overfit, definitely. Your objective of building a decision tree is not to come up with rules for each and every row. Your objective is to identify generalized trends, right? Generalized rules. So what if I want to stop the growth of my tree as soon as a leaf node gets 10 rows, right? So this hyperparameter that you see, right? Minimum sample leaves. It tells you the minimum number of leaves that are required to, this is not right. It tells you the minimum number of samples that you need in a leaf in order to go ahead and split it forward. Let's say I say that the minimum sample leaf is 12. I'm saying that you can only split a leaf if it contains 12 rows in itself, right? Now, as soon as my decision tree will come over here, it will see that there are 10 rows. 10 rows are less than 12. So what it will do is that it will stop the growth of the tree over here only. It will not let the tree grow further beyond this point, right? The growth will be stopped over here, which will actually contain overfitting. Does that make sense? Minimum sample leaves, meaning minimum number of samples that should be present in a leaf in order to split it further. We have considered the purity to end the split. So decision tree or splitting is a hungry process, right? It will keep on doing it until and unless it achieves 100% purity. But where to stop? If you don't stop the growth of the tree, right, it will grow to the maximum possible extent, because when it grows to the maximum possible extent, if you see over here, right, each and every row has been assigned to a node, which is not our objective, right? Our objective is to increase the purity, but our objective is not to increase the purity by creating a bunch of rules for each and every row. We are looking for general set of rules. We are looking for that, okay, if let's say if temperature is less than 20 degrees, then it is going to rain. We are not looking for if temperature is in the range of 19 to 20, it will range. If it is 18.5 to 19, it will not rain, and so on and so forth, because that is overfitting. You are clearly overthinking, right? So we don't want that. So although the criterion of splitting is purity, but that is a hungry process. Splitting of a decision tree on the basis of purity will be hungry, because all it will want to do is that it will want to increase the purity of the nodes that it is coming up with, right? But then you will have to assign some kind of a criterion beyond which your splitting should stop. Okay, so these are some of the hyperparameters. Once again, these are not all. There are many hyperparameters, many other hyperparameters as well, but these are the important hyperparameters. Once when you start building these models, that's why I keep on saying is that whatever you get from here, go ahead, take this and try to implement this on some case studies, on some data sets that you can get on the web, right? And try to experiment around with all the different hyperparameters, because then only you will be able to understand the impact of all of these. Now, there are certain hyperparameters in for these tree-based models which help you in increasing the model speed, right? So reducing the time that it takes to train the model, right? So one parameter we have is n jobs. N jobs is a parameter which you can assign different values to. If you make n jobs equals to -1, right, it will initialize parallel processing. So parallel processing can only happen if your processor supports that. Let's say you have a GPU, or you're working on cloud, or you have a distributed computing platform. In that case, if you give n jobs equals to -1, then the different decision trees that you are building, right, they will be built parallelly, simultaneously, which will make the model training process fast, right? If you give n jobs equals to if you give n jobs equals to +1, then it will turn off parallel processing, right? Random state, I hope everyone is able to understand this. It will make the model's output replicable. That is, each and every time the same output will be generated, right? Why do we need this? You might get an accuracy of 99% while training. You might go to your seniors and say accuracy is 99. You run it again and the accuracy drops to 98, 97. They might question you why this is happening, right? So in order to replicate the same performances each and every time, we give a random state value. It can be any random number. As long as you give the same value, the output will always be the same. All right. Now, the third one that we have is out of bag score, also called out of bag sampling. OOB is short form for out of bag. Now, this is a cross validation method in which about a third of the data is not used to train the model and can be used to evaluate its performance. Now, while we are building decision trees, right? Now, let's say you have given that 70% of your rows are going to go as an input each and every decision tree. So when the decision tree would have been built, after that, to test the out of bag or to test the performance of the decision trees on a data which it has not been exposed to, it will take the remaining 30% rows, right, which were not exposed to the model while training. It will take those 30% rows and it will calculate the model's performance there. Now, let's say if on 70%, the decision tree, the single decision tree is giving you an accuracy of 80%, right? Then for the remaining 30% data as well, the accuracy should be in the same range, right? That's where you will get to understand whether the tree is overfitting or whether the random forest is overfitting or not, right? All right. So I think this is the same example, but just that they're saying that each and every there will be different decision trees that will be built. Now let's say if I build these three decision trees, from two I'm getting the output as yes, from one I'm getting the output as no. So the final prediction will be that yes, the game is going to happen because if you take a vote, yes will get 2 votes and no will get 1 vote, right? And this is it on the theory. Any questions? So let's get started with the hands-on then. Now the data that we'll be working with today is churn data, this customer churn that we have, right? So if you have a look at this data contains customer IDs, and then it contains lots of customer related features, right? That is gender, whether the customer is a senior citizen or not, right? Whether it's a partner, whether they have a partner or not, that is whether they are single or married, how many dependents, what is the tenure of the customer with this company, right? So this is telecom data basically. So in this data, if you see, each and every row is a customer, right? Now this first customer is a female customer, right? Senior citizen, no. They have a partner, yes. No dependents. Tenure, 1. This person has been with this company for 1 year. Do they have a phone service? No. Do they have multiple lines on phone service? No. Do they have a net connection, internet? Yes, they have a DSL connection, right? Online security, no. Online backup, yes. Device protection, they have not opted for that. Tech support, they have not opted for that. Streaming TV, no. Streaming movies, no. Contract, they have a month-to-month contract, right? They are paying the bill each and every month. So there can be different kinds of contracts that we have. This is US data, right? So the contract over here is month to month. Paperless billing, yes, that is true. So they are not getting a bill, paper bill. They have opted for paperless billing. Their payment method is electronic check, and their monthly charges are $30, close to 30. Total charges are the same, and then we have the target variable, that is churn or not, right? That is yes or no. So this customer has not churned. Similarly, if you look at, let's say, this particular customer, this customer is a male, senior no, partner no, dependents no, tenure is 2 years. And if you look at this, you will have all the factors for this customer as well, right? So on the basis of this, we have the target variable, which is churn. Now we will be reading this data, and then we will be building our decision trees and random forest models on top of this data, right? Right. So we will also import decision tree. Then we will go ahead and we will read this data. My data is in my Google Drive. I am running this code on Colab. Hence, I'm using this piece of code. I am using these libraries, Google Colab. I'm mounting the drive and all. If you are running this code from your locally hosted Jupyter notebooks, you can comment this out. you can uncomment this and you can give the path to your file over here, right? But since I'm running this on Colab, I need to give all of this. These two lines are standard. For the third line, I'm just giving a pd.read_csv, and then I'm just giving the path to my drive, right? And this is the customer churn CSV. I will run this. The first time we run this, it will ask for authentication on Google Colab. Since I have already run this, it will not ask for that. So you can see that it has been able to read the data, and now I'll do a data.head, and you can see that the data that we were seeing on the Excel has been read over here in Python, right? Just do a basic sense check over here. All the columns are there. All the values that we were seeing in the Excel are also visible over here. Nothing has changed, right? The quality of the data looks to be same, right? We will go ahead and we will check that, but still looks like everything is in order, right? All right. What do we need to do next? We need to explore this data, right? So I will do a basic EDA over here, but ideally for you, so let's have a look at the columns, the different columns that I have. This I'm doing just to check that all the columns that I had seen in the Excel, do we have those or not, right? So you can just do a quick check, and all the columns that we were seeing in the Excel, right? We have those. So here, if you see, we had how many? We had 21 columns over here. If I go ahead and if I take, let's say if I convert this to a list, and then I take the length of the list, I also get 21 columns, right? So looks like everything is there. Every column that we had seen in the Excel is over here, right? At times it can happen while you are reading a data, maybe some of the columns might be corrupt, right? So Python will not read them automatically. So this is a good practice to do, right? Then we'll check the data types. What are the data types of all the different columns? So you can have a look at this, right? Now, customer ID, gender, all of these are object, partner dependents, object, phone service, till paperless billing, payment method is object, monthly charges is float, and rest all are objects, right? So most of the data over here in this case are of the object type. Object meaning that it might be categorical in nature, right? All right. Okay, what other functions could I have used over here? What other functions could have been there, which would have helped me in identifying the data types apart from this D type function? So info will give you two things, missing values and what is the data type. One thing we know, there are no missing values, but then along with that, we are also getting the data types, right? Now, I want you guys to go through all of this columns one by one and just see if the data types corresponding to these columns make sense or not. Because you have visualized this data in the CSV, you should be able to remember, or if you are not able to remember, go back to the CSV and see whether the data types that you are seeing over here are correct or not. What do you guys think? Are there any uh, anomalies that you are able to see? Anything that looks incorrect? So, right, so if you look at total charges, right, I think all the rest look fine. For senior citizen, Saran, that's fine, right? If you look at the senior citizen column, it is 0 or 1, but Python has automatically read that as a categorical column. So that should be fine. But if you look at total charges column, which is towards the end, right? This column looks to be this column looks to be object in nature, right? If you see total charges, monthly charges are coming out to be float, but the total charges are coming out to be object. Now, this is something that you would have been able to catch only if you would have done two things. That is, first, you would have had a look, you would have had a basic sense of how the data looks like, what are the different columns. Because now that you understood that total charges is a numerical column, what is the definition, you were able to identify that object is incorrect, right? And secondly, then when you went ahead and when you check the data types, you will have to go through each and every column one by one and see if every column has a correct data type or not. So here we are able to identify that this is incorrect, right? Now, why this is incorrect, if you look at this, there are no null values over here in the monthly charges column. But over here in the total charges column, you can see that there are blanks, right? And there might also be some incorrect values that might be populated, right? So there are lots of values. Now this is a continuous variable, but it is problematic, right? Going through this and trying to identify which values are correct or which values are incorrect, that can be a very time consuming process, right? Here we have only 8,000 rows, right? 8,000, 4,000, whatever, right? But in our actual data, we might be having rows running into millions and billions. So you cannot scan through the entire data. So what we do is that we have a function that is, I will forcefully convert this column into a numeric column. How will that happen? I'm doing a pd.to numeric, right? And I'm passing this column over here. Now, if I would have not passed, now let's look at this, right? So now let's say I do not pass errors equals to course over here. What will happen? It will give you an error. Why? Because at a given position where it is finding a non-numeric value entry, it is not able to convert that to a numeric number, right? So hence we have the option of errors equals to course. So when I do errors equals to course, what will happen is that it will actually drop those rows from your data, right? Any rows which or any rows coming from this column which are not numeric, they will be taken away. And now if I run this, if I do this, you will see that now we are able to convert. So we are forcefully converting this into our numeric data. Now, when I do errors equals to course, what will happen is that all the values which were null, they will actually forcefully be converted into zero, into a numeric value, right? So that's what has happened over here. That is for all these observations, right? These ones, if you see, for these 11 or 10, these 10 observations, it would have forcefully converted them into the number 0, right? And now if I once again go ahead and do a data type check, you can see that both monthly charges and total charges have become numerical in nature. So let's check this as well. This is the data.head. Let's look at the shape of the data. I have 7,043 rows and 21 columns, right? We will go ahead and we will coerce this. We will convert this into numeric. We will once again do this. This is fine. And once again, I do a shape. And you see 7043 only, right? So the shape of the data will remain the same. What it does is that any non-numeric value, right, it will automatically convert them to 0. Conversion of non-numeric or null values to numeric will affect further analysis. That's something that you can analyze. Now see, over here, what I would have done is that what this code will do is that this will manually convert these into 0. All these values will become 0, right? But what do you guys think? What could have been a better thing to do over here? Okay, have a look at the entire data first, right? Now look at the total charges column. See if you can extrapolate this column from some other details. So this is what I'm talking about, right? You will have to be smart. If I take monthly charges column and if I multiply this by the tenure, what will I get? Okay, have a look at this. This is, I have taken the monthly charges column and I have multiplied this by tenure, right? Now I want you to compare. Now let me take I will take this divided by the total charges, right? If I do this for all the values, right? Now what do you see? Anything that you are able to understand from here? What am I doing? Any idea what I'm trying to do over here? 490, it will show an error. If I focus on only the blanks over here, it will not give any values, right? So that's correct. But for others, can you think of, or are you able to extract any insight from here? Now, approximately these two values are very similar, right? See, when someone is going for monthly billing, maybe they are being charged more. When someone is going for yearly billing, maybe they get a 1%, 2%, 5% discount. But in all the cases, you will see that this value and this value will be very, very close to each other. 1889, 1936, 108, 107, 1840, 1900, right? Now, what if I go ahead and for the columns which are having missing values in total charges, instead of imputing these values with blanks, what if I impute these values by, right, this multiplied by the your tenure column? What if I do this for only these entries? Now you can see over here why I am getting the error, right? We are able to take the error because the tenure for these customers is coming out to be 0, right? So these are those customers for whom the tenure is coming out to 0. Because the tenure is coming out to be 0, the total charges is coming out to be 0 as well, right? Now, what does it tell you? What can we do next? If we don't have any tenure and we are seeing that the monthly charges are these, the best estimation is what? That the tenure will be easy way is what? You can impute the total charges by the monthly charges for 1 month, because these are existing customers. If these customers have not churned, they are new customers, right? If their monthly charge is 52, the bill that will be generated for them will be what? 52, 20, 80. So all you have to do is that you have to do this. Now, this is, I am saying that this is sensible missing value imputation that you are doing. You are looking at the data, you are seeing what values are missing. Is there any relationship of the missing values and all, right? And through that, we are trying to impute these missing values. Now, dropping is the most easy way out. If you want to drop as well, I'm not saying that that is incorrect, but generally you will not drop until and unless you are able to figure out some way of imputing the missing values, right? Either all the values being 0 is also fine, or you could have imputed these missing values by using the monthly charges column. Okay. But I think 0 should be fine. So we will go ahead with the value 0 only, because till now, these customers have not paid any bill. Hence, we are getting a total charge equal to 0, right? So let's move forward. Let's check for missing values now. So obviously there are no missing values because we have checked info before. There are missing values, right? Why do I see missing values now? Earlier, we were not able to see any missing values, but now we are able to see missing values. If you see previously, I was not able to see any missing values, right? When we had done this info, there were no missing values that we were able to find. But now we are getting missing values. Why? Because we changed the data type, and what errors equals to course has done is that it has imputed those values by nan, right? I was incorrect when I said it will impute that by 0. It has imputed the values by nan, right? So hence I am getting 11 missing values over here. So what we'll do is that we will go ahead and we will, if you want, you can drop. If you want, you can do a fill in as well, right? That's totally up to you. Now there are 7,043 rows. You could have dropped this data as well. Either you can do a fill NA or you can do a drop NA. That's totally up to you, right? So I'll give you both the codes. Choice is yours. You can do as per you like, right? You can do a fill in as well. If you will give it as blank, it will impute by value. All the missing values will be imputed by 0, right? What I am doing over here is that I am dropping these entries. Why am I dropping these? Because these are all new customers. They have only joined me recently. right? The tenure is equal to 0 months. When the tenure is equal to 0 months, I don't have any concrete data, and creating a model of attrition, creating a model predicting churn using customers which are totally new, right, is not correct, right? So hence we go ahead and we drop this. When we drop this, after dropping, you can see that now the shape has changed. We have 7043 previously. Now we have 7032 rows only, right? Now we will drop other columns as well. Customer ID is a column that is not required, right? So it is a one-to-one mapping. So I'll be dropping customer ID as well. So in place equals to true. I don't have to assign this back to the same data frame. Let's describe this data frame. Now here I have included object, right? So it will describe all the object columns, right? All the categorical columns. And if I just go ahead and if I use the simple describe function, it will automatically take the numerical values and it will discard all the categorical values, right? So you can look at this over here. Senior citizens, there are 16% senior citizens. On an average, the tenure is around 32 months, that is close to 3 years. Monthly charges are around $64, right? And your total charges, average total charges are around $2,200, right? If you look at the categorical columns, your gender, male has a higher weightage. There are more males as compared to females. More number of people are not married. More number of people have no dependents. Phone service, around 6,352 people in this data have opted for phone service, right? Internet service, 3,000 people have opted for internet service. Out of that, the topmost occurring value is fiber optic, right? So you can see this, that for all the categorical variables, if you want to use the describe function, you can use a include equals to object, right? And then obviously there are lots of categorical columns. So what we will do is that we need to do label encoding over here, right? We need to manually convert all of these categorical variables into labels. Now, either you could have used label encoded directly, right? But what I am doing is that I am assigning for each and every column, I am going ahead and I'm giving the mapping manually, right? Manually, because if let's say in some case there is a particular order or sequence that you have to follow, you can do that, right? So you can see that for all the categorical variables, for this one, I am just mapping a dictionary. For all the values which are yes, they will be converted to 1. All the values which are no will be converted to 0. If I would have done label encoding automatically, right, by using the function, it might have happened that no might have become 1 or yes might have become 0. So just to make sure that the labels are logical and they make sense, we have gone ahead with a manual mapping, right? Although it does not make any difference in the model performance and all, but from an understanding point of view, it might become confusing, right? Because generally, yes, we will assign to value 1. True, we will assign to value 1. False, we will assign to 0. No, we will assign to 0, right? So if you see, we have gone ahead and mapped each and every variable one by one. You can have a look at this. And want to know why can we assign 0 to both, Kaushik? I was explaining this, right? That no phone service and no, there is a difference, right? No phone service means that the customer doesn't even have an option of choosing between security, right? Between, let's say, all the extra services that you need, right? And a no means that the customer has the option, but the customer has not opted for that option. So no and no service, no phone service, no, let's say, internet service and all, there is a difference between these two values. This will be nominal only. Okay. Now, after doing the label encoding, you can see that this is how our data looks like, right? Now our entire data has been converted into a numerical form, right? And now we can feed this data to any mathematical model, right? Let's move on to the visualization. Let's have a look at, I'll just do a basic visualization of the target variable and a correlation matrix. So you can see here the value counts of the target variable. So if I multiply this by 100, 73% customers have not churned and 26% customers have churned. If you want to plot this in using a bar plot, you can do this as well, right? So you can see that around 73% customers not churned, 27%, close to 27% customers are churned, right? All right. Now I can also get the heat map. I can also get the correlation matrix, which can be given in the heat map, right? So for that, I just call the core function and pass it through the heat map function, which will generate the correlation matrix. I've given the color map as red, yellow, blue. If you don't give this, it will take the normal red, yellow, whatever heat map color it has, right? So if you give this annotate equals to true, it will write these values. If you make it as false, it will not write. Format, if I make it as 0.2f, you will see that it will print till 2 decimal places, right? These are basics, still I'm explaining, but let me reduce the size, right? So you can see that this is the heat map. Can you give me some examples of variable which are highly correlated? Right, so lots of variables now, tenure, total charges, right? If you look at all of these variables are related with monthly charges, internet service, online security, and all of these. But the good thing over here is that we are building decision trees random forest, right? So even if variables are correlated, it's fine, right? Unlike linear regression, logistic regression, wherein model performance will be impacted, over here, it does not impact the model performance as much because we want to build different decision trees, which will take a snapshot of the data, right? So if it's okay if the variables are correlated, it should not be the case that variables are correlated to, let's say, 99% or 95% greater than that, right? That means that essentially the same information is there. That should not happen. But other than that, even if you have variables which are decently correlated and you're building tree-based models, it should not pose too much of a problem, right? All right, so let's get started with the model building then. All right, now if you see over here, till now we had not transformed the target variable, right? The label encoding that we had done, we had not included the target variable over here. So we need to encode the target variable as well. So we will do that over here. So churn was our target variable. So we map the values yes to 1 and the values no to 0, right? So we do this. Then we divide our data into our features and the target variables. So the usual steps that we follow. So X becomes my all set of features. So what I'm doing is that I'm selecting all the columns, but the last column. The last column is the column churn, which is my target variable. And in Y, I am only selecting my last column, right? So I do this. And now if you have a look at X and Y will only be the target variable. I can show you the shape. If I show you the shape of X, it will have 19 columns only. And if I show you Y will be a single column, right? Which is your target variable. Next, we need to divide our data into training and testing. So I call train test with function, 20% in testing, 80% in training, and I run this, and this will split my data. I've given the random state as 0. So random state as 0. Each and every time, same rows will be going into training and testing, right? If I show you the shape of X test, it is around 1400 rows because I had 7000 in my data and 20% of that will be testing. And if I sum both X test and X train, you will see that you get the overall 7032 rows that we had in our data, right? So these are the usual steps that we follow. Now we will get started with the model. So first we will go ahead with the decision tree model. So for the decision tree, right, we just call the decision tree classifier with the standard parameters, and we pass our training data X train and Y train. So first step, we need to instantiate the model object, which we are doing over here, tree.decision tree classifier. This we are assigning to a variable CLF, right, which is the short for classifier. I'll do a CLF.fit. When I do a fit, I'm passing the training data. That means that the model training has started, right? And then once when the model has been trained, I go ahead and I use the predict function to get my predictions on the training data and the testing data both. And I am saving these values as y train pred and y test pred, right? The predicted values. So I run this. This will run super fast. And then I print the accuracy. Accuracy score is a function which will give the accuracy of the model. And I need to pass the predicted values and the real values of the target variable actual. So the training data accuracy and the testing data accuracy I'm printing together. And you can see that over here. This gives me a 99% close to 100% accuracy on training and only 73% accuracy on testing. So let's try the random forest model. So in a similar way, I will import the random forest classifier, instantiate the model object here, right? Uh, we go ahead and we do this, and let me just make the same code. Right. So if you see this, this is the same code, exact same that we have done. So I fit the model random forest classifier on the training data, and I get predictions both on my training and testing data, and then I print the accuracy of both the models, right? Now see, these are bare models. So obviously with the bare models, I'm just running this to see which model is performing better out of these two. Hyperparameter tuning we are going to do at a later point of time. But the hyperparameter tuning we will only do for the model which is doing a better job, right? So out of these two, decision tree and random forest, which one do you think is doing a good job, doing a better job? Random forest, right? Yes, the random forest model is also overfitting, but still you can see that the testing accuracy here was 73. Here it is almost 6% higher. So this all we have printed. So all of this is not required. We have already printed this. All right. So from here, from these bunch of codes, what we have gotten is that between the decision tree and the random forest model, it is the random forest model which is performing better, right? All right. So now for the random forest model, we will be moving on to the hyperparameter tuning, right? Now, how do we do the hyperparameter tuning? Well, let's try to have a look at that, right? Okay. Now there are different hyperparameters that we have, right? We have gone through these. We have bootstrap, max depth, max features, sample leaf, sample split estimators, and all. We will be trying to optimize most of these hyperparameters, right? Now, I'll come to this piece of code later, but let's try to understand. Now, see, in order to optimize the hyperparameters, how can we do that? Now, uh, every hyperparameter, right? If I look at each and every hyperparameter, that is number of trees, max features, the depth of each and every tree, I can iterate each and every hyperparameter through n number of values, right? So what will you do? Will you run the model 200 times? Let's say one model you run with number of trees equals to 5, other you run with 10, other you run with 15, 20. Do you think that you should do this manually, or there should be an automated function which will help you in doing this, right? So what we do is that we create a grid. This grid will have all the different possible values of the hyperparameters that we want to test, that we want to experiment with, right? So if you look at this over here, for each and every hyperparameter that I want to play around with, right? That I want to play around with the values, what I'm doing is that I am creating a list of possible values that they can take, right? Starting with n estimators, right? If you see, I have my n estimators as a list, which is starting from 200 going till 2000 with 10 values between. So 200, 400, 600, 800 till 2000. Max features is a hyperparameter which takes on two values, auto and square root. Auto is automatically the model will find out how many, what is the fraction of features that it needs to consider. Square root is that if I have 19 columns, it will take the square root of that. That is close to 4 columns will be given to each and every decision tree. Similarly, max depth, I am iterating this from 10 to 110 with 11 values in between. That is 10, 20, 30, 40, 50 till 110. Minimum sample split, this is the one that I have explained, 2, 5, 10, minimum samples leaf, 1 to 4. These are the values that I'm giving, and bootstrapping, either it will be true or it will be false, right? So looking at these, right, can you give me the total number of combinations that the model needs to try over here? Now see, if I give you one by one, one by one, if I run this, each and every, this will not run. So if I show you the length of the first hyperparameter, that is n estimators, it will have 10 values, right? If I give you the length of, not this, if I give you this multiplied by this, so you will get 20 combinations, right? So you can see what I'm doing over here is that I am multiplying by the length of each and every hyperparameter that I have, right? If I go ahead and if I multiply all of these values, you will see that there are around 4,000 combinations, 4,000 possible combinations that we need to try in order to find out the best set of hyperparameter values. So see, for n estimators, if I show you n estimators, right, I will try these different values for n estimators. Okay. For max features, I will be trying these two values, right? Max depth, I will be trying all of these values. Now, for each and every hyperparameter, if these are the list of values that I have, in order to find out the best. Now, let's say if I have max depth as 10, max depth of 10 will be iterated with n estimators equals to 200, max features auto, right? Minimum sample split 2, minimum leaf 1, and so on and so forth. Then the same iteration will happen for max depth equals to 20. Does this make sense? Every permutation and combination will be tried, right? So if you find out the total number of permutations or combinations, they will be how many? They will be 3960. Why? I am multiplying by the length of each and every hyperparameter values, right? So n estimators will have 10 values. 10 multiplied by 2 will become 20. 20 multiplied by 11, right, will become 220. 220 multiplied by 3 will become 660. 660 multiplied by 3 will become 1980. 1980 multiplied by 2 will become 3960. Correct? So these are the total number of combinations that you will have to try in order to find out the best hyperparameter for this model. So that's what I'm just uh, trying to show over here, that if we multiply all of these, we get 3960 combinations, right? And that is what we have defined over here, right? We have created a list of all the values. Through this, I have defined a dictionary. This dictionary is a random grid, right? Here, if you see the key value pairs, I have given n estimators. The key is n estimators, and the values are all the values that your n estimators can take. That is 200, 400 and all. Max features, all the values that it can take. If I run this and if I print the random grid, you can see that this is your overall grid that we have, right? These are all the possible combinations that the model will try one by one. Okay. Now see, you can see that there are 3960 combinations. If you run this on actual data, assuming that one model takes, let's say, 10 minutes to build, 10 minutes to run, it will take 3960 into 10, that is 39,600 minutes, right? If I do 39,600 divided by 60, you will get how many hours? 660 hours, right? And if you do 660 divided by 24, you will get 27 days, right? So close to 1 month you will take for training the model. Do you think that you will have this much amount of time while while building a model? No, right? So that's why we have something known as randomized search CV, right? So what randomized search CV does is that, let me show you this. Now, randomized search CV is a technique which what it will do is that it will take this random grid, right? And through this random grid, it will intelligently iterate through all the different possible combinations. You will have to tell how many iterations you need to run, right? Let's say there are 39,600 in total, but you only have the time to run 100. So randomized search CV will intelligently run only 100 combinations, right? How will it do that? So let's say it started with 200 trees, right? 200 trees, let's say it realized that the accuracy was 80%. Then what it will do is that it will run the next iteration with 2000 trees. That is the next maximum value. And let's say through that, it realized that the accuracy was 90%, right? Now it will try to come to the middle, right? So it will try to guess the best possible parameters. Randomized search CV, first of all, it will happen in a random way, but this random selection will be intelligently driven, right? So on the basis of that, what happens is that we don't go ahead and we run all possible combinations because that will be more time consuming. What we do instead is that we call this function randomized search CV. And if you have the bandwidth of running more iterations, let's say you can run 200 iterations, you can do that, right? Then what will happen is that you might get the exact set of values. But with randomized search CV, you might get to a very you might get to the ballpark, right? You might not get the best possible hyperparameters, but you might get closer to the ballpark, right? So that's what we do in randomized search CV. If you look at this over here, what I do is that I call the random forest classifier, and then I do not train the model over here. I do not pass any data. Before doing that, I instantiate a model object of randomized search CV. In randomized search CV, I pass the random forest model. Till now, there has been no data that has been passed to the random forest model, right? Then the second parameter that I pass is the random grid. That is the parameters on which this particular RF model will run. Third hyperparameter I pass is the number of iterations. I say that do not run 3960 iterations, right? Which we can see over here. I say that I only have the time to run 100 iterations, right? The scoring I give as negative mean square absolute error. This is just to look at the performance of the model, right? So this is a standard value that you can give. I give cross validation as 3, right? Cross validation, it will divide the data into 3 folds, use 2 folds for training, 1 for testing. Verbos equals to will print out the performance, right? This particular line that you are seeing, this you will get from verbos equals to 2. Random state 42, n jobs equals to -1. If you remember, parallel processing will be true. Return train score for the best possible model. Whatever model is coming out to be the best, it will return the training score, right? Now, if you will run this, I'm not going to run this because this takes around 50-60 minutes to run, right? So I have run this before. Run this with n iter 100, increase that to 200, 500, and you will see that the time will keep on increasing, right? But once when I would have run this, right, I will get in this RF2 parameter. So I think this notebook would have disconnected. Uh, I will not run this again. I have the best model results over here only. This is the best model. So I will take this. You can run this on your own time. And once when you run this, you run the best params and all, right? You will get the okay. So you'll have to run this again. I think this would have the details would have been dropped off. But once when you run this, right, and you run this code, this will give you the best params. Anyways, the best params that we were getting from this model, right, before I had run this cell, the output that you were seeing over here was this, right? I'll just comment this out and then leave it. So the best parameters that we were getting from this randomized search CV was n estimators as 2000, that is 2000 trees. Minimum sample split were 10, minimum sample leaf were 1, max features was square root, max depth was 10, and bootstrap was false, right? Now, if I run this random forest classifier with these models, right now, I know why this is not working because we have run this already, right? RF2. So this will uh, overwrite over here, right? So that's why. So once when you run this again, right, you should be able to get the best parameters. Now I have rerun the model. I have rerun the random forest model with the best set of hyperparameter values, right? And now if we go ahead and if we check the model performance using the same code, let's take this only, right? Okay, so now if you see, if I run this, all right, so you can see one thing that first of all, the testing accuracy has increased slightly, right? It has increased by close to 1%. Your training accuracy has come down. So your overfitting has actually reduced in the model. The testing accuracy has not gone up by a very high margin, because if you see here, it was 79%. And here after running your hyperparameter tuning, it has become around close to 80%, right? So 80%, 79%, only a 1% change, but that's fine. Still, we have been able to increase the accuracy by close to 1%, and your training accuracy has come down. That means that the overfitting aspect of this model has actually gone down, right? This is already run, so I will remove this, right? All right. So any questions till now? So see, this is how we actually do the hyperparameter tuning. Now in the hyperparameters, right, you can play around with different sets of values. It's not that this is a given, right? I have only given you an idea of how do we do this. Now you could have also done, let's say, started with 100, gone till 500, given a gap of 50, right? In between 100, 150, 200 and all, right? Now all of these things you need to do. Hyperparameter tuning is basically a very manual process. You will have to try different combinations again and again, right? Only then you will be able to identify the best possible model. Now over here, the 80% that we are getting, it's not that this is it. You can increase this even more, because these hyperparameters that we are getting, right, this once again is coming from randomized search CV, right? So this can, you might go ahead and you might try, let's say, values slightly above or slightly below, and try to see if the performance of the model is actually getting better or not, right? Okay, then evaluation of the model. One thing that we get from these tree-based models is something known as feature importance, right? So if you do, if you call the model object and call the function feature importance, it will pass you a list of weights, right? Now these list of weights are in the same order as your data, right? So what we do is that we create a data frame by combining the feature names and the importance that we are getting from feature importance. So I do this. So you can see that I am dropping the churn variable from our original data and all. I create a new data frame df. Feature will become my column names, and importance will become the importance that we are getting from here. And after running this, if I run this, you can see that these are the important features, right? These are not sorted. I can go ahead and I can sort these values by importance. So if I sort these values by importance, you can see that these variables are coming out to be important in predicting the churn. So you can see that tenure is the most important variable. Contract is the second highest. And this is what we were seeing, right? That these variables were correlated as well, right? Total charges, monthly charges, all of these variables in this order are coming out to be important. Variables such as partner, gender, dependents, all of these doesn't look to be important from a modeling point of view, right? If you want to plot this, you can also plot the feature importance. So I'll just go ahead and I'll plot a bar plot. X-axis is my feature, Y is my importance, and you can see that this is how the feature importance are varying, right? Now, if you want to rerun this model by eliminating some of the features which are not important, you can do that as well, right? So in this way, your tree-based models can also function as your variable selection as well, right? You can use them for feature selection as well, right? So this is the feature importance. And also we can generate the classification report. So as from sklearn.metrics, all of these are standard, right? We have used this in logistic regression as well. If I pass the values for, so let's say this is my Y test spread. So this is the classification report for our testing data. And similarly, if I take this and if you want this for training data, you can get train and train over here. And this is the classification report for the training data. Here you will see everything, the precision and recall. For training data, the precision for class 0 is 90, the precision for class 1 is 83. For testing, it is 84 and 65. The recall is 91 and 95, 70 and 50, right? So you can have a look at this. Overall accuracy, you can see 80% in the testing data and 88% in the training data, right? And this is generally all the things that we do, right? We just look at the model performance, and on the till now we have covered only 3 classification models: logistic regression, random forest, and decision trees. Now, if you want, you can also apply logistic regression model over here and see if it is able to perform better than these 2 models, right? Then ideally towards the end, you will go ahead and you will select that model which is giving you the best performance, right? Max feature, Vidya, apart from square root and auto, right? You can also have uh, values in the range of 0 to 1. So instead, along with this, right, you can also give, let's say, 0.5. 0.5 means it will take 50% of the features. 0.7, it will take 70% of the features, right? Now, if I change this, you will see that max features has changed. Now, if I run this again, this will now run for 50-60 minutes and it will try out all the different values, right? So just play around with all the different values. Now, this will obviously run for a long amount of time. You can see 100 candidates, 3 folds, 300 fits, right? So this will take time to run. All right.
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampark IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
Going to start the unsupervised learning, which is known as K-means clustering. What is K-means clustering? Before I get into K-means, I hope you recall what is unsupervised. So far we were doing only supervised learning, but if I may ask, what is unsupervised? Use of unlabeled data, right? That's correct. So see, remember when we were looking at supervised learning, we had a data structure like this. Just hold on. So let's say you used to see a table and used to have different variables, right? Right? X1, X2, X3, X4 up to Xn, n variables. And then you used to have a Y. This Y we call the labels, right? That actually helps you. So this is how we say level data, right? Y stands for your target or response. So in supervised learning, used to have this, but in unsupervised learning, this guy will not be present, right? This will not be there. Okay, it's only the X values. So this is what you see in supervised learning. So let me write here. This is supervised learning. And if I just make a copy of it and I say this guy will not be there. So let's say this is X5 dot 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 Xn. You got it, guys? This is X5. Just trying to, improvise that. Yeah. Then this becomes your unsupervised learning. So there are no targets, no labels. Okay. Means no labels. Implies unlabeled data. Cool. So you guys have an idea. So when you are in such situation, right, under unsupervised learning, right, uh, you try to group data into clusters. So it's more like you're trying to find patterns since data has no levels. So you find patterns on the basis of similarity and then try to group them into cluster. So maybe I can also write it down. So in unsupervised learning, there is no output variable to guide the learning process. Data is explored by algorithms to find patterns. Given that data has no levels, the algorithm identifies similarities on the data points and groups them into clusters. Okay. So let's try to understand within that there's a concept of k-means clustering. Okay. So k-means clustering, K stands for number of cluster and means stand for averaging the data point position to find the center of the cluster, right? That's your mean. So k-means clustering means you're trying to divide the data, right? Basis the similarity into groups. So let me take a very simple example of demographic data. So demographic data, when you go and visit a mall and you go to a store like Zara or something like, some similar kind of stores, they take some of the data points from you, right? They can collect the customer data and try to divide the customer into different segments. So again, this brings me to this topic of that, when you're trying to go to a certain store, you will be, giving some data to different, different stores. They will be taking your, name, age, gender. They might ask you some personal questions also, like how much your salary and all those things, and then try to, come up with down the line, you will get a mail on a mail, some marketing campaign is happening and you are getting informed, right? So that's what we say customer segmentation on the basis of similar trait. Okay. To solidify this conversation, I can take an example of, let's talk about how to say, have you ever gotten an ad or a call or any message for buying Audi? Anybody in this session? Audi or Merc? Merc is like Mercedes. Never ever, right? I know why. Because they know that we are not their customers, right? How they know that? Because they have the data for us. In India, too, it's very easy to get the data. बहुत आसान है. Now, if you talk about those kind of examples, right? Students never get called for credit card. Those who are really poor, laborers, right? They don't give a call for loans, right? Why? Some of the guys get calls for loans, some of the guys get called for credit card, and some of the guys get called for, audit, because they have the market segmentation. They know their market. How they know their market? So they have the data of their customers and then divide into different clusters. So can you see on the screen? And this is your customer base, right? On the left. I hope you can see a nice chart there. So this customer base, right? They divide into, as of now, here 4 clusters, saying that, these are my, recent customers. These are my champions. So they keep coming, keep buying, right? Keep spending money. They are like at risk customers. Maybe they have not, they have not bought anything in last 1 years, right? And these are my loyal customers, right? So those kind of segments they have done, so that uh, they know that how they can reach out to, uh, to these kind of segments. And to give an idea, I think if my customers are at risk, what you will do to retain them? What should a company will do, right? They'll give some discount, right, guys? Come on, discount or offers. You agree? Those who are their loyal customers, right, they might not get a lot of discount because anyway they are loyal to us, so they might come every time, even keep pulling them, right? Champions and are the ones which are very aggressive. They have done a lot of shopping in recent time. You might not also give any discount to them. But if a new customer has come, you might give some more offer so that they keep coming back to us, right? So those kind of strategies can be used or leveraged if you have proper segmentation. Now you understand the application of k-means clustering can be, one simple application can be like this. Okay, so as I go more into details, I'll tell you more about, but this is a very simple example and this algorithm is also very easy to understand. Okay, so how does k-means clustering, work and all, I'll talk about in some time. Okay, let's move on. So let's try to answer what is k-means clustering, right? Means how do we define it? In k-means clustering technique, each cluster is represented by each cluster is represented by its center called a centroid, which corresponds to the assigned to the cluster. So if you see, we are saying each cluster is represented by its centroid, right? So center is called centroid, which is the arithmetic mean of all the data point assigned to that cluster, right? So when I'll take an example, you understand, okay? Now the question comes, what is a centroid? So a centroid is a single data point within that cluster, within the cluster, which represents the center of the cluster, and that means the mean. And that's where this mean is related to your k-means. Okay, that's where you got the name. So a centroid is a single data point within the cluster, within each cluster, which represents the center of the cluster called the mean, and it might not be necessarily be a member of the data set. So it can be a calculated value also, right? It's not necessary it's coming from one of the data set, is assigned like the mean, okay? So that is a very important point to keep in your head. That is not necessary that one of the data point will be given the role of the centroid. It may be possible that you might have calculated the centroid, although that value lies within that cluster, that group, but it's not necessary it's coming from one of the data points. Clear? Now, see here. So I'm showing an image just for your reference. Can you see? So there are 2 groups of the data it has formed. One group is this one, okay? Other group is this one, and it looks very logical because all these blue data points are more closer to this centroid, which is your red color, right, guys? Come on. And these are close to green, right? You agree? Because finding someone close to this is really not making sense, right? Saying this is close. So here you have two clusters. This is cluster 1 and this is cluster 2. If you try to see cluster 1 and cluster 2, they are having centroids, right? So this is your centroid of cluster 1 or for cluster 1. This is your centroid for cluster 2. Clear? So that's how you get to the centroid. So K-means clustering is all about finding that centroid, you know, calculate. It's a calculated value. So calculate that centroid, and it's an iterative process. So first, they will assign any data point or any value as the centroid, and they keep updating it to find and I'll show you the example that how does this iteration work, but they'll keep trying to find the better one. And the whole idea is to minimize the within cluster distribution and maximizing the across the cluster distance. So what is the objective of the algorithm? K-means clustering tries to minimize distance of the points in a cluster with their centroid. So see, it tries to minimize what? Minimize the distance of the points in a cluster, right? There will be only one centroid for one cluster, Vikas. Okay. For now, you should also understand what is my message here. My message is that you are trying to minimize the distance of the point within each cluster so that you find only one centroid, the better one. Okay. So you might start here. This is my centroid. Then you realize, okay, no, I'm not in the center of the position. So tell me one thing. If I draw a circle, you will try to find the balance where till the time you reach the center. So centroid also works in the similar fashion. But your distribution doesn't mean that every time it will be a circle. Your distribution can also be like this. Then you try to find go there. Our distribution can also be like this. You can go there because here you have more data points, right? So it can be, keep shifting to find the balance. Okay. So that's the point I'm trying to make. Okay. Now, number of groups you can decide. That is also another discussion I will do. But for now, the idea is this. So I'll show one more nice image and you try to understand that what I mean by saying this. You have two types of cluster, right? One is intercluster. You see here, to use white color, intercluster, and here it is intracluster. Intra means within cluster. Okay. You know, right? Intra, very famous. Intraland, interland, intercity, intracity. And this is across clusters. So if you see here, within cluster means within a cluster, you want to minimize this distance between each data point. You try to find a cluster in such a way that within that cluster, data points are distance are minimized. That's the objective. And you want to maximize this across cluster distance. Why? So that the separability is highest. So you want to maximize this. I'm writing again. And you want to minimize this within cluster. Here also we'll say within these guys, I'll minimize. So that's I would say in a layman term, the beauty of this algorithm. But how will you do it? Okay. So to do that, you have a step-by-step algorithm in place. Okay. Now steps to do. So let me talk in steps. Steps for finding, or maybe I can say K-means algorithm steps. Okay. So there are few steps, guys. Number one, specify number of clusters you want. Specify number of clusters. Okay. So for now, I think starting this is an user input, means you will tell in the model how many clusters you need. Okay. Generally, people say 3, 4, right? k equal to 3 or k equal to 4. So this is more like, the modeler will give, right, who's building the k-means clustering model. Then second step says initialize centroids by first shuffling the data set and then randomly selecting k data points for the centroids without replacement. Okay, so that can be any weird k centroids, means that's the first one. So you are selecting k data points for centroid without replacement, means you are shuffling the data set, and you're trying to find any random k centroids. Okay. Now in this diagram, if you see, there are 8 data points, right? Or the model has randomly selected this as the centroid for cluster 1. Can you see that? And this data point as centroid for cluster 2. I have only taken, two groups, two cluster here. Clear? That's what I mean. So here, this red and green represents the cluster of within the data points. Okay, clear? Now, point number third, what you will do? Now you will assign all the points to the closest centroid. So as of now, all the data points are like, okay, so you will tell me here that, okay, you tell me who is my boss. So how will you find the boss? You will assign all the points to the closest cluster centroids, right? Someone has to go to some boss. Okay. So here idea is that you will find the Euclidean distance, right? And try to assign. Now you tell me this is closer to this one or this one. You tell me. You find the Euclidean distance, the C1, right? So definitely this is not closer. This one is closer, right? So that's why you assign the centroid to the closest point, assign all the points to the closest cluster centroid, and then you realize that you have another image coming as, right? Can you see that? Now, I think everybody will be okay with this coming to this guy, right? Except one, I know you might be thinking what's going on there. So this is closer to this. You also know that these guys are closer to this, but we have a doubt that whether this is closer to this or this, right? You can clearly see that it looks closer to this. Okay. But obviously you will not be doing like looking at like who is closer by doing eyeballing. You do a maths, and the maths is that you find Euclidean distance. Okay. So it's not like you are doing just looking at it. So what I'm saying, Anthony, yeah, that's why please pay attention. What we are saying, assign all the points to the closest cluster centroid. The meaning of it, this is my centroid which I have randomly assigned. I was talking about this particular data set, right? Tell me, is it closer to this guy or this guy? There are two centroid, right, for this point. Which one it is closest to? So C1, that's why you have assigned C1. So all these guys have been assigned to C1. All these guys have assigned to C2. Now this guy is a little controversial guy. As of now, it is also assigned to C1, but right, are we going to do something about it? Clear? So now you can clearly see that now the centroid itself doesn't make sense, right? Now this is we have calling centroid, right? But it might be possible that centroid might shift somewhere here. Okay. So once we have formed the clusters, right, you have to, you might have to recompute, and that's where I'm telling it's an iterative process. Recompute the centroids of newly formed clusters. Recompute the centroids of newly formed clusters. And again, finding the mean. So this is like using the mean. You have to recalculate this centroid again. So earlier you were just assigning one data point as the centroid. Now you are going to calculate the centroid again. If you look intuitively, guys, now you might feel that for the green, I think centroid should come here, somewhere here, right? That's where more balance you will find with this. So this is your cluster 1, guys. Can you see that? So centroid might look little bit here and here, right? Depends on how we are getting, and I'll show the image. And for the green one, please pay attention. Green one definitely centroid C2 doesn't make sense. It should come somewhere in the middle, guys. You agree? Everyone here? So if you try looking at, and the algorithm gives you a new centroid, and I was trying to do a more like a by gut feeling, but see, more or less, I was right? So this is the recomputed centroids. It will never come like this when you recomputed centroids. Initial centroids were selected randomly by the algorithm itself. See, read this point. Initialize centroid by first shuffling the data set and then randomly. So it's been random. We are not selecting it. Randomly, algorithm picks something. It's written in the first, second point. Okay. Then what will happen, guys? Once you have recalculated the centroid, okay, then again, right? Then again, they're going to repeat it. Means they'll keep moving it around. So they'll keep connecting, again, calculating the distance, where it should be, right? If every data point within the cluster is same or not. So that's the exercise it does, okay? That's the exercise it does. It doesn't stop here. It will repeat its step to fine tune the cluster till the time it doesn't find a better cluster. So that's where it will stop doing. Okay. So, so let me show you one more nice diagram and you will love it, I guess. Now this is how the step looks like, right? So if you don't look at the final one, if you just look at the first one step, right, you will realize that they are first trying to find the clusters. Like this is my, one group. Can you see the blue dots? Hello? So first they thought they will divide like using this plane, right? So two clusters. Everybody please pay attention. Then what if I try dividing like this? So then they divided the data on the basis of similarity again, saying, okay, maybe this can be my two clusters, right? Look at that, how it is changing every time, right? And then it fine tunes. See, so earlier, if you see the cluster points were like this, then the cluster has moved. If you are paying attention, don't look at every steps. Please follow me here. The cluster has moved somewhere here. See, and the blue has moved here. So I think earlier it was here, and then it has come here. Guys, can you see that? Somewhere here. Then they realize that what if I move this guy to this completely, right? All these guys are more closer to this. Listen to me. All these guys are more closer to red. So that's why it becomes all red. So the cluster definition has changed. Now what they're doing, they're fine tuning a bit. Can you see that? So now this cluster has to go somewhere center. So that happens in the next. See? So cluster is coming in more center. Then again, this has also come little more in the center. Then they are, trying to do more fine tuning little bit. And then finally becomes your cluster. So one becomes this, right? See, there are only two clusters, but look at the beauty. You might have thought the grouping is being done, right? But see how they evolve to find you the two fine-tuned clusters. So that's why they start randomly. They find the distance, then they update the cluster groups, right? As you can see here, to fine tune, and fine tune. But the steps remain the same. First, they will assign something to as a centroid, calculate the distance, right? And then recompute the centroid, again calculate the all the distance from all data points, distance from the new centroid. If they find that okay, we have to move to some other place, they'll move. Clear? Now I'll talk about some key applications, real life applications. Already I've given one, but maybe I'll just give you a few pointers around it. So real life applications of k-means clustering. Okay, so number one, customer profiling, right? Also known as customer segmentation, market segmentation, more or less related to customer segmentation, document classification, right? So different documents can be classified into more 4 or 5 clusters. So document classification, so there they use OCR, which is optical character recognition, to understand the document's nature. And then on the basis of similarity, they group into clusters. Okay. I think there are a few more like geostatistics, understanding the similarity of geologies, or finding astronomy, right? Astronomy is also about finding patterns. So yeah, astronomy is another big area. So where they do all those kind of understanding the planetary positions, and making some conclusions. This is the similarity and patterns, right? Although they also try to predict why, and why can be anything that you can change anytime. Yeah, that's all from my side on this. Maybe I'll talk a little bit more about how to also decide number of clusters, because sometimes people think clusters is like I can always give. It's not like this. What are the cool things about K-means clustering is that you can actually stop uh, going intuitively that how many clusters you need. You can also go by using machine learning concept. You can also find the value of K. So let me give the heading. I'll come back to Imran if I can put the heading. Finding the value of K. You can also find that by using the concept of elbow curve. So let me explain that. So using machine learning only, you find the how many K I should pick. So you can plot the elbow chart. So if you have seen an elbow, right? So this is your hand, but can you see this is known as elbow? Okay. So this elbow chart is just similar, right? Okay. So when you are trying to see that what is your sum of squared errors, right? And using that, you can see that if you take two clusters or three or four, right, till the time it keeps adding value to it, you're trying to minimize the error, right? So you will go with more number of clusters. Ideally, you have to find an elbow here in this chart, to be honest. So if you try to fit an elbow here, right, you'll realize that wherever the curve for the elbow comes, right, that will be your number of clusters. But how do we decide that? So if you have a sharp decrease, more like a very fast decline in the value of this y, which is WCSS, right? That is mostly your sum of squared errors driven, right? Sum of square error. If it decreases the error drastically, you will keep increasing the number of clusters. The moment it starts getting into a flat line kind of concept, just like this becomes like a flat line, you stop adding more. Because even if you take, tell me one thing, if I take, let's say this is 5 clusters, and if I take 8 clusters, do you see any much difference in the error? Guys, come on. So why do you want to add more clusters to your data? Hello? Does it make sense when I say this, guys? There's no point, right? But if you see, if you take 3 clusters and you take 5 and if you draw a line, can you see that how much error you have reduced, guys? Are you feeling it? And if I say I have taken 2 clusters, right? 2 to you have to anyway take minimum. So 2 to 3, you can also see that you have quite a lot come down. So that's how you can do this. Clear? So testing different number of clusters and measuring the resulting sum of squared errors, which is SSE, and choosing the K value at which an increase will cause a very small decrease in the error sum, and increase will cause a very small decrease in error sum, while a decrease will sharply increase the error sum. So this can be a little confusing language, but that's how it is. So guys, what we are trying to say, please understand, if you go from 5 to 6, so I'll also give you the color coding. If you increase K, increase means what? Increasing K will cause a very small decrease in the error sum, right? If you go from 5 to 6 or 5 to 7, do you see any big decrease in the error sum? No, guys, correct? While a decrease in the K, while a decrease K in K will sharply increase the error sum. So if you go backward from 5 to 4 or 5 to 3, can you see that? Your error sum sharply increase from here to here, guys. Can you see that? Look at this green line. That is the second part of the statement. So in the middle of that, can you see that? In the middle of that, in the middle of this, you find your optimal cluster. Are you feeling this? That's where the language is. That's where you find your optimal number of clusters. So far with me, guys? Clear? This is your optimal number. What is this in this case? 5 is the answer. So you can take it from me. Stopping criteria for k-means clustering. Stopping criteria for k-means clustering. Okay. So there are essentially, 3 stopping criteria that can be used to stop the k-mean. Number 1, centroids of newly formed cluster do not change. So I'm saying that your centroid is fixed, it does not change. Second, your centroids are not changing and your points remain in the same cluster. So nobody is changing the party here. Okay, that can be another one. And third, you can also set a maximum iteration. So suppose your algorithm, you don't want to run it forever. Just like in decision tree, you set, right? How many leaves you want to stop at or how many decision tree you want to stop at in random forest. Likewise, you can do maximum number of iterations and then you want to say, boss, stop it. I don't care. So in 3 ways, you can stop the k-means clustering. Make sense? Clear? So these are your like stopping criteria for k-means clustering. Okay. I'll be going up and do the hands-on and let me know once you have the data, guys. Okay, you try loading that data. In the meantime, I'll also get back to you. So I'm also loading the data. So we have those typical import. Let's do it. Import numpy as np, right? Import pandas as pd. Import os. Import matplotlib dot pyplot as plt. Import seaborn as sns, right? I might be using a bit of plotly also in this. So you can import plotly as py and import plotly.graph objects objs as go. So someone can say hi on Q&A. I can share all these libraries which we are importing. And here you go. Okay, Aryan has shared a big list. Okay, so you should also know, Aryan, which one we are using where, right? Now, let's load the customer data, guys. So df underscore customer, and it's a mol data. So let me read it. What happened? I'm not in this working directory where I am. I'm in, yeah, and data is also there. So what is happening? It was not in the right folder. See, now it came. Okay. This is the data, guys. Can you see that? So you have gender, age, annual income in $1,000, and what is your spending score? Look like more like a customer profile, right, guys? Agreed? Now to plot scikit-learn we need. So one more you need to build the cluster, and that is import k-means, right? So this is something we should also get it, and then we're good. So guys, first thing first, I'll teach you how to make a basic clustering, right? Basic clustering on 2D. So you can actually use more than 2 variables. But for now, let's understand age and spending, and then you can go from 2D to 3D, 3D to n variables. That's up to you. Let's get a good idea about clustering by looking at this. So you know that the columns are this. Maybe I'm going to pick only age. So I'll say df underscore customer. So I'll select the columns, age and spending. So I'll just say age and spending score. I'll take this guy out and should be good. See, this is my data, guys. Okay. And if you try to plot a scatter plot to understand the distribution, All right, guys, you know how to do it. I don't need to teach, but I'll write plt.figure, or we can use plt.subplots, and then you can write fixed size equal to, let's say 15,7. Yeah, looks good. I think I can give it 15,6, yeah. And maybe I can take 12,6. I'm just trying to get a good shape. plt.show. Okay. And then within this, you have to use plt.scatter. You have to use x equal to age, y equal to spending score. Data, you already know, you have df, and size of the scatter can be 100, right? Age, spending score. Okay, cool, guys. It's really bold. Now, better, everyone. So you might think that, okay, my groupings can be, people can think of different types of clusters here. If you are talking about two clusters, you might be thinking, I'll assign this to one, assign these guys to be two, right? Can you think like that, right? Someone can say, okay, Akash, can I do something like this? So how do you do that, right? Means clustering is all about that, right? So I think the first thing first, we need to decide the k value, right? And give some levels to the chart. So first, let me give the levels. So title is, age versus spending score, distribution, plt.x level, and it can be age, plt.y level, and can be spending score. Yeah, see, now we have to decide the k value. Why we are deciding the k value? So that, we can assign how many clusters we need. For that, I will use the elbow chart. Right, guys? Remember? So remember, elbow chart technique plots the different cost error function. As k increases, average distortion and variance will decrease, right? Cool. And this is some funda, right? The same thing. Now, guys, first need to create the data for elbow. So we'll call elbow df underscore customer, and then I'll pick only two column, which is age, and I'll check spending score, right? This one. Perfect. And now, guys, I want to get only the values. So I'll take, all of it, only the values. This helps you to get the 2D array out of it. Okay. And trust me, you can get the array in multiple ways. See, this is a 2D array. It's the same data. If you see 19, 39, 21, 81, 26. Let me come down and show you. It's the same data, guys. The only thing here is that you are getting a two-dimensional array. Remember, I taught you, so you cannot say no. It's starting with two square braces, ending with two square braces. So it's a 2D array. Are we clear, guys? See, ending with two square braces. It's a 2D array. That's a requirement for the plotting. Then I want to keep an empty list called inertia. So this is an empty list. And now I'm going to go one by one. So I'll say for n in range, I want to go in a range of 1 to 11 so that I can plot as high as 10 clusters. I'll use the algorithm to calculate the elbow, and I'll say k means, and I'll use n underscore cluster that is coming from scikit-learn. I'll put n here, and I'll say init. This is to initialize. K means init means initialize. Remember that oops, might have heard a little bit on oops. Init means initialize. So that's your initialization of the k means. And you want to go till 11. So last is 11. Max iteration, I think, right? I'm putting 300 iterations, which is quite enough. Tolerance is more like how much accuracy you want to maintain, like till where you want to go. 0.001 delta is fine. Random state is 45, again, to set the randomness of the sample. Algorithm is EK, Euclidean, so EK-LAN, right? So now this is your algorithm, okay? And then you will fit it to your data, which is your two dimension array, and then you will append the values you are calculating to this empty list, which is your inertia dot append. You have seen me doing append to a list, and once these values have been calculated, you can keep appending to your inertia. LCAN, not ECLAN. So you will see that inertia has taken your value of the cost, right? Right. And that's where you will also get the cluster. So let me do it. Let me plot the elbow chart. Okay. So again, I will use the same concept of it, PLT dot subplots. Maybe why don't we use that, right? Why to waste time? Let's use this now. Now we don't need a scatter here. So I'll say PLT dot plot. I need a line chart. And then I will create np dot arrange. Okay. 1 to 11 inertia, and line marker will be O. Okay. This is to just align with the number of clusters. Okay. So this np.arrange, guys, what it does, it creates a value from 1 to 10. Okay. And see, so it gives you like, the value of those data points, right? 1715135, right? Can you see that? 1715135. So are you feeling that you are getting an idea about, hold on, right? You are going to put some kind of this, right? No, 1 to 11 is that, remember, you have created, what is the length of this? Hold on. What is the shape of this? It's a list. So what is the length of this list? You tell me. 10 data points, right? So inertia is just the y-axis. You also need x, right? So that's where I've used this np.rh. So this is your y. This is your x. Line chart, no? So we need to, so that's why I needed an x also, no? Like 1, 2, 3. Now definitely this age will go. It will become your number of clusters, and you will start getting to making sense now suddenly. So that is more like your data manipulation to update your x-axis, because inertia just gives you the y-axis, which is your cost. Now you will start seeing a lot of difference, right? And title and I can go, it can be set here, elbow chart for optimal number of clusters, isn't it, guys? Now I also need a line to it. So I'll superimpose plt.plot. And again, it will be same thing, only the marker will change. See, so here marker will be a line this time, and you will see magic. Look at this, right? Isn't it the chart I showed you while I'm teaching you this, right, guys? Okay. Now, inertia. Okay. So Indrani asking, what is inertia? Inertia is nothing. Inertia is your cost, which is being calculated from this algorithm, scikit-learn k-means. So now if you look at let me show you the documentation. Hold on. Right. So if you see here, I've written, init k-means, let's understand it. Okay, hold on. See, init means you have more like to initializing the method for your solving. So k-means is your algorithm you're using, clear? Init is clear. Right now, what is it? N cluster, how many cluster you want to take? So that's why you're plotting for 1 cluster, 2 cluster, 3 cluster, and what is your cost? Okay, now come back. What is your max iteration? Maximum number of iteration for the k-means algorithm. I talked about it, right? So that's your max iteration. N init is what? Number of times the k-means algorithm will. If I'm running a for loop, for how many times? If it is 1 to 11, it will start from 1 till 10 only to run. So total, how many times I'm running the k-means clustering? For 10 clusters, right? So it will also has to match this, right? That's why I've written the same thing, 11, 11. So this means it will run for 10 times. Okay, and that's where if you see, you will see that I have given number of cluster 10. So it is solving every time, my dear. When you have only 1 cluster, when you have 2 cluster, when you have 3 clusters, every time it will solve and calculate the cost. Model is doing that. I think rest everything you can handle. Simple, clear? Inertia is an outcome of this, right? Inertia is more like your cost. So don't worry too much on it, okay? It's your cost, okay? That's sum of square error if you are trying to divide it into the syntax, okay? Now, once you look at it, guys, you can clearly see that I think ideally you should have minimum 3 clusters, right? See, between 3 and 4, see 4 and 5 same. 3 and 4, you have some delta. I think let's start with k equal to what? K equal to 3. First, we can start with k equal to 3, guys. You agree? That's correct. Very good, Indrani. You got it. Each data point on this elbow chart is one iteration with the cost, right? So every time you run it, you get a cost out of it. Let us start with k equal to 3. So again, it's the same algorithm. I'll use k means 3 means 3 clusters, k means, and then I'll copy everything from right. यहाँ आपको 3 clusters. I think number of iteration can be 3. Maximum is fine. Tolerance is fine. Random state is also fine. Everything is good. Okay. Now you will say algo3 dot fit on your data, which is your elbow, which is your array. Sorry, this is your whatever it is data frame. I think elbow was your array, right? Let me print and see. Yeah, it's an array. And then you can find, so this is your done, model is ready. Labels, one you can say algo3 dot labels underscore and centroids. See, centroid will be cluster centers. So guys, you can see that labels will get that, first data point goes to cluster 1, 0 means 1, 1 means 2, and cluster 2 means 3. So there are 3 clusters. That's why it starts from 0, 1, 2. And if you look at the centroids, you will see 3 values. Can you see that? The value of centroid 1, value of centroid 2, and the value of centroid 3. Yes, cool. You have everything to plot the clusters. So I'm going to, guys, now plotting the clusters with centroids. Okay. So again, plt dot subplots fixed size equal to 15,7. Maybe I'll keep it 12,6. The same plt dot scattered. So you already have the data elbow, 0, elbow, everything, and 1. C can be your color, can be your labels 1, and C map can be bodies. Where it is, right? And then I also need to plot the centroids. So I'll use centroids :0, centroids 1, and you can give the marker like X. Yeah, good observation, Prava. And color equal to red, 200, and bingo, done. See, interesting, guys. Can you see this? Remember, the data distribution was looking like this. So this is what you had, and when you try to look at it, guys, can you see it has created a centroid, sorry, cluster like this. Another one is little different, something like this it has done. It's a real data, so you can expect clusters like this. And the other one is this. And the centroid makes a lot of sense, guys. As you can see, center, center, and center. Because of the, outliers on this side, it has shifted to us little with this. Else it could have been here, right, guys? Agreed? Same story with this one. But see, this is real data, and you have 3 groups of people basis your age and the spending score. So how it is dividing, guys? Those who are spending between 60 to 100 and those whose age is less than, hold on. So the demarcation is like this. Anybody whose age is less than 40 and spending score is 60 is one cluster. And you are saying that I don't care about the age. I only care about the spending score. So anybody who is having 40 to 60, roughly, you have one cluster, right? Another line coming, guys, correct? Hello? You agree? So another line is this one, 40 to 60, and anybody who's spending score is 0 to 30 is another cluster. See, so beautifully it has classified. That is with 3 clusters, right? But if you want more finer cluster, I think you can go with So I can just see, you have to be very smart. You have to just copy this whole thing and I'll paste it. And now what I'll do, I will say, let's go with 4 clusters. So you have to do nothing. You have to just change here 4, make this guy equal to 4, make this 4 so that you don't overwrite. Let the model solve for 4. Create the level for 4 by calling it 2. See, I'm just repeating the step. You could have written a for loop to do that. Trust me on that. Okay. So let me run it. Ta-da. See, now you can see there are 4 cluster points. You can just use same data, but you have to use labels as 2, centroids as 2, 2, right? I don't want to. See, now it makes a little more sense that now you have divided this part. Then again, so see, I thought so. Can you see that? So now it has divided like this: 1, 2, 3, and this whole thing is like a 4 cluster. Interesting, guys? And it seems intuitive also, right? So you know that who will be part of your which cluster and how you can target that. That's all from my side, guys. So nothing else on this. You can try to get more in details of it, but I think I'm done from my side on the K-means side. Segments are already there, no? So if you see, you have to just join the data. So you have this data set, right? You have an array here, right? So what you have to do? You have to use label 2 and assign it to the elbow data, right? So maybe let me do it. So you have your elbow data, correct? And you have an array. So you can convert these two into a pandas frame and just, concatenate, right? That to by axis 1, right? So you already have this guy. You know how to convert an array to a pandas data frame, right? So what you can say, df levels for 4 clusters, right? And you can say pd.data frame and your, I think, levels 2 column equal to cluster. Okay, guys, this is my, and now I'll do pd.concat. And I'll say, remember, I have taught you these things, and you have the data df underscore customer, and you also have this guy df levels for axis 1. And that will be a combined thing, right? df customer with clusters, right? Correct, Indrani? So you have to do a little bit of data preparation, which I expect you guys to do it. Now you can clearly see that these are your customers in which cluster you are. Now interpretation I did. So while I was drawing this vertical lines, what is the meaning of it? So vertical horizontal line. So anybody who is in the age group of 65 plus and spending score of 60 plus and age group of 40 or so, that's your one group. So you can use this for selling premium products, right? So their spending score is really high. So you can always target this customer for like some premium product, high pricing, high value products, right? Premium means like selling some goods, jewelry item or whatever, XYZ. But if you look at these guys who are part of the bottom one, can you see that? Irrespective of age, their spending score is really less. So you have to give some offers here, and that too on like a low price products, right? LPP, right? So that's the interpretation. So you know that whom you have to target, right? If you don't have this cluster, you might be giving offers to these guys who are anyway premium customers. They keep buying things. They are like people like me who are spendthrift. So you don't need to give them any offer, and you have to position premium products to them, right? And then these are your like mid-level kind of customer. Okay, you got it? So that kind of interpretation comes from the your clustering algorithm.
So let's begin with our very first question, which is what is machine learning and why is it important? Now, as you can see in this diagram, machine learning is a part of artificial intelligence, right? Under machine learning, we have concepts like neural networks and deep learning. Right, machine learning basically consists of dozens of different machine learning methods or algorithms, which we will be covering a few in this particular video throughout our questions. So machine learning is basically teaching computers to learn on their own. Right. So what machine learning basically does is it will show the computer hundreds of pictures of, say, apples and oranges. Okay. So machine learning is basically going to pick these two fruits and show them to the computer. Now what machine learning is doing here is basically it's not telling that apples are going to be red and round. Similarly for oranges, that they're going to be orange in color and they're also going to be round. Instead of giving certain rules, it is going to let the computer figure it out by itself. It is going to go through the hundreds of images and going to figure out a pattern by itself. So this way, whenever a new kind of apple or a new kind of orange is shown to the computer, it is going to be able to figure them out. So this is the basic idea behind machine learning, right? So it basically reduces the repetitive manual work. Like, so say you want to filter out the spam emails, right? So you do not need to do that manually. Rather, machine learning is going to do that for you based on certain keywords. So basically, if an email contains words like free and offer, so keywords like that, so based on that, machine learning is going to help you identify that these emails could be spam. So machine learning reduces repetitive manual work. It helps businesses make data-driven decisions. It powers personalized recommendations like Netflix and Amazon. So you guys must have noticed every time you open Netflix, you will be suggested some movie or the other, or some series or the other based on your previous watches. So that is again machine learning behind. It drives innovations like self-driving cars and medical diagnosis. So again, it is not just limited to the basic applications we see like Netflix. In fact, it is seen everywhere like self-driving cars and medical diagnosis as well. So our second question is differentiate between supervised, unsupervised and reinforcement learning. So first let's go to supervised learning. So as you can see over here, we have some raw data, and whatever algorithm we apply, it is going to have labeled data. This is basically supervised learning over here. This is the major point, that we're going to have labeled data. And then we're going to have a prediction. So now let's look at that in detail. So supervised learning, one of the three types of machine learning models, is when the model is given labeled data. That is your input and the correct output. You have it labeled. Your algorithm knows that this is the input I'm getting and this is the output that is supposed to be predicted, right? It is going to learn the relationship between the input-output to predict the future results, right? It is used for tasks like, say, classification and regression. Classification is, say, your spam or not spam emails, and your regression could be predicting your house prices, right? So basically what supervised learning does is it learns from the examples and it predicts the answers for new unseen data. Right, another example you can consider is we give labeled photos of cats and dogs. Right, we give photos and we label them as cats and dogs. Now it is going to learn to identify animals as either cat or dog in the future pictures. And since we have already told the algorithm when we were giving our data that this is a cat and this is a dog, this makes our data labeled. Right, so this is all about supervised learning. Then we have unsupervised learning. Now, whenever we give our raw data, it is going to be unlabeled. So this is the major difference between supervised and unsupervised learning. Let's look at it in detail. So basically, unsupervised learning is, if you were to consider a real life analogy, a student solving problems without a teacher. Right, so it is doing everything on its own. So no answers are provided. The student, or you can say our algorithm, has to find patterns or similarities on its own. So basically, unsupervised learning is when the model is given data without labels and must find patterns or groupings on its own. Now, in this case, we just have given some random pictures of animals. And now our algorithm, that is our unsupervised learning method, has to figure out on its own which one's a cat, which one's a dog, or maybe it is going to group similar pictures together and then we can identify a pattern between them. So it works like that. So the model basically doesn't know the answers beforehand. It tries to group similar data together, like clustering customers by their buying habits, right? So it is going to find a common pattern between the data, and it is going to try and group them together. That is what unsupervised learning basically is. Moving on to a third type of machine learning model, which is reinforcement learning. Now, reinforcement learning works like, say, you're teaching your pet dog some new tricks. So, whenever the dog is going to do something right, or it is going to get the trick right, it is going to get a treat. And if it is not able to perform that particular trick, there will not be any treat, or you can even introduce some sort of penalty. So that is the same way reinforcement learning works. So whatever agent you have, it is going to learn through interacting with the environment, right? So if the agent gets the action right, there's going to be a reward, or there could be a penalty for getting anything wrong, right? So let's look at it in detail. So the model learns through trial and error, train software to make certain desired actions, right? So you can say like a robot who is left out in the open is going to interact with its environment, and through trial and error it is going to learn what actions lead to rewards and which ones lead to penalties, right? It is going to learn by interacting with the environment. It gets feedback in the form of rewards and penalties. So that is basically how reinforcement learning works. So we have a table over here differentiating the three based on data, goal, and an example. So you can say supervised learning is labeled data, unsupervised has unlabeled data, and reinforcement learning learns by interaction with the environment, right? Then there's the goal. So supervised learning has the basic goal of learning the mapping between the inputs and the outputs. Unsupervised learning finds patterns and groups the similar data, whereas reinforcement learning maximizes the rewards by trial and error. Then we have our example. Supervised learning could be classifying emails as spam or not spam. Unsupervised learning could be clustering the customers based on a particular habit or behavior. Then reinforcement learning would be training a robot to walk, right? So moving on to our third question, what is a model in machine learning and how is it used? So a machine learning model is like a recipe, you can say, or a set of rules that basically helps the computers to solve the problems. It's built by learning from data and figuring out the patterns. So basically you have your training data, you extract patterns from the data, and then you use those patterns to predict the results. That is basically how you evaluate whatever you have trained your model on, right? So a machine learning model is, as we discussed, a set of rules or instructions created by learning patterns from the data. It is used to train data to make predictions or decisions, right? So say for example, you're training a student. So when you give that student a textbook, so the student is basically going to study from the textbook and answer the questions based on that, correct? So that is similarly how machine learning models also work. They basically study from the training data that they receive, and then they implement whatever they have learned, whatever patterns they have figured out from the training data set, they implement it on their test data set or whatever new data they receive, and then go ahead with the predictions, right? It is used to understand relationships, classify things, or predict outcomes. So basically there are two steps. First is training the model. The model learns from examples or the data to understand patterns. This is your training data. For example, feeding the model pictures of animals labeled as dog or cat. That is your training data, right? You're giving your algorithm, your model, some sort of data, and you're telling that this particular image is of a dog, this particular image is of a cat. Now it is your duty to understand it, to understand why this is a dog, why this is a cat, and then you test it or you make predictions, right? You are going to show a new picture that the model or your algorithm has not seen previously, and then test it whether the model is able to predict the right answer or not, whether it's a cat or a dog. So that is basically how a model works, right? Moving on to our fourth question, explain overfitting and underfitting with examples. Now let's first look at these diagrams over here. So basically what these dots are your data points, right? You can see all these dots, these are your data points. Now in your first graph, you have a straight line going through the data points, but not really covering or not really touching a lot of them. So this is what is called as underfitted or underfitting, right? Then you have this image over here where your line is basically trying to touch every single data point that is there. This scenario is called overfitted. And then you have your middle image where your line is trying to find a middle path where it doesn't really touch every data point and it does not also exclude all the data points or is not too far away from all the data points, right? So this is called a good fit or a robust fit. This is what we ideally want. And these are the two conditions that you want to avoid. So now let's go ahead and look at them in detail. So overfitting basically happens when your model learns the training data too well. Now, say for example, you are preparing for an exam and whatever materials you have, so instead of understanding the concepts, you try and by heart every single example, every single definition that is given to you in your material. Now, if in the exam you get the exact same questions with the exact same numbers, you are good to go, right? You are going to know every answer because you have by hearted, you have memorized them. But in case you get some unseen questions, that is the time you're going to suffer. So that is basically overfitting. What overfitting is doing here is basically it's trying to memorize each and every data point in your data set, right? So in this case, whenever a new data set is given to your model, it is not going to perform very well, right? It is going to perform very poorly on unseen data. Why? Because it captures all the noise and the irrelevant details. So say for example, you're training a model to classify dogs and cats. If it is overfitted, it is going to learn that cats only have one specific background in the training images. It is going to capture that maybe all the cats are white or some unnecessary detail, right? And whenever you're given, say suppose you give a picture of a white dog, your model is going to classify it as a cat because it has learned or it has memorized that this particular image or this kind of image belongs to a cat. So that is what overfitting means. Then you have your underfitting. This occurs when your model is too simple. Like we saw in this diagram, when you have an underfitted model, your line is not really going to care about the data points as such. It is going to oversimplify the things and fail to capture the underlying patterns in the data, right? As you can see in that diagram, the line is not particularly capturing any sort of patterns. So this leads to again poor performance on both the training data and the new data. Now if we were to consider the example of a student again, so now in this case what the student is doing is he is basically skimming through the pages, just reading the headlines and moving ahead, thinking that he has learned everything about the topic, right? So this is underfitting. Now a model which is meant to classify cats and dogs is going to be underfitted if it predicts every animal as a cat because it hasn't really learned the difference between features of dogs and cats, right? So that is what underfitting means. So here we have a table differentiating overfitting and underfitting. So performance on the training data for overfitting is going to be excellent, whereas for underfitting it is going to be poor. Performance on the testing data is going to be poor for the overfitting models, and for the underfitting model it is also going to be poor. Now as you can see, the underfitting models are going to perform poorly no matter whether it's a training data or a testing data. Why? Because they do not really capture any sort of patterns right from the beginning. So even on the training data, they're not going to perform well. Whereas overfitting is going to do exceptionally well on the training data, but it is going to fail to perform well on the testing data or with whatever new data that is presented to the model. So then we have our model complexity. So overfitting is going to be too complex because as we discussed, overfitted models literally try to learn every single detail of the model or of the data set. So it is going to be way too complex, whereas underfitting is going to be way too simple because they barely capture any details or they barely try to understand any sort of pattern. So the solution is to simplify the model, use regularization or get more data. Whereas in underfitting models, you can use a more complex model or tune the parameters, right? So reading these points, you must have gotten an idea that what is important is a balance between the two to achieve a good or a robust model, right? Your model shouldn't be overfitted or underfitted. That is, it shouldn't be too complex or it shouldn't be too simple. It should be just midway between these two to achieve the best balance, which is also known as the bias variance trade-off, right? You can also mention this point because, let me just write it down. So it is also called the bias variance trade-off, right? So moving on to our next question, what is a confusion matrix and how is it used in evaluating the models? Now, a confusion matrix is basically a table that helps you to evaluate how well a classification model is performing, right? So it compares the model's predictions with the actual outcomes. Basically, whatever predictions your model is going to make, you're going to have some correct values, you're going to have some incorrect values or incorrect predictions. So all that is mapped in a very organized way and shown in a table which is called the confusion matrix, right? So it is useful for understanding the types of mistakes your model is making. So this is what a confusion matrix looks like. You have your actual values, that is, say you have your training data and your testing data. Right. So for your training data, you have your actual values, that is, say you have a column predicting yes and no, right? So it basically goes like this: yes, no, yes, no. Whereas your testing data is going to predict something like yes, yes, no, yes, right? So as you can see over here, this particular prediction is correct over here, whereas all these are wrong, right? This was supposed to be no, this was supposed to be yes, this was supposed to be no. So all this can be mapped in a very organized way, as you can see over here. So our actual values are here and our predicted values are here. So if our actual value was positive and our predicted value is also positive, we call it a true positive. So this is basically a correct value. But if our actual value was positive but our predicted value was negative, we call it a false negative. That means this value is incorrect. But if our actual value was negative and our predicted value was also negative, we call it a true negative. That means it is correct. But if our actual value was negative and our predicted value was positive, we're going to call it a false positive. That means it was incorrect. So this is basically how a confusion matrix maps out all your predicted and actual values to help you analyze how well your model is performing and how much of your predictions are correct and where exactly your model is making mistakes, right? So true positives, we just discussed. The model correctly predicts a positive outcome. False positive is when the model incorrectly predicts something as positive. This is also known as a type 1 error. Then you have your true negative. The model correctly predicts a negative outcome. False positive is when the model misses a positive case and instead predicts it as a negative. So that is called a false negative. Alright. So now that you have understood what is a confusion matrix, let us also see how it is used in evaluating the models. So for evaluating the models, we use terms like accuracy, precision, recall, and the F1 score. Now, accuracy basically means the overall correctness of your model. This is what accuracy is going to test. Precision focuses on how many of the predicted positives are actually positives. Recall focuses on how many of the actual positives are correctly identified. And F1 score is basically a balance between precision and recall. So you can give an overview of how these terms, you can also go ahead and explain the formula for these particular metrics, right? So that was all about the confusion matrix. Let's move on to our sixth question, which is define cross-validation. Now, cross-validation is nothing but a method that is used in machine learning to test how well a model will perform on unseen data. So how is it going to test? It is basically going to split the data into multiple parts. So say you have a data containing 50 rows. So what this cross-validation is going to do is it is going to split the entire data set into say 5 rows each, and it is going to create 10 parts of such 5 rows, right? So it is going to train the model on some parts and test it on the remaining parts. So that is basically how cross-validation works. Now this ensures model performs consistently. So it is going to prevent overfitting, it is going to have a reliable testing, and it is also going to maximize the data usage, right? So as you can see, cross-validation has split this particular data into 5 parts, right? So what cross-validation is doing here is it's going to train the data on these 4 parts and then test it on this 5th part. And it is going to do that until and unless each and every part of it is tested, excluding the remaining 4. As you can see, at the second time, it is going to train the data on these 4 parts and then test it on the 4th part over here. then it is going to test it on the third part, then on the second part, and then on the first part. Basically, it is going to create a combination for all the number of parts that it has created for the particular data set. Now, this is going to ensure that our testing is reliable. So this also prevents overfitting and it maximizes the data usage. Now, consider this example where, say, you're preparing for a spelling bee competition. Now, you have a list of 100 words that you need to prepare for. Now, instead of testing on the entire list of these 100 words, what you are going to do is you're going to split these 100 words into 10 smaller groups, right? So, you're going to have 10 lists, each having 10 words, right? So, now you're going to study these 9 groups and then test yourself on the 10th group, right? Now, you're going to repeat this process until you have tested yourself on every group. The next time, you're going to go ahead and practice on the first 8 and the 10th group and then test yourself on the 9th group. So this is exactly what cross-validation is doing in this case, right? So make sure whenever you go in an interview, you give relevant examples and you are very clear with your explanation so that the interviewer understands that your concepts are clear, right? So moving on to the 7th question, what is the role of precision and recall in evaluating a model? Now let's understand this diagram first. So basically we have our spam emails over here in this section and we have our not spam emails in this section. Simple. Now what our algorithm is doing is, it is predicting all these emails as spam. Now as you can see, the green section is correct because it is correctly identifying these spam emails as spam. Now but the red section over here is that the not spam emails are also classified as spam. So basically what our recall and precision is doing is, our recall is going to test all our true positive. That means all the correctly predicted spam emails as spam based on our spam emails. So precision basically measures how accurate the model's positive predictions are. So in other words, you can say that all the predictions the model made as positive, how many were actually correct, right? So basically it is going to compare these two sections. Now say for example you have 10 emails in total and 8 of them are actually spam. So in this case our precision is going to be 8 upon 10. Alright. Now let's look at recall. So now recall basically measures how well the model identifies all the actual positives. So it is basically going to compare this entire section, right, as you can see in this image. So out of all the spam emails, how many did the model catch? So say we have 20 spam emails, alright, and the model actually figured that 8 of them were spam. This is a prediction, right? So our recall is going to be 8 out of 20. This is what the recall is going to measure. So both these metrics work on true positives, false positives and false negatives. So again we will have to use a confusion matrix in order to calculate these. Right, this is the formula for precision, true positives upon true positives plus false positives. Basically trying to predict how many of the predicted positives are correct. Right. Then for recall we have true positives upon true positives plus false negatives. How many actual positives were identified correctly, right? So a precision and recall basically give the insights beyond the overall accuracy. Now if your model has a very high precision, your model is basically trying to avoid the false alarms. Basically that means very few false positives. Whereas a high recall is going to minimize missed positives, that is very few false negatives. Now these criteria are very important. Let us quickly look why. They are especially important when the cost of errors vary. Now consider a scenario of a medical diagnosis. Now missing a disease, that is a low recall, is going to be worse than a false alarm, right? In cases of medical diagnosis, you're going to prefer that if there is even a slight chance or a slight possibility that a person could have a particular disease, you would prefer a medical diagnosis in that case. Rather missing that particular disease and hence not going for the medical diagnosis is going to be worse in this particular scenario. Whereas another scenario where you are detecting spam emails, So in case you flag the genuine emails as spam, now say for example you have a very important email and you flag that particular email as spam, which is in the case of low precision, it can be annoying or it can even cost you, say, a missed opportunity. Right? So you need to consider these scenarios in mind and choose which metric, it could be precision or recall, which one you need to be higher in which scenario, right? So moving on to our eighth question, what is the F1 score and how is it calculated? So the F1 score is basically a metric that combines precision and recall into a single number. Now, just as we discussed the two scenarios where a high precision or a high recall is going to be beneficial in one case, whereas so the F1 score is basically a metric that combines precision and recall into a single number. So it basically provides a balance between the two, right? Precision and recall. Now, just as we discussed in our previous slide, the medical diagnosis and spam detection situation, where keeping one variable low and the other high is going to be beneficial in one case, whereas it could be harmful in the other. So in cases like this, we need something that is known as the F1 score, which does nothing but provide balance between these two metrics. So the F1 score basically ranges from 0 to 1, where 1 indicates perfect precision and recall. So if you achieve your F1 equal to 1, that means you have a perfect balance between precision and recall. So this is the formula for your F1 score, twice into precision into recall divided by precision plus recall. So F1 score is, like we discussed, very helpful when your precision and recall are in conflict, right? Right. So that is all about F1 score. So moving on to our ninth question, what is the purpose of regularization in machine learning? So regularization is basically a technique that is used to prevent overfitting by adding a penalty to the model's complexity during training. Now it adds this penalty to the loss function during training. Right, this prevents overfitting. Now overfitting occurs when a model performs well on training data but poorly on unseen data, as we already discussed previously. Right, so regularization is going to help the model generalize better on new data. So basically it's a technique that is used to prevent overfitting. That is the main criteria. Now there are two types of regularizations, that is L1 and L2. L1 is called the lasso technique and L2 is called the ridge. So as you can see, without regularization we have an overfitting where our line is trying to touch each and every data point. Whereas after regularization, we're going to have a better fit where our line is more generalized. It is near all the data points, but it is not really memorizing any data points as such. So the L1 or the lasso regularization is basically when it shrinks some weights to 0. Basically, it tries to remove the irrelevant features and it tries to make the model more simpler, right? Whereas the ridge regularization focuses on reducing the large weights. It encourages the model to balance the complexity without exactly eliminating any features, right? So basically, regularization reduces overfitting. That is, it prevents the model from becoming too complex, right? Or we can say it reduces the complexity. Reduces complexity. We've already seen how. It simplifies the model. It basically encourages more interpretable weights, right? It improves generalization. That is, it makes sure that the model performs well on unseen data as well, right? So the training as well as the testing data is focused over here through generalization. Then we have multicollinearity, that is the high correlation among input features. So say we have two features, that is number of bedrooms and number of bathrooms. So if these two features have a very high correlation, there's going to be a problem in simple models like linear regression, right? So this multicollinearity problem needs to be handled and it can be done through regularization. So these are the benefits of regularization and I hope you guys understood it and will be able to explain it in an interview as well. So moving on to our 10th question, explain the bias variance trade-off. So the bias variance trade-off is basically the balance between two sources of error in machine learning, bias and variance. So we have already discussed underfitting and overfitting. Underfitting, and let me write overfitting over here. Right. So underfitting basically occurs when we have a very high bias, whereas overfitting occurs when we have a very high variance. Right. So now in order to find a balance between underfitting and overfitting, we have something known as the bias variance trade-off. Right. So as bias decreases, variance increases and vice versa. So this is how these two variables are correlated. Alright. Let me just clear my screen. Okay. So now the goal is to find a balance where both bias and variance are minimalized for best generalization. Now we do not want any of these terms to have a greater effect on our model. So we're going to have to minimize both of these terms to achieve a better generalization. Right. So as I already told you, if we have a very high bias, our model is going to be too simple that it is going to be underfitted. Right. And if we have a high variance, that is, a model is going to be too complex. We're going to have a good accuracy on our training data, but a very poor performance on our testing data. So that is what high variance does or overfitting does. Right. So consider an example where you're hitting a target. Now, if you have a very high bias, your arrows are going to land very far away from the target, but in a very consistent, or you can say systematic error. Right? Either they're all going to go, say, towards the right direction. But in case of a high variance, your arrows are going to scatter unpredictably. Right? One arrow could go here, one could go here, one could land over here. It is going to be very unpredictable. Some could even hit the target and some could miss it. Right? But a well-balanced model is going to be a case where all your arrows cluster close to the target. Right? So consider a very well-balanced model, and in that particular model, all your arrows are going to land somewhere over here, over here, over here, right? All near the target. So this is when both your bias and your variance has been minimized. So that is all about bias variance trade-off. Moving on to our 11th question, what is feature engineering and why is it crucial in machine learning? So you can see in this diagram, we have raw data. And then we have something known as feature engineering, and then we come to our ML model. So now what feature engineering is, it's basically involving refining or creating input variables to make them more useful for a machine learning model. Right? In order to implement a model on your raw data, you need to have a well-refined, or you need to have your input variables that are very useful. So that is done through feature engineering. Right? So feature engineering basically involves steps like feature selection, feature transformation, feature creation to improve a machine learning model's performance. So feature selection is where you pick the most important features for your model. So say in a house price prediction model, the area of your house is going to be more relevant than the color of the house. Right? Then comes feature transformation. So this involves modifying features to make them more suitable for analysis, such as you can say normalizing your numerical data or encoding your categories. Right? So basically you transform your data into a more useful format. Then you have creating input variables or features. So this is basically called feature creation. This is where you create new features from the existing ones. So say for example, you combine the height and weight into a BMI feature or a body mass index. Right? So that is called creating your input variables. So the benefits of feature engineering are model accuracy improvement. So by providing the model with the right information, you improve the accuracy of the model, right? Then comes reducing the overfitting or preventing overfitting. This is done by focusing on relevant features, right? So once you reduce the noise or the irrelevant information like color of the house, automatically your overfitting is reduced. Then comes simplifying models. Now, when you eliminate the unnecessary complexity, your model automatically becomes simplified, right? Then your final advantage is highlights the domain knowledge. Now, when you perform feature engineering, it incorporates domain expertise, right? If you have a good domain knowledge, you can make your model much smarter and you can tailor it to the problem, right? So again, feature engineering has a advantage of highlighting your domain knowledge. Moving on to our 12th question, example of when a false positive is more crucial than a false negative and vice versa. So this scenario we have already discussed, but let's look at it in detail. So we know a false positive is when a model predicts something as positive, but it is actually negative. Example, a fire alarm going off when there is no fire, right? Then we have a false negative when a model predicts something as negative, but it is actually positive. So this is missing an actual fire when it occurs, right? So there is a fire, but you missed it. You predicted it as negative, like there's no fire, but in actual there was a fire. Basically, that's what it means. So now that we have covered what is false positive and what is false negative, let's look at an example or a scenario where one is more important than the other. So let's look at the scenario when a false positive is more crucial. So in case of a spam email detection, what a false positive is going to mean is basically you classify a legitimate email, that is an important email, as spam, and now what the consequence is going to be is it is going to get missed by the user. It could be a job offer or a client communication letter. It could be any sort of email. And a false positive is going to mean is that that important email is going to get classified as a spam, right? So this is where a false positive is very crucial. You cannot just blindly mark any email as a spam. Then you have your false negative. So in case of a cancer detection or any say medical diagnosis, right? So a false negative is going to delay the diagnosis and the treatment, which could be life-threatening. We've already discussed. So the model is basically going to fail to detect cancer in an affected person. So this is where a false negative is crucial. Moving on to a 13th question, what does naivety stand for in naive bias, right? So naive bias is again a machine learning algorithm based on the Bayes theorem. Now this is used for the classification task. Now what the naive stands for in naive bias, basically it refers to the assumption that all the input features in your data set are independent of each other, which is again not true in the real world, right? Now say for a house price prediction model, you cannot have a number of bedrooms and the number of bathrooms or number of bedrooms and the price feature as independent variables. They cannot be independent of each other because obviously each of these factors are interrelated and are going to affect each other, right? If you have lesser number of bedrooms, your price is definitely going to be affected, right? So it is not true in the real world, but it is an assumption made in machine learning whenever we use naive bias, that all the assumptions, that all the input features are independent of each other. So basically this is how the Bayes algorithm works. It basically classifies all, or basically groups the different items into different groups, and this is the formula for the Bayes theorem. So we already saw naive bias assumes that changing one feature is not going to affect the others. This is the independence assumption. We have already discussed this. Now this works well with limited data, mainly for one reason, because it does not really need the complex relationships between features, right? So it is again fast and efficient, that is, it makes the computation really efficient. Then again, it is surprisingly accurate, even though in the real world, the assumption that the naive bias algorithm considers is not true, it is surprisingly accurate in machine learning. So basically, even in the example we discussed, so even when the independence assumption is violated, it will still provide accurate predictions for many tasks, right? So that is one advantage or one very important characteristic of naive bias. Moving on to our 14th question, give an example where the median is better measured than a mean. So now we know mean is basically when you add up all the numbers and divide by the total count, right? So say for example, you want to find the average of 2, 4 and 6. You're going to add 2, 4 and 6, and since the total count of these numbers is 3, we will divide by 3 and our answer is going to be 4. Whereas median is basically finding your middle number when all the numbers are arranged in a particular order, right? They need to be in a descending or an ascending order, and whatever middle number you find is your median. So the median of 2, 4 and 6 is going to be 4. This is the middle value, right? So now when does median outperform mean? Now when do we prefer using a median rather than a mean? So consider a scenario where you have 5 people and you're given their incomes. First is 30k, then you have 35k, 40k, 45k, and then you have 1 million. Now you can notice that these 4 numbers come in a very close range, whereas 1 million lies in a very far range. That is, this particular number is an outlier, right? So if you were to plot these numbers in a graph, 1 million would stand out compared to the rest of the numbers, right? So that is basically what outlier means. So if we were to find the mean of these particular values, we would have a number something like this. This is not accurate, because if we were to find the mean for these particular values or these particular incomes, we wouldn't have such a huge mean, right? Our mean has been changed, or it has been influenced because of this particular outlier. So in cases like this, where we have a heavily skewed data, this is when median is more efficient. Now if we were to find the median for these particular values, it would be 40k, and this would represent the income of these 5 people more accurately, right? So basically median is not affected by the extreme values or the outliers, as we just saw in this particular example, right? So it gives a more realistic picture whenever data is skewed, like in income or in property prices, right? So whenever you have a high range of your data, you're going to prefer median over mean. Moving on to our 15th question, what are the key differences between bagging and boosting in ensemble methods? So let's understand what is bagging first, right? So bagging basically stands for bootstrap aggregating. Now this creates multiple models by training them on different random subsets of the data. Now each model makes a prediction and their results are averaged for regression or voted on for classification. Now example of bagging is random forest, right? Now in case you're not familiar with ensemble methods, let us quickly discuss ensemble methods. So ensemble methods are basically like building a team, right? Multiple models or players, they all come together to make better predictions. So all these factors coming together basically reduces the errors and increases the stability of the model. So bagging or bootstrap aggregating, let's consider an example to understand it better. So imagine you're dividing your classroom into groups and giving each group a problem. Now whatever answer each group comes up with, you average their answers. Now this method is going to reduce the variance, and it is also going to make the final model more stable. Now random forest is a classic example of bagging. Then we have boosting. Now boosting takes a little bit of different approach. Now models are trained one after the other, with each new model focusing on the errors made by the previous one. So instead of combining the models simultaneously, boosting is going to combine them sequentially. Here each model is going to correct the errors of the previous one. So the boosting algorithm basically corrects the errors or improves the mistakes as the algorithm moves forward, right? The examples of boosting algorithms are the gradient boosting or the adder boost algorithm. So let's understand boosting by an analogy of real world example where a teacher is helping the students who struggled the most in the last test. So now boosting is going to be a very great way of correcting the bias and weak models, right? So whichever students struggled in the last test are going to be trained separately and help improve their performance in the next exam. So this is exactly how boosting also works. Let's quickly look at the difference between bagging and boosting methods. So bagging basically works in a parallel method where models are trained independently, right? All of the models are being trained at the same time independently. That is, they do not have any sort of connection between each other. Whereas boosting works sequentially. Models depend on each other where one model corrects the mistakes of the previous model. Bagging focuses on reducing the variance, whereas boosting focuses on reducing the bias. Bagging treats all the data points equally, whereas boosting focuses on correcting the errors only. Bagging is less complex, whereas boosting is more complex due to the dependency. Bagging is good for stable models with high variance, whereas boosting is good for weak models with high bias.
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampal IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.